Hello. Hi, I'm Jim Heffron. This is a series of videos that are based on my undergraduate linear algebra textbook. The idea here is to enable a person to work through the textbook over the course of what would be sort of a typical semester for an undergraduate first linear algebra course. So I have a couple things that I wanted to say by way of introduction, so let's get started. So the book covers, and these videos will cover, a standard linear algebra course, undergraduate linear algebra course. It covers Gauss's method, then vector spaces, then linear maps, homomorphisms, then it goes on to cover determinants, and finally finishes with eigenvalues and eigenvectors. So that would be kind of what a person would typically do over the course of an undergraduate U.S. Semester. Okay, you can use these videos either as part of a standard course, or as a supplement to a standard course, or as something that you can study on your own. A lot of people use the textbook as for self-study because it's freely available. Any of those is great. However, if you're studying on your own and you could use some tips to be more effective, then I can recommend a resource. I'm going to put a link in the description for this video. Of course, you can Google around for yourself, but just in case you're looking for some recommendation, I'm happy to put one in the link. No connection to me, just I found it useful with my students. So the idea of this presentation is that for each topic, let's say Chapter 2, Section 3, Part 1, the first subsection, you can first watch the video. It might be 20 or 25 minutes. Some of the longer subsections I've broken up into two videos, a part 1 and a part 2. So you first watch the video, then you study the book. So having watched the video and gotten some idea of what's happening, then you open up the book and go through the examples and the theorems and the proofs in the book. And then you're ready to do the homework. In the homework, I've check marked some of the exercises. I would do at least those. The answers are available. You can download the answers from the same place you download the book from. Again, look in the description of this video. And so you can verify that you've done them right. The answers are completely worked. So if you get stumped on a question, you can, after trying it, you can go and look and see, oh, I see, I should have done. Okay, so the answers are completely worked. So they should be usable to a person who is on their own. Okay. I can also recommend the linear algebra videos by the YouTube author named 3 Blue 1 Brown. Just go to YouTube and search for linear algebra 3 Blue 1 Brown, and you'll find them. They're just wonderful, just delightful videos. However, I have to caution you to kind of figure wagging before I leave here, and that whatever resources you use, those videos, for example, these videos here, you have to watch, you have to do the homework. It's absolutely critical that you do the homework. If, for example, you say to yourself, well, I got a 45-minute bus ride, these videos from Heffron are 25 minutes each, so I'll watch one video a day, and after so much time I'll have learned linear algebra. No, you won't. You'll have watched a bunch of videos. The way you learn the material is by doing the homework. The video resources, either from me or from 3 Blue 1 Brown or whatever other videos you find online, and there are a lot of good ones, those are great. But until you have done the homework, you have not learned the material. So if you have not done a lot of homework, enough homework so that you start saying to yourself, okay, yeah, I get it already. If you have not done a lot of homework, then you simply have not learned linear algebra. You can't watch videos, that's all there is to it. It's like learning to play a violin. You can't learn to play a violin solely by watching other people play violins. That's just not how it happens. Okay, enough finger wagging. Nice to meet you, and I hope that you enjoy the videos. Hope you find them useful. So next up will be Solving Linear Systems Part 1. Very good. Hello. I'm Jim Heffron. I'm going to be talking about the material that's in my linear algebra book here, and at this website. It's freely available for download along with the answers to exercises. I'm going to be going through the slides for that book in the same way that I would if this were a course during the regular semester. And so a person can take this if you're interested in doing it as an independent student or doing it as an adjunct to a regular course, whatever need you have. You can go through the course of the regular semester. As I mentioned in the introduction, if you are an independent student or a person who is working on their own, that's absolutely wonderful. I admire your industry. Good for you. But it's extremely important in that context that you do the exercises. If you don't do the exercises, you won't learn the material. I went on about it at some length in the introduction, so I won't go on about it here, but very important to do the exercises, in particular the check-marked exercises. The answers are available for download. They're complete answers. They're worked completely through. I don't think a person would, after looking at the answers, say, I don't see why we did step 4. But you have to try the exercises. You can't just read it and look at the answers. You have to try it yourself. That's how a person learns. Okay, enough. Okay, so I want to start in then. Very exciting start in. So we're looking here at the very first job that a person would think to do, and that is to solve equations. That's a very mathematical activity. Seems to a person exactly the kind of thing that you do in mathematics is you write down some equations and you try to find the x's that solve them. So that's exactly what we're going to start out doing. We're going to happen to solve these systems by a method that's called Gauss's method. It isn't that Gauss invented it or anything, just happens to be associated with his name. And we're only going to solve a particular type of system, what's called a linear system. So I have to introduce those systems. They arise a lot in practice, a real lot in practice, very important systems, but nonetheless, there's only, not completely general, it only applies to certain cases of equations. And so, here we go. So a linear combination of variables, x1 through xn, it looks like this. You have some numbers, a1, a2, a3, etc. through an. Those are real numbers, 3.4, 7, -5, kind of thing. The variables, x1, x2, x3, etc. Those letters, x1, x2, those do not have x1 squared. It doesn't say the square root of x1. It doesn't say arc cotangent of x1. It just says x1. So what characterizes a linear combination is that this is basically x1 to the 1 power, x2 to the 1 power, x3 to the 1 power, etc. Okay, so that's a linear combination of those variables, and the letters, the AI, are called the coefficients. And as an example, here's a linear combination of 3 letters, 1/4 x plus y minus z. So that's x to the 1 power, y to the 1 power, z to the 1 power. There's a 1/4 in front of x, there's a 1 in front of y, and there's a -1 in front of z. And then a linear equation is just a linear combination, only you made it into an equation, so now it says equals some letter. In this case, I use the letter D. I have a not very imaginative name for that letter. That I'm calling that the constant. But in any event, you have here that you recognize the linear combination on the left and the letter D on the right. And when we can, we will try to always rearrange the linear equations that we have to have all the variables on one side, always the left, almost always the left, and the constant, the number not associated with a variable on the right. And then we always want to solve these things. So we always want to find some real numbers that work in the equation. So if you have some real numbers that work in the equation, you must have n of them. That's called a solution of, or you say that this n tuple satisfies the equation if you substitute these numbers in for the x's and you get the right answer. And what we will mostly be interested in is when you have many of these. One sometimes, but more often 2, 3, 4, 5, lots of them. That'll be a system of linear equations, and we'll say that something solves a system if it solves every equation in that system. So this is kind of a quintessential mathematical activity. We'll be given a collection of equations, and we're looking to find the real numbers, in this case down here, x, y, and z, that make all the equations true. And this is very typical kind of linear system. It's got 3 linear equations, and we're looking for x and y and z that make all 3 of those equations true at the same time. Now, naturally, we want to solve them by some systematic way, looking at it and saying, well, it seems to me it's just not going to do it. We're going to learn a method that always works. That is to say, it always gives you the solution to the problem. It has the advantage that it never gives you something that isn't a solution. It also has the advantage that it is basically the fastest method known. So we are going to do what's called Gauss's method, and it will involve transforming this system through a sequence of steps until we get it in a form where the answer is perfectly obvious. So I'm going to transform this system to a new system that has the same solutions, and then transform it again and transform it again until I get it into a form where the answer to the equation, what is x equal, what is y equal, what is z equal, is perfectly clear. Okay, so here's the first transformation. You see how I wrote it with an arrow because I have a system of equations here and a system of equations here, and then I wrote that I'm transforming this system by taking the first row. That's the Greek letter rho. It's supposed to be a little bit of a joke. It's the first row, 4 times row 1. And I just went through and multiplied 1/4 times 4, y times 4 minus z times 4, and 0 times 4. And so I have a slightly different looking, but really the same content, system of equations. I changed only one of the rows, and I didn't change it in a very interesting way. Next transformation is the one that really matters. It's the one that we will find does most of the work. And so I'm going to go through this at a little more length. So you see how it says minus row 1 plus row 2. There's another one on the bottom, but I'm just going to do the one on the top first. Minus row 1 plus row 2. So in my head, I went through the coefficients of the first line and also the constant. I multiplied by minus 1 and added. So minus 1 times x and add, and that gives me 0x. I didn't bother to write it. Minus 1 times 4y and add to 4y, and that gives 0. I didn't bother to write it. Minus 1 times minus 4z makes positive 4z, and add to the 2z that's down here makes a total of 6z. And then on the other side of the equation, it's minus 1 times 0, add to 12, and you get 12. So minus 1 row 1 plus row 2 means that I use row 1 to act on row 2. I use row 1 to change row 2. Row 1 itself is unaffected. I use row 1 to change row 2, and in my head I work on the coefficients in row 1 and have them change the coefficients in row 2. All right, so of course there's a second one here, so I'll go through that one just to try to reinforce what I did with the first one. It says minus 2 times row 1 add to row 3. So I'm going to take the things in the first row, multiply them by minus 2. Again, I'm doing that in my head. Multiplying them by minus 2 and adding them to the things in the third row. So minus 2 times x, add to 2x makes 0. I didn't bother to write it. Minus 2 times 4y, add to minus 3y makes let's see, minus 2 times 4y is minus 8y. Add to 3y makes, yeah, that's right, minus 11y. That's right. A person can make a mistake. It's not hard, but a person can make a mistake. Minus 2 times negative 4z makes positive 8z. Add to minus z makes positive 7z. And last, of course, minus 2 times 0 and add to 3 makes 3. So I have transformed the original system and then this system. I have transformed the system to get a new system that contains the same information, but in a somewhat different form. In particular, you notice this minus row 1 plus row 2 and this minus 2 row 1 plus row 3 is designed to get rid of all the other x terms. So at this stage, I'm going to go to one more step, but at this stage, I only have one row that contains an x term. Okay, last thing is, it doesn't fit all in one slide, so I have to go to the next slide, is I'm allowed to swap 2 of the rows. You're allowed to just rewrite them in a slightly different order. So row 2 and row 3 are swapped here. You see the double-ended arrow means swap the 2 of them. And just to flip back just for a second here, all I did was take the row 3 and move it down to row 2. It's going to be row 2, move it down to row 3. The row 3, move it up to row 2. So it didn't do anything of any interest at all. I just rewrote them in a different order. And now I have the information that was in the original system, but it's been transformed into a new form where it's obvious what the answer is. Look at the bottom row. It's obvious what z equals. So z's got to be 2. Now, knowing that z equals 2, you can substitute that into the second row. 7 times 2 makes 14, and solve the second row. And then knowing that z equals 2 and y, you can solve the first row. So the bottom row clearly says z equals 2. with that, you can figure out what is the value of y. Y is 1. And next up, because there's only one row that involves an x, you substitute the y and z stuff into the x row, and you end up with what x equals 4. Okay, so we now know that the original system had, there we go, the original system had one solution, one and only one solution, and through a sequence of steps, we were able to figure out what is the solution of that system. And again, this sequence of steps will be the basis of the whole semester. We're going to be doing this hundreds of times through the course of the semester. The sequence of steps is known to be, people have studied this, known to be the fastest sequence, and known to also have the advantage that it always gives the right answer. If there's an answer, it finds it. And it never gives the wrong answer. It never finds an answer where there isn't any answer. So it is in some sense an ideal system. Gauss's method, sometimes called linear elimination or some other terms like that. Gauss's method is, in some sense, the ideal mathematical procedure. Just as an aside, you may have learned a different method in high school. Sometimes people tell me, I have students who tell me that. They'll say to me something like, oops, went too far. They'll say to me something like, well, you take the first row and you bring z over to the other side. And now you know that z equals 1/4 x plus y. You substitute that into the next two rows. Oh, please don't do that. Please don't do that. Don't do that. That's slower, more error prone, harder, and has a disadvantage that it can sometimes give you the wrong answer. People then say, oh, you always have to check. I'm showing you a method here that you never have to check it. If it gives you an answer, it's always the right answer. So this is the method to do. Do not, please don't say I learned a way in high school. I really like the way. I'm sorry you learned the wrong way in high school. I apologize, but you learned the wrong way in high school. And if you're studying to be a high school teacher, please do the whole world a favor. Don't teach people that way. That's not the right way. Okay, anyway, off the soapbox, back to reality. So we found the solution to this system. Okay? This is, I need some terminology. This is Gauss's method. When you get to the end here, you have, the goal is to have this triangular form where you have a row with only z, a row with y as in front, and a row with x in front. Those are called the leading variables. I'll say that here z leads this equation, and here y leads this equation, and here x leads this equation. And we'll call this triangular form where they fall off to the right, we'll call that echelon form. Echelon, the French word that means this is something like in rows. And that's, once you have the system in this triangular form, then you can easily figure out what is the answer. Okay, I have a bigger system because sometimes the right way to figure out a problem is to do one so big that you say, okay, there's nothing special about it. There's no step where you say, well, because this is a equation 3 unknown problem, this one is big enough that we'll see for sure exactly what's happening. So I won't go through the arithmetic. A person can check the arithmetic, and anyway, it's not very interesting. But I want to go through the procedure. So the very first step, you start out with this system has 4 equations and 4 unknowns. And you see that there's x's in the first, second, and third row. So your goal is to use the x in the first row to get rid of the x in the second row and get rid of the x in the third row. We're using this row combination method that I've told you a number of times already. It's the best way, so that's the way we're going to do it. So you take the first row, and you got to get rid of an x. To get rid of an x, you need a minus 1 times x. To turn 2x into minus 1 times x, you multiply by minus a half. You can't just multiply one thing by minus a half. You have to multiply everybody by minus a half and do the combination. But the goal, though, that's just fallout. The goal is to use this x to turn that x into a 0. All right, so everybody's a smart person. I don't need to go on at great length. So minus 1/2 times 2 and add makes 0x. Minus 1/2 times minus 3 makes positive 3/2, and add makes 3/2. Minus 1/2 times minus 1 makes positive 1/2, and add to 3z makes 7z. Minus 1/2 times positive 2 makes minus 1w, add to 1w makes 0w. I just leave them out, I don't bother to write them. Minus 1/2 times minus 2, add to 6, and it comes out to 7. Likewise, minus row 1 add to row 3, minus 2 and 2 makes 0. That's the goal of this step. The other stuff is just collateral damage. You have to work with the other letters, the Y, the Z, the W, but the goal is to use the 2 to get rid of the 2, and so it's just minus row 1 add to row 3, minus row 1 add to row 3. Minus row 1 add to row 3 gets rid of the x. It so happens to get rid of the y. It so happens to get rid of the z. And it happens to leave you with a w. And again, I won't go through the arithmetic because everybody knows how to do arithmetic. On this side, it leaves you with a minus 1. Comment here about, so I sometimes run across folks who don't write this. I must have done thousands of these in my life. I always write it, and the reason because it gives you some kind of accounting. You can go back and check that you did it right, and say, well, what was I doing at that stage? And it's there. And just on a more prosaic level, you can get partial credit for writing the right answer if you're taking this on a test or something. You say, your instructor will look and say, well, he wrote down the right thing, he or she wrote down the right thing but made a mistake and didn't realize the z's cancel. Okay, so please, I urge you to write those. All right, next up here, we've used the x in the first row to get rid of the x's below. Next step is to transform this system. We're going to use the y in the second row to get rid of y's below it. Not y's above it, just y's below it. So we're using that 3/2 to get rid of a 1. To get rid of a 1, you need a minus 1. What does it take to turn positive 3/2 into minus 1? There we go. You take minus 2/3 row 2, add to row 4. And again, I won't bother you with the detailed arithmetic, but basically minus 2/3 times positive 3/2 and add, minus 2/3 times positive 7/2 and add, minus 2/3 times 0 and add, minus 2/3 times 7 and add. And it comes out to be what it comes out to be. Okay, so far we have arranged that in the first column there is just an x. In the second column, starting from the second row, there's just one y. And now we want to arrange that in the third column, starting from the third row, there is just the one z. But we look there, we say to ourselves, what do we have to multiply by? There's no z there to multiply by. That's not going to work. So what do we got to do? We got to take this z from the row below and swap it up into place. So you see why the swap operation, rewriting things in a different order might seem like a foolish thing to do, but it solves my difficulty here. The difficulty is I've got a 0 there, so I got no way to get rid of the minus 4/3 z because I can't turn a 0 into positive 4/3. So there we go. I swapped row 3 and row 4. And now I have a system. It was kind of, bigger than the previous system, and the numbers are not exactly beautiful, but they're not brutal either. Now I have a system that I transform through a sequence of steps into one that is in echelon form. X, down and over, Y, down and over, Z, down and over, W. And the answer is obvious. W is clearly equal to minus 1. Knowing that W equals minus 1, you substitute in and you get an equation that involves only Z. Knowing what W and Z are, you get an equation that involves only Y. Knowing what W, Z, and Y are, you get an equation that involves only X. Turns out that X equals 0, X equals 1, Y equals 0, Z equals 2, W equals minus 1 is the only solution. Okay, and it's not particularly hard to find the answer. There's a certain amount of arithmetic, but arithmetic is, especially in this calculator age, arithmetic is not a challenge. Okay, so again, this is called Gauss's method. It turns out that Gauss used this method, which was well known at the time and known as far back as we know, ancient Chinese mathematicians, all very old stuff. But anyway, Gauss used this method to find the orbit of the first known asteroid, and somehow it got attached to Gauss's name. There are 3 things you can do. You can swap 2 equations. You can take an equation and multiply both sides by a non-zero number. You don't want to multiply both sides by 0. And finally, you can take an equation and replace it. You could, for example, replace row 2 with somehow a combination of itself and a multiple of row 1 type of thing. This is the third step. We're going to call it row combination. That's the important step. That's the step where most of the work takes place. The swapping is, we need it sometimes. I needed it on the previous slide, but it's no particular intellectual content there. Multiplying both sides of an equation by a non-zero number, which is actually not something we often do, but still it's a legal operation. We use these three operations, and in particular the third one, we use these three operations in a systematic way to arrange the system of equations so that the answer is obvious. And that's called Gauss's method. The three operations here are called elementary reduction operations, sometimes called row operations, sometimes called Gaussian operations. I tend to call them row operations when I have choice. Okay, next time, we're going to talk about systems that don't have a single solution. They have more than one solution. Sometimes they have no solution. We'll continue to use Gauss's method because Gauss's method is the method that, again, tells us what the answer is, and if there isn't an answer, it will tell us that also. Gauss's method is simply the right thing to do. And for the homework, you should try a number of problems that involve Gauss's method and make sure that you feel perfectly comfortable with the steps that are necessary. I don't see what's wrong with the check-marked exercises. Those are the ones that I recommend to my students, so I think you should give them a try. Okay, very good. See you next time. Hi, hello again. Hello. Hi. So I want to continue with the discussion of Gauss's method. And this time I want to talk about, in some sense, what can go wrong. What things could happen when you're doing Gauss's method that tells you that there's something else, something other than just a unique solution. So last time we saw the theorem that justifies Gauss's method. It says that if you perform any of those three operations, then the set of solutions before you perform the operation and the set of solutions after you perform the operation is the same set of solutions. So you don't change the solutions to the set of linear equations by performing those three operations. And so if you systematically apply them in the way that we saw last time, you will end up with a system that you hope tells you that here's the answer. Now, sometimes you end up with a system that tells you something else about the system, and about the starting system, and we want to talk about that today. Okay, so let me pop that down for a second and get myself some paper to write on here. Okay. Okay, so so the first thing I want to talk about is how do you make up a system of your own? So there's sometimes a person can learn a lesson from trying to make up problems like homework problems of their own. So the natural thing to do is to decide, oh, I'm going to take, say, I want a system where the solution is x equals 4 and y equals 1. And so I'm just going to make up a couple of linear equations where x equals 4 and y equals 1. This is two unknowns, so I just to do something, I'm going to have two equations. How about x minus 3y equals 1? And again, just to make something, I don't really have anything in mind, especially 2x plus 2y equals, let's see, that's 8 and 2 is 10. So that's a linear system. I know in advance that it's going to have this solution, and that would be perfectly amenable to Gauss's method. In fact, why don't I give Gauss's method a whack here? So I'm going to transform that system. I'm going to use the x to get rid of the 2x, so that's minus 2 row 1 add to row 2. The x minus 3y doesn't change at all. And the 2x plus 2y, let's see, so minus 2 times an add makes 0. Minus 2 times an add, so minus 2 times minus 3 makes positive 6. And add to 2 makes positive 8. Minus 2 times positive 1 makes minus 2. And you're looking at 8. Not a very good 8. And so, of course, from this is in the echelon form that we talked about last time. From this, a person immediately concludes, so y equals 8. Excuse me, y equals 1. And then with y equals 1, x minus times 1, x minus 3 times 1 equals 1. So x minus 2 minus 3 equals 1. And so x equals 4. Okay, so this gives a person some insight into how you construct these systems. Basically, if you want to have a unique solution, you start off by constructing some equations that have that for a solution. It also gives us some insight into how you might construct a bigger system. So let me start off. I have one chosen in advance here. I'm going to take x plus y plus z equals 6. X plus y plus z equals 6. And then x plus 2y plus z equals 8. X plus 2y plus z equals 8. And now let me think about the third equation. So a person can say, well, I'll just make some stuff up. And probably if you just make some stuff up, you'll probably find some solution. But I want to think about a particular way of making these systems. That is to say, suppose I take here 2x and 3y. See what I'm doing? Of course, adding down. And 2z. And let's think about what happens over here. So that's to say, what if there is some relationship among these equations? Say it again because it's the most important thing in the first month of the class. What if there is some relationship among these equations? Over here on the left-hand side, row 1 plus row 2 adds to row 3. What could I do on the right-hand side? Well, I could make row 1 plus row 2 add to row 3. I could write a 14 there. Or I could make row 1 plus row 2 not add to row 3. I could write a 13 there. And that's basically what we're going to talk about today. What happens when there's a relationship and the relationship, in this case, gets violated. So let me pop up the slide. There we go. Oh, there's me again. So we want to talk today about what happens with Gauss's method. Oops, clicked on the wrong thing. What happens with Gauss's method when it's not the case that when it's not the case that there's a unique solution, the x equals 4, y equals 1 case. When that's not true, when instead you come to a system that does not have a unique solution. So here we're looking at the system that I drew on the paper just a second ago. X plus y plus z equals 6, x plus 2y plus z equals 8. And again, the left-hand side, x and x makes 2x, y and 2y makes 3y, z and z makes 2z. But 6 and 8 doesn't make 13. So it can't be the case that if you're going to have an x, a y, and a z that add to 6, and it's also going to be the case that your x and your 2y and your z are going to add to 8, then it cannot be the case that your 2x and your 3y and your 2z adds to 13. That just can't happen. So it has to hold here that this system has no solution. There can't be any x, y, z that make all three of those equations true at the same time. It just can't happen. So the question is, I advertised last time that Gauss's method was perfect. Okay, so how does Gauss's method tell me that? You know, it's not a computer program, so it's not going to have a line that says, print, you idiot, you asked a nonsensical question. So it's got to tell me somehow that there's no solution. Well, how could it possibly tell me that? Okay, so as so often in linear algebra, you just do it. Just do the reduction here. Minus row 1 plus row 2, minus 2 row 1 plus row 3, and you get you get what you get. The arithmetic is not very interesting. A person already spots y equals 2 and y equals 1 and says, but I'll pretend that I didn't notice that because, of course, if the system of equation had hundreds of equations and this was some conflict between equation 71 and equation 243, I wouldn't have noticed it. What happens if you go on to get to echelon form? And there you go. Echelon form tells you very explicitly you asked a question all the way at the start that doesn't have an answer. This system doesn't have an answer. And the theorem that I just showed 30 seconds ago, whoops, went too far. Theorem that I just showed says the set of solutions is unchanged. So since the set of solutions was unchanged and this doesn't have any solutions, then backing up, this must not have any solutions. This is how Gauss's method tells you. Gauss's method perfect in this sense. Gauss's method tells you there is no solution. It doesn't give you a bogus solution. It tells you there is no solution because when you get to echelon form, at least one of the rows has some impossibility. 0 equals -1, 0 equals 12, 0 equals 192, some kind of impossibility. So you will spot when you're doing a Gauss's method problem, if you ever run across an equation that says like 0 equals -1, what that tells you from the previous theorem is that it must be the case that the set of solutions to the original system is empty. No solutions. You asked a question that can't be answered because, well, it can be answered by saying there's no solution because no way for an x, a y, and a z to satisfy all three of these. Okay, now there's one other thing that can happen here that's maybe a little more subtle than this case, but one other thing that can happen here, you remember I did it on the piece of paper. I said x plus y plus z equals 6, x plus 2y plus z equals 8, and then I said 2x plus 3y plus 2z, and I put a question mark there, and I asked myself, what if I put a 13? That was one of the two questions that I asked. But I also asked myself, what if I put a 14? Now you see, if you put a 14 there, then you're putting in basically the same information twice. What happens when you have redundant information? What happens when you have, in that case, a third row that contains the same information as the previous two, or aggregates the information from the previous two? And so here we have a problem that does basically the same thing. 3 equations, 3 unknowns. Just to glance at it, at least in my mind anyway, just to glance at it, you don't spot right away that there's something funny about it. You apply Gauss's method, row 1 add to row 2 to get rid of the x, 3 row 1 plus row 3 to get rid of the 3x. Next up is to use that minus y to get rid of the minus 4y, and you end up with echelon form. And you're like, okay, well, no, it doesn't say 0 equals 5 or 0 equals 21, so it doesn't have some impossibility, but it also doesn't have an equation for z. It's got an equation where y leads, it's got an equation where x leads, but it doesn't have an equation where z leads. So there's no way to get started on that back substitution process. More precisely here, in this 2 equation, 3 unknown system, if you tell me a z, I can solve for x and y. So for instance, if you tell me z equals 0, I can tell you that y equals -6, and then I can go on to solve for x. If you tell me that z equals 1, I can tell you that it's like that. If you told me that z equals 142, I could then solve for y, and using the y and the 142, I could then solve for x. That is to say, there are infinitely many solutions. There is a family of solutions, and every z gives you a different solution. So there's a family of solutions, I'll say parameterized by z. Those solutions are different. Z equals 0 gives one solution, z equals 1 gives another solution. Now, in the previous case here, we got 0 equals -1, and how could a person miss that? You know, right away you'd spot that there was something wrong, and you just circle it and write something like no solutions and move on to the next problem. Here, there's something a little subtle about the 0 equals 0. 0 equals 0 does not tell you that there are infinitely many solutions. That's not right. Back here, 0 equals -1 told you, without any need to go any further, that there are no solutions. But here, 0 equals 0 does not tell you there are infinitely many solutions. 0 equals 0 tells you that one of the equations was redundant on the others. What tells you that there are infinitely many solutions is that you've got echelon form and there's no equation for one of the letters. There's no equation here where z leads. There's an equation where x leads, there's an equation where y leads, there's no equation where z leads. That's what marks infinitely many solutions. So let's look at another example that I hope drives that point home a little better. So don't say to yourself, look for 0 equals 0. No. Say to yourself, look for a row for every letter. All right, so here I have the x plus y plus z equals 4, x plus 2, x minus y plus z equals 4, x plus y minus 2z equals -1, and I do the Gauss's method step, there's only one. And I've got echelon form because as much as I can, the variables fall off to the right. But again, I do not have a row for z. I just don't have it. There's only 2 rows. I have 3 letters and only 2 rows. I just don't have a row for z. But if you told me, for example, that z equals 0, then I could solve for x and y. If you told me that z equals -1, then I could solve for x and y. If you told me that z equals 5, then I could solve for x and y. There are infinitely many solutions, a different one for every z. There's no 0 equals 0. It's 0 equals 0 is not your clue about infinitely many solutions. What your clue about infinitely many solutions, the thing to look for, is when you get to echelon form, does some row, is there some letter for which there is no row that it leads? Here, 0 equals 0 only means that z's chance to lead a row is just not there. Okay, so for no solutions, that's an easy one. A person spots that there's some impossibility. If at some point in the process you spot an impossibility, you don't need to go on with the process, you can just stop. However, if you get to the end and you say to yourself, there's not a unique solution here, there's not a unique solution here, well, then you're looking at infinitely many solutions. And you can use the letter that doesn't lead. You can use a variety of things, but we're going to use the letter that doesn't lead. You can use the letter that doesn't lead, in this case z doesn't lead. You can use the letter that doesn't lead to give you the infinitely many solutions. Okay, we're going to do that next time. The talk next time is called Describing the Solution Set, and so we're going to talk about how you write down the infinitely many solutions. Okay, very good. Bye-bye. Hello. Hi. So last time and the time before we talked about the basics of Gauss's method. Basically, how do you get from a linear system, transform it through a sequence of steps, and then get to echelon form, and what that echelon form can tell you. It can either tell you that there's a unique solution or that there's no solution. Or the third case, the case we want to talk about today, it can tell you about infinitely many solutions. The linear system you wrote down has infinitely many different solutions. All right, so of course we're going to want to write down some kind of equations that describe that solution. What are the set of solutions to the linear system that you started with? All right, so we're describing the solution set, so I'll write down some linear system. Here is a 3-equation, 3 unknown linear system. Looks perfectly innocuous. You wouldn't know it to look at it, that it has some special character to it. It really isn't a special character. Linear systems can do this. You go through some Gauss's method steps, and I didn't bother you with the actual arithmetic of those steps because we covered that last time, and because in my experience, after a little bit of practicing, people don't have too much trouble with it at all. You end up with echelon form. And we see here the characteristic echelon form that implies infinitely many solution, namely that there is no equation in which one of the letters z leads. The 0 equals 0 takes the place of an equation where you might expect to see z leading, but there isn't an equation with z leading. Instead, there's this sort of placeholder 0 equals 0. Okay, so we want to describe, there's infinitely many solutions, we want to describe them all. We want to somehow write down the equations that mark them all. And here's the technique, and I can't overemphasize how much we will be doing this technique throughout the course of the semester. It is looks like a small point when you first see it, but it is a key to understanding much of what we're going to do. So the idea is to take the letter that is in some sense missing. Z doesn't have a row, so we're going to take Z. You could do other things, but this will turn out to always be the thing we want to do. So you take the letter that is in some sense missing, the Z, and you express the letters that are leading in terms of those that are, the technical word is free. So I'm going to express Y in terms of Z, and then I'm going to express X in terms of Z. So expressing Y in terms of Z is very easy. You just move all the stuff over until you have Y equals, and there's some expression on the other side of the equation with Z's in it. I always write them left and right. So I always put the Y equals on the left and the Z stuff on the right. Just a habit, but I don't see any reason to do it any other way. Okay, so what about expressing X in terms of Z? Don't we have a mixture of X and Y there? And the answer, of course, is that we're going to substitute into that first row. So in the place of Y, we're going to write minus 6 plus 4Z. So we get minus X, and there's the minus 6 plus 4Z, and there's the 3Z. And you do the necessary algebra, and you bring everything over to the other side of the equation. It turns out that when all the smoke clears, you get X equals, and then there's a 3 minus Z. So I now have Z, of course, Z is itself, but I now have the other letters, the Y and the X, in terms of Z. And that will be what we always want to do. We always want to express the leading variables in terms of the other variables. I'll call that parameterization. And we'll spend an awful lot of the time doing that. When you're doing homework, an awful lot of time, the answer will be parameterize. This description of z can be whatever you like, x and y depend on z, this description is awfully convenient because it enables you to take a z, 1, a 2, a minus 1/2, 127, a 3,409.6. You take whatever z you like and you generate an xyz, an xyz, an xyz, an xyz, however many xyz's you like. It's obvious that there are infinitely many xyz's because they have to be different. It can't be the case that they're all the same because they all differ at least in the z place. So there are infinitely many solutions here, and I will say, parameterized by z. This enables you to find solutions to the system, to the starting system, but it also enables you to conclude something isn't a solution to the starting system, because if somebody says to you, what about 1, 6, 3, you say to yourself, 3. So if I put in 3 for z and I put in 3 for z, I don't get a 1 and a 6, so that can't be a solution. So that is to say, when you have y and x expressed in terms of z, you have a criteria for solutionhood, whatever is the right word. You have a way to tell whether or not something is a solution, and that's exactly what we want. We'll call that parameterizing. This is one example. Of course, I'm going to do another example in just 30 seconds, but this contains all the information you need. There are some letters, only one letter in this picture, there are some letters missing from the echelon form system. There's some letters that do not lead a row. We use those letters to express the other letters. We parameterize the leading variables in terms of those that are not leading variables. And that parameterization serves as a criteria for what is a solution and what is not a solution. In an echelon form linear system, the variables that aren't leading are called free because you can pick them to be whatever you like. In the previous slide here, I could pick z to be 0 or 1 or 2 or whatever I liked. Once I picked z, x and y were fixed. So x and y aren't free in the same sense in this way of thinking about it. And then the variable that we use to describe a family of solutions is called a parameter. The way that we will proceed is we will parameterize using the free variables. A person can say to themselves, well, I could have expressed z in terms of x. Yes, you could have. But when we're solving these systems, we will always parameterize, we will always express our solutions using the free variables, and that just turns out to be the convenient thing to do, so that's what we'll do. Experience from later on in the course shows that this is the way to go, so rather than start out the wrong way, go start out the right way. We're going to parameterize with the free variables. I don't want to hear any more argument about it. Okay, here's another example. I already put it in echelon form because that's not the hard part. What differs between this and the previous example, of course, there's no 0 equals 0, but we discussed in the last video that the 0 equals 0 is really a canard. That's really not the point. What the point here is that there is no equation in which z leads, and for that matter, there's no equation in which w leads. So I have two leading variables, x and y, and just by taking them away, what's left is z and w are the free variables. So I am going to parameterize this system. I will express the solutions to this system. I'm going to parameterize this system using the free variables, using z and w. I will express y in terms of z and w. I'll have an equation that says y equals, and on the other side of the equation will be some stuff involving z and w. And I'll also have an equation that says x equals, and on the other side of the equation will be some stuff involving z and w. I will parameterize the solution set using the free variables z and w. And again, I know it's not brain surgery, but we're going to do it so much through the rest of the semester, I'm very keen that the words sink in. And it's not especially hard. I mean, obviously, everybody can do this. To express y in terms of z and w, you move stuff over to the other side of the equation, you worry about the SIGN, and you end up with y equals minus 6 plus z plus 4w. Up here, a person might say, well, what about the y? It's in the way of expressing x in terms of z and w. But we saw this in the previous slide. No, substitute for y what you just figured out. Y is minus 6 plus z plus 4w, and then you have a whole bunch of stuff, x's and z's and w's, and you move everything but the x over to the other side of the equation. You get rid of the 2, all this other, you end up with x equals 11/2 minus z minus 3/2 w. So I have expressed y in terms of the free variables. I have expressed x in terms of the free variables. So I have parameterized the solution set using the free variables. And again, that's, we can't see everything we're going to do at once, but But this is, we will want to do this throughout the rest of the semester. Okay, another one. Looks like the first one, some small change. Here, the free variables are not z and w. The free variables are what? Right, leading is x and z, and the remaining ones are y and w. So the only difference between what's up here and what's down here is which variables are going to be the free variables, which variables we're going to parameterize with. You don't necessarily parameterize with them sort of left to right. You can end up with sort of x and a z down here, and the y is stuck by its lonesome. But nonetheless, we will use y and w to express x and z. All right, so you start off, use y and w to express z. Z equals 1/4 plus 1/2 w happens not to involve any y's. If you like, you can think of it as involving 0 times y. In any event, I've expressed z using only, or at most, the letters y and w. And down here, then when you go up to x, you say, well, z is equal to 1/4 plus 1/2 w. You put that in place. You get an equation that has x's, y's. There's no longer a z. There's now w's and w's. And you move everything over. And when all the smoke clears, if you do the arithmetic right, sometimes it takes a while. If you do the arithmetic right, you get x equals, and then there's some stuff over there. There may be some constant, and there's a coefficient for y and a coefficient for w. And there you go. You're done. You've expressed x and z in terms of z and w. There we go. X is some, it's not very pretty, but something involving y and w. Y is just, I don't know how else to write it, so I just wrote it as y equals y. It's can strike a person as a little silly, maybe it is, but I wanted to write down all 4 letters in terms of those two, so I just wrote what I had. There is z expressed in terms of y and w, and there's w expressed in terms of y and w. It's a little silly. Okay. An example that goes start to finish. The Gauss's method part doesn't sort of keep us awake at night here. There we go, minus 2 row 1 plus row 2 gets rid of, so that only the x in the first row is left standing. Minus 3/5 row 2 plus row 3 uses the minus 5 to get rid of it, and you end up with a y there, and then you have this system here. You noticed, of course, that that there are 4 letters, x, y, z, and w. 3 of them lead a row. 1 of them does not. So I'm going to express the x, the z, and the w in terms of the y. The only thing that happens here is that w is in fact determined. Did you notice down here 22/5 w equals 65/5 gives you right away w equals 3. Technically, that's w expressed in terms of y, that's times 0y. So there we go. W is 3, still expressed in terms of y. Z is 2, expressed in terms of y. It's kind of silly, but nonetheless expressed in terms of y. Y equals y, also kind of silly. X expressed in terms of y. There are infinitely many solutions here. The only thing that's sort of especially interesting about this case is that some of the letters are in fact fixed. W is 3, Z is 2. Some of the letters vary, but it can happen that one or more of the letters are fixed. The point, though, the global point for this section is that we have the leading variables x, z, and w expressed in terms of the free variables y. Okay. All right, so very good. So we can express here the infinitely many solutions using this criteria, and just as, for example, if you took y equals 1, you'd know that 2, 1, 2, 3 is a solution to this system. So that's sort of ideal, and that's a way to completely describe infinitely many solutions in a way that you can actually use it to determine what is and what is not a solution. So that's just about ideal. Okay, very good. So next time we're going to talk about a particularly convenient way to write down these solution sets. That's called matrices and vectors, and so we'll see you next time when we talk about describing the solution set part 2. Whoops. There we go. It's describing the solution set, part 2. Okay, very good. Bye-bye. Hi, hello, hi, how are you? So last time we talked about describing the solution set in the context where there are infinitely many solutions. And I want to continue that today. Today I want to introduce a way of writing these things, both the linear systems and also the solutions, that saves a lot of the bookkeeping burden, and also it will turn out add some conceptual meaning to the whole thing. So you may have seen matrices and vectors in another context. You might have seen it in a physics class, for example. At the moment, we're not interpreting it so much as the kinds of things you see in a physics class or a calculus 3 class. At the moment, we're just going to introduce them as a place to put numbers. That's all. But soon enough, we'll give them a more conceptual meaning. But at the moment, just simply a place to hold numbers. So an m by n matrix is a rectangular array of numbers. It's just numbers, no particular physical meaning. M rows, n columns. You read that aloud as m by n, always the number of rows first, because you got to put something first. You might as well always put the same thing first and be organized about it. The numbers in the matrix are called entries. So 3 is an entry, minus 5 is an entry, 6 is an entry. This is a 2 by 3 matrix, 1 row, 2 rows, 3 columns, 1, 2, 3. So 2 by 3, always the number of rows first. You often name matrices with capital Roman letters. And then when you want to talk about the entries in the matrix, for example, the 4 here in the second row, first column, you often use the associated lowercase Roman letters. That's the convention that I'm going to be sticking to. Not 100% of the time, but 95% of the time we'll be writing here capital Roman letter for the matrix and lower Roman letter for the entry, and you'll often see that in practice, very often. Okay, a column vector is often just called a vector, is a matrix with a single column. If a matrix has a single row, it's called a row vector. And again, you may have seen these things where they have some meaning, and we'll get to those soon enough, but at the moment, we're just simply using them as places to hold numbers. The entries of a vector are sometimes called components. Instead of entry up here, you often call it component. And the column or row vector whose components are all zeros is the zero vector, happens to come up a lot in practice. I like to denote vectors with an over arrow, with an arrow on top. So let me bring up my, there we go, and bring up my piece of paper here. And so I'll, whoops, a little shadow there. So I'll denote vectors, there we go. I'll denote vectors with an over arrow. In handwriting, I'll write something like that, V or W. Something like that. Okay, so I'll denote vectors with an over arrow. Let me bring back to the, there we go. In the textbook, the over arrow is easier to read than my handwriting. That's just the way it goes. This particular column vector has 3 components: -1, -1/2, and 0. Oh, I should have mentioned, I like over arrow because you often see boldface, very often see boldface in other books, but I can't do boldface in handwriting or on a blackboard, so I like the over arrow and I put it in both places. But boldface is very common, very common. In fact, maybe more common than over arrow. So this is a row vector with 3 components, and this is the 2-component 0 vector. See a 0 with an over arrow. Oops. I'm going to want to be able to add these and to scale and to rescale them to double them or triple them. So I need to define those operations. So this says if you have 2 vectors, u and v, then you can add them by adding the components. You notice, don't you, that this says down to un and this says down to vn, so they are the same size. If this one has 5 entries, then this one has 5 entries also. Anyway, if they have the same number of entries, then you add just by adding the components. And you can also rescale the components. That's called a scalar multiplication of the real number r. In this context, r is called a scalar. And if for example, you want to multiply the whole vector by r, well, you multiply each of its components by r. And the advantage of all this is that we can take linear combinations, and that's the key in this course. We can take linear combinations of vectors 3 times 1, 2, minus 2 times 0, 1. And when you do 3 times 1 minus 2 times 0, you find yourself at 3. When you do 3 times 2 minus 2 times 1, you find yourself at 4. So these definitions on the top half of the slide enable me to do linear combinations as the example on the bottom half of the slide. One advantage of the matrix notation is when you write these systems down, there's a lot of sort of writing x's and y's and equal signs, and we can get rid of all that just by writing the numbers themselves, the -3, the 0, the 2, and that's what I have here. So I can turn this system into what's called here an augmented matrix. The vertical bar makes it augmented. By just simply writing down the real number coefficients on the left of the vertical bar and the constants on the right of the vertical bar. The vertical bar just reminds me that the ones on the left and the ones on the right are a little different. Do Gauss's method, the same Gauss's method steps as we've been doing for so long. This is obviously echelon form, and it so happens to be the case you see that there is a row with x leading, there's a row with y leading, but there's no row with z leading, so we know that there's going to be infinitely many solutions. And we see the two equations on this. This abbreviates the two equations. Minus 3x plus 2z equals -1. There we go for the top. And minus 2y plus 8/3 z equals -2. There we go for the bottom. There's no reason why I can't take those two equations and do what I've been doing before, which is to parameterize. That is to say, take z and use it as the variable with which you express the other variables. So you express x in terms of z and y in terms of z, and you end up with this three equations here. X is expressed in terms of z, y is expressed in terms of z, and it's a little silly, but z is expressed in terms of z. That gives me this solution set, and I wrote it in vector notation here. The vector notation is very nice here because it organizes the constants, the 1/3, the 1, and the 0, all in one place. And the coefficients of z, the 2/3, the 4/3, and the 1, all in one place here. So this is an especially organized way to write down the information that is here. And it's awfully nice because right away we see, for example, what happens when you plug in different z's. If you plug in a 0 or a 1 or a 2 or a -1/2 for z, you get the whole family of solutions, the whole family of x, y, z's written out there very plainly. So this is an organized way to write this. Just to have a second example, there's nothing special about this example so much, just a simply different example illustrating the same thing. Here's a system, and I can write it in this augmented matrix form. When you do Gauss's method there, you get echelon form, and you convert it to this way of writing the solution set, the way of writing the infinitely many different vectors that all solve this system, infinitely many different x, y, z, w's that all solve this system I started with. You see there is a z times and a w times, and there's also some constants. So it's, again, the advantage of this particular notation is that it shows the constants isolated, the coefficients of z isolated, and the coefficients of w isolated. So it's an organized way of doing the job that we've been doing so far already. Okay, then so the next section is going to be noticing something about that particular way of writing the solution set, and we'll see you then next time. Very nice, and there we go. Okay, bye-bye. Hello, hi, hello. Okay, last time we talked about solving a linear system, finding the solution set description using matrix and vector notation. And this time I want to give some justification for that. I want to explain why we're so keen on matrix and vector notation. In particular, it enables us to characterize the solution set of the linear system. We can completely understand what solutions look like. Okay, so let's start off by backing up to the previous slide. That's the slide that we showed in the last video at the end. We had a linear system like so. We did Gauss's method like so. We came up with a complete solution set written in vector notation. And you notice that it has really two parts. There's a part of a vector of constants, and you also notice that the remainder of the solution set has something associated with z, something associated with w. So there's vector times letter, vector times letter. We want to show that every solution set can be written in that form. Particular here, this is called. Homogeneous here, this is called. So there'll be a vector of constants, and then also some letter times vector, letter times vector, letter times vector. Okay. So I want to describe that looking at the form of the solution set. So here is just like the previous one that I just showed you a second ago. Here is a system. Gauss's method gives you some answer, gives you echelon form. You take the echelon form, you put like so. And now I want to ask you to notice something about those. If you take z and w, you can take them to be anything you like, they're free. If you take z and w to be 0, well, then this part 0, this part 0, and you just get the vector of constants, the 12/5 for x, the minus 1/5 for y, the 0 for z, and the 0 for w. That is to say that this vector here in the solution set is a particular solution of the original system. That if you plug in 12/5 for x and minus 1/5 for y and 0 for z and 0 for w, you'll get 2. And if you plug in 12/5 for x and minus 1/5 for y and 0 for z and 0 for w, you'll get 5. So this one here is a particular solution of the linear system. So we can understand this solution set in some way by understanding the parts, and we're starting off by understanding the part of that very first part, the vector of constants. Okay? To understand the rest, to understand the vector times a letter stuff, I want to isolate on a particular kind of, on a special kind of linear system. I want to take those, the constants on the right-hand side, the constants over here on the right-hand side, the 2 and the 5, I want to take them and change them into zeros. If you change the 2 and the 5 into zeros, then what you get is a system that is simpler in the following sense. I can tell at a glance that it has the solution x equals 0, y equals 0, z equals 0, and x equals 0, y equals 0, z equals 0, w equals 0. So the vector of zeros definitely solves this system. So I know one of the particular solutions of this system. It is the vector of zeros. Gauss's method goes through the exact same steps, and you end up with a solution set that I didn't bother to write the vector of zeros. So I have vector times a letter, vector times a letter. So this is the other half of the general solution. Back here I had a general solution that had a vector with some constants in it, and then vector times a letter, vector times a letter. Well, here I've managed to isolate on the vector times a letter stuff by turning those into zeros. So, in general, when you look at a linear equation like the top line or the bottom line here that has a 0 on the right-hand side, you say that a linear equation is homogeneous if it has a constant of 0. So it has a 0 on that right-hand side. Homogeneous. And of course, the system is homogeneous if it has all zeros on the right-hand side. Now, homogeneous systems are linear systems. So they're just like other linear systems, except they have one special property. The homogeneous system can have infinitely many solutions. Look at this one here, has infinitely many solutions. Homogeneous system can have a unique solution. This one here has a unique solution. But we know one of the solutions for a homogeneous system is all zeros. For example, if you plug x equals 0, y equals 0, z equals 0, you definitely get one of the infinitely many. If you plug x equals 0, y equals 0, z equals 0, you get the one solution here. So that is to say that homogeneous systems are linear systems, but they cannot have the no solutions possibility. That can't happen with a homogeneous system. Oops, I spelled solution wrong. Oops. Okay, so in general, if you have a homogeneous system, then the solution set has to look like this. Vector times a letter, vector times a letter, vector times a letter, however many you've got. It's how many will you have? It says k is the number of free variables. So when we had z and w for free variables, why we had 2 vectors. Now, I'm going to do something here that we do sometimes. Rather than give a proof for the lemma, proof is in the book, but rather than give a proof for the lemma, we're going to try to convey the idea here of the proof by giving an example. Of course, you should refer to the book for the proof. That's the right thing to do. So I want to instead convey the idea of the proof, since the slides are intended to introduce the discussion that's in the book. Okay, so for the main idea here, you consider this system of homogeneous equations, and using the bottom equation, you can express y in terms of z and w. Okay, that's fine, but notice that when you do, there's no constants or a constant of 0, whichever way you like to say it. If you take the value of y and you substitute into the top equation, again, no constants. or a constant of 0, whatever way you like to say it. And so you get x expressed in terms of z and w with no constants. So you end up with no constants or a constant of 0. So you end up with z times a vector, w times a vector, no vector of constants, or again, a particular solution of the 0 vector. And then this right here, minus 2, 1, 1, 0, that's the beta 1. And 0, minus 1, 0, 1, that's the beta k, if the k is 2 within the case. So we have that the general solution can be written as vector times a letter, vector times a letter, vector times a letter. Okay, so the homogeneous solution set is special in some way, that we have a characterization of how you can write it, and that stems from the fact that when you have a homogeneous system, the particular solution is there is a particular solution that is the 0 vector. Okay, so in general then, for a linear system in any particular solution, the solution set looks of this form, p plus h. If you give me a linear system, I can write its solution set in this form, where H satisfies the associated homogeneous system and P is any particular solution. Now this one we are going to prove. I am going to go through the argument. It's not very long, but it involves 2 steps. This says that the set of solutions can be written in this form. Set of solutions equals this set here, where P is any particular solution. So this is 2 sets, a set of solutions and this set here. To show that 2 sets are equal, the most straightforward thing to do, not the only thing to do, but the most straightforward thing to do, is to show that each one is a subset of the other. And that's what we're going to do here. To give the proof, I couldn't fit it all in one slide, so it's on the second slide too. But to give the proof, I'm going to show, first of all, that if a vector is in the solution set, then it is in this set also. And then on the second slide, I'm going to show that if a vector is in the set given, the p plus h set, then that vector solves the system. So that's called mutual inclusion. I'm going to show set inclusion both directions. If a vector solves the system, then it's of this form. Okay, so to show that, what do I have to do? Well, you assume that S solves the system. So then I want to show that S minus P is the right form for H. If I show that S minus P equals H, why then S equals P plus H. Okay, so what is H? H means that when you plug the components of the vector in, then you got to get 0. That's what homogeneous system means. Okay, so I'm taking the components of S minus P and plugging them into each equation. I'm only going to show one equation, of course, but I'm taking the components of S minus P and plugging them into that one equation. Well, you do some algebra here, so let's see. You distribute the A's, and you get A's times S's minus A's times P's. Well, A's times S's gives you D. That's exactly what S is, a solution of the system, so that's exactly what that means. A's times S's, A's times the components of S gives you D. And P is a particular solution also of the system, so so A's times P's gives you D, and they're D minus D 0. So that's exactly what I needed to show. I needed to show that S minus P has the right form for H. H is a vector that has the property that when you plug it into the left-hand side of the linear system, it will give you zeros. Okay, so that's half of the argument. I have to show the other half of the argument. The other half is that if a vector has this form, particular solution plus a member of the set of homogeneous solutions, then it is a solution of the system that you started with. So you take a vector of the form p plus h, and you want to show that that p plus h solves the given system. So that's just a matter of plugging the components of the vector p plus h into each equation. So here I plug the components of the vector p plus h, the first component all the way down to the nth component of the vector p plus h. I plugged it into the equation. I did the obvious algebra. I distributed the a's. So I have the a's times the p's and the a's times the h's. A's times the p's, p is a particular solution of the linear system. So a times the p's gives you d. H, on the other hand, is a solution of a homogeneous system. And I know we only just saw the definition a few minutes ago, but the homogeneous system is the one with zeros on the right-hand side. So a's times the h's gives you 0. And d plus 0 gives you d. Whoops. So in general here, we can always write the solution set in this form. we can always write the solution set in the form we started out the day by looking at here. You have particular solution, and here you have what the homogeneous solutions are, vector times a letter, vector times a letter. Okay. Now, we like this for a number of reasons. One is that I can write down the solution of a linear system and understand completely what the solution set of a linear system looks like. It looks like any particular solution at all that you find can go there. And then here is vector times a letter, vector times a letter, vector times a letter, etc. I just copied that from the solution of the homogeneous. That's the H part. And in particular, what happens here is that by looking at the previous slide, there's the previous slide. By looking at the previous slide and understanding what the various parts can be, I can see that solution sets of linear systems have three possibilities. Solution sets of linear systems are either empty, have one element, that is to say there's a unique solution, or else have infinitely many elements. Those are the three possibilities that can happen. Here I've got a nice box on the next slide that I'm going to point to. So in this box, this little array here, there are two possibilities. Either a particular solution exists yet, or else it doesn't. And we've certainly seen linear systems that don't have a solution, so that would be the bottom line. Well, if a linear system doesn't have a solution, then there's just no solution. That's all there is to it. On the other hand, if a linear system does have a solution, if a linear system does, whoops, I went too far. If a linear system does have a solution, if there is a p that you could write there, then what can happen for the homogeneous case? What can happen with homogeneous systems? And you'll remember from a couple slides ago, homogeneous systems are just like regular systems, except there's one thing that can't happen. So here we go in the box. Homogeneous systems can have infinitely many. Homogeneous systems can have unique, but they can't have the other case. They can't have no solutions. So we get this array here. So the number of solutions to the homogeneous system can be one or can be infinite many. And if the number of solutions to the homogeneous system is one and a particular solution exists, why then the system you started with has a unique solution. If the number of solutions to the homogeneous system is infinitely many and a particular solution exists, then the system you started with has infinitely many solutions. And of course, the no solutions case means that there's no particular solution. Okay, and just to close, let me sneak a word in here before I let you go. So an important special case is when the linear system has the same number of equations as unknowns. So when you look at the matrix of coefficients for that linear system, there's two cases. Either it has a unique solution, or else it doesn't. So in the case where the matrix of coefficients of the homogeneous system has a unique solution, you say that that matrix is non-singular. Non-singular here means something like normal or usual, or doesn't stand out, or not particularly problematic. On the other hand, if the homogeneous system has infinitely many solutions, if we're looking at that case, if the homogeneous system with that matrix of coefficients has infinitely many solutions, then we say that the matrix is singular. And singular here has the connotation of being a little bit odd, or a little bit troublesome, or mathematically interesting, whatever way you like to say it. Now, there is something a little odd, a little peculiar about the terminology. It is the case, I didn't mess this up. Non-singular is associated with unique solution. I know that's confusing, but it's the right word. It's the standard word. Non-singular is associated with unique solution, and singular is associated with not unique solution. That's true. But this is the standard way of using the words, and again, you have to think of the other meaning of non-singular and singular. If you're like reading a Sherlock Holmes novel and it says, the singular case of the dancing men, singular means stands out, or peculiar, or interesting, or somewhat unusual, and that's what's intended to happen here. Non-singular case is the case where you find that the linear system has exactly one solution. The homogeneous system has exactly one solution. That's kind of the expected, or the usual, or the typical. Okay, very good, very good. That ends the first chapter, so I'll let you go, and it ends the first section, so I'll let you go, and I'll see you next time with the second section, vectors in space. Very good. Okay, bye-bye. Hello, hi, hello. Ready for the second section of the first chapter. So because this is the second section, we are going to introduce something new, which is a look back on the previous material, which we didn't have anything to look back on in the first section. So here I have a couple of quick questions that will give a person a chance to feel like they're sure that they're following the main thrust of what we're talking about. So this is an easy one. They're all supposed to be relatively easy, but they're supposed to be just a kind of a quick check-in. All right, so there's 4 linear systems, 1, 2, 3, 4. They're all in echelon form, so a person doesn't have to do the arithmetic. And it simply says how many solutions does each one have. So for the first one, what do you think? So there is no solution here because 0 equals minus 1. Anytime there's a contradictory equation, you stop and say no solution. Over here, second one. So this is the one a person could be fooled by the 0 equals 0. That 0 equals 0 does not signal that there are infinitely many solutions. That's not right. Instead, what's happening here is that there is a row led by z, there's a row led by y, there's a row led by x, and there's no contradictory row. So we're looking here, in this case, we're looking at unique solution. Down here. So here, again, there's a 0 equals 0, but again, we're not going to be confused. There is a row led by x and there's a row led by y, but there's no row led by z. So we're looking at infinitely many solutions in this case. And finally down to here, this fourth one. And so I'm sure that at this point you've seen that there's a contradictory row, and so never mind the 0 equals 0, never mind that there's no row led by z. No, all that doesn't matter, it's a contradictory row. So the answer is no solutions. Okay, so that was the first. Let's see if I can manipulate my stuff here. There we go. There we go. And here's the second. It just says produce a 3 equations, 3 unknown system that has infinitely many solutions. Produce one with no solutions and then also produce one with 1 solution. So I gotta produce that on a piece of paper here if I can figure out how to do this. There we go. Produce that on a piece of paper. So I'm just going to make one up. Of course, you would make up a different one. The idea with these systems is to produce, for example, infinitely many solutions. You might produce an equation that is redundant on the other two, that is just a repeat of the other two. So let's have a look here. Let's see. How about something like x plus y plus z equals 1, 2x minus y equals 5. And then I'll just make the third row be a repeat of the other two, the information in the other two somehow. So for example, how about if I take 2 times the first row and add it to the second row? So 2 times x plus 2x makes 4x. 2 times y minus y makes plus y. 2 times z plus 0 makes 2z. 2 times 1 plus 5 makes 7. And that's going to be infinitely many solutions. Okay, now if you want to have no solutions, then you want something like this. You want to do basically the same thing. X plus y plus z equals 1. 2x minus y equals 5. Just a couple of equations that I made up. And then over here I'm going to do 4x plus y plus 2z. And then I'll put anything but 7 here. So as long as I don't take twice the first row and add the second row, if I do something other than 7 here, I will get a contradiction because the left side is twice the first row plus the second row. The right side is not. So if I put anything but 7 there, how about minus 5? No solutions. So it's about linear combinations. That's what it's about. And last, for unique solution, really the thing about unique solution is that it's what almost always happens unless you've got some very special circumstance. So I'm just going to do here, how about the same first 2 rows? X plus y plus z equals 1, 2x minus y equals 5, and 4x plus y plus z, not 2z, just plus z. So something different here. The third row is not twice the first row plus the second. And I can write anything I like over here. 94. Okay, and there'd be unique solution. Okay, so the 3 things that can happen is there can be redundant, there can be a contradictory, or there can just be really kind of the random case of just any old jumble of things. Whoops. Come on, there we go. Okay. Okay, so that's what can happen in those three cases. All right, so let's bring up the material for the day. Come on, there we go. For some reason, the clicker is giving me trouble. Okay, so I want to look at, last time we had solution sets that had a particular form. It was a particular vector plus the vectors that made up the solution set of a homogeneous system, the associated homogeneous system. So that had a particular form, and last time I was a little bit, you can only do so many things at once. So I started off by introducing matrices and vectors and saying that they are, for the purposes of last class, they just were holding numbers. That's all. They were just like a little database that held numbers. Well, now I want to introduce, it's really, I expect it to be a review. I want to introduce the geometry that vectors and matrices, but really vectors at the moment, represent. So the thing is that there is, behind linear systems, there is a geometry. It all makes sense if you think about it geometrically. So you have to start somewhere. We started by solving them. That makes sense. But when you step back a little bit and look at what they're about, that makes a lot of sense too. So here, for example, are two equation, two unknown systems, 1, 2, 3 of them. This two equations, two unknown systems is a unique solution. You can see that the second equation is not a combination somehow, not 5 times the first or anything like that. This one here has no solutions. You can see that the second equation on the left-hand side is indeed just the first equation repeated, but on the right-hand side it isn't, so there's a contradiction there. No solutions. And over here you get infinitely many solutions because the second equation is really just double the first equation. It's a repeat. And when you think about the geometry, that's the three things that lines can do. When you plot these 3x plus 2y equals 7 and x minus y equals minus 1, when you plot them as lines, if they fall kind of askew here, or if they fall parallel here, or if they happen to be the same line, why then you get the three cases that can happen. So the fact that in linear systems three things can happen in these three pictures, it all makes sense now. You say, well, that's exactly what geometrically can happen, and that's indeed one of the advantages of the geometry, is that it makes clear to a person just exactly what could conceivably be going on. The geometry is a way to understand what linear systems have to say, and we'll be looking for as many different ways to understand what systems have to say as we can grab our hands on. Okay, so I want to talk then about the geometry. So to talk about the geometry of this general solution sets that we talked about last time, I have to start by talking about vectors. What are vectors? And again, I anticipate that this is, for most folks, this is a review, that you've seen this before either in a prior math class, so let's say Calculus 3, for example, or maybe in a physics class, for example. Okay, so for our purposes, a vector geometrically will be an object consisting of a magnitude and a direction, and the right way to think of it is that it models a displacement. In this case, for example, you might be going to the left by 1 and down by 1. And that's a displacement, and I've drawn that displacement as an arrow. The arrowhead, of course, points to where you end, and the beginning of the arrow points to where you started. Vectors, that is to say, for example, displacements, with the same magnitude in the same direction are equal. So I have a bunch of vectors drawn there on the plane, and they all have the same magnitude, they all have the same direction. They are the same vector. I know that they look like they're different vectors because they're drawn in different places, but they're all the same displacement. So they're all the same vector. Each of them is a 1 over and 2 up displacement. Okay, so if I want to write down what is the displacement, then I need to write down the start point and the end point and then do the subtraction. B1 minus A1 is the difference in the x direction. B2 minus A2 is the difference in the y direction. So for example, a 1 over 2 up vector is written as 1, 2. And we often picture a vector by starting at the origin, just because you got to start somewhere, so it's convenient to start at the origin. If you start at the origin, then the vector whose components are v1 and v2, for example 1 and 2, will end at x equals 1, y equals 2, or end at v1, x equals v1, and y equals v2. So we often say that the plane is the set of points x1, x2, or the plane is the set of vectors x1, x2. We won't really distinguish all that much. We'll find it convenient sometimes to blur the distinction between the point and the vector which, when started at the origin, ends at that point. And all this stuff, one advantage of all this stuff is that it all instantly extends to higher dimensions. So 3-dimensional, 4-dimensional, 5-dimensional, and sometimes when you work with linear systems, you're working with hundreds of unknowns, hundreds of equations. So you could have hundreds of dimensions in your vector, in your collection of vectors, and so all this stuff extends immediately to many dimensions. Okay. The operations that we introduced for vectors last time were addition and multiplication. Multiplication is the easier of the two, so starting with multiplication. If you multiply a vector times 3, you make it 3 times as long. Pointing in the same direction, but 3 times as long. If you multiply a vector by -1, you make it point in the other direction. If you multiplied a vector by -3, you'd make it point in the other direction and be 3 times as long as it was before. So scalars, the 3 or the -1 here, rescale the vector. The geometry is they simply make it bigger or smaller. That's all. The addition of two vectors, again, familiar. I expect that this is a review for most folks. The addition of two vectors is if you add v and w, then the way to construct the sum, v plus w, is you take the end point of v and the begin point of w, put the begin point of w on top of the end point of v, and then the vector v plus w extends from the beginning of v to the end of w. Again, we're thinking of vectors as being a displacement. So one way to imagine what's happening here is imagine that you're on a boat. And over the course of a minute, the boat moves this way. And you on the boat, on top of the deck, move this way. Then combined, your motion, the boat underneath you and you on the deck of the boat, your combined motion is this. You often hear this described as the parallelogram rule because you draw a parallelogram and then the v plus w extends from the lower corner to the upper corner. So it's got a kind of a nice picture. I want to talk about some of the usual geometry things that we're going to use throughout the course of the course. So, for example, a line. So we're used to maybe y equals mx plus b expression of a line, but we have a reason to think here about the vector expression of a line. This is the line that goes through 1, 2, and 3, 1. There it is in dark, 1, 2, and 3, 1. And you'll see that I've written that as 1, 2 plus t times 2 minus 1. So the 1, 2, of course, comes from the 1, 2, and there's the vector 1, 2. Where's the 2 minus 1 come from? So you take 3 minus 1 and 1 minus 2. Again, 3 minus 1 and 1 minus 2. In other words, you take the offset, so the slope. Take the offset and you get 2 and minus 1. So there's the 2 minus 1. That tells you how to get from the 1, 2 vector to the 3, 1 vector is the 2 minus 1 vector. Okay, and then of course this line, the dark line, is comprised of the endpoints of vectors that have this form for various t's. T equals 1, t equals 2, t equals 0, t equals minus 1, t equals minus 2. Okay? All that stuff is, I hope, familiar from previous classes. We often call that the direction vector for a line. 2 minus 1 is the direction vector for a line, and in higher dimension, you just have, instead of having 2 components, you might have 3 components, 4 components, 5 components, kind of stuff. Planes. So planes work basically the same way, and you'll recognize that this has a familiar form. It has the form of the solution set of a linear system, and that's why we're talking about all this stuff. Here's a plane drawn there in that kind of funny color, the yellowish color. So 1, 0, 5, 2, 1, minus 3, and minus 2, 4.5. So kind of just a generic plane, random plane, nothing special about it. And it consists of the endpoints of vectors in this set. You recognize the 1, 0, 5. That's actually this greenish vector here. So you recognize the 1, 0, 5. Where'd the 1, 1, minus 8 come from? Where'd the minus 3, 4, minus 4.5 come from? Well, it came from the same place that the vectors came on the previous slide. So where, for example, did the 1, 1, 8 come from? It's 2 minus 1, 1 minus 0, minus 3, take away 5. Where did the minus 3, 4, minus 4.5 come from? It's minus 2 take away 1, 4 take away 0, 0.5 take away 5. And that's the two red vectors that you see here. Those red vectors are drawn in the plane. This is the vector representing displacement, and this is the vector representing displacement. Okay, so the vector associated with t and the vector associated with s are drawn as red. They lie in the plane. Their body lies in the plane, not just the tip. The 1, 0, 5 vector, only its tip lies in this drawing. Only its tip touches the plane. It starts at the origin. And then those column vectors come from those places. A set of that form, a form that we at this point recognize as the solution set of a linear system, a set of that form is called a k-dimensional linear surface. This is, of course, going to be a two-dimensional linear surface because a plane is flat, so 2 dimensions. A k-dimensional linear surface, sometimes called a k-flat. Okay, so this, of course, takes us back to what we talked about last time, that we are talking about the solution sets of linear systems, and we can see them as having some sensible geometry. The subject is called linear algebra because everything is linear. Lines, planes, that kind of stuff. Okay. Okay, next time we're going to talk about length and angle measures. So we'll see you then next time. If I can work my systems here, we'll see you then next time. There we go. Okay. All right. Bye-bye. Hello, 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 hello. Welcome back. We're going to talk today about length and angle measure. But first, I want to do another quick example of some look-back questions. Some questions about the previous section that will, I hope, give a person some sense of whether they know what's going on. So for starters here, we have these three. So the first one is, what is a linear equation? So if you have an x plus 2y plus 3z equals 4, or a minus x plus 2y minus z equals 1, what does that represent geometrically? So, of course, in doing the homework, and because the materials review probably from previous classes, you recognize that x plus 2y plus 3z equals 4 is, strictly speaking, is a one-equation linear system. One-equation linear system with two free variables, y and z. So you can express x in terms of y and z. It's not very hard. You can express x in terms of y and z, and so you get a solution set that looks like particular vector plus y times a vector plus z times a vector. So again, x plus 2y plus 3z equals 4, or the other one, is a linear system with one equation. So we know what the solution set looks like, and the solution set looks like the equation that we saw last time for a plane. So x plus 2y plus 3z equals 4 is some kind of plane in 3 space. It's a two-dimensional flat surface in 3 space. And likewise, minus x plus 2y minus z equals 1 is also a flat two-dimensional surface inside of 3 space. Okay. So that's why we're interested in, that's why we call the course linear algebra, because it's about these linear things. What are the possibilities, question 2, what are the possibilities for the intersection of two planes? So really the point of this question is to have a person think about, in your head, you imagine two planes. Some people are better at imagining these kind of things than others, but still, two planes, it's like two pieces of paper. If you lay two pieces of paper out in space, what can happen to those two pieces of paper? Well, it seems to me there's a limited number of cases. If you have two planes, it can be the case that the two planes are parallel. That could happen. It only happens in a special case, but nonetheless, it could happen that the two planes are parallel and never touch. The other possibility is that it can be that the two planes are canted at some kind of angle to each other, and so in fact the two planes touch, and when they touch, they meet in a line. It's not possible for two planes to intersect in exactly 2 points. It's not possible for two planes to intersect in exactly 1 point. If two planes intersect, they have to intersect either in 0 points, meaning that they're parallel planes, or else in a line, in infinitely many points. And then, of course, question 3 is the three planes. What can happen? So if we have three planes, which we're linking in our mind with three linear equations, if we have three planes, what can happen? Why, it can be the case that two or maybe all three of them are parallel to each other. That can happen. So there is, in fact, no common intersection to the three planes. That could happen. A more likely case, though, is that the three planes intersect in the following way, that two of the planes intersect in a line, and then the third plane cuts that line, so that you find one point, a single unique point, a common point for the three planes to intersect. And then the last thing that can happen, and again it probably strikes a person as unlikely, but doesn't mean you couldn't make up an example of it, is the first two planes intersect in the line that we just had a second ago, and the third plane also happens to share that line, so all three planes intersect in that line. So the two cases, the cases of where the three planes are parallel, might strike you as being not very typical, as being a little bit unusual, a little bit off the beaten path. You said, well, you'd have to set the system up very specially in order to have that happen. That's probably true. And likewise, to have the three planes intersect in a single line, you say, well, if you're just going to throw three planes into space, you wouldn't think that would happen. Yes, very true. And then the third case, that the three planes intersect in a single point, two of the planes intersect at a line, and then the third plane cuts the line. That's kind of, you say to yourself, that's kind of the case that I kind of expect to happen most of the time. Yeah, that's right. We've used the word non-singular before. But anyway, that's kind of the random case that you think would happen most often. Okay, all right, so let me go to today's material on length and angle measure, and again, I'm anticipating that the material for today is largely a review, that you probably had it before in some other math class like Calculus 3, or else you might have had it in say, a physics class or some other class like that. And so we're going to go through it a little bit more quickly than we go through material that we thought was entirely new to everybody. Okay, so the length of a vector. Length of a vector is the Pythagorean length. You take you square each of the components, and then you take the square root. You square each of the components, sum them up, and take the square root. We use absolute value bars for length here, just because absolute value bars are the general symbol that you use in mathematics to indicate magnitude or size of, and so that makes sense for length of a vector. And just as an example, the length of -1, -2, -3 works out to be 14. Notice that the negative signs do not matter. You don't run into trouble with length when the vector points in the negative direction or any such thing. The squares make the negatives go away. So the length of this particular vector is the square root of 14, which is not a very particularly handy number. It will often be the case that we want to take vectors that are of kind of an arbitrary length, like square root of 14, and resize them to make them be of length 1. So we'll take this vector and come up with a new vector that has length 1 for a size. And the right way to do that, that's called normalizing the length. The right way to do that is to divide the vector by its size. In this case, I will multiply v by 1 over the square root of 14. Multiply v by 1 over the square root of 14. See the length of v on the bottom of that fraction, and we end up with a square root of 14 on the bottom of each of those three fractions. And when you do the calculation, -1 over the square root of 14 quantity squared, -2 over the square root of 14 quantity squared, -3 over the square root of 14 quantity squared, and you add them all up and take the square root, you end up with 1, which is what I wanted. So normalizing is how you turn a vector and start with a vector and get a new one whose length is 1. And it works as long as the original vector is not the 0 vector. Of course, if you tried to divide the 0 vector by its own length, you'd find yourself somewhere where you don't want to be. Okay, I want to introduce an operation. Again, I'm anticipating that this is review for folks, so introduce in some, in not really telling the truth sense. This operation is called the dot product, sometimes inner product, sometimes called scalar product. Authors call them different things. In this context, of two n-component real vectors, they have to have the same number of components. Dot product of two n-component real vectors is you take their components, first components, second component, third components, you multiply the components, multiply together the first components, multiply together the second components, etc., down to multiplying together the nth components, and then you add the result. In this book, I'm writing it with kind of a bold-faced dot. That's just you know, just a convention that I've adopted. You can't write a bold-faced dot on the whiteboard, so there's, you know, only so much a person can do there. But I do think that the making the dot especially dark helps a person to remember that it's not regular multiplication, not scalar multiplication. It is instead some different operation. Person could tell, of course, because they're vectors, that it isn't scalar multiplication. But anyway, I've adopted this kind of darker dot that you won't necessarily see in other books. And it's not hard here to do the operation. 1 times 3, 1 times minus 3, minus 1 times 4, add them all up. Turns out it adds to minus 4 in this case. And the thing to notice about the result is that when you take two vectors and combine them in this way, you don't get a vector, you get a scalar, which is why it's often called scalar product. Okay, and then the other thing to notice with the dot product is that if you take the dot product of a vector with itself, you get the vector's length. The importance of dot product is that it tells us something about the spaces that we're interested in, about the linear spaces that we're interested in, and this result really gives you the central core of the idea here. Is that if you have two vectors, u and v in real n space, so you have available the dot product, then the length of u plus v is less than or equal to the length of u plus the length of v. And this picture really tells you what you want to know here. The length of u plus v, so that's the length of u plus v right there, that's the darker of the two vectors, is less than or equal to the length of u plus the length of v. And of course that person recognizes it because it's written on the slide, that the shortest distance between 2 points is in a straight line. So that's called the triangle inequality for the obvious reason, because you illustrate it by drawing a triangle, but it says something about how spaces work. It says that spaces are flat in some sense. The proof of the triangle inequality, you can find all kinds of proof of them all over the internet. For example, if you Google, but I chose a particular one that I want to illustrate something. So because all of the numbers are positive, I can square both sides here, and I don't have to worry about changing the direction of the inequality. So I took the length of u plus v and squared it, and I took the length of u plus the length of v and I squared it. And from the previous slide, I remember that the length of a vector, the length of u plus v in this case, the length of a vector squared is equal to the vector dotted with itself. And here, when you square a plus b, you get a squared plus 2ab plus b squared, and so I just multiply that out. And then you go on and do some algebra. It turns out, we haven't given it as a lemma, but it's one of the exercises. It turns out that you can distribute the dot over the plus sign here and get u dot v, excuse me, u dot u and u dot v, and v dot u and v dot v. And likewise here, length u quantity squared is u dot u, length v quantity squared is v dot v. You see that the u dot u and the u dot u cancel. You see that the v dot v, oops, there it is, the v dot v and the v dot v cancel. And when all the smoke clears, we've got 2 times u dot v, the u dot v and the v dot u give the same answer. 2 times u dot v is equal to 2 times length u, length v. Of course, you can cancel the 2's to get u dot v is less than or equal to, I said equal to a minute ago, forgive me, I'm sorry, less than or equal to, u dot v is less than or equal to length u, length v. Remember, u dot v is a scalar, so less than or equal to makes sense. I want to show that that's true. And so I'm going to pull the following trick. This part up here, it was all perfectly routine sort of plug and chug stuff, but now I'm going to pull a trick that probably would not occur to a person right off the top of their head. I'm going to multiply both sides by the non-negative numbers length of u and length of v, and then I'm going to group it in a way that you wouldn't think to group, and that's, so there's a trick here, and but it gives me this. I'm interested in this inequality along the way, so I need that trick. I'm taking length v multiplied by u and length u multiplied by v. And here I have 2 times the length u squared and length v squared. And I rewrite the whole thing by moving everybody to one side of the equation. You recognize that that's the equation for a square. And you recognize that it's got to be true because when you square something, you've got to get a positive. So this must be true, and since it's equivalent to what's at the top of the screen, that the thing at the top of the screen is true. But again, my main interest in the proof is that along the way I ended up bumping up against this inequality. The fact that the equality holds only when the length u times v minus the length v times u is a zero vector, and that can only happen in the case that one vector is a multiple of the other. For example, if v is length v over length u multiplied by u. And I mentioned a number of times here is that I was keen on this inequality here, so that's why I did that particular proof. And it came up in the course of the triangle inequality, so I was interested in it for that purposes. That was the reason to go through that particular proof of the triangle inequality. Okay, so I said I was going to do length and angles. We're going to need angles at some point, so that fits with length, so we're throwing it in here. So the angle between two vectors is given by that equation. Oops, my mouse is in the way. The angle between two vectors is given by that equation. You take u dot v, you divide by length u, length v, and you recognize that stuff appeared in the triangle inequality. I mean, it's all tied together, and then you want to view that as the cosine of the angle you want. So if you have two vectors like u and v in space here, to find the angle between them, the cosine of that angle, pardon me, the cosine of that angle is this expression here. And the basic idea is that if neither one of them is a multiple of the other, then they form a plane. You bring them down to start at the origin, and they form a plane. And in that plane, you can apply whatever stuff you remember from high school trigonometry. And one thing you might remember from high school trigonometry is the law of cosines. Do you remember the law of cosines? Probably not, but it rings a little bit of a bell. It's a generalization of the Pythagorean theorem to non-right angles. There we go, there's the law of cosines, and I'm not going to go through the details here. It's basically the same sort of stuff. You cancel the sides, and it gives you the expression that I had on the previous screen. That expression, the expression on the previous screen, that expression on the previous screen here is tells you that has the special case for when they form a right angle. So the two vectors are perpendicular. They form a right angle, orthogonal. Perpendicular, they form a right angle if and only if their dot product is 0. So the only way that you get a right angle in this expression is if the top of the fraction is a 0. And of course, they're parallel only in the other case. Okay, so that expression for the angle here tells you when they're perpendicular, and we will not use it as often, but it also tells you when they're parallel. Okay, that's the material on length and angles. There we go, and I'll see you next time when we're going to talk about an extension to Gauss's method called Gauss-Jordan reduction. Okay, very good. Thank you. Bye-bye. Hi, hello. So today we want to talk about an extension to Gauss's method called Gauss-Jordan's method that has some advantages. So before we start that, I want to revisit what the geometry of solution sets are. When I do these sort of check-ins, these quick questions, one of the things I try to do is to connect what happened in the last class, or maybe the class before, to this class, to this discussion. So so that's what's happening here. I want to look at 3 questions. The first is says this is a solution set of a linear system. I'm not going to give you the linear system because I want to talk about the sketch. I want to draw a picture of what that solution set looks like. And of course, the lesson that we learned last time is that this is a plane in this is a plane in R3. So I'm not a very good sketcher, I'm sorry, so that's why I use the word sketch or instead of draw precisely. So I'll do the best I can. So so the idea is something like you have a plane somehow. See how I do. Did I leave enough room for the x-axis and the z-axis and all that kind of stuff? There's the z. Oh, I didn't leave it. I didn't do it right. All right, there's the z-axis and the x-axis, and the y-axis is somehow, who the hell knows? So x, y, and z. Who the hell knows? Okay, so that's the solution set of some linear system, and the particular linear system isn't important. What matters is that we are somehow looking at a plane in R2. This is the set of all vectors x, y, z, which can be written in the form 1, 1, 2 plus, and then there's 2 where you have vector times a letter, vector times a letter. So it's 1, 2, 1, and I use the letter t, and then a 0, 2, minus 1. My t and my plus look too much alike. 0, 2, minus 1 times s. Okay? Now, a person can make sense of those parts of the expression. We talked about this being the homogeneous part, and we talked about this being the particular part. A person can make sense of those parts of the expression, and we saw that last time. I'll use a pencil here. Pencil doesn't come out as well on this particular camera, but it gives me sort of a different color. So the 1, 1, 2, the 1, 1, 2 vector somehow looks like so. 1, 1, 2. Okay. It gives you, it's a vector that starts at 0, 0, 0, and whose endpoint is 1, 1, 2. So the endpoint of that vector just touches the plane. Of course, you can draw 1, 1, 2 anywhere in space, and it'll be the same vector, but I choose to draw it so that it starts at 0, 0, 0. And then what's the 1, 2, 1 and the 0, 2, minus 1? Why, if you draw 1, 2, 1, and I'm 1, 2, minus 1. If you draw 1, 2, minus 1, I didn't write the minus sign there, sorry about that. If you draw 1, 2, minus 1, then you get a vector that somehow lies in the plane. The entire body of that vector lies in the plane. I didn't start that one at 0, 0, 0. So the entire body of that vector lies in the plane. If the plane was colored red, that entire vector would be colored red, but only the very tip of that vector would be colored red. And of course, 0, 2, minus 1, same sort of stuff. 0, 2, minus 1. Also, the entire body of 0, 2, minus 1 lies in the plane. The entire vector would be colored red. Okay, so we can identify the parts here. The particular reaches out from the floor and just touches the plane. The homogeneous parts lie entirely within the plane. Okay. One thing I want to point out about this that leads into the discussion we're going to have moving forward, and that is that a person might think we're solving linear systems. A person very sensibly might think we're solving linear systems, and so I'm interested in the particular solution, the 1, 1, 2, because that solves the linear system. That's one of the vectors. When you plug it into the linear system, gives you the answers on the right-hand side. So this is what I'm really interested in. But that proves to be not really right. There's another point of view that proves to be the more fruitful one. And that is that what's interesting about this solution set is that there are infinitely many solutions. Where does that sort of infinite ability to make infinitely many solutions come from? And the answer is it comes from the homogeneous part. It comes from this vector and this vector. So the 1, 2, minus 1 and the 0, 2, minus 1 are sort of the interesting part of this picture. And the 1, 1, 2 simply takes you, it's like an elevator, it takes you from the floor, takes you from, excuse me, the entrance up to the floor you want to go. So in some ways I think of this, it's a little silly analogy, but it's the analogy that I like. So if you want to play tennis, if what you're interested in is playing tennis, then what you're interested in is what happens on the tennis court. And this vector here is taking you to the tennis court. This vector here is the actual court. So this is only taking you to the court. This is where the real action happens. This vector here takes you to the court, and these two vectors give you the real action, the infinitely many solutions. Now we see that when we go to the second question. If I bring back the second question, if I do it right, always a big if. Come on, there we go. It says find the particular solution vector for t equals -1 and s equals 1, and then sketch it. So find the particular solution vector for t equals -1 and s equals 1. So I'm simply going to plug in, this was 1, this is 2. I'm simply going to plug in t equals -1 and s equals 1. So I get 1, 1, 2 plus 1, 2, minus 1. Remember the minus 1 that time, times -1 plus 0, 2, minus 1 times 1. And I'm not very good with arithmetic, so I got to be super careful. So I'll do that as 1, 1, 2 plus -1, minus 2 plus 1 plus 0, 2, minus 1. And even I ought to be able to add those up. That's 0, 1, and 2. Okay, and it says sketch it, and the only point of the sketch it is to make you think of that vector as living somewhere in 3 space. So 0, 1, 2, 0, 1, 2 looks somehow like, I'll draw it like I drew the other ones in pencil. 0, 1, 2 looks somehow like so. Okay, and then part 3, for question part 3, and again it's always tricky when I bounce that one up, is I took the old set here, 1, 1, 2, and I replaced the particular solution with the 0, 1, 2. So I replaced the 1, 1, 2, what happens when you take t equals 0 and s equals 0, and I replace it with what happens when you take t equals -1 and s equals 1. And then it says sketch it. Right here, sketch this. And of course pop it down. Of course, so for part 3, the answer is C part 1. That is to say, it's the exact same sketch. It's the exact same set of solutions. If you change the old particular solution to a new particular solution, anyone, I could have taken anything value there and any value there. If you change the old particular solution to a new particular solution, it leaves you with the exact same solution set. Instead of having this way to get to the tennis court, and my maybe stupid analogy, you have a new way to get to the tennis court, like so. But it still takes you up to the tennis court, still takes you up to the plane. That is to say, in some sense, the plane is where the real action happens, and all the particular solution, you can swap out the particular solution for a new one, all the particular solution does is take you to that plane. So the solution set of this linear system, which I didn't bother to give you, is a plane in 3 space, and you start at the origin, you use a particular solution as the offset to take you to that plane, and the real action happens on the plane. So the geometry I'm directing your attention to is that this part here, the part we call the solution to the associated homogeneous system, this part here is what gives us the interesting behavior, the infinitely many solutions. And this part here, the particular solution, is not special in the sense that I can change it for a different particular solution and I get exactly the same plane for a solution set. Okay, so we will, moving forward, we will be interested in the particular solution more than we are, we'll be interested, in the homogeneous solution more than we are interested in the particular solution. When we try to study what is it about solution sets of linear systems, what is it about these planes in 3 space or in general flats, what's happening there, we will be less interested in the offsetter than we will be interested in kind of where the action happens. Okay. Let's bring that down and bring up what we want to talk about today. So far in this series of talks, we've been doing Gauss's method, and then spent a couple minutes trying to make some conceptual sense of what we got there, the solution sets of linear systems. So we did Gauss's method, and we're able to write the solution sets of linear systems in some organized way using the vector notation, and then we took a second to review, or maybe for some folks it might be a first look, but in general review what the vector description of the solution set has to tell us. Okay, and what I want to do today is I want to introduce an extension to Gauss's method, so-called Gauss-Jordan. I want to introduce an extension to Gauss's method that will have some advantages and that will tell us something about what we're doing. Okay, what happened? Why am I not? Oh, I see. There we go. Okay, so it's called Gauss-Jordan reduction. Apologize, hit the wrong button. It's called Gauss-Jordan reduction. So, so I have a linear system here, and it doesn't look especially doesn't does doesn't look especially different than any other linear system we've been working with. I used Gauss's method to the minus 2 row 1 plus row 2 kind of stuff, and I got to echelon form down here, and we could absolutely solve the system. For example, it's plane from what I have written here that's equals to. But I want to go on here. Instead of just doing back substitution, I'm going to continue doing row operations, and I'm going to go on to get the system, in some sense, completely reduced. Instead of having this junk up here, I'll turn those into zeros also. So we'll start off, I have a particular process in mind. I'll start off by, here I have a 1 in front of x and a minus 3 in front of y and a 1 in front of z. I want to turn all the coefficients of the leading variables into 1s. So of course I'm going to take minus 1/3 row 2. And then I'll take that system, that right here is the same system as from the previous screen. I copied it because I didn't have enough room all on one screen. And I want to introduce a new kind of step. Before, I first use the x to eliminate, and then I use the y to eliminate both of them down. Here, I'm going to eliminate up. When you eliminate up, you don't start with x. Instead, when you eliminate x, you start and you work right to left. So I'm going to start with the z that's right here. And I'm going to use this row, row 3, to eliminate the minus 2/3 z, and I'm going to use this row, row 3, to eliminate the minus z. So we know how to do those steps, it's just that we've never thought to do them up before. So using the row 3 to simplify row 2 is to take 2/3 row 3 plus row 2. 2/3 row 3 plus row 2. We'll turn that into a 0. And you see it there, 0. I just have simply the y equals 3. Of course, when you take 2/3 of 2 and add to 5/3. So anyway, you get y equals 3. And likewise, if I want to use this row, row 3, to eliminate that minus z, then I need to take row 3, add it to row 1. Notice that the changed rows, as before, the changed row is always written second, and the row you're using to act on the changed row is written first. You've got to write them in some order. You might as well write them in the same order every time. So when you do this, you've used z to eliminate both of the things above it. So we're not only clearing out downstairs, we're clearing out upstairs also. And a person can guess what's going to happen next. I'm going to move from right to left. I'm going to use this y to get rid of that y with a minus row 2 add to row 1. So there we go. Now this method has a disadvantage that there's more arithmetic than with Gauss's method, but it has the advantage that when you finish, the answer's right there, just looking at you. So using one entry to clear out the entire rest of the column is called pivoting on that entry. So for example, I've cleared out the entire rest of the z column here, I've cleared out the entire rest of the y column, and I actually came to this screen with the x having cleared out the rest of the x column. It's called pivoting on that entry because of some geometry that we're not going to go into. So I don't like to do one example of anything, especially something very important, so I'm doing another example. You see here that this is a 3-equation, 4 unknown system, 3 equations, 4 letters. So I must be going to end up with a row, at least one row, that does not have, at least one variable that does not lead a row. So just to do something different, I just thought to do a system that will have infinitely many solutions. Looks perfectly innocuous linear system, and it is perfectly innocuous. So of course we recognize the Gauss's method. It so happens that it takes only one row operation to do Gauss's method, and to get so that below this diagonal is all zeros. Only took one operation, and you get some other arithmetic, and it's not very interesting. Next step, so after you clear out below the diagonal, next step is to turn the diagonal into ones. So I have to turn the 2 into a 1, I have to turn the 5/2 into a 1, and that involves some other arithmetic on the row, but again, it isn't especially hard and it isn't especially interesting. The new part, the part that we haven't seen before, is to eliminate upwards, is to use the one that's here to eliminate above it, and to use the one that's here to eliminate above it. Now I couldn't fit it all on one screen, but to use the one that's here to eliminate above it, oh, forgive me, what did I do wrong? Oh, there it is. Forgive me, I lost sight of what I was doing. Use the one that's here to eliminate above it. There we go. Takes minus 3 has row 3 plus row 2. There we go. And then to use the one to eliminate above it takes row 2 plus row 1, and I end up with a system. I didn't, something was in my way, I'm sorry. So end up with a system that it has this property that below the diagonal is all zeros and above the diagonal is all zeros, and there's some other junk simply because there are more unknowns than there are equations. So you can't have the case that every unknown leads an equation. So we have some other junk and some other junk. Here, the rest of the description, there's the matrix copied from the previous screen. The rest of the job is to put it into a description, a parameterized description of the solution set, and a person can't help but notice that just like on the previous problem where I said the disadvantage is more arithmetic, but the advantage is that it gives you the solution set plainly written out. Well, look, I mean, we've got the solution set plainly written out. It's just a question of transcribing it to write down the solution set. So this particular method here, you see that these have changed their sign, changed their SIGN. To write down the solution set is once you have this form, to write down the solution set is all very straightforward. So this Gauss-Jordan elimination has the disadvantage of more arithmetic, and when you're doing it by hand, then it can get a little uglier and you make a lot of mistakes. Believe me, I've made many, many mistakes on these over the years. Although in this computer age, I make fewer because I get the computer to do it for me. But it has the advantage that to get from this final matrix to the solution set is just trivial transcription. So this extension to Gauss's method is called Gauss-Jordan method or Gauss-Jordan reduction. Just a small historical word. This Jordan is not the same Jordan that will appear at the very end of the course. Just a coincidence that they both had the same last name. So just not that it matters, but this is called Gauss-Jordan method, and it's not the same Jordan as a Jordan you haven't heard about yet. Not the same as the Camille Jordan. So so I'm going to call that form. I can't call it echelon form because I use that word for a different form. So I'm going to call that reduced echelon form. So a matrix or a linear system's in reduced echelon form if addition to being in echelon form, not only do you have zeros below the diagonal, but you also have every entry on the diagonal is a 1, and every leading entry is a 1. And it's the only non-zero entry in its column. So you've pivoted on that entry and cleared completely out of that column. And again, the cost of Gauss-Jordan reduction is that it takes additional arithmetic. People have spent a lot of time in the computer age counting the number of steps that each method of solving a system takes, and it turns out that Gauss's method takes fewer steps. So the cost of Gauss-Jordan reduction is the additional arithmetic, but the benefit is that the solution set is quite plain. It will have other benefits for us also, but in particular at this moment it's perfectly clear that that's a benefit. Now I want to talk about some of these other benefits. The first is that what we're going to occupy ourselves with today is that I want to point out that that we get something about the solutions, about the solution matrices. First, an observation. Elementary row operations are reversible. When I do Gauss method here, or Gauss-Jordan method, there we go. When I do Gauss's method or Gauss-Jordan method, I have a mental image that I start with some kind of mess and I end with something that's very neat. So that is to say, I have a mental image that I proceed. This one comes after, and then comes after, and then comes after, and then finally I arrive at my goal. So I have a sense of some kind of that they proceed in some order. But in fact, that proves to not really be perfectly right. If I do Gauss's method on a matrix, any of the Gauss's method operations, if I do any of the Gauss's method operations, the elementary row operations, on a matrix, then I can reverse them. So for example, if I write down a matrix A and swap row I and row J, and then swap row J and row I, I'll be back to the original matrix again. If I write down a matrix and multiply row I by k, if k is not 0, and then multiply row I, same row, by 1 over k, I'm back to the original matrix. If I write down a matrix and take k row I plus row j, and then do minus k row I plus row j, I'm back to the original matrix. You notice in particular that the third case requires that i's be unequal to j. This also has the restriction that k can't be 0. And we somewhat artificially put in the restriction that I and j are not allowed to be equal for row swaps. But all that is a minor point. The major point is that each of these row operations are reducible. So whereas before I thought of myself as naturally going from upper left to lower right. In fact, I could, if I wanted to, if for some perverse reason I wanted, for example, if I wanted to make a homework question, I could go from lower right and make my way back to upper left. So that's to say it's a little bit of a linguistic problem that I describe myself as reducing from here to here, because in fact these are interreducible. It's not the case that this is somehow lesser or after this. In fact, they are sort of equal to each other. I can go from the one to the other, sensibly go from the one to the other. So we say that matrices reduced to each other are equivalent with respect to row operations. It's a little awkward phrase, but the point of the phrase is to give some implication that you should not necessarily, I'm asking you to not necessarily think of the reduced matrices as somehow later or lesser. That in fact they're the same. They contain exactly the same information as the original matrix. So the way that you write this down formally is you describe the phrase that the matrix between matrices reduces to via elementary row operations is an equivalence relation. Been my experience that sometimes people taking this course, many times people taking this course, have not talked about equivalence relations or have not talked about it very much. Sometimes people have taken this course having already had the proofs course, and so they've taken a proofs course that described equivalence relations. That's great, good for you, good for you. But for those folks who have not, I'm going to play down a little bit the technical phrase equivalence relation and play up a little bit more the intuition. And the intuition is exactly that. Although we think of this matrix here as being somehow after this matrix, that's not really sensible. We can in fact go from this matrix over to this matrix, and I do that sometimes when I'm making homework problems. That in fact all of these matrices 1, 2, 3, 4, 5 are interreducible. They're all collected together in some sense. They're all somehow the same. They contain the same information as each other. So they are equivalent in some sense. The technical jargon is equivalence relation. They're equivalent in some sense. They are equivalent in the sense that they all somehow contain same linear information. We'll describe them all as row equivalent. The picture to have here is that I've broken the collection of all matrices. The previous slide showed 2 row, 3 column matrices, but in here I could have all matrices. I've broken the collection of all matrices up into different equivalence classes. Inside of a particular class are matrices that are equivalent to each other. So on the prior slide I had 5 matrices, 1, 2, 3, 4, 5. All of them go in the same class. They all can be interrelated to each the other. Isn't that a terrible phrase? They're all interrelated. So I could stick all 5 of those matrices in this section here, and they're all row equivalent. So one thing that we're seeing is that Gauss's method, Gauss-Jordan method in particular, enables you to break the universe of matrices up into different types of matrices. And one type of matrix is this type right here, is the matrix that contains whatever this kind of information is. Okay? So we break the universe up into row equivalent classes. Okay, very good. Okay, so let's see here. Next time we're going to talk about, oops, I went too far. Next time we're going to talk about the linear combination lemma. So I'll put that slide up. and we'll see you then next time. Very good. Hi, hello. Okay, so last time we talked about Gauss-Jordan reduction, and we ended by talking about matrices being row equivalent. So today we're going to use the Gauss-Jordan reduction to make an observation about how to tell when matrices are row equivalent. I want to start by reviewing row equivalence. I want to, in the check-in, I want to give a quick sort of idea of what row equivalence is about. Okay, so the first question, really a couple of straightforward questions. Produce two matrices that are row equivalent, and then produce two matrices that are not row equivalent. It would be pretty silly if I had a relationship between matrices and all of them satisfy it. That'd be pretty silly. So let me do the first one. Produce two matrices that are row equivalent, and of course I can give all kinds of answers. I can give a matrix with itself, for example. That'd be silly but technically correct. But I want to get across something that makes the lesson for later on in the course. So so the idea here is I want to look at two matrices that are row equivalent to contain some concept. So the concept is that matrices are row equivalent when they contain somehow the same information. So my example of two matrices that are row equivalent is going to be this. How about 1, 1, 3, and 0, 1, 1 from my first matrix. And you know what? I'm going to make it an augmented matrix to make it look like a linear system, to make it look like I'm solving a linear system. And when I do, it would be natural to do the Gauss-Jordan step here of minus row 2 add to row 1 and end up with the matrix 1, 0, 2, 0, 1, 1. Those two matrices are row equivalent, and the row equivalence has a conceptual feeling here that the reason they're row equivalent, technically they're row equivalent, the reason they're row equivalent is that they contain somehow the same information. They, in this case, are supposed to represent linear systems with the same solution, namely x equals 2, y equals 1. So row equivalence has a meaning. It somehow contains, tries to capture that two linear systems are row equivalent when they say the same thing in some sense. In this case, they say that the linear system has that unique solution. Of course, I could have made up other row equivalences. I could have made up, say, a 3 by 3 matrix and done 3 or 4 Gauss method steps, and then I'd have two row equivalent matrices. That's all perfectly fine. I could have made up a matrix and then multiplied the first row by 5. That's all perfectly fine. But this one, I think, captures an idea. So let's see, what was the the second question was to make up two that are not row equivalent. Okay, well, one cheap way cheap answer, smart guy, wise Alec way to make up two matrices that are not row equivalent is to make up different sized matrices. 1, 2, 3, 4 is not row equivalent. I'll put a twiddle with a slash. Not row equivalent. That's just a symbol. 1, 2, 3, 4, 5, 6, 7, 8, 9. True, but not really. Not really showing any concepts. So maybe something that shows a little more in the way of concepts is, how about this one here? If I have 1, 0, 0, 0, 0, 0, and I contrast it with 0, 0, 0, 0, 1, 0. And now I can say, you can think of those as augmented matrices if you like. I won't bother to write in the vertical bar. Now, when I say they're not row equivalent, I'm making the observation that you cannot get from here to here by doing row operations. And the reason is simple. There's no ones in that column. There's no way you can manufacture a 1. No combination of these two, of the 0 and the 0, will allow you to make a 1. Or going in the reverse direction, no combination of these zeros will allow you to make that 1. So these two matrices are not row equivalent. So the relation row equivalence is not trivial. Some matrices are row equivalent. I know this is a silly way to be not row equivalent, but this is less silly. Some matrices are not row equivalent. And here I had in mind one more example. Suppose I look at 1, 0, 0, 0, 1, 1, And also I should have put a twiddle with a slash to it. And also 1, 3, 3, 0, 1, 1. Now these two matrices are row equivalent because I can get from the first to the second by some row operations. I can take 3 times row 2 and add to row 1. I take that linear combination 3 times row 2 and add to row 1, and that'll take me from here to here, or I can reverse it. I can do the Gauss-Jordan step of taking minus 3 row 2 adding to row 1 and get to here. They are interreducible. But if I contrast what's here with this one, 1, 3, 2, 0, 1, 1, there's no way to get from here to here. These are not row equivalent. There's no way to get from here to here, because if you're going to get a 3 there, you've got to get it by somehow using the 1. Oops, sorry, using the 1. If you're using that 1, you've got to use this 1. So these two have to be the same number. So again, row equivalence has something to say about the linear content of this collection of rows. The linear content of this collection of rows. Somehow this collection of rows has a different linear content than this collection of rows, but this collection has the same as this. The question we want to address today is how can you tell when two matrices have the same, sort of the same information in them? And I know, of course, that's all very vague, but we're going to make precise definitions today. We're working on it. We're working on it. Whoops, went to the wrong place. Sorry about that. There we go. Okay, so when I was first started teaching, I had a professor that I worked with. I was a teaching assistant for this professor who every day would say at least 15 times, "This is very important." Well, when everything's important, then nothing's important. And Van Clausewitz made the same observation. He said a general that protects everything protects nothing. A general that defends everything defends nothing. And I hope that I've gotten pretty good about only saying this is important for those things that are really super important. This is super important. So the linear combination lemma is really at the heart of an awful lot of what we're going to be doing in the rest of the semester. So just to ask you to sort of pay sort of a special attention to what to what happens next. Okay, so the linear combination lemma. So I want to talk about how Gauss's method acts, and the way that it proceeds. Of course, we've seen it acting here. The way that it proceeds is illustrated by this simple Gauss-Jordan elimination here. Okay, so I eliminated below the diagonal. I changed the diagonal to 1s, changed the leading entries to 1s, and then I eliminated above. I'm going to call those matrices capital A, capital D, capital G, and capital B. I want to use delta and gamma for the letters for that matrix. Anyway, I'm going to call them by those letters. And then the point is that the steps that I go through, the minus 2 row 1 plus row 2, the minus 1/2 row 2, and the minus 3 row 2 plus row 1, the steps that I go through do something to the rows of the matrix. The rows of the second matrix, here first, second, the rows of the second matrix somehow reflect the rows of the first matrix, and it's just as straightforward. If you start off with alpha 1 and alpha 2 for the rows of A, then delta 1 and delta 2 it's just simply that delta 1 is alpha 1 and delta 2 is minus 2 alpha 1 plus alpha 2, because that's exactly what it says right here, is that you want to make the second row be minus 2 times the first row plus the second. So that might strike you as doesn't say anything you didn't know before. When I do the next operation, minus 1/2 row 2, of course, to get the matrix G, the rows now are that the first row of the matrix G, I call it gamma. First row of the matrix G is still alpha 1. The second row of the matrix G is half of the second row of the matrix D. So I halved everything. Minus 2 alpha 1 became alpha 1. Alpha 2 became minus 1/2 alpha 2. And last, I went from this matrix here to this matrix here with some kind of Gauss's method combination step. minus 3 row 2 plus row 1, and now you see it happening. This is the matrix B. So row 1 of the matrix B and row 2 of the matrix B. Row 2 of the matrix B is the same as row 2 of the matrix G, because that's how we proceed. We leave the acting row unchanged, and the acted on row is the one that gets changed. So I took minus 3 row 2 plus row 1. Minus 3 times alpha 1 added to alpha 1 became minus 2 alpha 1. Minus 3 times minus 1 half makes positive 3 halves alpha 2. Added to 0 alpha 2 became 3 halves alpha 2. So Gauss's method acts by taking linear combinations of the rows. The matrix at the end has linear combinations of the rows of the matrix at the beginning. We are studying linear combinations. Gauss's method proceeds by taking linear combinations. That's all this says. If you look in there, you're seeing linear combinations of the rows of the starting matrix. That's all it says. Small observation, but a lot of times big things are built on small observation. And the linear combination lemma is codifying that small observation. It says that a linear combination of linear combinations is a linear combination. What is that? What does that? What does that mean? So, for instance, if you take a linear combination like 4x1 plus 5x2, and another linear combination 7x1 plus 8x2, and you write them down, there's the 4 and the 5, there's the 7 and the 8, and you take a linear combination of those two, 3 times the first plus 6 times the second. What you end up with when all the smoke clears, 3 times 4, 6 times 7, that gives you 54. 3 times 5, 6 times 8, that gives you 63, if I did it right. If you take a linear combinations, two of them, and you find linear combinations of them, you end up with a linear combination. A linear combination of x1 and x2 combined with a linear combination of x1 and x2 gives you a linear combination of x1 and x2. A linear combination of linear combinations is a linear combination. It's a small observation, but an important one. Before we go on, I've got to give the argument, but before we go on, I'll just note that if you take quadratic combinations of quadratic combinations, just as an example, if you take quadratic combinations of quadratic combinations, what happens when you take quadratics of quadratics? Well, of course, you end up with all kinds of junk. You got third powers and fourth powers. So a quadratic combination of quadratic combinations is not a quadratic combination. There's something about linear. We're studying a property at least peculiar to linear. And the proof is taking this example and writing it down with A's and B's and C's sort of stuff. So I have a bunch of linear combinations of x1 through xn. There they are. And I take d1 times the first all the way down through dm times the last. And then just distribute d1 over the c's through dm over the c's, gather together all the x1s, gather together all the x1s and the xn's, and I end up with a linear combination of the x's. So this proof right here is simply putting into i's and j's what this example has in numbers. So the proof doesn't contain any content that the example doesn't contain, except that it shows how you do the proof. So it's a small observation. It's just a question of saying that's just a distributive law, but everything is easy once you know how. This one, it doesn't take you too long to know how. The statement, however, is the basis for what we will be doing for the rest of the course. A linear combination of linear combinations is a linear combination. You can take linear combinations and keep taking them and keep taking them and keep taking them. We saw that with Gauss's method, and you'll always have linear combinations. That is to say that we'll be working in systems that are closed under linear combinations. If you keep taking linear combinations, you'll never find yourself outside the system. And the corollary is just simply that when one matrix reduces to another, every row of the second is a linear combination of the rows of the first. And that's just the example that I started out by looking at with the matrices, A, D, G, and B. Okay, the proof is in the book, but the proof is just a question, as with the prior proof, of writing down what we already observed. Okay, so that leads me to another important observation that I need for today, and that is that there's something special about echelon form. There's something special about echelon form, and it is that if you have an echelon form matrix and you look at the non-zero rows, none of them is a linear combination of the others. If you have an echelon form matrix and you look at the non-zero rows, none of them is a linear combination of the others. And as with many of the things that we'll do in this class, the book contains the proof, and you should absolutely work through the proof. But in order to work through the proof, you need to have some understanding of what it's about. And so I'm doing an example here of what it's about, and I hope that a person can then go from that to seeing the same ideas in I's and J's. All right, so I wrote down a matrix that is in echelon form. I want to show that no row is a linear combination of the others. It so happens that in order to best illustrate the proof, the thing I should do is to show that the middle row, 0567, 0567, is not a linear combination of 1, 2, 3, 4, and 0008. Okay, so I want to show that there's no linear combination that gives you this. And it's just a question of proceeding in 2 steps. The first step is to look at the first column. That is to say, look at columns to the left of the 5. To look at the first column. If you look at the entries in the first column, you have a 0, a C1 times 1, and a C3 times 0. A 0, a C1 times 1, and a C3 times 0. Well, when you look at that relationship, it's obvious that C1 has to be 0. So again, I'm looking only at the first column, the 0, the C1 times 1, and the C3 times 0. When you think about that relationship, of course, it's clear from that the C1 has to equal 0. So the C1 equals 0, so you can sort of take your finger and cover that part up. That part's gone now. We've concluded that if this relationship is going to hold, then C1 has to be 0. So we're now down to 0567 equals C3 times 0008. Okay, and now isn't it clear what to do next? Whoops, I hit the wrong button. It's not clear at all what to do next. Is that you now look at the column that contains the 5. Remember that C1 is 0, so this stuff is gone. So look at the column that contains the 5. It says 5 equals C3 times 0, this 0 right here. 5 equals C3 times 0. Well, that can't be, it doesn't make any sense. So we conclude that there is no way to satisfy this equation. It was 2 steps. One was to look at the columns that are to the left of the 5. There happens in this example to be only one such column, but anyway, look at the columns that are to the left of the 5. And then the second step is to get a contradiction by looking at the column containing the 5. Okay, so it is not the case that the first row is a linear combination of the other 2. It is not the case, this is the example we did, that the second row is a linear combination of the other 2. And it's also not the case that the third row is a linear combination of the other 2. No non-zero row, no row here is a linear combination of the others. If I combine those 2 lemmas together, the 2 lemmas that we just saw here, the first lemma was that a linear combination of linear combinations is a linear combination, and the second lemma is that no non-zero row is a linear combination of the other non-zero rows, then what we get is our first really deeper understanding, or deeper than just procedural understanding of what Gauss's method does. Gauss's method acts by taking linear combinations of the rows. We saw that at the first slide for today. Gauss's method acts by taking linear combinations of the rows. The purpose, the purpose of which is to systematically eliminate any linear relationships among the rows. If row 3 is a combination of row 1 and row 2, then in echelon form, row 3 can't be there. It's going to be 0 equals 0 because of this. Again, if row 3 is a linear combination of row 1 and row 2, then when you finish Gauss's method, this lemma tells you row 3 will have been eliminated. It will say 0 equals 0. Okay, so Gauss's method acts by taking linear combinations of the rows, systematically eliminating any linear relationship among those rows. So we're studying linear relationships. We didn't know it. We thought we were solving linear systems, but actually we're studying linear relationships. Okay, so what you see here is I made up a matrix where the third row is a combination of the first two. It happens to be the first row plus the second row. And then when you do Gauss's method, you find that it ends up being eliminated. It doesn't go away in a puff of smoke, but it ends up being a zero row. And that's just simply because I can't have it being related to the first row. Gauss's method, the previous lemma says Gauss's method wouldn't allow that. Okay, and that gives me, I'm not going to do the proof here, I'm going to do an example, but that gives me the conclusion of this, the last conclusion in the first chapter, the conclusion of this section, that each matrix is row equivalent. So we're thinking about row equivalence, we're thinking about the linear content of a matrix, the information that a matrix contains. Each matrix is row equivalent to a unique reduced echelon form matrix. So if you want to know if two matrices contain the same information, for example, the two matrices give you the same solution if they represent a linear system. If you want to know if two matrices contain the same kind of linear content, contain the same linear information, then what you do is you do Gauss-Jordan elimination on both of them and compare. Do you get the same endpoint? You do Gauss-Jordan elimination on each of them and compare. If you get the same endpoint, why then they contain the same information. They're all three of them, the two matrices and the Gauss-Jordan one that you got, the reduced echelon form that you got. They're all three of them interreducible. But if you start with two matrices and do Gauss-Jordan reduction and you don't end with the same, exactly the same ending matrix in both cases, why then they're not row equivalent. So this is a test for row equivalence. This is a test for when matrices sort of contain the same linear information. Okay, so I'll say a word about the proof in just a minute, but what I've got here, of course, is an example, and I started with 1, 2, 1, 2, 4, 0, 3, 6, 3, 6 minus 1, and I did Gauss-Jordan reduction. I don't bother you with the arithmetic. I did Gauss-Jordan reduction to end up with the reduced row echelon form. And so what that tells you is that this 1, 2, 1, 2, 4, 0, 3, 6, 1 is not row equivalent to, for example, this one. Because look, they're not the same reduced echelon form. They're just not. And 1, 2, 1, 2, 4, 0, 3, 6, 1 is not row equivalent to this. And 1, 2, 1, 2, 4, 0, 3, 6, 1 is not row equivalent to this. I know that's a 2 and that's a 3. That's what makes them different. They simply don't contain the same linear information. It might seem like a small difference, but that's all it takes, just that one, to make that difference. Okay, a comment about the proof here. So the proof is a lot of i's and j's, a lot of subscript i's and j's. Basically, you do what's called mathematical induction, and again, some folks will have seen mathematical induction, and some folks will have not. So I'm tending to there's a description in the back of the book in the appendix. I'm not embarrassed about it, but I'm tending to downplay the mathematical induction part in favor of the linear algebra part. So that's why I'm doing an example rather than the proof. But the proof rewards some close study. It's well worth a read, and we'll use it later on in the book too. So so the fact is we need the statement. But most important is the statement. Unique reduced row echelon form. So I need a picture for that. So the picture goes like this. You remember earlier when I grouped matrices into different categories, I partitioned matrices into different classes, where you got that matrices belong in the same category, in the same class, matrices belong in the same part, if they are interreducible. So we now know that each part contains exactly one reduced echelon form matrix. Exactly one reduced echelon form matrix, exactly one reduced echelon form, exactly one, and there's in fact infinitely many different parts. It didn't draw them all because there's infinitely many, but each one of these contains exactly one. You can somehow think of the reduced echelon form matrix as being, in some sense, like this is a state, this is a state, this is a state, and the reduced echelon form is the capital city. So one way that you can think of this, let's say this, for example, might be the state of Vermont, and the reduced echelon form matrix of all of those matrices in here are many matrices, and all of them reduced to the same reduced echelon form matrix, and that somehow characterizes this class. So this is in some sense the best way to write all those matrices. So it's kind of you call it the canonical representative. If you want to say which collection are you looking at, you might say, well, here's the reduced echelon form for that collection, and that's how you can recognize. Okay, so reduced echelon form matrices represent their classes is a fancy way to say it. And to test if two matrices are row equivalent, just looking at them, you say, I don't know, could be, but maybe not, I can't tell. The answer is to do Gauss-Jordan on each, get to reduced echelon form, and check if the results are exactly the same. Even one little bit, like the 3 and the 2 we saw a minute ago, is enough to make them be not the same. So I did that here, and I put down the steps, but it isn't very interesting. I won't bother you with the arithmetic. The point is that when you get to the end here, they're just not the same. They're just not. So that means that these two matrices to start, these two matrices that I started with, are not row equivalent. They don't contain the same linear information. If you think of these as being like three equations with two unknowns, and there's an augmented matrix bar in each of them, if you wanted to think of them that way, then these would be linear systems with different solutions. These would be linear systems with different solutions. This one would have the solution 4/5 minus 6/5. This one would have the solution 2 minus 8, and they're just simply different. They contain different linear information. Okay, so the lesson for today is that you use Gauss-Jordan elimination to tell you when matrices are row equivalent, to tell you when they somehow say the same thing. Okay? All right, let's see if I can do this right this time. I did it wrong last time. There we go, yay! So next time we're going to talk about a new chapter, vectors, and so we'll start in with something brand new. Okay, very good. Bye-bye. Hi, hello, hi. So last time we finished the first chapter, and one of the lessons of the first chapter was that we are studying linear combinations. When we're talking about solving linear systems, we're really talking about taking linear combinations of the rows. We're studying linear combinations. So in this chapter, we want to expand what linear combinations are about, so that today's check-in is that first step in that direction. Here I have a linear combination of three vectors. Not a linear combination of numbers like we saw in a lot of the previous chapter, but a linear combination of three vectors. We've already seen some of this when we wrote the solution sets of linear systems and when we wrote the equations of planes, but nonetheless I'm making it explicit here. This is a linear combination of three vectors and we're asked to solve it. So we're thinking about what can happen when you try to do equations involving these objects. Okay, so let's write it down. So I want to take the linear combination of those three vectors, and so I have, just to start in here, I have 1, 2, 0 times x, 1, 1 minus 1 times y, and 0, 3, 0 times z equals 0, 0, 0. I like the 0, 0, 0, the homogeneous case, for reasons that we'll see later on today. And I want to figure out what x, what y, what z makes this true. So this is just like when you had numbers, except now it's letters. And of course, we've seen this already, but I'm trying to bring out a fact that we're taking linear combinations of things other than numbers. Okay, so of course, a person thinks to look at the first line and get, let's see, x plus y equals 0. The second line gives you 2x plus y plus 3z equals 0. And the third line gives you minus y equals 0. And these zeros over here means that you cannot have a contradictory equation. So you've either got one solution or infinitely many solutions. I don't know, I'm not going to actually solve it because watching me do arithmetic is not very interesting. So the point though is that off we go. Gauss's method gets us an answer. That's all we need to know, is that we can solve that, and then off we go. Okay, next up though, I want to underline the same thing here, is that we can take linear combinations of things other than numbers. So here I am taking a linear combination of matrices and asking basically the same question, is can you give me a solution in x, a y, and a z that makes this particular linear combination equation true? And of course, for number 2, of course, it's exactly the same idea. The point was to illustrate that I can take linear combinations of things other than numbers in some reasonable way. All right, so just to illustrate here, I get the system 2x plus y equals 0. That's from the upper left. From the upper right, I get x minus y equals 0. And the lower left gives me 1/2 y minus z equals 0. And then the lower right gives minus 2x plus z equals 0. And again, I don't really care about what the answer is. The point is that I can do Gauss's method. Off we go. We get an answer. So I can make sense of trying to figure out linear combinations of things other than numbers. We started out with chapter 1 by thinking about linear combinations of numbers, 3x plus 2y minus z equals 7 kinds of systems. Here we're thinking about things other than numbers, and that's the thing that we're introducing in this chapter. Okay, so let me bring up what it is that we want to talk about today. We want to talk about taking linear combinations, what it means to study linear combinations, taking linear combinations of things that could be numbers, but could be other things, like linear combinations of vectors. We already saw that in chapter 1. Linear combinations of matrices, linear combinations of whatever you happen to want to be taking linear combinations of. Okay, so that when you say you're taking linear combinations of things, you're going to formally describe that. When you say, I want to be in a place where I can take linear combinations, you formally describe that by saying, look, I'm studying a vector space. And you have to say what particular vector space you're studying. So a vector space is a category of problems, but nonetheless, we're going to study that category. So first, of course, I have to define it. I'm going to give a number of examples because it is the central object of study of the course, but I only can get one example onto the video today, so that the follow-up video will contain a number of other examples, so I'm not just going to leave you with one. Okay, so here's the definition. In fact, it's not even the whole definition. In fact, there's another 5 conditions, but I broke it into two different slides just to try to illustrate what's happening. So a vector space V, there are many different vector spaces. There is, for example, the vector space of all 3 tall vectors. We just saw that in the checking. There's the vector space of 2 by 2 matrices. We also saw that in the checking. So there's going to be piles and piles of vector spaces. We'll see dozens of vector spaces over the course of the semester. All those vector spaces satisfy a number of conditions, and we're writing down the conditions that they all satisfy. In every one of those cases, vectors or matrices, there's a plus operation and there's a times operation. The plus operation, for example, the plus operation between vectors, and the times operation is, for example, the 3 times a vector or 5 times a vector. That is to say, this is scalar multiplication, multiplication of a vector times a scalar. This is called a vector space. Sometimes it contains vectors, but sometimes it contains other things. It can contain, for example, 2 by 2 matrices. Vector space is just a word. When you look at the conditions, and I already mentioned there's 10 conditions, when you look at the conditions, they break into 2 different kinds of conditions. There are conditions here like 1 and like 6, and there's also conditions, the rest, 2, 3, 4, and 5, and 7, 8, 9, and 10. I'll look at the 2, 3, 4, and 5 first. 2, 3, 4, and 5 describe something about linear combinations. So for example, we will consider that if you had some kind of plus operation that was not commutative, then we won't think of that as a linear combination. That linear combination, really the plus operation has to be commutative. If you add 2 vectors, that's commutative. If you add 2 matrices, that's commutative. So we're thinking of the plus operation has to be commutative, or else we won't consider it a legal case. Likewise for associative. There has to be a 0 object. There's a 0 3 tall vector. There's a 0 2 by 2 matrix, etc. There has to be a 0 object. And you have to be able to cancel. So if you have the vector 1, 2, 3, and you add it to the canceling vector, the -1, -2, -3, you get the 0 vector. And so we'll consider that if you don't satisfy those properties, you're not really the kind of plus that we're thinking about. Condition 1, the condition of closure, is the one that we'll talk about the most. It is the one that turns out will be adds the real flavor to the subject. It's the one that's most interesting to us. And you see the same thing for condition 6. So condition 1 and condition 6 both say that the space has to be closed under those operations. That is to say, if you add two vectors, you have to, if you add two members of capital V, you have to get a member of capital V. If you, in condition 6, if you take a member of capital V and you multiply it by a scalar 3 times or 4 times or 5 times or 0 times, you have to get a member of capital V. And then you see conditions 7, 8, 9, and 10 are similarly conditions that a person thinks, if you didn't have them, you wouldn't really think of this as a scalar multiplication. That applying the word scalar multiplication would be a very peculiar thing to do if you didn't have conditions 7, 8, 9, and 10. Just as a for example, if you had something you called scalar multiplication, and multiplication by 1 didn't give you back the vector you started with, if you took 1 times v, you didn't get v, you'd say, I'm not thinking about that case. That's a case that is not on my plate at the moment. Okay, so for example, a scalar multiplication distributes over addition. We'll expect that in the collections that we look at, for example, the collection of 3 tall vectors or the collection of 2 by 2 matrices, in the collections that we look at, you can always distribute scalar multiplication over vector addition. And again, the word vector doesn't necessarily mean 3 tall vectors or 4 tall vectors or 5 tall vectors. It might mean 2 by 2 matrices. I'm sorry, just a historical word that we're stuck with. Okay, so there are many familiar vector spaces. We're going to talk about the familiar cases soon enough. I can only fit so much on one video, but I'm going to start off by looking at a less familiar case, because sometimes the best way to understand something is to look at not the first case that a person runs across. So here's the very first example I want to do. I want to look at this line that passes through the origin. So this is a line in the plane. Here's the plane. It's a line in the plane, and it's all the multiples of the vector 1, 2. You see 1, 2 is in blue here, so this is the line with slope 2 that passes through the origin in the plane. That's a collection of vectors. It contains, for example, 1/2, 1. It also contains 2, 4. It contains -1, -2. It contains 0, 0. So this set, capital V, is infinitely many vectors. I'm going to contend that this set satisfies all 10 of these rules. Of course, I'm going to check them. I'm going to check them at some length. Some of the rules are very obvious. Almost all of them are very obvious. The two that will usually concern us are Rule 1 and Rule 6, the rules about closure, that if you add 2 members of this space, you get a member of this space. And if you multiply a member of this space times a scalar, you get a member of the space. Okay, so here we go. I'm gonna walk through the conditions, but before I do, it's very important not to lose the forest for the trees. The point of vector spaces is that vector spaces are a place where linear combinations happen. So if I'm looking at the vectors that are that have the property that the second component is twice the first, second component is twice the first, second component is twice the first. If I'm looking at vectors with that property, I should be able to take linear combinations of them. What do you mean by should be able to? Well, there I am with a linear combination of them, and I get a result, 5, 10, with the same property. The point of vector spaces is that you can take linear combinations and not be afraid that when you do the arithmetic, you'll find yourself with something that is not in the space. Instead, anytime you take a linear combination of members of the space, you get a member to the space. That's the point. So when I say linear combinations can happen in this space, exactly what I mean is that if you take linear combinations, you stay in the space. Okay, so I have to tell you what the operations are, and we know the operations because we studied them already. We had a review, but I suspect that a person, most of the time when a person came to this class, they already knew that if you add a pair of 2 tall vectors, you get this way of getting a 2 tall vector, you add them component-wise. And same thing, scalar multiplication, you multiply by 3 times 5 or by -1. You just multiply the components by 3 or 5 or -1. The first condition, closure, is that the sum of 2 members of V is also a member of V. And the only tricky part to understand here is what is it you're required to check. you have to check that if you take two members of the space, and remember, member of the space means second component is twice the first. So if you take two members of the space, two vectors with the property that the second component is twice the first, the second component is twice the first, I wrote it there, then you'll get a vector with the second component twice the first. So of course, here's the two vectors. Here's me adding them. I have to check that y1 plus y2 is twice x1 plus x2. Well, of course it is, because if you add these two together, then you get twice x1 plus x2 and you're done. So it's not hard to do. The hard part here is to understand what you're asked to do. What you're asked to do is to check that if you have two vectors from the space and you add them according to the rules of addition, the regular sort of physics 1 rules of vector addition here, you get a member of the space. Get a member of the space means second component is twice the first. So we checked it, so that's good. Condition 2, commutativity of addition. You have to check that if you add two vectors either as v1 plus v2 or as v2 plus v1, you'll get the same thing. And really, the problem with these, with some of these conditions, 2, 3, 4, 5, is that it's not that they're too hard, it's that they're too easy, and a person has trouble figuring out what exactly is it that happened. So I'm going to compare v1 plus v2 to v2 plus v1 and note that they're the same. And of course they're the same. x1 plus x2 is a real number. x2 plus x1 is a real number. And you add real numbers in the opposite order, doesn't matter. y1 plus y2, y2 plus y1 are the same real number. The order doesn't matter. So commutativity of addition here we say inherited from commutativity of real number addition. But in any event, it's not that hard. The hard part is figuring out what it is that you're asked to do. So some conditions have nothing to do with the fact that y1 equals 2x1 and y2 equals 2x2, and this is an example of such a condition. I mentioned that conditions 1 and 6 will be the ones that mostly concern us. That's because they're the ones that it will involve that. And again, just going slowly through conditions 1 through 10, trying to answer a question so the person can say, well, when I got to the homework, I knew what I was asked to do. Associativity of addition, I have to check that if you do v1 plus v2 and later on add v3, you'll get the same as if you do v2 plus v3 and later on add v1. And I'm not saying it's hard, I'm saying the hard part is to understand what you're asked to do. So here, v1 plus v2 later on add v3 gives you this. And v2 plus v3 later on add v1 gives you this. And of course they're the same because real number addition is associative. So again, didn't need the second component is twice the first, didn't need it. Condition 4 just says that there's a vector that when you add it to other vectors doesn't do anything. And again, a person can say, well, I wasn't sure what I was being asked to do here. So you're being asked to exhibit that vector. Name a vector with the property that when you add it to other two tall vectors, it doesn't do anything. And I go, nobody has trouble naming the vector. You just have to name it. Of course, I verified that when you take a vector and add 0, it doesn't change the vector. But the hard part is not doing it. The hard part is understanding what you're asked to do. 5, same thing, it says existence of an additive inverse. So you're asked to name. If you're given a vector that's a member of the space where y is twice x, what would you add to this to make it equal 0, 0? And I know everybody knows. The answer is you add minus x and minus y, and the y equals minus 2x here. The only thing you have to worry about is, does minus x and minus y live in this space? If xy is in this space, is minus x and minus y, is that vector in this space? And the answer, of course, is yes, because if y is twice x, then minus y is twice minus x. And I wrote all that stuff down. But again, the question is usually figuring out what it is you're asked to do. The condition asks you to show there is an additive inverse. The easiest way to show something exists usually is to just produce it. So I was given an xy, subject to the condition, given an xy where I got the vector v in capital V, and asked to produce a w that cancels v, and then verify that w is also in capital V. I verify that w is also in capital V by verifying that minus y is twice minus x. Okay. Next up, I'm on to the conditions that really talk about scalar multiplication. I just broke it in two just to try to break the job up into smaller parts. So condition 6 is about closure under scalar multiplication. So I have to start with a vector from the space, v in capital V, and I have to multiply it by a scalar. And I got to show that no matter what scalar I multiply it by, the result, written right here, the result is still in capital V. In capital V means that its second component is twice its first. So if I start with a vector where the second component is twice the first, and I multiply it by, say, 108, do I get a vector whose second component is twice its first? Well, of course you do, because if y is twice x, then ry will be twice rx. That's not hard. None of these are hard. The hard part is understanding what a person is asked to do, because very, very typically, almost 100% of the time, this is the first time a person has seen this kind of thing where you're required to check the conditions on a structure, and so you're like, oh, I'm not 100% sure what I'm doing. Never done this before, so that's why I'm walking through these one at a time. None of them is hard. Every one of them leaves a person thinking, am I sure I was supposed to do that? So that was 6. That's the other closure condition besides 1. The closure conditions are the ones that we'll usually be paying attention to. 7. So to check that real number addition scalar, real number addition distributes over scalar multiplication. So we just check here that there we go, that r plus s multiplied by v gives you if you take v in the vector space capital V, do you get a result that's in the same vector space? So if y is twice x, will ry plus sy be twice rx plus sx? If v is in the vector space capital V, will rv plus sv be? And the answer, of course, is yes. That's easy to see, but a person has to know what to check. The next one, maybe you're getting kind of the swing of this. You'll have r times v1 plus v2, and you're comparing it to rv1 plus rv2. And do you get that? And again here, when you do, as with the previous question, when you do r times v1 plus v2, you get this. When you do rv1 plus rv2, you get this. And they're equal because r times x1 plus x2 is equal to r times x1 plus r times x2, just because they're real numbers. R times y1 plus y2 does equal ry1 plus ry2, just because they're real numbers. So that's 8. 9. We have to do here two real numbers that are multiplied together, two scalars here. So it might be 7 times 5 multiplied times the vector v. You get the same result as if you took 7 times 5 times v. And you just check here, rs, the definition of rs scalar multiplied times v is rs by the x and rs by the y. The definition of r by sv is r by sx and r by sy. And of course, these are all real numbers, so they all come out equal. That's all right. That's all correct. Okay. And then the last one, condition 10. Condition 10, you just have to check that multiplying 1 times a vector. If you work your way through the definition of multiplying 1 times a vector, does it change the vector? And of course it doesn't change the vector. Of course it does. Okay, so what we've done is we've worked through conditions 1 through 10. Worked through conditions 1 to 10. Many of them were routine. Many of them, there was really very little to do in some sense. We had to recognize, though, the concept of what we were doing. So we had to recognize, for example, what does the question ask us to do? When we say there is a zero vector, what am I asked to do? And the answer is, it says there exists. So we produced it. We produced the thing which, when you do the defined operation, doesn't change the vector. For condition 2, we had to write down the left-hand side, v plus w, and the right-hand side, w plus v, and check that the two of them are the same vector. So for many of these cases here, for example, 9, 8, for many of these cases, it's extremely easy to check. It's a question of knowing what to check. So the difficulty is figuring out where it is you're asked to proceed. The ones that are more interesting is a mathematical word that means sort of hard, or maybe the heart of the question lies here, is conditions 1 and condition 6. In condition 1 and condition 6, we had to check that if you add two vectors, add two members of the space, you get a member of the space. And if you multiply a member of the space times a vector, times a scalar, you get a member of the space. So if you take two members of the space and add them, you get a member of the space. The space is closed under addition. Down here, if you take a member of the space and multiply it by a scalar, 10, 12, 108, minus 6, 0, you get a member of the space. Those are the ones that will turn out to be the crux of the matter. Most of these other questions, it's not that they're stupid, it's that they're routine, or they tend to come out to always be so. Okay, very good. Okay, so that was a long one, but I'm not going to leave you with just one. I'm going to go through and do on the next video, going to go through and do a bunch of examples so that a person, when you come to the homework, can feel like, okay, I have some idea what it is I'm asked to do. It turns out that questions 1 and question 6 here, conditions 1 and condition 6, are the heart of the matter, and that's what we'll focus on in the next slide. So let's see here. Next part will be the definition of vector spaces, part 2, and we'll see that. Hello, hi. So last time we went through the definition of a vector space and did one example at great length about a case, namely a line through the origin, the line y equals 2x through the origin, that showed that it was a vector space. There are many different kinds of vector spaces, and today we're going to see a number of other examples and do some checks. So, for example, the 2 by 2 matrices are a vector space. The 3 tall vectors are a vector space. Many different kinds of vector spaces, and what we're trying to do today is to get used to those different kinds by seeing a lot of examples. Okay, so that leads me to the check-in that I want to do. Vector spaces are about linear combinations. Vector spaces are a place where linear combinations take place. So I want to, of course, do a check-in that connects to that. So the check-in is I want to look at the example from last time, the line y equals 2x, and remember what it means, conceptually, what it means to say it's a vector space. And then I'm going to contrast that with something that isn't a vector space. So question 1 says, consider the line y equals 2x. And so I have here the line y equals 2x. I rewrote it as 2x minus y equals 0 just because it fits with the second example that I want to do. So 2x minus y equals 0. And I'm going to do just to pick two vectors at random and make a linear combination and check that indeed the linear combination does give me a vector from the space. So I'm looking here for question 1 at for question 1 I'm looking at the line y equals 2x. So it's the set of xy where 2x minus y is 0. And I'm just going to pick two vectors at random from that space. Really, it doesn't matter what I do. So how about if I take v1 equals 1, 2, and v2 equals, and just really minus 3, and I want y to be twice that, so minus 6. Darn it, having a little trouble with my handwriting. And I'm just going to take a combination of the two, and any combination, it doesn't matter, but just to give an example, kind of a random pair, how about 5 times v1 plus 6 times v2? So let's see, what's 5 times v1 is 5, 10, and what's 6 times v2 is minus 18, minus 36. And when you add them together, what do you get here? You get 5 take away 18 is minus 13, and 10 take away 36 is minus 26. And indeed, we started off with two vectors that had the property that the second component is twice the first. We took kind of a random combination of those two, and we ended with a vector that has the property that the second component is twice the first. So we're illustrating closure under linear combinations. If you start with two members of the space and take any combination at all, you end with a member of the space. So now the one way to understand something, to help understand something, is try to see examples where it doesn't work. So make a contrast. So I'm looking at the set of xy where 2x minus y is no longer going to be 0, but instead is going to be 1. And I'll pick two vectors again at random just to pick here. V3 is not supposed to be anything especially special. So if I take the x component to be 2, then that'll be 4 take away. I need a 3 there in order to get 1. And if I take V4 to be, oh, I don't know, 5, 2 times 5 is 10, so I need that to be a 9 in order to get 1. So I have two members of the space. And again, I'm going to take a random linear combination, just, I don't know, whatever occurs to a person, and at the end, I will see that I do not get that twice the first component take away the second component is 1. So just illustrating that it's not closed by giving a specific example of it not being closed. So I don't know, how about 5 times V3 and then minus 2 times V4? I don't have anything in mind, I just made up some numbers. So 5 times V3 is what, 10, 15? And 2 times V4 is what, 10, 18. So when you do the subtraction, you get 0 minus 3. And it's obviously not the case that twice the first take away the second gives you 1. Twice the first take away the second does not give you 1. So this is an example where you take a linear combination, you end up with a vector in the same category as you started. Here's the case where you take a linear combination, you end up with a vector not in the same category as you started. This is closed under linear combinations. This is not closed under linear combinations. Vector spaces are characterized by the most important property, the conceptual idea of a vector spaces. You can take linear combinations and you can go nuts. You can take any linear combination you like and you'll still end up with a vector in the space. However, if you have a non-vector space, if you take a linear combination, you can end up outside the space. Okay. Okay, so that's the idea of a vector space. That's the concept behind a vector space. So let's see. Let's see here. So I want to talk today about some more examples of vector spaces and try to get across again some more of the concepts that illustrate here what it's about. So the main concept, there's a lot of detail here, but the main concept in this detail is line 1 and line 6. A vector space is a place where linear combinations take place, and these other conditions, the conditions that are not 1 and 6, it really serve to define what I mean by linear combination. You can multiply by a scalar. When you multiply by a scalar, for example, the multiplication distributes over addition. Or vector, or the addition of two things is the same either way, it's commutative. It's condition 1 and condition 6 that will most often concern us. That's what I tried to illustrate with the check-in. Last time we went through all 10 conditions at some length, trying to be careful and to say what each of them meant. This time we're going to go through a number of examples, so spend less time on each individual example, but try to illustrate that there are many different kinds of vector spaces. You might say, I have a vector space. Well, I have a different vector space, sort of thing. So there are many different kinds of vector spaces, and we're going to see a number today. Okay, so this is the one that we saw last time and saw it at great length. 4, 5, 6, 7, checked all of the 10 conditions. And now I want to look at a new, instead of a line through the origin in R2, I want to look at a new collection of vectors, and this is going to be a plane through the origin in R3. The plane 2x plus y plus 3z equals 0 through the origin in R3. I have it drawn there in yellow. And I drew some vectors from the plane onto it. I had the computer draw that because I'm not a very good drawer. All right. That's a vector space under regular vector addition and regular vector scalar multiplication. Those are the operations that a person would think to do. That's what it means by natural operations. I'm not going to check every one of the conditions. I'm only going to look at condition 1 and condition 6 because I've tried to highlight those will turn out to be the conditions that most concern us. And again, I'm trying to make sure that a person can do the homework. That's absolutely right. You have to be able to work through the I's and J's, but also feels that they understand the concept here. Condition 1 is that if it's closure under addition, is that if you add two vectors in this space, add two vectors in P, the sum is you get a vector in P. Translating that into the geometry here, it says that two vectors in the plane add to make a vector in the plane. I'm going to confirm that algebraically, but before I do the algebra, here's the geometry. There's a red vector in the plane, there's a red vector in the plane. Both of those sit, not just their tip in the plane, but their entire body sits in the plane. Remember, this is a plane through the origin. So their entire body sits in the plane. When you add them, you are doing a parallelogram, and the parallelogram, the entire parallelogram sits in the plane, so that the sum of these two vectors reaches to the far corner of the parallelogram. That one also sits in the plane. So the sum of the two vectors is also a member of capital P. Briefly, if you take two vectors in a plane through the origin and you add them, you get a vector in the plane through the origin because everybody's entire body sits in the plane. All right, so that's the concept, and the algebra, the thing that a person would think to do with i's and j's, is that if you take two vectors from the plane, p1 and p2, when you say they're from the plane, exactly what you mean is that if you take 2 times the first component plus the second component plus 3 times the third component, then you get 0. And over here, if you take 2 times the first component plus the second component plus 3 times the third component, then you get 0. So both of these vectors are numbers, and they have this property, and they have this property. Of course, when you add vectors, of course, they add component-wise. Of course they do. That's what we meant by natural operations. And then all I have to do is check that this vector, this is a 3 tall vector. Its first component is x1 plus x2. Its second component is y1 plus y2. Its third component is z1 plus z2. I have to check that those 3 components have the relationship that I want, the relationship from the previous page. This relationship right here is 2 times the first component of the sum plus the second component of the sum plus 3 times the third component of the sum. When you do that all together, do you get 0? So I check it. Here we go. 2 times the first component plus the second component plus 3 times the third component. Do you get 0? And of course you do. It would be embarrassing if I set the whole thing up and it didn't come out to be 0. You just do a little algebra, multiply the 2 through this kind of stuff, and it comes out to be 0. So to verify condition 1, I have to suppose I have 2 members of the space, a capital P, that satisfy the condition. That's what members of the space means. I then write down what is their sum, and I have to verify that their sum satisfies the condition. When you're doing the homework, you're saying to yourself, what does it mean to satisfy the condition? It means 2 times the first plus the second plus 3 times the third adds to make 0. So you start off the left-hand side of the equation, 2 times the first plus the second plus 3 times the third, and after some amount of head scratching here, it's not very much head scratching, you get 0 on the other side. All right, so of course, we're also going to verify the same thing for scalar multiplication. So I start off with a vector that is in the space. In this particular case, being in the space means 2 times its first plus its second plus 3 times its third makes 0. And I multiply it by a scalar. You can't multiply it by 7 and check just 7. That's not enough. You have to check for an arbitrary r. And likewise, too, the formal proof requires that you check for an arbitrary x, an arbitrary y, and arbitrary z. This is not like the check-in where you check one and you figure they're okay. This is instead a formal proof, so I have to check it with letters. But nonetheless, it's not hard to see that r times p is this, and that p satisfies this. And what I have to do to finish is I have to verify that r times p is a member of the space. So I have to check that 2 times its first component plus its second component plus 3 times its third component makes 0. And so you write down there 2 times the first plus the second plus 3 times the third, and then you do not very much algebra, and you end up with 0, and they're done. Okay. The next thing I want to check is a vector space. You could think about checking the 2 tall vectors. You could think about checking the 3 tall vectors. You could think about checking the 4 tall vectors. All those, that's all true. I'm going to check all of them at once by checking the n tall vectors. This is a good illustration of my first example, really the first couple of examples here, the line through the origin and the plane through the origin. And I did those as first examples because they're not too easy. Sometimes examples can be too easy, and it's really not clear to a person what it is that's happening in that check. when you look at the n tall vectors, they're in some ways they're too easy. If I say the sum of two vectors, if the sum of two n tall vectors is an n tall vector, I don't know, it's very hard to understand what that means. But if I say the sum of two, from the previous example, the sum of two members of the plane is a member of the plane, that's a little more meat to sink your teeth into here. But here, when I say the sum of two n tall vectors is an n tall vector, there's no restriction, and so there's nothing to check. That makes this in some ways a harder example than the first two, or maybe not as good as a first example as the first two, but it's still true. The sum of two n tall vectors without restriction is indeed an n tall vector without restriction. And likewise, the scalar multiple of an n tall vector without restriction is an n tall vector without restriction. So the collection of n tall vectors, the collection, for example, of 3 tall vectors is a vector space. The collection of 4 tall vectors is a vector space. The collection of 5 tall vectors is a vector space. I am not saying that the collection of 3 tall vectors unioned with the collection of 4 tall vectors. That's not hard because you can't add a 3 tall and a 4 tall. I'm not saying that, I'm saying instead that if you fix n and just look at, say, the 8 tall vectors, then the collection of 8 tall vectors is a vector space. The 8 tall vector plus an 8 tall vector without restriction, when you add them, you do indeed get an 8 tall vector. Okay, this is another example that's a good example because it's because it's at least slightly surprising. So I'm going to, as I illustrated in the last couple of videos, I'm interested in taking the linear combinations of any kinds of things where linear combinations make sense. One place where linear combinations make sense is it makes sense to add vectors, 3 tall vectors. Another place where linear combinations make sense is it makes sense to take linear combinations of 2 by 2 matrices. Well, here's still another place where it makes sense to take linear combinations. It makes sense to take linear combinations of quadratic polynomials. If you have 3 plus 2x plus 1x squared and 10 plus 0x plus 5x squared, it makes perfectly good sense and perfectly algebraically sensible to take 5 times the first and subtract 7 times the second and figure out what you get. And of course, we have to check that what you get is indeed a quadratic. So we know how to add quadratics. If you take a first quadratic and a second quadratic, you add them component-wise. That's exactly right. The constants, the coefficients of x, the coefficients of x squared. And we know perfectly well what it means to scalar multiply a quadratic polynomial. If you have a quadratic polynomial like 3 plus 2x plus 1x squared, you could perfectly sensibly multiply it by minus 106. That is to say, you simply multiply component-wise, r times a0, r times a1, r times a2. And the intuition always in these cases, always, you want to be able to do the sort of pushing letters around to get the homework. That's very important, that a person is keen on getting the answers, doing well in the quizzes, but just simply learning what it is that they're required to do. But you don't want to lose sight of the concepts. The concept here is that vector spaces are about taking linear combinations. It makes perfectly good sense to take a linear combination of these vectors. Makes perfectly good sense to take a linear combination of 1 plus 2x plus 3x squared. You call that a vector in this context because it's a member of a vector space. It makes perfectly good sense to take 4 times that, a minus 1/5 times 10 plus 5x squared. That has, you can think of it as having 0 times x written in the middle. And what you get is a quadratic polynomial. So a linear combination of quadratic polynomials is a quadratic polynomial. That's closure under linear combinations. That's the key to being a vector space. So so a person has to be able to check with the letters. That's absolutely right. But don't want to lose track of the concept. The concept is that you can take linear combinations of these guys and you get one of these guys. Now, I'm not going to give a full verification, but I will give the check for conditions 1 and 6 because those are the 2 key conditions. So for number 1, I start off with a first quadratic polynomial, and there's a second quadratic polynomial. I use the a's and b's. First quadratic polynomial, second quadratic polynomial. I don't know why this one has parentheses around it. And then I add them, and I'm simply going to verify that the sum is a quadratic polynomial. So I add them. Of course, you know how to add them. I'm verifying that it's a quadratic polynomial because it's a constant term plus some linear term plus some quadratic term, and there's nothing else. This is not like when you square a quadratic, you get fourth powers. No such thing happens here. This is when you take a sum of two quadratic polynomials, you get a quadratic polynomial. That's all. Likewise, for condition 6, if you give me a quadratic polynomial and you multiply it by some number, 0 or 2 or 107, it's still a quadratic polynomial, or the result is a quadratic polynomial. That's all this 6 says. One thing that happens sometimes with these, when you consider a new system and you start looking at the rules seem a little strange when you first see them, and you go through a number of examples, and then at some point you start saying, oh, is that all it says? That's what's happening here. That's all it says. 3 by 3 matrices. I'd rather do one example too many than one too few. So here we are, 3 by 3 matrices. A person can add a pair of 3 by 3 matrices, and a person can multiply a 3 by 3 matrix by a number like 5 or 10 or minus 6. And that's a vector space under the usual matrix addition and scalar multiplication. The check is perfectly simple, but I don't want to lose track. This is not the answer, but this is to get across the concept that you can take linear combinations of 3 by 3 matrices and you get a 3 by 3 matrix. So here I have them take 1 times the first minus 3 times the second, and you do the arithmetic. I hope I did the arithmetic. Do the arithmetic, and you get a 3 by 3 matrix. So a linear combination of 3 by 3 matrices is a 3 by 3 matrix. Of course, I might put some restriction on 3 by 3 matrices and have to check that, just like I check the case for planes through the origin or lines through the origin. I could, for example, write down, what about the 3 by 3 matrices that have the property that the upper left entry plus the lower right entry adds to 0? That's not this example, but you could look at cases like that and there would be more to check. But conceptually, at first glance, when you're first approaching vector spaces, what the heck is a vector space? Vector space is about, you can take linear combinations and not have to be concerned that what's on the right-hand side of the equation is not a member of your space. That can't happen. Vector space is where whatever you do on the left, you'll be good on the right. Okay. Couple of small results that follow from the definition. First of all, the empty set isn't a vector space because the definition requires that the space contain the additive identity, the 0 vector. So it's got to contain at least one thing. So there you go. You can have a vector space that has only one element. That can happen, and I listed as an example the vector space that contains only the too tall 0 vector, and the plus and times operations are pretty dopey there, but it's still perfectly possible and satisfies all the rules. You call that the trivial space for the obvious reason, and we'll have occasion sometimes to mention the trivial space for much the same way that you have occasion in high school algebra to mention the number 0. It just comes up sometimes. Next up is a small lemma. When you look at the 10 conditions for vector space, a person can say, well, where those 10 rules come from? Why, for example, include the rule that 1 times v equals v, but not the rule that 0 times v equals 0? And the answer is it so happens that some of the rules imply other rules. So for example, we don't need 0 times v equals 0 because from the 10 rules we have, we can derive it. Oh, why include this one? Why leave that one out? Well, that's a question when you're constructing the definition. You try to make it work so that it's convenient as possible, and the verifications of the extra conditions are not too hard, this kind of stuff. We're not going to go into the details of that, but the point is that some of these rules follow from the rules we already have. So if you're saying, why did we leave off? Well, we left it off because we don't need to add it. And the proof of most of these is kind of a fiddling around algebra stuff. So to show that 0 times v, that if you use the scalar 0, you get the 0 vector, I took v, I rewrote that as 1 times v, which I then wrote as 1 plus 0 times v, and then I distributed 1 times v and 0 times v, and then I basically have a v and a 0v, and I subtracted off. Anyway, a little bit of algebra fooling around. Don't get too concerned about this. A little bit of algebra fooling around gets you the rule here. Sometimes I've had folks raise their hand and say, are all the things we do in the rest of the semester going to be like rewriting things in the? No. Okay, this just so happens that the technical manipulation to say that you don't need this rule among the 10 is a little bit maybe overly slick. And item 2 and item 3 are along the same line. They're not especially tricky. Just as an example for item 3, r times the 0 vector is a 0 vector. If you don't think of the 0 vector as a 3 tall vector, if you think it could be a bunch of things, it might be the 0 vector might be the 2 by 2 matrix that is all zeros. The 0 vector might be the quadratic polynomial that has all 0 coefficients, 0 plus 0x plus 0x squared. Then 3 becomes a little bit less obviously true. But it's easy to verify r times 0 is r times 0 times 0, r times 0. Anyway, again, the rest of the semester we will not be doing this kind of algebraically pulling things out of the air. Nothing about these are illegal. They just sometimes give a person an uneasy feeling that they're going to start being asked to do tricky things. No, we're being asked to follow the concepts here. That's what we're keen on. Okay, next time we're going to talk some more about vector spaces by virtue of talking about something called subspaces, but I want to emphasize that we will still continue to practice the idea of vector spaces, and that a person is being exposed to something that's brand new, and you're not just sort of expected to instantly snap it up and it's all perfectly obvious. That the best thing to do here is to see lots of examples, and that's exactly what we're going to see. Okay, all right, bye-bye. Hello. Hi. So last time, of course, in the time before, we looked at the definition of vector space and we tried to get some sense of examples of vector space. So there are many different kinds of vector spaces: 2 tall vectors, 3 tall vectors, 2 by 2 matrices, 3 by 3 matrices, 2 by 4 matrices, quadratic polynomials. There's a whole lot of vector spaces, and we tried to see a number of examples and to check through the conditions in the definition to verify that they are all vector spaces. I a number of times mentioned that condition 1 and condition 6, the closure conditions, are the ones that we'll worry about most of the time. They prove to be the ones that are the trickiest, the ones that are kind of the key, the sort of central point of the matter. So with the check-in today, I want to reinforce a little bit what makes something a vector space, and also give a little bit of a suggestion of what's coming. So here we go. It says this is a plane through the origin in R3, and I want to verify that it's a informally verify that it is a vector space by showing that if you take two members and take kind of an arbitrary linear combination, you get a member. So I'm just going to do kind of a made-up couple of examples, and then down here it's the same thing with another kind of space. So first example, I look at the set of x, y, z's where x plus 2y plus 3z is equal to 0, and I'll just make up two vectors where x plus 2y plus 3z equals 0. I don't know. V1, x plus 2y plus 3z equals 0. So how about 3, 1, so that's x plus 2y makes a total of 5, plus 3z equals 0, so minus, 5/3. Right, x plus 2y plus 3z is equal to 0. And then take another one, v2. So x plus 2y plus 3z equals 0. So how about if I say minus 1 and 1 and 1? Okay, and both of them have the property that x plus 2y plus 3z equals 0, and x plus 2y plus 3z equals 0. I'm going to take just an arbitrary linear combination. I don't know. How about if we take 6v1 plus 4v2? And I'm going to check at the end, when I get to the end, I'm going to check that x plus 2y plus 3z equals 0. So let's see if I can do this. This is always the hard part. So that's 18, 6, and minus 5/3 times 6 makes minus 10. 4 times v2 is 4, 4, and minus 4. And I add them together, and I get here 22, 10, and minus 14. So is it the case that 22 plus 2 times 10 plus 3 times 14 equals 0? So let's see, 22 plus 2 times makes 42. 3 times minus 14 is, 3 times minus 10 is minus 30. 3 times 4 is, so it is indeed minus 42. Okay, so that of course isn't a proof. You'd have to do a proof with x's and y's and z's, but nonetheless, it's some kind of reminder that the point of a vector space is that you can take linear combinations, and when you take a linear combination of things from the space, you get a thing from the space. That is to say, vector spaces are closed under linear combinations. This is an illustration that vector spaces are closed under linear combinations of two of their members. Of course, you could take 3 members or 4 members or 5 members. I just happen to pick 2 just to do an example. Okay, I'll remind you back to the screen. Oops, went the wrong way. There we go. Remind you back what the second question is. It's the set of x, y, z's where x plus 2y equals 0 and z equals 0. That's a line through the origin because you have one free variable, y. And I'm going to pick two 3 tall vectors that have that property and do a linear combination of them. So let's get rid of it and see how we do with 2. So V3 and V4. So let's see, x plus 2y equals 0 and z equals 0. So the z equals 0 part is not hard. X plus 2y equals 0. How about if I say 2 minus 1? And how about if I say 3? And then I need to have a negative, so negative 3 halves. Right. I think it's the case that x plus 2y makes 0 and z is equal to 0, and x plus 2y makes 0 and z is equal to 0. So I think I'm good. Now I'll take a combination of those folks. Oh, how about 1 times v3 and minus 5 times v4. And at the end, I'm going to check that x plus 2y makes 0, and furthermore, z is equal to 0. So what the heck do I get here? So I get 2 minus 1, 0. And then I got to do 5 times v4. So I got 15. 5 times minus 3 halves is minus 15 halves, and 0. I don't know. So that's 17. So that's 2 halves minus, so that's minus 17 halves, and 0. And indeed, a person can see that x plus 2y does indeed make 0, and z is equal to 0. So I do have closed in this particular case. You'll notice also that the question asks not just to check that it's a member of the line, but also to check that it's a member of the plane, meaning this plane up here. So let's try that. Is it the case that in all 3 of these, that if you take x plus 2y plus 3z, you get 0? Well, that's right. X plus 2y plus 3z does give you 0. In all 3 cases, the z equals 0 part means the question boils down to x plus 2y equals 0. So the point of that question was just to notice that really this line is a subset of this plane. This line is the specialization z equals 0 of this plane. So this line is a subset of this plane, and for that matter, this plane is a subset of 3 space. So all these vector spaces are kind of nested inside each other, so you can have vector spaces that are somehow subsets of other vector spaces. And that's what we want to talk about today. Vector spaces that are subspaces of other vector spaces. So for any vector space, a subspace is a subset that's itself a vector space under the inherited operation. Inherited operation just means that in all 3 cases that we were looking at in the check-in, R3, the plane through the origin, and the line that lies in the plane, the line through the origin, all 3 of those, you add 2 vectors in the same way, you add them component-wise, and you multiply vectors times a scalar in the same way, you multiply component-wise. So they all share the same operations. Any vector space has a trivial subspace. We saw that last time. At the opposite extreme, any vector space has itself for a subspace, because it is indeed a subset of itself. A subspace that is not the entire space is called a proper subspace. Just a word, just a vocabulary word. And we've seen already, besides the check-in, we've already seen that the line y equals 2x, the second component is twice the first, is a vector space. And I'm just noticing that's a subspace of the plane. So the line y equals 2x here that we checked earlier is not just a vector space in its own right, but it's also shares the operations with the superspace, shares the operations with the plane, shares the operations with R2. So S is a subset of R2. And that makes it a subspace because it's the same operations. Okay, so a subspace gives me more examples of vector spaces that I can talk about and also introduces a new idea at the same time, so it's economical. The collection of 2 by 2 matrices we know is a space, is a vector space. You can take combinations of 2 by 2 matrices and you get a 2 by 2 matrix. You can also here, you can also look at the collection of 2 by 2 matrices that have some limitation on them. This is a collection of 2 by 2 matrices with the property that the upper left and lower left are the same number and the upper right and lower right are the same number. If you like, you can rewrite it this way, and we will like. If you like, you can rewrite it this way, that this is A times 1010 plus B times 0101. And you recognize this as what we called in the first chapter parameterization. We brought the A and the B out as parameters, so that I'm expressing vectors of this form as a sum, a linear combination, of two vectors here. And this is a vector space. It's clearly a subset of the 2 by 2 matrices, so it's going to be a subspace of the 2 by 2 matrices. And what we're finding is that vector spaces can have inside them vector spaces, and this is just an example. So again, one of the best ways to understand what something is to give examples of it not, to contrast the examples of it yes with the examples of it not. You understand what a dog is in part by pointing to things that are not dog. That's a cat, that's not a dog. So this is an example of something that is not a subspace of R3. It looks like a plane through the origin except that it says 1 instead of 0. So because it says 1 there, it's not a plane through the origin. So it's perfectly well a subset, but it's not a vector space. For example, it's not closed under vector addition. Here's two members of capital T, and when you add them, you get something. It's a perfectly legal thing, but it's not a member of capital T. X plus Y plus Z doesn't add to 1. It adds to 2. So although it's a perfectly good subset of R3, it isn't a vector space, and so that makes it not a subspace. So one of the things that a person kind of gets their antenna up, pays a little attention to, is the fact that that's a 1 and not a 0. There's a little something about zeros that happens here. And the key result in this section is this one here. It says if you have a subset of a vector space, then each of these three statements say the same thing. They say something that we've noticed many times in the few videos that we've been doing so far, but we've noticed that it's about linear combinations. So a subset of a vector space is itself a vector space, provided that it's closed under linear combinations of pairs of vectors. We've often taken linear combinations of pairs of vectors. And also, that's the same thing as saying you take linear combinations of any number of vectors, R1S1 through RnSn. All three of these statements say the same thing. They're equivalent statements. So 1 is the same thing as 2, 1 if and only if 2. 1 is the same thing as 3, 1 if and only if 3. 2 is the same thing as 3, 2 if and only if 3. We will often find 2 to be the most convenient, not the only one we'll ever use, but we'll often find it to be the most convenient way to state what's happening. And you notice that this lemma really captures what I've been trying to emphasize now for some time, that vector spaces are about linear combinations of the members. In particular, vector spaces are about closure under linear combinations. Closure of 2 or closure of n, it's not important, but about closure. Vector spaces are about, you can take a combination, linear combination, of the members of the space, and you're sure to end up in the space. You're sure to end up in the space. Okay, and as so often happens in here, the videos are an introduction to the material, so the book has the complete proof, but I'm going to try to go through the basic idea here. So that you remember that in the first example of vector space, the line y equals 2x, I commented when we were checking several of the conditions that they don't depend on the y equals 2x part. They just depend on sort of the addition. So for instance, x1 y1 plus x2 y2 equals x2 y2 plus x1 y1 didn't use, the proof of that didn't use the fact that the second component is twice the first. It just didn't need it. So it turns out that to show something is a vector space and to show something is a subspace, we will only need to check closure under linear combinations. You can check closure under linear combinations of 2 if that's most convenient in the space you're looking at. You can check closure under linear combinations of more than 2 if that proves to be convenient. But once you know you're inside a vector space, the important thing is the kind of key idea is linear combinations land you back in the space you're in. Linear combinations land you back in S. And I'm going to do a number of examples. And oh, I'm sorry, I forgot I was supposed to go backwards. There we go. I'm going to do a number of examples. And as we move through the examples, I'm going to be emphasizing something that appears, something that's emergent. And that is that this idea of parameterization here proves to be a key one. This idea of bringing out the A's and B's, or C's and D's, or whatever letter they are, proves to be a key one. Okay. So here, we'll start here with the vector space of quadratic polynomials. And we've already checked that that's a vector space, or at least we pretended to check that that's a vector space. The basic idea there is that a linear combination of quadratic polynomials is a quadratic polynomial. Of course, there are 10 conditions to check, but nonetheless, it has a conceptual basis. If you look at the quadratic polynomials that have the property that a2 equals 0, then you're looking at linear polynomials. I'm claiming that linear polynomials form a subspace, it's capital L, forms a subspace of the quadratic polynomials. To verify that by the previous lemma makes verifying that very easy. You don't need to check all 10 rules. You only need to check closure under linear combinations. So I did. I wrote down R times the first plus S times the second. So I have R times a first linear combination and linear polynomial plus S times a second linear polynomial. And when you distribute the R's and add together, you get a constant term, a coefficient of X. This is a linear polynomial. It's got a constant term. It's got some letters there, but it's not hard. It's a constant term. That's a real number. And a coefficient of X. And again, that's a real number. It's a somewhat convoluted way to write a real number, but it's a real number. So real number plus real number times X, that's a linear polynomial. So the right side is a linear polynomial with real coefficients. So capital L is closed under linear combinations, and by the prior lemma, linear combinations of 2, by the prior lemma, that's enough to show that it's a subspace. You don't have to check that scalar multiplication distributes over addition. You don't need to check any of those things. You just need to check closure under linear combinations. Another example of a subspace, so I'm looking at a subspace again of quadratic polynomials. Another example of a subspace is when the quadratic polynomials have all 3 letters the same. Do you see it says A? So for example, 5 plus 5x plus 5x squared. 8 plus 8x plus 8x squared. Minus 2 plus minus 2x plus minus 2x squared. And here you see I brought out the A. So this parameterization where you bring out the A is something we're going to find very convenient as we move through. It's just a small little gadget, but it proves to be a convenient gadget. To check that this collection is a subspace, all I got to do is check that it's closed under linear combinations of 2. So I'm only going to do 2. I'm not going to do 3 because I don't need 3. I can get away with 2. So R times one of them plus S times one of them. Of course, it doesn't have to be AAA. In both cases, it might be AAA and BBB. And when you do the algebra, it's not hard to do the algebra. You get RASB for the constant term, RASB for the coefficient of X, RA plus SB for the coefficient of X squared. That's 3 equal coefficients here, 3 equal numbers. And that's exactly the criteria to be a member of A, is to have the same constant term coefficient of X and coefficient of X squared. So that means that it's closed under linear combinations. So that means that by the prior lemma, that means that it's a subspace. And again, the parameterization here, the fact that I brought the A out and just expressed this as all multiples of 1 plus x squared. Capital M is all multiples, all scalar multiples, of 1 plus x squared, any scalar you like, to 108 minus 4.3. That parameterization proves to be a very convenient way to understand vector spaces, and we'll talk about that more as we move through, but just giving you a little preview. Okay, and here's another example. This subspace is a plane. It's a plane through the origin. I want to illustrate that you can also understand it as parameterized, and then that makes it easy to show that it's closed under linear combinations. So to parameterize the plane, I think of 2x minus y plus z equals 0 as a linear system that has only one equation. When you think of 2x minus y plus z equals 0 as a linear system with only one equation, then the leading variables x, y, and z are free. So you express x in terms of y and z. There it is. Express x in terms of y and z. Y and z are free. And so you're looking at this description of capital P. These describe the same set. This is a collection of vectors. This is a collection of vectors. They contain the same vectors. Now, to parameterize, it's got y's and z's, so I got to bring out the y's and z's. So here they are over here. These are the things associated with y, the numbers associated with y. These are the numbers associated with z. So I took this description and parameterized it to get this description. I'm trying to get across why I'm interested in the parameterization as part of showing that something is a subspace, why parameterization is so darn convenient, and so I'm just about to get to that. This is copied from the previous slide, didn't all fit on one slide. I want to show that a linear combination of two of these makes a third that is one of these. So here I go. Here's one of them, y1 plus z1. Here's another of them, y2 plus z2. I took a linear combination, r1 times the first, r2 times the second. I want to show that the result is the third of these, that it's something times this vector plus something times this vector, and of course it is. r1, y1, r2, y2 added together times the first, r1, z1, r2, z2 times the second. So when you have the description parameterized, it's very easy to see that a linear combination of two of them makes a third that's of that form. So the fact is that capital P, as opposed to what's on the previous slide, this description here doesn't make this so plain. Capital P describes, this description right here, describes members of capital P as a linear combination. Right? Isn't that what it does? Not so much on this slide. Doesn't show you how members of capital P are a linear combination. But down here, members of capital P are explicitly written as a linear combination. And down on this line here, we are taking linear combinations of linear combinations, and the result is a linear combination, which we knew it had to be because the linear combination lemma. That's that little, it's a very small observation, but it proves to be at the heart of everything we're doing. A linear combination, R1 and R2, of linear combinations, y1 times the first plus z1 times the first, y2 times the second, z2 times the second. A linear combination of linear combinations is a linear combination. Okay. So the parameterization brings out the linearity and will prove to be a key to understanding what's happening as we move through doing more and more of these. We're going to keep wanting to say, how can you describe this vector space or this subspace in some way? How can you describe it as a linear combination of things? How can you parameterize it? And that will make many of the problems give you an answer. Another example of the same thing. I don't like to do one example. I especially don't like to do one example when it's a very key idea. Okay, so these are 2 by 2 matrices, and they have the property that A equals B, also that C equals B. And these are 2 by 2 matrices that have the property that A equals B, and also that C equals B. So basically, the upper triangle here are all three the same number. the bottom part of the triangle of D could be anything it likes to be. So you might have, for example, 3, 3, 3, 5, or 1, 1, 1, 0. That's a perfectly good collection of 2 by 2 matrices. I'm claiming that it's a subspace. In order to show that it's a subspace, I'm going to do what I'm illustrating. I'm going to parameterize it. Let's go. C, 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 D. I took the upper left, C, 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 and D can be anything it likes. I parameterized, I broke out a C part and a D part. And now I've explicitly written members of capital Q as a linear combination. So when I go to take R1 times the first plus R2 times the second, I'm looking at a linear combination of linear combinations. So this is guaranteed to be a linear combination, and you're starting to see some first hint that linear algebra has the property that this is just a hint, but that it all kind of fits together. It's that linear combinations are the tie. It all makes sense. A person can say it's the same thing over and over again, or you can say it all makes sense. There are themes, and I'm going for the second. Okay, so we've expressed this set as a linear combination. Then we showed that we showed closure under linear combinations because this boils down to a linear combination of linear combinations, and so we were done. Okay, next time we'll introduce the general word for what it means to say that something is the collection of all linear combinations, and we'll work some more with the ideas there. Okay, so let's see here. I got to bring my next time window up. There we go. So next time we're going to do subspaces again, and we're going to again bring out the themes of linear combinations, that it's about figuring out in what way these things are unfettered, free linear combinations. Okay, very good. Bye-bye. Hi, hello, hi. Lot to do today, so let's get to it. So for today's check-in, we're thinking about subspaces, and we're thinking about a particular technique we saw with subspaces, and that is the parameterization technique. I'm going to do that twice, and then I'm going to briefly mention why the parameterization shows that something is a subspace. Okay, so this says this is a subset of the space of quadratic polynomials. So I'm going to refer to members of this subset as vectors because they're members of a vector space. Now I know they're quadratic polynomials. They don't look like 3 or 4 tall columns, but they are vectors. So I'm going to call them that. And here's a technique that helps a person a lot in trying to understand the descriptions of the spaces. I found by teaching the course that often people have trouble with the descriptions of the spaces. In some ways, it's too compact. So to help unpack it here, here's a nice technique. You write down 3 members of the space and 3 non-members, and that helps a person think through. When you write down a plus bx plus cx squared, where b plus 2c equals 0, you just kind of write it down and say, okay, what's the question now? But if you name 3 members and 3 non-members, you think through what is it that the space consists of. So let's get to it. Down to click that off and get to my pen. Okay, so I'm looking for the collection of a plus bx plus cx squared, where b plus 2c is equal to 0, and I'm looking for 3 members and 3 non-members. And I'm just going to take random ones. In fact, it's better to take random ones than it is to take special ones. If a person looks at the description of the space, a plus bx plus cx squared with b plus 2c equals 0, and says to themselves something like, well, 0, 0, 0 works. That's true, 0, 0 does work, but 0, 0, 0 doesn't help you think through what makes something a member and what makes something not a member. So since that's the point of the exercise, I'm going to pick kind of generic ones rather than special ones. Okay, so when I was thinking about what I want to write here, I wrote down a couple, and the first one was 5 minus 8x plus 4x squared. And I'm checking again that b plus 2c, so the coefficient of x plus twice the coefficient of x squared, does give 0. So that's right. So b plus 2c does give 0. And if you want to have a non-member, then you probably want something like 5 minus 8x
plus 3x squared. That's a perfectly good quadratic polynomial. It's a perfectly good member of the set. It just simply of the set of quadratic polynomials, but it just simply doesn't satisfy the condition that b plus 2c makes 0. So it isn't a member of the subset that I'm interested in. It isn't a member of the subspace. Okay, so another example. How about minus 2 minus 6x plus 3x squared. Okay, so again, a person sees something of a pattern here. There's no restriction at all on the constant term, no restriction on what the problem calls A, but you have some tie between B and C. They're connected in some way. B plus 2C is supposed to equal 0, so I have a minus 6 and a 3, just like I had a minus 8 and a 4. So for a non-member, you might have something like minus 2 plus 6x plus 3x squared. So I just simply do not have b plus 2c makes 0. I just don't. B plus 2c makes 12. So it's a non-member of this particular subset. Okay, well maybe a person says, I got it. But I'm going to do one more because it's better to overkill than underkill. And the example I had in mind was to change the plus and minus signs. So 4 plus 10x minus 5x squared. Okay, and it satisfies the condition that b add to twice c makes 0, and it does it by putting the pluses and minus signs in the opposite place. So that's all there is to it. Over here, for a non-member, you could have, say 4 minus 5x plus 10x squared. And it just doesn't satisfy the condition. All I did was move the numbers around a little bit, but it changes, so it no longer satisfies the condition. The next part of the question says parameterize, so I'm going to take a plus bx plus cx squared subject to b plus 2c equals 0, and I'm going to rewrite b plus 2c equals 0 as that's a linear system. Only one equation, but it's a perfectly good linear system. It's got a leading variable and a free variable. So I'm going to express the leading variable in terms of the free variable to get b equals minus 2c. That's all. Now you're writing down here equals a plus minus 2c plus, times x, plus cx squared. Sorry about that. Where A and C are free. They can be anything, no restriction. And I like to break the A's and the C's out. I like to break all the letters out, so I'll write that as the polynomial 1 plus 0x squared times A, and then the polynomial minus 2x plus x squared times C, where A and C are free. Okay? That's parameterization with the two parameters A and C, and this is a particularly handy description of a vector space. Okay, you probably don't remember the second question. The second question asked basically the same thing, only with a slightly different vector space, because this parameterization is something we will do over and over and over again, so I would just simply want to practice it. Not hard, I just wanted to practice it. So I'm looking here at number 2. I'm looking here at A plus bx plus cx squared subject to a minus b minus c equals 0. Again, linear system. It's got a leading variable and two variables that are free. We've done so many linear systems that a person is comfortable with this now. So I can write that as a plus bx plus cx squared subject to a equals b plus c. And I can rewrite that as b plus c times the polynomial 1 plus 0x squared plus bx plus cx squared, where b and c are free. B comma c are free. Boy, having some trouble with my penmanship today. I like to break the b and c out as parameters, so let's see if I can do that correctly. I've done so little correctly. So I think I'm looking at b gets an x plus 1, so that's x plus 1. I like to write them in ascending order. 1 plus x times b, and I think I'm looking at 1 plus x squared times c, where b and c are free. Okay, so really the same problem in the two cases, but just sometimes you do a second one and you feel a little more confident. And then the last part says check that this is a subspace, and the point is that this parameterization here makes it easy to check that something is a subspace. Because if you have something like r times 1 plus x times b, 1, plus 1 plus x squared times c1, plus s times 1 plus x times b2, 1 plus x squared times c2, why then it's clear that it's something times 1 plus x, and it's something times 1 plus x squared. I'll let you work through what the somethings are. But it's clear that when you take a linear combination of linear combinations, what you get is a linear combination. This thing is back in the original space. Again, a linear combination of linear combinations is a linear combination. So I get a linear combination of 1 plus x and 1 plus x squared, and that's a member of the original space. So that's right, that's closure under linear combinations, and we saw last time the key result from subspaces is that makes something a subspace, is that if it's closed under linear combinations, then it's a subspace. Okay, very good. Okay, so we're ready to talk then about collections of linear combinations. We've come to see that subspaces, vector spaces in general, are well understood as a collection of linear combinations. You take a free collection where the letters are unrestricted. It doesn't say b plus 2c equals 0. It just simply says all b's and all c's kind of stuff. You take a collection that is unrestricted collection of all possible letters that are reals and vectors that are in some collection of vectors, and you call that a subspace. And it's a very easy way, very natural way to understand what a vector space is. We get that description by parameterizing, but anyway, once we have it, it makes a subspace. Just a very small remark here. If capital S is the empty set, then we're going to take that the span of the empty set is the trivial subspace, a subspace that consists only of the zero vector. That's convenient for a number of reasons. I'm not going to go into it because it's a small point. I write square brackets for span. There's no real standard notation for span. You do often see authors write span of S. That has the advantage of being explicit. It has the disadvantage of taking more letters, taking up more space. And you see some people write SP. Anyway, I'm giving you a heads up. I personally write square brackets, but you see other things. Okay, and then if some examples. So if, for example, I look at the vector space of all two wide row vectors, then I can look at the span of this one element set, and I get all multiples of that one element set. So if you just have C1, S1, and there is no S2, and there is no S3, and there is no S4, so if you just have C1, S1, that's what I'm looking at here. I'm looking at A times 1, 2, and that's going to be a subspace. Here's another example. This is a collection of two members of R3, two members of 3 space. You notice that they both have zeros. I'm going to assert that if you take linear combinations of 5 times this plus this, minus 7 times this plus 4 times that, 0 times this, minus 6 times that, if you take the collection of all combinations of S hat, that you'll get a familiar subspace. And the claim that I'm making is that the familiar subspace, the span of S hat, is the xy plane. And the answer is because if you give me a member of the xy plane, like 3, 2, 0, I can find a linear combination to give me 3, 2, 0. I can find a C1 and a C2 to give me 3, 2, 0, because put your hand over the third components. You're looking at a linear system. 1 times C1 plus 1 times C2 equals 3, minus 1 times C1 plus 1 times C2 equals 2, and you know, we've done enough with linear systems to know that we can solve that and get a unique solution, and we're home free. So this subset has a span, and just noticing the span is in fact the xy plane. So you don't get any you don't get something that isn't in the xy plane, but I don't think, that's not a surprise. It's true. It's not a surprise. So just another subset of real three space, just to name it. So this is less special than the xy plane. You 1, 0, 2 and 0, 2, 1. I like ones and twos. I don't know. Makes it easier to draw. If you use 10s and 12s, then the picture gets so big you can't see it. So vectors that are in the span are combinations of these two. So I drew 1, 0, 2, there it is, and I drew 0, 2, 1, there it is. And vectors in the span are combinations of the two, so the span is a plane through the origin. It clearly goes to the origin here, because you could take 0 times the first plus 0 times the second. That gives you the 0 vector. So you just have some kind of plane through the origin, and vectors that are in the span lie, the whole body, not just their tip, whole body lies in this plane. That's all. So it's a collection of combinations of 1, 0, 2 and 0, 2, 1. And the lemma says that in a vector space, the span of any subset is a subspace, but we already saw that really in the check-in, is that when you take linear combinations of members of the span, you're taking linear combinations of linear combinations, and that's a linear combination, so you stay inside the span. So that's exactly what the proof, I'm not going to go through the proof here, but it says if you take a linear combination, P times the first thing plus R times the second thing, then a linear combination of those linear combinations is again a linear combination, and so is an element of the span. So spans are a particularly felicitous way to view subspaces or spaces in general, since anything's a subspace of itself. So just to illustrate that previous lemma, sometimes an illustration helps a person more than going through the i's and j's. Not that the i's and j's are hard, but just sometimes it's more helpful. So I have that example where the s hat, where I have the two vectors whose span together makes the xy plane. I just illustrated by taking two members of the span, 5 times the first plus 3 times the second, minus 2 times the first plus 10 times the second. I just sort of made up some numbers, and then took a linear combination of those two, minus 3 times the first one plus 7 times the second one. So just a bunch of numbers instead of i's and j's. Sometimes when a person is taking this course, which often is the first sort of really abstract course that people take, sometimes they find all the i's and j's a little hard to wade through. The trick, the real key, to figuring out i's and j's is to take out a piece of paper and turn the i's and j's into numbers, and then you look at it and you say, well, there was nothing special about the minus 3 and the 7, there was nothing special about the 5 and the 3, there was nothing special about the minus 2 and the 10. This all works with any number. Any number means i's and j's. Okay, and of course that's exactly what a person sees here. I want to illustrate something about subspaces. I've introduced subspaces and said that a good way to understand them is as spans. So I want to illustrate that subspaces are not sort of a willy-nilly pile, that in fact there's some order and organization to them. So I'm going to close today by illustrating that order and organization to them. So I'm going to show, for example, some subspaces of real three space. I'm going to show planes, lines, sort of stuff. I'm going to show subsets connected to their supersets. So let me flash over to the next slide. I know a person is probably still reading, but let me flash over to the next slide. I didn't pick anything special because, as I said, when you're trying to illustrate something, picking special things is sometimes less helpful than picking generic things. So these are supposed to be a collection of just kind of generic subspaces. But you'll notice something about the collection. So there's R3 all the way at the top. Here are the planes. Here are the lines. Here's the trivial subspace. Just the origin. What's this line mean again? I've connected this and the trivial subspace because the trivial subspace is a subspace of this line. I connected this line to the xy plane because this line is a subspace of the xy plane. It's the line y equals 2x, and that certainly lies in the xy plane. I connected the xy plane to R3 because the xy plane is a subspace. It's the span of S hat. Anyway, the xy plane is a subspace of R3. So that's what the lines are showing. And the other thing a person notices about this picture is that the subspaces fall naturally into layers. There's 3 dimensionals, there's 2 dimensionals, there's 1 dimensionals, and there's 0 dimensionals. I'm going to call that 0 dimensionals because it's the span of the empty set. So you make it by spanning a set that has 0 many things in it. Anyway, I'm going to call it 0 dimensional. So that is to say, subspaces, I don't want to leave the impression leaving today. I don't want to leave the impression that subspaces are willy-nilly things. They do have some order and organization to them. Exactly what that order and organization is right down in the parameterization. For example, if you take this plane, x, y, z's, where x plus y plus z equals 0, a person recognizes that as the equation of a plane. Okay, so it's certainly a vector space. And I parameterized it in the way that I illustrated in the check-in. I parameterized it to write it as a linear combination of 2 things. If you do that to all the subspaces from the previous slide, there were not hundreds of subspaces on the previous slide, but if you do that to all the subspaces from the previous slide, you get that all the planes parameterized to be described by 2 vectors, all the lines parameterized to be described by 1 vector, and like that. Here's another plane. When I parameterize it, it's described by 2 vectors. 2 vectors. I know that there's no y in the equation, but it doesn't matter. It's described by 2 vectors. One of them is associated with y, and the other one is associated with x and z, but anyway, 2 vectors. So when you do that for the slide that I showed, connecting all the subspaces, you find that the subspaces fall naturally into the categories that, whoops, oh, and I did a line. I want to get to the categories. Too far. There we go. That the subspaces fall naturally into categories. Those subspaces that are parameterized using 3 vectors, those subspaces parameterized using 2, those subspaces parameterized using 1, and those subspaces, this is why I took the trivial subspace to be parameterized by, to be described by the empty set, it's the span of the empty set, is to make this picture work. Okay, so flashing back here to, I did the planes, each of them parameterized by 2 vectors. Here's the line. 1 vector suffices. It's all multiples of the red vector. There it is. I parameterize it as a description. I got a description where I described every vector in that line as a multiple of 1 vector, 1/2, 1, 0. The y-axis obviously is all multiples of 0, 1, 0. And of course I can describe all of R3 as a span, in an almost silly way. Trivial subspace is the span of the empty set. And so I get to the picture that I just showed you a second ago. It's also the same picture that I showed you at the beginning of this section of the subspaces of R3 connected with the blue lines. And I get this picture. All of the described by 3 vectors, and then there's a layer of all the described by 2 vectors, and then there's a layer of all the described by 1 vectors, and then there's a layer of all the described by 0 many vectors. Okay, I want to close by saying that isn't just true for R3. R3 has a geometry. Everybody's familiar with planes and lines. So R3 has a geometry, and we started off by saying we expect to find planes, we expect to find lines. What happens when you look at a space where there isn't a geometry to point to, there isn't the same natural geometry to point to? And of course, the same thing happens, otherwise I wouldn't be talking about this. In P2, we find that there are all kinds of natural subspaces, linear polynomials, constant polynomials kind of stuff. And we find that the quadratic polynomials have subspaces. Here's a typical one, ax squared plus bx plus c, where a plus b plus c equals 0. Down here is the ax squared plus bx plus c, where a minus c equals 0 and also b minus c equals 0. And then there's a trivial subspace, consists only of the 0 quadratic polynomials, 0 plus 0x plus 0x squared. And again, they fall into layers depending here on sort of how much freedom you have. What do I mean by how much freedom you have? Well, we're going to make that precise by parameterizing. The top layer and the bottom layer are not especially hard. You can describe members of the quadratic polynomials by taking three different, I'm going to call them vectors because they're members of a vector space, three different vectors, x squared, x, and 1, and you can describe members of the trivial subspace. Trivial subspace isn't empty. It contains exactly one, again, vector, 0, x squared plus 0x plus 0, and that's the span of the empty set. The linear polynomials, you express them as combinations of two. Constant polynomials are expressed as combinations of one. If you have ax squared plus bx plus c, where a plus b plus c equals 0, you parameterize it and you end up with combinations of two. See them there? B and c are free. Minus x squared plus x minus x squared plus 1. So this is just like the check-in. I end up with two parameters. So the spanning set has size 2. And similarly here, when I have two restrictions, I end up with a single vector in the description. The spanning set has size 1. So the subspaces of P2 also fall naturally into layers. The layer where you describe things as a combination of 3, the layer where you describe members of those subspaces as a combination of 2, the layer where you describe members of those subspaces as a combination of 1, and the layer where you describe members of those subspaces as a combination of 0. That layer, I understand, that layer may strike a person as a bit of a stretch. But anyway, there's no such thing as describing quadratic polynomials as combinations of 1 and a half. That just doesn't happen. So, again, summary, what we're seeing here is that quadratic polynomials, real 3-space, 4x4 matrices, whatever it is we look at, vector spaces are most naturally described as spans. We get a description of as something as a span by parameterizing. It will be the case that we're interested in the number of members of the spanning set. That will turn out to be an important number because it illustrates the structure, shows you what can happen. You can't have 2.5 members of that set. So there'll be something about those sets that we're interested in. Okay, long day today, very good, but long day. So let's see here, pop up my slide for next time, and we'll see you next time. Hello, hi. Okay, so last time we saw that you can best describe vector spaces, subspaces, or spaces in general, best describe vector spaces as a span of a collection of members. So all linear combinations of a collection of members, which is called a span. So the check-in here today is trying to illustrate that important idea, is that you can express any member of that space, the collection of a plus bx plus cx squared, where b plus 2c is equal to 0. You can express any member of that space as a combination of members of the set S there, where it says 1 comma minus 2x plus x squared comma and 3 minus 4x plus 2x squared. So I'm going to write down three members of the space, and you might remember them, they're the members from last time. You're going to write down 3 members of the space, and I'm going to express them as linear combinations of members of S. That is to say, S is a spanning set for the space. Okay, let's give it a try. So let's see here. The first one from last time, I'd better write down S because I'll forget. So the space is A plus bx plus cx squared, where b plus 2c equals 0. And S was, what the heck was it? It was 1. That's 1 plus 0x plus 0x squared. So it's a perfectly good member of the space. Minus 2 plus x squared, minus 2x plus x squared. And then 3 minus 4x plus 2x squared. If I remembered it right, if I wrote it down right. And the very first one was, it was 5 minus 8x plus 4x squared. And the basic idea here simply is I'm going to write that as something times the first member plus something times the second member plus something times the third member. And it's just a question of coming up with somehow what it is that you want to do and just doing it. So I'm going to fill these parts in. Why don't I use a pencil to dramatize that? I'm filling these parts in. So for example, I see the 2x squared and I see the 4x squared, so I'm thinking to write a 2 there. Not the only thing a person could think to do, but that's what I thought to do. And if I put a 2 there, the 2 times 2 becomes a 4. That's what I'm looking for. The 2 times minus 4 becomes a minus 8. So good, got lucky there. 2 times 3 becomes 6. I don't want a 6, I want a 5. So how about if I put a minus 1 here? And then I guess a 0 there. So I express this member of the subspace. Perfectly good member of the subspace. It satisfies the condition. I express this member of the subspace as a combination of 3 of these. Happens not to need any of these, but it's a perfectly good combination. Minus 1 of the first, 0 of the second, 2 of the third. Okay. Next one, I'm trying to remember what I had last time. Next one was minus 2, minus 6x, and then plus 3x squared. And again, with the fill in the blanks. Okay, oh, I didn't quite make it on the sheet. So I don't know what to do here, but I guess I'll come up with some numbers and see how it goes. I think I tried when I wrote this down while I was thinking about what I wanted to say here. I wrote down a 1 and a 1 because I'm trying to illustrate that I can sneak this second guy in there if I want to. So if you put a 1 there and a 1 there, then you get 1 times 2x squared, and 1 times x squared makes a total of 3x squared. That's what I wanted. Now when I put the 1 there and the 1 there, I also get a minus 4x and a minus 2x, so that's a total of minus 6x. Good. And I get a 3 and a 3 and a 0. 3 and a 0, so that's 3 so far. And how many of these do I need? I guess I need minus 5 of these. Okay, did I do that right? So 3 and 0 minus 5 makes a total of minus 2. I think I did that right. And then the last one, just again to illustrate here, I'm looking for, what the heck was it? It was 4 plus 10x minus 5x squared. And again with the blanks. I know it's annoying if you do too much of it, but I'm trying to leave, of course, a visual impression, and so I'm putting visual symbols down. Okay, and I guess here, what the heck do, so, guess, what to do, I'm gonna put a minus 5 there to pick up the minus 5x squared. Okay, if I put a minus 5 there times the minus 2 makes a positive 10, so I get the 10 automatically. So I don't need this x squared and that x. I don't need it. So minus 5 there and a 0 there. And what am I going to do for the constant term? Why, this doesn't have a constant term. This has a constant term, but it's multiplied by 0. So this doesn't have a constant term, so I don't need to worry about it. So I think if I put a 4 there, I think I'm in business. So I think I'm in business. Okay, so what I found is that I can, by just thinking about the numbers, not the letters yet, but I can write any member of the space. It's just the 3 I tried, but I can write any member of the space as a combination of those things. So that was the first question. Then the second question, I forgot the second question already, is, observe that the third member of S is a combination of the other two. 3 minus 4x plus 2x squared is a combination of the first two. Yeah, it is. Yeah. And then it says use that to express V1, V2, and V3 as combinations of just the first two members of S. So it turns out I didn't need this third member. I could have got away without it. I could have made the spanning set even smaller, and I still would have been good. Okay, so what 3 times 1 minus 2 times, okay, so I better write that down because I'll forget. So I have 3 times, 3 times 1 minus 2 times, no, plus 2 times minus 2x plus x squared makes the third one. 3 minus 4x plus 2x squared. Yes, that's right. Okay, and this is just a question of noticing that I can go up and take, I'll just take the second one, just to illustrate something, I'll take the second one. I can take minus 2 minus 6x plus 3x squared, take the expression that's written there, minus 5 times 1, plus 1 times minus 2x plus x squared, plus 1 times 3 minus 4x plus 2x squared, rewrite that as minus 5 times 1 plus 1 times minus 2x plus x squared plus 1 times, I'm going to copy, of course, this right into this blank space here, 3 times 1 plus 2 times minus 2x plus x squared. And now I'll combine the ones and combine the minus 2x plus x squared, and what do I get when all the smoke clears? There's 5 and there's minus 5 and there's 3, so I'm ending up with a minus 2 times 1. And how many minus 2x plus x squareds are there? 1 and 2 more makes a total of 3. And I better check. So minus 2, yes, that's right. What about coefficients of x? Minus 6, that's good. What about coefficients of x squared? 3 and 3, so that's right. Now obviously the same trick would work, it's the same technique, would work for the other two. That is to say, you can expand the third term and get rid of the third term in some sense, get instead a combination of the first two, and you don't need the third term, you can boil it down to the first two, so you can get by with a smaller spanning set. If some member of the spanning set is a combination of the others, why, you can get rid of it. Okay, so the check-in is some practice. The check-in is some practice with spanning sets and is making a point about parameterization here and making a point about how you can express a vector space, subspace, or any vector space at all using somehow these members of the spanning set. Members of the spanning set. Okay. Whoops, what happened here? Oh, I'm in the wrong place. Sorry. There we go. Linear independence. So I want to introduce an idea here based on what we talked about in the check-in. I want to introduce an idea here, and I know the last video was pretty long. Fortunately, this one's relatively short. I want to introduce an idea here that talks about having somehow a minimum number of members of those spanning sets. So I have to define the term, and then we're going to see that it relates to a minimum number. So in any vector space, set of vectors is linearly independent if none of its elements is a linear combination of the others. Linearly independent. So in the check-in, we saw that the third member of the spanning set was in fact dependent on the other two. You could express the third member as a linear combination of the other two. So we would have said, now with the vocabulary that we have now, we would say that the set I started with, the 3-member set, was linearly dependent. When you cross that third member out, then the remaining two are independent. You can't express the one as somehow a multiple of the other. I want to make a point here about linear independence and linear dependence to start out. It's very often the case in mathematics that you see a definition that tries to capture somehow the concept of what independence and dependence is. Linear independence is when none of its elements is a linear combination of the others. But then a lot of times you'll follow up a definition like that with a lemma or a small result that says to compute whether something is. In this case, whether something is linearly independent. Here's the most convenient way. And that's exactly what's happening. If I write a vector as a linear combination of the others, if I write S0 as a linear combination of the S1 through Sn, visually I've set S0 off, but in fact algebraically I've got a kind of an unbalanced situation there because I have one vector being treated differently than the others. It's algebraically convenient here to move it over to the other side of the equation and get 0 on the left and then just some combination of S0 through Sn on the right. And basically here, if you have a combination on the other side, if you have a combination on the right-hand side of all these vectors, these SIs, you can, in fact, if you want to, move it over to the left and get isolated, or you can think of it as all being on the same side and 0 on the other side. When we don't want to single out one vector as sort of different than the others, and we often won't, when we don't want to single out one vector as sort of different than the others, what we'll say instead is that they're in a linear relationship, and we'll write them all on the same side. And that proves to be convenient here. If you write all your vectors on the same side, and then equals 0, that will prove to be the most convenient way to check whether a subset is linearly independent or not. Okay, so I'll read it. A subset of a vector space is linearly independent if and only if, among its elements, the only linear relationship, I have the s's on one side of the equation and 0 on the other, is the trivial one, namely all the ci's are 0. Okay, and I'm assuming that si is unequal to sj. So the point here is that I defined a concept that no one is a combination of the other folks. And then I immediately followed it with a lemma that says, here's how to compute. If you're given a set on the homework, question 1 says, here's a set, decide whether it's linearly independent. You write it in this form here. You write it as all the vectors on one side, a linear combination of all the vectors on one side, and 0 on the other side. And then you see whether that implies that the only vectors, the only combination that works is to have all the coefficients, the scalars, the ci's, equal to 0. Okay, now I gave a proof, but do we really need a proof? Is that if S is linearly independent, then there's no linear relationship where some of the S's have non-zero coefficients, because otherwise you could move everything to one side of the equation and get that Si all by itself and you'd have a combination. And vice versa here. If S is not independent, then you have Si is some combination of the others. And when you move it over to the other side of the equation so that you get 0 on the left and the Si is in there on the right side with the others, why you have some collection where there's a linear relationship and not all of the Ci's are 0. It's okay if some of them are 0, but not all of them are 0. Not all of them are 0, it says up here, would tell you not independent. Okay, so to decide whether a list of vectors is linearly independent, what happens is you set up the equation, you put 0 on one side, and you write a linear combination of the SI's on the other, and you do what it takes to figure out whether any solution exists other than all of the Ci's are 0, other than the trivial solution. High time for a numerical example. So here's two vectors in the plane, and they're linearly independent. You can tell at a glance that neither of them is a combination of the other one. What do you do here to follow the lemma? And the answer is to follow the lemma, you set up a linear combination of those vectors equals to 0. And you ask yourself, can I find a C1 and a C2 that are not both 0? And of course, at a glance, you see, no, you cannot find such a C1 and C2. No. And you also get a hint that what's going to happen here is we're going to get linear systems, and we'll solve the linear systems. Another example, we'll try and have a sort of the first one was very easy, the second one is a little less easy, but not all that hard. I have a set 1 minus x and 1 plus x that is a subset of the collection of cubic polynomials. Well, this is a cubic polynomial, this is a cubic polynomial, fair enough. And I'm asking, is it linearly independent? And of course, the question says it is linearly independent. So to prove that, I set up a combination of the two members of the set. They're vectors because they're members of a vector space. I set up a combination of the two vectors, set it equal to, that's not That's the zero polynomial. 0 plus 0x plus 0x squared plus 0x cubed. So don't get confused. That's the zero member of the space. So there I go. I have a linear combination of the two on the left, and I have the zero polynomial on the right, and that leads me to what's the constant term on the left, what's the constant term on the right? That gives me an equation. What's the coefficient of x on the left, what's the coefficient of x on the right? That gives me an equation. There's also an equation for x squared and x cubed, but it just says 0 equals 0, so I left it out. When you look at this system, C0 plus C1 equals 0, minus C0 plus C1 equals 0, we've done a lot of these. A person can tell, this is not one that you need to go through Gauss's method, a person can tell at a glance that the only solution is C0 equals 0 and C1 equals 0. So the lemma says if the only solution is the trivial one, then you write down the word independent. If there's any other solution, you write down the word dependent. Or another example, trying to have a wide variety of examples. Important idea, but we want to focus just on the one idea today. So wide variety of examples. The rows of this matrix. The rows of this matrix form a linearly independent set. Can you write down C1 times the first row plus C2 times the second row plus C3 times the third row? We won't worry about the zeros there. Can you write down C1 times the first row plus C2 times the second row plus C3 times the third row and get the zero row vector 0, 0, 0, 0, 0? Can you write down, is there a non-trivial collection of C's that gives you that? And of course no. If I were to write down here, if I were to write down, if I can hit my buttons there, if I were to write down C1 times the first row plus C2 times the second row plus C3 times the third row, and I ran out of space, equals the 0 row. Let me remind myself what the parts are. It is 2, 0, 1, minus 1, 2, 0, 1, minus 1, 0, 1, minus 3, 1 half, and 0, 0, 0, 5. If I write down that equation, then I think, of course, I can do Gauss's method. I can set up the system of first components, the system of second components, the system of the equation, excuse me, of second components, the equation of third components, and the equation of fourth components, and I get a homogeneous system. Or you can just apply your noggin, just apply your noggin. Look at the equation of first components. C1 times 2 plus 0 equals 0. You conclude C1 equals 0. I mean, nobody. I'm not providing any penalties for being smart enough to see the answer, and a person could just see the answer. Sometimes with these linear systems, you have to apply Gauss's method. It's just too hard, but this is not in that category. Knowing that C1 equals 0, look at the equation. Look at the combinations of second components. Because C1 is 0, I can cross that off and no longer have to think about it. I'm looking at C2 times 1 plus 0 equals 0. Okay, so C2 equals 0. Sort of stuff. We get that C0, C1, C2, and C3 are all 0, and so I get that the only solution is the trivial one, and so I'm looking at linear independence. This subset of R3 is linearly dependent because when you take C1 times the first plus C2 times the second plus C3 times the third, you get a linear system, and it has more than just a trivial solution. Whoops, excuse me, more than just a trivial solution. So that's the only case. Okay, so that ends the day. We're interested here in figuring out when these systems have more than just a trivial solution, that's linear dependence. When they have only the trivial solution, that's linear independence. And we'll talk more about it next time. Okay, very good. Bye-bye. Hello, hi. So we're talking about linear independence today. Last time we did the first linear independence part, and this is the second linear independence part. So the exercise, the check-in exercise that we're looking at, is a straightforward linear independence problem. One thing a person might notice is that it says, show that the first is linearly dependent, and a person might say to themselves, so I need to think out exactly what combination of 1, 2, 3. What adds to, so a person might say, I noticed that if you take the first one and then you double the, very true, very true. If you happen to notice exactly what the dependence is, well, that's great, good for you. Nobody made seeing the answer a crime. But I'm going to go through, when I do this problem, I'm going to go through and produce how you would solve the problem in general, because for those times when you're stuck, you don't see quite what to do. It doesn't do you any good to have seen a couple of clever answers and then be called upon to be clever. At least it doesn't do me any good. Okay, so I'm looking to show that that the first set is linearly dependent. So I'm looking to say something like C1 times 130 plus C2 times 120 plus C3 times 1 minus 10 is equal to 0, 0, 0, and I expect to find more than just a trivial solution. I expect to find that there's some C1 and C2 and C3 that are not all three of them 0 that make this equation true. So of course I'm going to answer this question the way I answer so many other questions in here, is I'm simply going to do Gauss's method. So here we go. I get C1 plus C2 plus C3 equals 0 by looking at the top line. Then I get 3C1 plus 2C2 minus C3 equals 0. And the bottom line is 0 equals 0. If you do minus 3 row 1 plus row 2, then you get C1 plus C2 plus C3 equals 0. And then the next line is minus C2 minus 4C3 equals 0. And the 0 equals 0 line is not very interesting. Okay? So from this, you can, of course, express, you can pick C3 to be something. Pick C3, for example, to be 1. Pick it to be 5, I don't care. Pick C3 to be some value. If you take C3 to be 1, then that'll give you C2. Once you know C3 and C2, that'll give you C1. So there are infinitely many solutions. And so that makes this linearly dependent. And you can name a particular solution by picking a C3. On the other hand, if you want to show that the other set is linearly independent, then you're taking C1 times 130 plus C2 times 120 plus C3 times the new one, 1 minus 1, 1 equals 0, 0, 0. And again with the Gauss's method, C1 plus C2 plus C3 equals 0. 3C1 plus 2C2 minus C3 equals 0. And then C3 equals 0. Okay, off you go. Minus 3 row 1 plus row 2. C1 plus C2 plus C3 equals 0. Minus C2 minus 4 C3 equals 0, and C3 equals 0. And we have so much experience with these, we spot echelon form right away. There's a unique solution. So you get linear independence. Okay? So checking linear independence or dependence is very straightforward. You are going to set up the linear system. Of course, if you can see at a glance what the dependence is, good for you, good for you. But if you don't see at a glance, you set up the linear system, chug away. Infinitely many solutions implies linear dependence, and you can pick a particular, for example, C3 equals 7. That'll give you C1 and C2, and now you can exhibit a dependence. On the other hand, unique solution gives you linear independence. Okay, what I want to talk about today is the relationship between, there we go, whoops, There we go. I want to talk about the relationship between sets that are linearly independent and the supersets or subsets of those. So let's see here. I want to remind a person what the definition of linear independence is. Set of vectors, of course, is linearly independent if none of its elements is a linear combination of the others, if each element is somehow independent of the others in a linear way. Otherwise, it's linearly dependent. And we did the calculation of linear independence last time as we illustrated it with the check-in. And today I want to talk about the relationship between subset and superset and linear independence and dependence. So, if you have a vector space and S is some subset of that space, then you can add vectors to S. You pick a vector V and you throw it into S, making a new set S hat. You pick a vector V, you throw it into S, and the question is, does it make the span grow? Or does it leave the same? So if V is already an element of the span, then the new span, the span of S union singleton V, will be the same as the old span. If, on the other hand, V is not an element of span of S, then when you add it to get the new set S hat, then the new span will be bigger than the old span. Okay, so when we first started looking at linear systems, we worried about, we would write like a first equation and a second equation, and then we'd say something like, okay, now, if the third equation is, for example, the sum of the first two, then it isn't anything genuinely new. And so we would get what we today call a linear dependence. That is, in the terminology we have today, the third row would be in the span of the first two rows. And so we found that it didn't add anything new to the equations. If, on the other hand, it was something genuinely new, it wasn't a combination of the first two, why then it sometimes made, for example, a system have a solution. Now, I don't want to make this more complicated than it is, so I want to do an illustration rather than a proof. Sometimes the proofs is you can lose the ideas a little bit. So I'm going to take a set capital P, and the span is the xy plane. I want to make it perfectly clear that the span is the xy plane, so I took a very straightforward example. I can add a vector to get a size 3 set, either P0 or P1. I can add a vector to get a size 3 set, and I can do one of two things. The vector is called Q. I can either add something from the xy plane, or I can add something that isn't from the xy plane, somehow sticks up. If the new vector is from the xy plane, in the P0 case, well then the span of P0 will be the same as the span of P. You haven't added anything new. Whatever new means, well, of course, we're in the process of defining new. But if the vector that you added lies outside the span, then the span will grow. The span of P1 is strictly bigger than the span of P. You can get not just xy plane vectors, but you can also get vectors that have a vertical component. Okay, so the corollary is that if you have a V and S in your what I'm thinking of as a spanning set, if you omit that vector, then omitting that vector does not shrink the span if and only if it's dependent on the other vectors in the set. So if you have a vector that's dependent on the other vectors, you can toss it and it won't change the span. And this is the right example to look at. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Have you noticed that 7, 8, 9 is a combination of 1, 2, 3, and 4, 5, 6? Maybe you noticed because it said so down here. If you take 2 times the second vector and subtract the first, 2 times 4 minus 1 does make 7. 2 times 5 minus 2 makes 8. 2 times 6 minus 3, 12 minus 3 does make 9. So 7, 8, 9 is a combination of the first two vectors, and in some sense it's a repeat of the first two. So the span of this set is the same as the span of this set. What you can do with a linear combination of vectors from this set is exactly the same as what you can do with a linear combination of vectors from this set. The third vector is a repeat of the information in the first two. Okay, and just turning it now to talk about linear independence, a set is linearly independent if and only if for any vector in S its removal shrinks the span. So if I take, for example, since it's here on the screen, I'll use it, 1, 2, 3, 4, 5, 6, that's linearly independent. If you throw out the 4, 5, 6, no longer do you span a plane, now you only span a line, all the multiples of 1, 2, 3. Here's another example. Of course, this is a linearly independent subset of the cubic polynomials 1 plus x, 1 minus x, and x squared. Because it's linearly independent, if you take out any element, for example, if you remove the middle one, to get the new set s hat 1 plus x and comma x squared, then that'll make the span smaller. The span of s hat is smaller than the span of s. So there's an interaction between linear independence and span. Again, all these results that each of them are small results at a time, lemmas and corollaries, but they all add up to the intuition about what is new and what is not new. If you're in the span, if you're linearly dependent on the other vectors, then you don't add anything new. So suppose S is linearly independent and that V is not in S, then the set S union singleton V is linearly independent if and only if V is not in S. That is to say, if it's not in the span of S. If V is something genuinely new, then when you add it to a linearly independent set, you retain linear independence. But if V is not genuinely new, if V is in the span, then adding it to a linearly independent set will cause the new set to be linearly dependent. And here's the illustration. So this is a linearly independent subset of P2, 1 minus x and 1 plus x. Its span is a set of all linear polynomials, and I think that should be clear, but if it isn't clear, here's the check. You can get any linear polynomial as a combination of these two. There are two ways that you could add a vector to S to get either S1 or S2. If you add a linear polynomial while you're adding something that's in the span of S. So S1, it takes S and it adds something that's already in the span, so something that you could already reach. Whereas S is linearly independent, the set S1 with this repeat information will be linearly dependent. The other thing you can do, of course, is to add a vector that's genuinely new in the sense that it isn't in the span. Where S is linearly independent, so too S2 is linearly independent. This has linears, this has a quadratic, so it's something genuinely new, it isn't in the span. Okay, so the point here is that there's an interaction between span and linear independence that we're working up to. The next section, we talk about the interaction very closely. There's an interaction between span and linear independence, and it all has to do with this idea from first day, second day, of talking about things that are linearly new. A corollary, another small result in a vector space, any finite set has a linearly independent set with the same span, and I'm going to do this by example, but the basic idea is it's a finite set, so you can throw things out one at a time, and eventually you'll get down to where all that's left is linearly independent, and that's the idea here. So I took a set with many vectors in it, and clearly linearly dependent. For example, the second one is 3/2 the first. If I write down a linear relationship, I get a lot of R1s, R2s, and R3s. Do Gauss's method, and you spot that R1 and R3 are leading variables. And the other aren't leading variables. Free variables. When you do the parameterization, there you see the R2, the R4, and the R5 are free variables. Now I want you to notice that if you set R5 to be 1 and R2 and R4 to be 0, set R5 to be 1 and R2 and R4 to be 0, then you get an R1 and an R2. So there's R3, there's R3, and there's R5. This is a linear relationship among those three vectors. This is a linear relationship among those three vectors, so it exhibits a linear dependence. So S5 in particular is in the span of the set S1, S3. And likewise, if you do the same deal for R4 and you do the same deal for R2. This vector right here will be in the span of the set S1, S3. This vector right here will be in the span, the vector S4 will be in the span of the set S1, S2, excuse me, I misspoke, and S1, S3, and then the vector S2 will be in the span of the set S1, S3. Excuse me, I misspoke. Okay, so what that tells you is that you can throw those out. You can throw out S5 because it's in the span of S1, S3. You can throw out S4 because it's in the span of S1, S3. You can throw out S2 because it's in the span of S1, S3. And now you're down to a linearly independent set, and so the result is that you can throw out any of the other variables and retain only the vectors associated with the leading variables, and that suffices. And corollary, really it's a restatement of what we just did, but it's sometimes convenient to do it in this order. A subset of a vector space is linearly linearly dependent if and only if some SI is a linear combination of the vectors that come before it. And the proof is here, but the basic idea is pretty straightforward. You just add the first, then you add the second, then you add the third. At some point you get to a dependent set. At that point the vector you just added must be dependent on the previous ones. So that's all. So a small observation. So that we're now at the conclusion that linear independence and span interact in some way. In particular, a subset of a linearly independent set is also linearly independent, and a superset of a linearly dependent is also linearly dependent. Just to take the first sentence, if you have a linearly independent set, there is no relationship, no linear relationship, no non-trivial linear relationship among the vectors. Throw out some of the vectors, there's still no non-trivial linear relationship among the vectors. Likewise, but flipped over, with linearly dependent, if you have a linear relationship among some of the vectors, and you add more, the old linear relationship still holds. So that gives you these two corners. If S is independent and S hat is a subset of S, then S hat must be independent. On the other hand, if S is dependent and S hat is a superset of S, then S hat must be dependent. That's this lemma restated. The other two corners of the box can go either way. If S is independent and you add stuff to it to make it bigger, to make it S hat, well, if you add stuff that's already in the span, then you flip from being independent to being dependent. On the other hand, if you add stuff that isn't in the span, then you stay independent. So this could be either. And likewise, this is exactly the same thing. If S is dependent, then if you're going to throw stuff out to make a smaller S hat, you can throw out stuff that brings you down to independent, or you can fail to do that. We've seen examples of both of those happening. Okay, so we talked about here the relationship between independence, between linear independence and subset and superset, and always at the heart of those was that there's some interaction between linear independence and span. The two of them have to do with each other very closely, and we're going to next time talk about how very closely they are related. Okay, very good. Okay, bye-bye.
Hi, hello. So last time we talked about linear independence, and we described specifically the interaction between linear dependence and independence, and adding elements to the set. So we're gonna the check-in is going to focus on that, and we'll last time we noticed that it had something to do. Linear independence has some interaction with span, and so this time we'll combine the two in what is probably the most important single idea of the course, most important sort of single definition of the course, or maybe after the definition of vector space itself. Okay, so you can see the question asks me to find a spanning set for the plane, and that's a pretty routine spanning set for the plane. That's a pretty routine question from the homework, and show the spanning set is linearly independent. And then finally, I'm going to add a vector to that spanning set and ask whether the resulting set is linearly independent or dependent. Okay, so let's give it a try. So let's see if I can remember the plane through the origin first. It is the set of all x, y, z, where it's what x plus 2y minus z equals 0. And we've seen before how to do this. The idea is to view this as a one-equation linear system So x is leading, y and z are free, and you express x in terms of y and z. You get the set of x, y, z, where x is minus 2y plus z. And then you rewrite that as the set of minus 2y plus z, y, z, and the advantage is here that y and z are free. So no longer do you have to worry about some interaction between the variables. Instead, you just take any y and any z, and this is a very straightforward criteria for membership in this set. We have liked to break out the y and the z in the description. So I'm looking at what minus 2, 1, 0 times y, and is it 1, 0, 1 times z? Okay, so that makes the spanning set. Manifestly, from this description, a person can see that the spanning set is this vector and this vector, and any combination of those two vectors suffices to make any member of the plane. That's just obvious from that description. So the spanning set is going to consist of the two vectors, minus 2, 1, 0, and 1, 0, 1. Okay. The second part asks me to show that that's linearly independent, so that's not hard. Oops, this was the first part. Here's the second part. Show that that's linearly independent. That's not hard once you know the idea for computing whether or not a set is linearly independent. It's very straightforward. You make a combination of the two vectors, minus 2, 1, 0, and 1, 0, 1, add to 0, 0, 0. And that leads me to a linear system. Let's see, what is it? Minus 2c1 plus c2 equals 0. c1 plus 0 equals 0, and c2 plus 0 equals 0. And so obviously here, there's a unique solution, c1 equals c2 equals 0. And so you conclude that oops, I wrote two L's. You conclude that you have linear independence. Okay, so that calculation is relatively straightforward. And now there's the part I knew I would forget. This part. I have to add a vector. Oh, 1, 1, 2. That's right. I have to add a vector to the set 1, 1, 2 and decide whether the result is linearly independent or dependent. So I'm going to need a piece of paper for that. Let's see. So for part 3, what I want to do is I want to consider the set. It's a new set, so I'll give it a new name. S hat will be, is it minus 2? Minus 2, 1, 0. And then, whoops, 1, 0, 1. And then it is 1, 1, 2. And I want to decide whether that's linearly independent or dependent. But the lesson that we learned last time, the thing that this check-in is reminding a person about, the lesson that we learned last time is that the original set here, S, these two vectors, the original set is linearly independent. So the result will be linearly independent if the new vector is something brand new. If 1, 1, 2 is not in the span of these two, if 1, 1, 2 is not in the span of S, then the result will be linearly independent. On the other hand, if 1, 1, 2 is in the span of S, if 1, 1, 2 is a repeat in the kind of language we were using the first day or two, if 1, 1, 2 is not in the span of S, you get linear independence. If 1, 1, 2 is in the span of S, you have linear dependence. Okay, so I'm going to note here, we know what the span of S is. It's the set of vectors that satisfy the criteria x plus 2y minus z equals 0. So I'm going to note that 1, 1, 2 does not satisfy x plus 2y minus z equals 0. Does not satisfy. So that means 1, 1, 2 is not in the span of S. 1, 1, 2 is not a linear combination of these two. 1, 1, 2 is not in the span of S, so it should be linearly independent. The result, S hat, should be a linearly independent set. I'm going to check that with the actual calculation, but we already know from the results we saw last time that because 1, 1, 2 is genuinely new, genuinely new, that it will result, adding it will result in maintaining and preserving the linear independence of the set. So when we go from S to S hat, we preserve the linear independence. So anyway, I'm going to do the problem as though I hadn't noticed that. So I'm looking at C1 by minus 210, C2 by 101, and C3 by 112 equals 0, 0, 0. Okay, and then I get a linear system. Minus 2C1 plus C2 plus C3 equals 0. C1 plus C3 equals 0. And C2 plus 2C3 equals 0. And we've done so many of these. 1/2 row 1 plus row 2. Minus 2C1 plus C2 plus C3 equals 0. That one's unchanged, of course. The next row gives me 1/2 C2 plus 3/2 C3 equals 0. And then, of course, the bottom row is unchanged, so C2 plus 2C3 equals 0. And then one more step, I got to use this to get rid of that. So I'm looking at minus 2 row 2 plus row 3. Copy down the first row. I should have done this with arrays. It would have been less writing. Minus 2C1 plus C2 plus C3 equals 0. 1/2 C2 plus 3/2 C3 equals 0. And finally, minus C3 equals 0. Minus C3 equals 0. And of course, this is echelon form. I have a unique solution. The unique solution must be C3 equals 0, C3 equals C2 equals C1 equals 0. And so we have linear independence. Okay, so again, we saw, because of the results that we saw last time, that because 112 is not in the span of S, therefore, we would get linear independence, and indeed, that's what we found. Okay. Okay. All right. So let's turn that now to talking about the material that we're going to do today. And the material that we're going to do today is we're going to introduce a new idea that tries to sort of capture what it means to say minimal spanning set. Succeeds in capturing what it means to say minimal spanning set. So basis. So a basis for a vector space is a sequence of vectors that's both linearly independent and spans the space. Now there's a couple of different things in this definition, linearly independent and spans the space. Certainly a person notices that. But the other thing that a person notices is that it's a sequence of vectors. So a sequence, you'll remember, is that order matters. Because the basis is a sequence, I have to denote somehow that order matters, and to help a person remember that order matters, I'm using these diamond brackets that have become pretty standard way to denote a sequence of things. So the point of the diamond brackets instead of set brackets is that order matters. If I change it from beta 1, beta 2, etc., to beta 2, beta 1, that'll be a different basis. We won't see so much why that's true today, but we'll see it with the next talk. Okay, and of course I need to do an example, and the first example is a particularly commonly occurring basis. So this is a basis for the plane, 1, minus 1, and 1, 1, and again this just happens to be the case that this is a basis that comes up a lot, so it's a good first example. I can easily check that it's linearly independent, doing the kind of stuff I was doing just 5 minutes ago. Remind a person how to check that it spans. You can do C1 plus C2 equals XY. So the idea here is that if you give me any XY in the plane, can I find the appropriate C1 and C2? And yes, this work shows you how to find the appropriate C1 and C2. Before we go any further, I'll just comment that a person undoubtedly says to themselves something like, well, you kind of did the same thing twice. Very true, very true. We have to get through things in a certain order. You can only do so many things at a time. But you have noticed that there's some interaction between linear independence and span. You're absolutely right about that. And of course, we'll talk about that. All right, another example, just because basis is so important, and also because I don't like to do one example of anything, especially something important. So this is the vector space of linear polynomials. constant term plus a linear term. And one basis is, it looks like the basis from the previous slide, 1 plus x and 1 minus x. Easy to verify linear independence. Easy to verify that it spans the space. If you give me an arbitrary element of the linear polynomial space, it's got a constant term and a linear term, and I want to say, is there a C1 and a C2? And after a little bit of arithmetic, it turns out, yes, take the constant coefficient plus the linear coefficient, add them, divide by 2, that's C1. Take the constant coefficient, the linear coefficient, do the subtraction, divide by 2, that's C2. So if you give me an A and a B, I can give you a C1 and a C2. So in short, you can, with the right combination of these two things, get any linear polynomial at all. So that makes it a basis because it combines the two things of linear independence and spans the space. And you'll notice again I wrote it in diamond brackets because order matters, but order won't really matter until next class, next video. Okay, here's a basis for the 2 by 2 matrices. So I just made one up. It's easy to verify that it's a basis. It's pretty easy to see, for example, that it's linearly independent. It's also easy to see that it spans the space. Here's another basis for the 2 by 2 matrices. So one thing that a person learns in this example without seeing the verification that these are bases, one thing a person learns in this example is that a space can have more than one basis. You'll notice that both of these have 4 elements that will matter too. All right, and oops, hit the wrong button. So this is a basis for 3 space, a basis for R3. So it's kind of the obvious basis. It's clearly linearly independent. If you sort of close your eyes for a second and ask yourself, can one of these be a combination of the others? No. And then what about, does it span? If you give me an XYZ, can I find an appropriate? Yeah, well, yes, obviously. I'm going to call that script E. So we're going to use E for what is the kind of the usual basis for R3. Calculus books sometimes call those I, J, and K. They have a different tradition that they're responding to, but one in particular point is that if we had R4 or R5 or R6, we'd eventually run out of letters. So we're not going to do that. So for any Rn here, E sub n is the obvious basis, the kind of natural basis, the canonical basis, the standard basis, and I'm going to denote its members with lowercase e's. And it's pretty obvious. I mean, you can write it down on a piece of paper, but can't you do it in your head? Show that it's both linearly independent and that it spans the space. A basis is a sequence. Order matters, and again, we'll see why that's important in the next class. Although this theorem gives us a preview of that, but it's common practice to refer to a basis as a set, and we'll also probably routinely refer to a basis as a set. I'm just following common practice in the field, so just so that I'm not doing you any favors if I use entirely different words than everyone else in the world. Okay, so basis is important for many reasons, but one reason that a basis is important is this theorem. In any vector space, a subset is a basis if and only if each vector in the space can be expressed as a linear combination of elements in the subset. Now, before I go on, all that says so far, every element in the space can be expressed as a linear combination of elements in the subset. All that says so far is that it spans the space. Well, that's part of the definition, so that's not interesting. It's the following part that makes it interesting. It says can be expressed as a linear combination of elements in a unique way. So if I write down a basis for a space and I figure out how to express another element of the space, it's not the case that there are 2 of those or 3 of those or infinitely many of those. There's only one way. If you give me a basis and an element of the space, there's exactly one way to write the space element as a combination of basis elements. And we really basically saw this in the early calculations, but just to go through the proof, just to go through the argument here, is that sequence is the basis if and only if its vectors form a set that spans and that's linearly independent. And of course, the members of that set, the subset, is a spanning set if and only if each vector in the space is a linear combination in at least one way. So emphasizing again what I said, what I broke off to say in the middle of the theorem, that we already know that a basis, if you drop the whole sequence thing and just call it a set, that a basis is a spanning set. So saying that every element of the space can be expressed as a combination of basis elements in at least one way is hardly surprising. What the theorem instead says is that it can be also expressed as a linear combination of basis elements in at most one way. So we'll finish if we show that a spanning subset is linearly independent if and only if every vector in the space is a linear combination in at most one way. So basically there's a tension here. So a set gets to be linearly independent if it's small, right? Suppose that you have, for example, vectors from the plane. We saw this in the last video. You have vectors from the plane, and you have like 5 of them. So we had 5 vectors in the plane, and we showed you can throw things out. That spanning set can have many things in it, and there's no harm done. But with a linearly independent set, it tends to be small. So spanning sets tend to be big. You throw new things in them, it doesn't do any harm. Linear independent sets tend to be small because if you take a linearly independent set and you put in something new, you run the danger of destroying linear independence. So there's a tension here, trying to go top to bottom. There's a tension here. Spanning sets have a tendency to be big. Linear independent sets have a tendency to be small. And the spot in the middle, where you're both spanning and linearly independent, is sort of a sweet spot. So what we're saying is that if you span, then you get the at least one way. We're going to show linear independence gives you the at most one way. And I don't have space on the slide for it, so I fit it onto the next slide. Okay, so here's the idea. Suppose I want to express a member of the subset in 2 different ways. So the member of the subset is V, and I'm going to express it in 2 different ways using the basis elements. And I use beta for the basis elements just because beta and basis just makes it more memorable. Okay, so here I go, C1, C2, etc., D1, D2, etc. Then, of course, I have equality between the 2. They both equal V, so they equal each other. And you know what's going to happen. We've done so many of these now. I'm going to bring everybody over to one side of the equation and leave 0 on the right-hand side. So there I did. And we recognize instantly what's happening here is that you have linear independence if and only if each of these subtractions is 0. Asserting that there's only one way, asserting that each of these subtractions is 0, asserting that C1 equals D1, C2 equals D2, etc. So asserting that there's only one way is exactly asserting linear independence. That's exactly what linear independence gives you. Okay, so the theorem, back to the theorem, which is an important result. In the vector space, a subset is a basis if and only if any element of the space can be expressed in exactly one way. Okay. And then next time, when we come back next time, not finished this today, when we come back next time, we're going to talk about that this gives us a way to kind of characterize members of the space, that we'll have that members of the space are characterized sort of relative to the basis. Okay, very good. So we'll see you next time. Hi, hello. Okay, bases. So let's get to it. So the check-in, of course, asks us to find things out about a basis, show that there's basis for the plane, and asks what linear combination of basis elements make that particular plane vector. So 3 minus 2, and so I'm going to find the C1 and the C2 that make 3 minus 2. And then this third question is the same thing, only with a different vector space and a different set. Okay, so let's have a whack here. So let's see. It says show that the basis, show that the sequence 1 1 1 minus 1 is a basis. So the very first thing to do, of course, is to worry about linear independence. So C1 times 1 1, C2 times 1 minus 1 makes 0 0. All very routine. We've done this a lot, so we're getting good at this now. C1 plus C2 equals 0, and C1 minus C2 equals 0. A person can notice that if you add the two, then the C2s cancel, but I'm just going to do them all just the same way, just to have a pattern for how I do them. So, whoops, let me get this light. There we go. So let's see, we're looking at minus row 1 plus row 2, and I get C1 plus C2 equals 0, and then what, minus 2C2 equals 0, and of course that's in echelon form, so it has a unique solution. C1 equals C2 equals 0. So we're looking at linearly independent set. Next up is to worry about span. So I ask, if you give me an xy, can I find a C1 and C2? If you give me an xy, can I find a C1 and a C2? All right, so again, it leads to a linear system. In fact, it leads to pretty much the same problem. C2 equals x, and then C1 minus C2 equals y, minus row 1 plus row 2, and you get C1 plus C2 equals x, and then minus 2C2 equals, what is it, minus x plus y? Right away, I get from that C2 is what, 1/2 x minus 1/2 y. And then C1 plus 1/2 x minus 1/2 y is equal to x. And when you solve that, you get that what C1 is x minus 1/2, so 1/2 x, and then bring it plus 1/2 y. So if you give me an xy, I can find the appropriate C1 and C2, and so we've got spans. Okay, part B asks about the vector 3, question 2 asks about the vector 3 minus 2. So C1 times 1, 1, plus C2 times 1 minus 1, get an idea, there's a theme here, equals 3 minus 2. And I could do Gauss's method and get an answer, and there's nothing wrong with that. But I've got, right up here, I've got how to calculate C2 and how to calculate C1 from the x and y, so I'm going to use it. So let's see, what am I looking at here? C1 is 1/2 times the 3 plus 1/2 times the minus 2. So that's 3/2 minus 2/2, so that's 1/2. And C2 is, it's minus. So 1/2 times the 3 minus 1/2 times the minus 2. So 3/2 plus 2/2, so that's 5/2. Okay, so we can get any vector at all in the plane as a combination of those two. And in particular, I just kind of picked the generic vector and illustrated what happens. You can get 3 minus 2. All right, and then to answer the second part, I'm going to need a new piece of paper. I'm practically out. So let's see, how does it go? It says 2 minus x, 3 plus 2x. So that's a basis. And then it says what combination gives minus 1 minus x. And so once I show it's a basis, of course, I put in diamond brackets. So let's see, let's give it a whack. We're looking at to show linear independence for question number 3. To show linear independence, I take C1 times the first, 2 minus x, plus C2 times the second, 3 plus 2x, and I'm going to write down here 0. It's perfectly correct to write just equals 0. That's perfectly fine. But I've noticed in the course of teaching this, over years of teaching this, that just writing 0 the first couple times, just writing it down these polynomials, sometimes gives a person a little bit of a wait. How come you have polynomials on the left and number on the right? So I'm going to explicitly write it as the zero polynomial. I won't do this for the whole course, but just the first couple times, then try to make it perfectly clear. No, polynomials on the left, polynomials on the right. Okay, so this leads to a linear system. I'll take the constant terms, 2c1 plus 3c2 equals 0, and then minus c1 plus 2c2 equals 0, and off I go with Gauss's method. So 1/2 row 1 plus row 2, and I get 2c1 plus 3c2 equals 0. Of course, just copying that down, and then this is 7/2 C2 equals 0, and I'm looking at echelon form here, so I get linear independence. Linear independence. Okay, so next up is to worry about span. So I'm going to take an arbitrary linear polynomial, something like a plus bx, and try to express it as a combination. So c1 times the first plus c2 times the second equals a plus bx. And here we go. I'm going to do the linear system, 2c1 plus 3c2, 2c1 plus 3c2 equals a, and then minus c1 plus 2c2 equals b, 1/2 row 1 plus row 2, same stuff. I'm really doing a lot of repeat job, but trying to do one thing at a time instead of being over smart about it. So just to kind of make it clear before I worry about taking in shortcuts, 2c1 plus 3c2, 2c1 plus 3c2 equals a, and then 7/2 c2 equals 1/2 a plus b. Okay, and now comes the hard part. I messed this up about 3 times before I finally got it right. So let's see, the C2 here is not so bad because you multiply both sides of the equation by 2/7. Can you detect a spot that gave me trouble? Multiply both sides of the equation by 2/7, and you end up with C2 equals 1/7 A plus 2/7 B. And now it gets ugly. 2C1 plus 3 times 1/7 A plus 2/7 B equals A. I spent a long time writing down 1/2 A plus B there, but then 1/2 A plus B isn't right. I just simply wrote it wrong and ended up in a terrible swamp. So 2C1 plus 3/7 A plus 6/7 B equals A, and so finally you end up with the right answer. C1 is what, the 2/7 A, take away 3/7 B. Okay, when I carry it over to the other side and divide by 2. Okay, now the second half of this problem, the second half of this question is to for the second half of 2, I can't remember, is to worry about -1 minus x. Express -1 minus x as a linear combination of these two. Linear combination of members of what we are now showing as a basis. So as with the previous problem, I could put -1 minus x up there and go through the Gauss's method and get an answer that's perfectly fine, but I have the C2 and the C1 here, so I'm gonna use it. So I get C2 is what C2 is 1/7 times -1 plus 2/7 times -1. So minus 3/7, and C2 here. No, that was C2. That's what I wrote, C2. I did that right. C1 equals, for this problem gave me, now it's in my head. So C1 is 2/7 times -1. Take away 3/7 times -1. So you take away, and that involves minus and minus makes plus, and when the smoke clears, you get 1/7. Okay, so what the check-in refers to here is that we can express members of the space as a linear combination of vectors from what we've shown here are the bases, and so in today's section we're worried about the fact that that there is in fact a unique way. Talked about this at the end last time, that when we found the 3 minus 2, when we found the -1 minus x, when we found, for example, the -1 minus x, there was a way, and furthermore, the way was unique. If you give me A and B, I find not just a single C2, but not many C2, but in fact only a single C2. So there is a unique way to express each member of the space as a combination of basis vectors, and that we're going to use that today. And so let's bring that up. Okay. Okay, so the theorem that we saw at the end last time is that in any vector space, a subset is a basis if and only if each vector in the space can be expressed as a linear combination of elements of the subset in one and only one way. One way is not surprising because it's a spanning set, so of course everybody's expressible. That's the point of spanning. But only one way, that's the thing in this theorem that makes a point, that you can't express it in two ways or three ways or infinitely many ways. Only one way. So if you say to me, what are the coefficients? You're not asking an ambiguous question. It can't be the case that I get one set of coefficients and my friend next to me gets a different set. That's not right. Instead, if you say to me, what are the coefficients? There's a unique answer. Okay, and here's an example. So here's a vector and a basis for the vector space R3. So 1, 1, 1, 1, 1, 0. 1, 0, 0 is a basis for R3. I won't bother to check that, but it's not hard to check. And I'm going to express 1, 2, 3 as a combination of those three. So you write 1, 2, 3 as a combination, and that gives you gives you a linear system. Gauss's method gives you that C1 is 3, C2 is -1, and C3 is also -1. Okay, it doesn't give you that C1 is like 4 plus 3 times. There's only one solution. Okay, so when you write down that solution in an organized way, our habit will be, when we write down that solution in an organized way, is to write the coefficients in a vertical vector, column vector. And so the terminology is that in a vector space with basis B, the representation of the vector with respect to the basis is the column vector of coefficients that you use to express V. So you write those coefficients down vertically in a vector. Representation of V with respect to B. Really, both V and B are variables here, but for the kinds of problems that we'll typically do, especially at the beginning, we'll hold B constant and maybe vary V. So we're writing this as a function of V, where B is a parameter. B is kind of fixed for the length of this problem. This B subscript here is that we sometimes find it convenient to write the B, but we also sometimes can find it convenient to omit the B. When we're always using the same B through the length of a problem, we won't keep writing it over and over again. Right, and then the C's, the things in this vertical vector, those are the coordinates of V with respect to B. Coordinates of V with respect to V. And of course, on the prior slide, I calculated the 3, the -1, and the -1. So those are the coordinates of V with respect to V. And we've done a lot of these now, and really they're not much of an extension over regular Gauss's method on linear systems. So I don't need to do hundreds of examples, but it's an important idea, so I want to do a couple. So here's a basis for the linear polynomials, 1 plus x, 1 minus x. I got a formula here to express, given A and B, how do you find C1, how to calculate C1, given A and B, how do you calculate C2? And if you gave me 3 plus 4x, I could find that the coefficients are 7/2 and -1/2. So you write those coefficients down. This is our organized way of writing down this information right here. You write those coefficients down, 7/2 and -1/2. B is fixed for the conversation. In principle, this line here says that we could change the A and the B, although I only going to look at one because I can't be bothered looking at 20. And 3 plus 4x, 7/2 and -1/2 is the outcome. Is the outcome. I just want to make an observation about representations with respect to the standard basis in R3. So if I take a vector, and I just made up some crazy vector here, and represent it with respect to the standard basis, remember the regular basis from calculus, 1, 0, 0, 0, 1, 0, 0, 0, 1, what they call calculus IJK. Then the representation is how much what's the coefficient of 1, 0, 0? What's the coefficient of 0, 1, 0? What's the coefficient of 0, 0, 1? Well, you need a 2 in front of 1, 1, 0. You need a minus 3 in front of 0, 1, 0. And you need a 1/2 in front of 0, 0, 1. And obviously a person notices that this and this are the same, of course. How could you not notice? So in general, that is, the representation with respect to the standard basis of a vector in Rn is the vector. So a vector represents itself with respect to the standard basis and often convenient. The definition uses the word represents. So I want to describe what we mean by represents. And this lemma is the key. So what the lemma tells you is that a relationship holds among a set of vectors. A relationship holds among a set of vectors. A linear relationship holds among a set of vectors if and only if that relationship holds among the representatives of those vectors. A relationship holds among a set of vectors if and only if that relationship holds among the representatives. So they represent these vectors perfectly because we're only interested in linear combinations. So rather than go through the proof of course is in the book, but rather than go through the proof, which has kind of a lot of I's and J's, I'm just going to do an example. I picked a basis and I picked some members of the plane that have some linear relationship among them. 2 times the first minus 3 times the second minus the third gives you 0. When you do the calculation for the representation of V1 with respect to the basis, the representation of V2 with respect to the basis, and the representation of V3 with respect to the basis, again, a couple minutes to get the arithmetic right, but I'm pretty sure that's right. And a person can easily check that just like I had a 2, a minus 3, and a minus 1, so too here, a 2, a minus 3, and a minus 1 gives you 0. Okay. So these representations perfectly express what's going on with the vectors in the sense that we're interested in this with the vectors, and it matches perfectly well there. Okay. Okay, very good. So for next time, of course, we're going to be talking about dimension, and we'll see you for that. Okay. Bye bye. Hi, hello. Well, last time we did the second half of bases, and we represented vectors with respect to bases. So naturally, the check-in asks us to represent some vectors with respect to bases. So here we have 2 different bases, B1 and B2, and we're going to represent a single vector, V, with respect to those 2 bases. So let's get to it. Yeah. Okay, so let's see. I'm trying to represent 1 minus 2x minus 2x squared. 1 minus 2x minus 2x squared. I'm trying to represent it with respect to that first basis, so I'm looking at C1 times the first basis element plus C2 times the second basis element plus C3 times the third basis element. So of course, I can absolutely write down a linear system. I find all the constant terms, they make an equation. I find all the coefficients of x, they make an equation. I find all the coefficients of x squared, they make an equation. And I write those down. I get a linear system. Gauss's method will solve it. And you can always fall back on that. But nobody made it a crime to be smart enough to spot a pattern, even if it's slightly different from the pattern that you've looked at in previous cases. And in this case here, you see that on the left-hand side, there's only one term involving x squared. On the right-hand side, there's only one term involving x squared. So from that, I conclude that C3 is minus 2. Nobody made it a crime to be smart. Not yet, anyway. So now, likewise with the x's. On the right-hand side, there's only one term involving x's. On the left-hand side, there's only one term involving x's, so C2 is minus 2. Taking those two together, if C2 is minus 2 and C3 is minus 2, the constants give you minus 2 and minus 2 plus C1 equals 1, so I conclude C1 is 5. And that gives me the representation. The representation with respect to the basis B1 of the polynomial is, you got to write them in the correct order here, 5. 5 comes first, and minus 2, and minus 2. Notice that I'm calling it a vector and writing it as a vector even though it's a polynomial because it's a member of a vector space. This is a member of a vector space, perfectly fair, so I can write it as a vector. Okay, second question asks me much the same thing. 1 minus 2x minus 2x squared, and I'm supposed to write that as somehow a combination of 1 plus x squared. C2 is times 1 plus x, and C3 times 1. And again, I could set it up and get Gauss's method, set it up and get a linear system, and off I go with Gauss's method and get an answer. That's a fallback, works perfectly fine, absolutely perfectly right. But in this particular case, I can see by looking at both sides of the equation that the only time x squared appears on the right is as c1 times. The only time x squared appears on the left is as minus 2. So I get that c1 is minus 2. If c1 is minus 2 and I compare the x's, then I'm looking on the left at minus 2 c1, minus 2x, and then plus c2. So I get the c2 is 0. So again, absolutely nothing wrong with Gauss's method. Gauss's method would come to the same conclusions, but there's also nothing wrong with having a little brain power, having a little brain power and figuring it out. Okay, so what does that give me for the constant terms? So I have c1 times 1 plus 0 plus c3 makes 1. Oh no, I said that wrong. So that's minus 2 times 1 plus 0 plus c3 makes 1. So c3 is c. Okay, so again, to write the representation with respect to the basis B2 of V, it'll be different than this representation, but still be a representation. I got to write it in the correct order, minus 2, 0, 3. You can absolutely write, for example, a subscript B2 if you're in a context where sometimes there's one basis and sometimes another, but we often, when we're working, often leave that off. They're just a question of laziness, just too many I's and J's, and a person starts to say, I'm just going to leave it off. Okay, so that brings me to talking about the material for the day. The title of this section is Basis and Dimension. So we've already done basis, so we must be about to do dimension. Oops, here we go, dimension. Okay, so the definition. A vector space is finite dimensional. Finite dimensional if it has a basis that with only finitely many vectors. So we've seen that a vector can have many different bases if one of them, it could be many of them, but if at least one of them has finitely many vectors, then you call the vector space finite dimensional. Just as an example, we've been working with R3, and R3 has a basis with 3 elements, the standard basis. We've also been working with the quadratic polynomials, and the quadratic polynomials has a basis with finitely many elements. Here's a quadratic polynomial, 1 plus 0x plus 0x squared. Here's another quadratic polynomial, 0 plus 1x plus 0x squared. Here's another quadratic polynomial, 0 plus 0x plus 1x squared. So this is 3 different quadratic polynomials, makes a basis for P2. So P2 is finite dimensional because it has at least one basis with finitely many elements, only finitely many elements. And then the vector space of 2 by 2 matrices here has a basis with 4 elements. I'm not going to check that it's a basis, but it's pretty easy to check that it's a basis. So that makes this a finite dimensional vector space. And in fact, the vector spaces that we've talked about have all been finite dimensional. You never noticed till now because I never needed the finite dimensionality until now. From this point on, we're going to restrict our attention to vector spaces that are finite dimensional. All the later examples and the theorems, everything assumes finite dimensional. You can work with infinite dimensional vector spaces. They're interesting and important, but we're just not going. You have to start somewhere, and finite is easier than infinite, so we're going to start with finite. What we're going to show is that for any finite dimensional space, all of the bases have the same number of elements. So here's an example. For the quadratic polynomials, here are 4 different bases, and I'm not checking that they're bases, but they're not. None of them is hard to check. This is the one I was just talking about a second ago, and here's ones from the check-in kind of stuff. Okay, so 4 different bases for the space of quadratic polynomials. They're all different. Sometimes they share elements, sometimes they don't. But Every one of them has 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3 elements. So although the bases are all different, they share a commonality. They share a number of elements. Likewise with the 2 by 2 matrices. Here's one basis for the 2 by 2 matrices. Here's another basis for the 2 by 2 matrices. They're different, very different, but they share the property that they both have 4 elements. Okay, so ready for the theorem that in a finite dimensional vector space, all bases have the same number of elements. And before I go on and talk about the theorem, there's a couple of comments I wanted to make. The first is that in some sense, this is the key result of the course, that this is the first sort of genuinely, perhaps unexpected fact about vector spaces. And so it's sort of the central thing that you absolutely must cover when you're talking about covering this course. That's the first thing. The second thing is the note that the proof in the book is different. This proof here relies a lot more on sort of I's and J's. The proof in the book is a little more abstract, a little more conceptual, and there are proofs in the exercises that are even more abstract, even more conceptual. In general, when you understand something in terms of I's and J's, you've proved something in terms of I's and J's. That's good. It's good to prove things. But if you can prove it a little more conceptually, that's better. And if you can prove it quite conceptually, that's quite good. I also think it's good to see something more than one way. So what I'm deliberately doing here, we don't do this very often, but what I'm deliberately doing is exposing you to 2 different proofs, the proof here and the proof in the book. Not because I'm dubious and so I need to prove it more than once, but because sometimes seeing it in more than one way is a help. And in particular, walking up that ladder of conceptual, walking from low level to higher level to higher level is a help. Okay, so going to go through the proof. So you fix a vector space with at least one finite basis. So there may be more than one finite basis. Look at all those finite bases. One of them's got to have the least number of elements. I mean, if one of them has 6 and the other one has 7, then pick the 6. Okay, there it is. This is one of the bases that has the minimal size. I'm going to show that if you have any other basis it's got to have more than n members. Excuse me, if you have any other basis, it has to have the same number, n members. That it can't have more than n members. Now, because B is chosen to be minimal size, D can't be fewer than n members. That's what minimal means. What we're going to argue is that D can't be a basis and have more. That there's some impossibility about being a basis and also having more. All right, so I wrote D here as possibly having infinitely many elements. But I don't need infinitely many. It turns out, only going to need the first n plus 1. So B has n elements. I'm only going to use the first n plus 1 elements of D. So the fact that it says dot, 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 and it looks like it could be infinite, I'm not going to need that. What I'm going to show is that from among those n plus 1 different vectors, there's a non-trivial linear relationship. That is to say, a1 delta 1 through a n plus 1 delta n plus 1 equals 0, where not all the coefficients are 0. And of course, a basis can't have such a thing. So it's not possible for a basis to have n plus 1 many different elements. All right, so that's the outline of the argument. Here we go. We set off. So the first thing you do is you take the deltas and you represent them with respect to B. B here, B. And when you represent the deltas with respect to B, you get some numbers, a C11 through Cn1, all, 5, 3/2, minus 7, sort of stuff, and all the way out to delta n plus 1. You get all these numbers. Okay. The lemma that we saw at the end of the video last time says that the point of calling them representatives is that a relationship holds among the vectors if and only if the same relationship holds among the representatives. I'm interested in the relationship among the representatives because these are numbers. These, in principle, could be anything. They could be 2 by 2 matrices. They could be cubic polynomials. I don't know. But these are numbers, and so very good with numbers, so I'm comfortable there. So I've shifted over from talking about arbitrary vectors to talking about column vectors of numbers, of real numbers. You notice, right, you remember from the previous slide that these C's, all the C's are numbers. They're fixed. They're representatives. They're in the representation, they're coefficients of. They're in the representation of delta 1 through delta n plus 1. So they are just simply numbers. I'm looking to see whether it's possible to have a's to make this relationship true. Okay, so c's are fixed, the a's are variables. I'm looking at I'm looking at a linear system. It's a homogeneous system because those are zeros over there. Because it's a homogeneous system, it has to have at least one solution. You can't have no solution in a homogeneous system. So a person thinks, okay, well, there's either unique solution, in which case you get linear independence, or else there's infinitely many solutions, in which case you get linear dependence for the set capital D. Which is it? Well, there are n equations. You see them down there? That's an n. There are n plus 1 many variables. You see that? That's an n plus 1. The a's are unknowns. The c's are known. C's are real numbers. So there are n equations with n plus 1 many unknowns. Some variable, some a, does not lead a row. If you do Gauss's method on this, you get down to echelon form. Some a does not lead a row. There are infinitely many solutions. In particular, there's more than just the trivial solution. So there's a linear dependence among the members of capital D, so D isn't a basis. So back up to remind myself of the statement, in any finite dimensional vector space, all bases have the same number of elements. They can't have more than the minimal number. They all have the minimal number. Okay, so that gives me a definition for dimension. The dimension of a vector space is the number of vectors in any of its bases, and they all have the same number, so that definition is not ambiguous. In particular, where does the word dimension come from? Well, in the regular n-dimensional space, Rn, that's how many members are in the standard basis. So that's how many members are in any basis. So that's where the word dimension comes from. The quadratic polynomials has dimension 3 because I can name a basis that has 3 elements, and any basis has the same number of elements. So there I go. I'm looking at all of them have 3 elements. And in general, Pn has dimension n plus 1. The n by m matrices has dimension n times m, and it's easy to produce a basis that has that many elements. On to a sort of less obvious example. The solution set for this system is a vector space. If you solve the system, what you get is you parameterize, you get a basis with 2 vectors. There I go, a basis with 2 vectors. So the solution set for this system, I know it's a 3 equation, 4 unknown linear system, but the solution set for this system has size 2. So the solution set is a vector space of dimension 2. It's a plane. Because there are 4 letters here, this is a plane in R4, plane to the origin, in R4, spanned by those 2 vectors. Okay, a couple of results the theorem that we just saw gives us sort of an immediate payoff. It gives us a number of results. So no linearly independent set can have a size greater than the dimension of the enclosing space. So if you have a 5-dimensional space, you can't get a linearly independent set of size 6. If you have a 4-dimensional space, you cannot get a linearly independent set of size 5 or 8 or 100. That is to say, reinforcing the intuition that we had earlier, linearly independent sets tend to be small. They like to be small. If you have a space of size 6, of dimension 6, a vector space of dimension 6, you could have a linearly independent set of size 6, you could have a linearly independent set of size 5, you could have a linearly independent set of size 4 or 3 or 2, but you can't have a linearly independent set of size 100. It just can't happen. And it's just simply, you examine the proof, and I never used anything about span, only linear independence. So the result actually proves this statement. Just as a remark in passing here, this statement is an example of what I said earlier, that we're going to take vector spaces to be finite dimensional without ever saying so. It doesn't say enclosing finite dimensional space, it just says enclosing space. I'm never going to mention that again. So if you give me a linearly independent set, I can expand it to make a basis by adding 1 element, 2 elements, 3 elements until I'm up to the size of the space. That is to say, I don't have to worry that I'd need to add infinitely many elements. Don't have to worry about that. Any linearly independent set in a finite dimensional vector space, any linearly independent set can be expanded and the process will stop. You add a new one to make the span bigger, you add a new one to make the span even bigger, add a new one to make, at some point you hit the dimension of the space, and at that point, guaranteed, it's not going to be necessary to add more elements to the basis because the basis isn't any bigger. And the flip of that is that any spanning set can be shrunk to a basis. Again, you don't need to worry there. You call the spanning set S. If S is empty, then S already has a basis. If S just consists of the zero vector, then it can be shrunk to the empty basis without changing the span. The technicality is that the empty basis is linearly independent. So otherwise, S contains a vector that's non-zero, and we can form a basis that consists just of lowercase s. If the span of that linearly independent set is all of S, then we're done, and is all of S's span, then we're done. If not, then you just add a new one and add a new one. You'll never have to, because these are finite dimensional spaces, you'll never have to worry that you keep adding infinitely many things. After some finite time, this process stops, and all of the lowercase s's that you have not yet added in, you can throw away. Okay, so this idea that there's a limit to what you have to throw in, because there's a limit to what it takes to make up a basis, is key for both of these results. And then finally, in an n-dimensional space, a set composed of n vectors is linearly independent if and only if it spans the space. So if you have an n-dimensional space, and you have a linearly independent set with n vectors, you don't have to check span. Or in an n-dimensional space, if you have a set with n vectors, a spanning set with n vectors, you don't have to check it independent. You get independent for free. Okay, and the proof is, so first we'll show that a subset with n vectors is linearly independent if and only if it's basis. The only if, the if part is trivial, the only if holds because a linearly independent set can be expanded to a basis, but a basis has n elements, so there isn't any expansion at all. So it must be that it was a basis to begin with. And then to finish, we'll show that a subset with n vectors spans the space if and only if it's a basis. Again, the if part is nothing, that a basis has to span. The only if part is because any spanning set can be shrunk to a basis, but a basis has n elements. And so if the shrunken set if the set you started with was n elements, that must be the set you're looking for. Okay, and so to look at this, we saw this earlier, to look at this particular subset of R3, I wrote it as a basis. I wrote the diamond brackets, which is we pretty much reserve for bases here. So I wrote it as a basis. If you glance at it, it's clear that it's 3 elements. That's clear. No matter how quickly you glance, it's clear that it has 3 elements. It's also clear that it spans the space. Because it has 3 elements, it must therefore be linearly independent. It must be a basis. Okay, so that finishes us and for the day. And what we're going to do next is we're going to talk about how the things that we have discovered so far apply to linear systems. We're going to take it around and tie it back to linear systems. Okay, look forward to that. Bye-bye. Hi. So last time, of course, we went through dimension, and we talked about the dimension of a vector space as being the number of elements in any of its bases. So naturally, the check-in asks some questions about dimension. Find the dimension, in this case, of each space. Okay, so let's have a whack here. So let's see. I'll just click that off. There we go. And so the first space is a plus bx plus cx squared, a plus 2b equals 0. So B1 is a plus, things having trouble with the light. How's that? A little better? A little better. Is a plus bx plus cx squared, a plus bx plus cx squared, where, let's see, it's a plus 2b equals 0. A plus 2b equals 0. Okay? And we've done these many, many times. So we're gonna do it again, I guess. So the idea here is you think of this as a linear system. It has only one equation, but so what? It's a linear system. A leads, B is free, B is not leading. So A plus BX plus CX squared, where a is minus 2b. We write that as minus 2b plus bx plus cx squared, where b and c are both free variables. And I like to break out the b's and the c's. I like to parameterize out, so we're looking at b times minus 2 plus x and c times x squared, where b and c are real, are free. Okay, so what we get then is we get a basis minus 2 plus x and x squared. It's easy to check that it's a basis. I won't bother, but it's pretty clear this is the only one with an x squared. This is the only one with an x. So they must be linearly independent. So anyway, so it's easy to check that it's a basis. So we get dimension is 2 because there's 2 things in it. Okay, 2. Same problem, slightly different arrangement. V2 is it's the ABCDs, 2 by 2 matrices, where A is minus 2D and B is minus C. I already wrote them out as where the leading variables are expressed in terms of the free variables. And just mimic what happened upstairs. So A is minus 2D. So forgive me, I'm misremembering. A is minus 2D, that's right. A is minus 2D, so I'm writing this as minus 2D. B is minus C. And C and D. I like to break out the D and the C. So C times 0, minus 1, 1, 0. And D times minus 2, 0, 0, 1, where C and D are free. And so I get a basis, B2. 0, minus 1, 1, 0, and minus 2, 0, 0, 1. Easy to check that it's a basis. Linear independence obviously spans. There it is, it's spanning. It's easy to check that it's linear independent. So, I mean, look at the upper lefts, for example. It's easy to check that it's linearly independent, and so the dimension here is also 2. Okay, so dimension is just a question of coming up with a basis and counting 1, 2, 1, 2. Okay, let's talk then about the next topic. The next topic is we're going to circle back around and think about vector spaces and linear systems. So we're reaching back and thinking about linear systems again, only now we're thinking about it in the context of what we know now. So this going back and touching again what we had before is a very good technique, and we'll employ it a number of times in the course. Okay. So some words here. Now we're in the second chapter, so we can talk about vector spaces. The row space of a matrix is the span of its set of rows. The row rank is the dimension of that. So the row rank is the number of linearly independent rows. And the result here is that if 2 matrices are connected by some Gauss's method steps, then their row spaces are equal. That, as said sort of more sharply, row equivalent matrices have the same row space and therefore have the same row rank. Row equivalent matrices you get from one to the other by doing Gauss's method steps. Row equivalent matrices have the same row space and therefore the same row rank. Okay, and really the proof is all stuff that we've seen now, and we can apply the sort of relatively more advanced terminology and ideas to the stuff we saw in the first chapter. So we showed that when you have a Gauss's method step between A and B, then each row in B is a linear combination of the rows of A. So that is to say, in the terminology that we now have available to us, each row of B is an element of the row space of A. So the row space of B is a subset of the row space of A. Okay. And for the other containment that row space of A is a subset of the row space of B, remember that all of the Gauss's method steps are reversible. So if you have A connected to B by a sequence of Gauss's method steps, why then you have B connected to A by just the reverses. So you get exactly the reverse containment until you're done. So again, the result says that if two matrices are related by row operations, then their row spaces are the same, and so row equivalent matrices have the same row space, and in particular have the same row rank. So the next result is that the non-zero rows of an echelon form matrix make up a linearly independent set. And the reason is because we've seen it before. We didn't have the terminology in the first chapter, but nonetheless, the first chapter had this result that said no non-zero row of an echelon form matrix is a linear combination of the others. No non-zero row of an echelon form matrix is a linear combination of the others. And this is just a restatement. No one is a linear combination of the other elements of the space, makes it linearly independent set. So time for an example. So this matrix before Gauss's method and after. So I did a couple steps. I'll spare you the arithmetic. Have equal row spaces. If you can get some row vector as a combination of these three, then you can get that row vector as a combination of these two, and vice versa. The non-zero rows over here, or the top row and the second row, form a basis for that row space. So clearly it has dimension 2. So trying to understand Gauss's method from sort of this little bit higher level, I talked last video about trying to understand things first on a low level and then on a higher and then on a higher level. Okay, so we're now understanding Gauss's method on a little bit higher level. Gauss's method produces a basis for the row space of a matrix. Gauss's method produces a basis for the row space of a matrix. It looks at the span of the rows, winnows out the repeat information, and you end up with a basis when you throw out the zero rows. Okay? So I talked about row space. Next up, I'm going to talk about column space. The column space of a matrix is the span of its set of columns, just like the row space of a matrix was the span of its set of rows. Column rank is dimension. So that's the number of linearly independent columns. And why are we interested in column space? Why does that tie into what we've been thinking about? Well, excuse me. Here's a system, 2x plus 3y equals d1 minus x plus 1/2 y equals d2. And I'll ask myself, for which d1s and d2s can I find solutions? And we've certainly done that a number of times. And the answer is if there's an x and a y making this equation true. So that is to say, this system right here has a solution if and only if the d1, d2 is in the column space of this matrix. So we talked about this kind of stuff in the first chapter. When can you get a particular right-hand side? Well, we now have the terminology for it. When the right-hand side is in the span of the columns on the left. When the right-hand side is in the column space of the matrix. Just as a small aside here, I need the word transpose, so I'm just going to introduce it here. The transpose of a matrix is what happens when you interchange the rows and columns. And I use a superscript T there. It's kind of a funny font. Anyway, superscript T there for transpose. Authors do different things. Anyway, I use superscript T. I think that's pretty common. So column space is a vector space, so you can easily imagine being called upon to find a basis for it. We know how to find the basis of a row space. How do you find the basis? Because that's what Gauss's method does. How do you find the basis of a column space? Why, you turn the columns into rows. That's called transposing. Turn the columns into rows. See, the 2 minus 1 became the row 2 minus 1. The 3 1/2 became the row 3 1/2. Do Gauss's method, off you go. It didn't take very long because I'm not trying to illustrate Gauss's method. I'm trying to illustrate transposing. And now I have a basis for the row space, but the row space of this is basically the same thing as the column space of that. So there we go, transpose them back and you're done. I suppose I could introduce some kind of reduction method on the columns, but we already have a reduction method on the rows. So I'm just going to convert them to rows, do the reduction method, convert them back. The basis turns out to be the columns 2 minus 1 and 0, 2. Obviously, that's a two-dimensional. The basis is the basis for a two-dimensional space. Since R2 is a two-dimensional space, this must be the basis for R2. Okay, a couple more results that, again, circle back to the kinds of things we have observed earlier and try to put them in a context of the ideas we've expressed since. So, first, we have the idea in the first chapter that when you do Gauss's method operations, you preserve some things about the system. For example, you preserve the solutions. It'd be pretty stupid to go through and solve it using a method that sometimes lost solutions. I urge you not to do that in the very first video. So here we go. We're looking for we're looking to say what's preserved. Row operations preserve column rank. Row operations don't change the linear relationships between the columns, so row operations don't change the number of linearly unrelated columns. What do I mean by row operations don't change the linear relationships between the columns? Well, I mean that if x times the first column plus y times the second column equals 3, 2, 5, and you do a row operation, you don't change that. That was the whole point of what we talked about in the first chapter. We're not changing the x's and y solutions. Anyway, so let's go to an example. In this matrix, the second column minus the first is equal to the third. So 236 minus 102 gives you 134, if I did it right. When you perform row operations on the matrix, the resulting matrices still has that relationship. So second column minus the first equals the third, that's right. Second column minus the first equals the third, that's right. Next result, a very often used result, that the row rank and column rank are equal, very often used in practice. Row rank and column rank of a matrix are equal. The number of linearly independent rows and the number of linearly independent columns is the same number. And the proof is, at this point we have a lot of machinery, so the proof turns out to be not many sentences. You bring the matrix to reduced echelon form, not just echelon form, reduced echelon form. Remember where you eliminate up as well as down. Then the row rank, of course, is the number of leading entries. That's the number of linearly independent rows. It's equal to the number of leading entries because each of the rows in what's left has a leading entry. But the number of leading entries equals the column rank because the set of columns containing leading entries is some subset of the EIs from a standard basis. Because when you do reduced echelon form, you eliminate up as well as down, and so all you have is a bunch of zeros with one single one in that column. That's an EI. So in the reduced echelon form matrix, the row rank equals the column rank. In the reduced echelon form matrix, the row rank equals the column rank because each of them is equal to the number of leading entries. But we've shown that row rank and column rank are not changed by row operations. So back to the matrix where you started from, the row rank and the column rank are the same. So we use a single word for row rank and column rank. Just call it the rank. Rank of a matrix is either its row rank or its column rank, whichever one you prefer, whichever one is easier to compute. Example. Time for an example. Although these are ideas we've seen before in a number of different contexts, the whole point of introducing them back again and again is to connect things together because connections make the idea stronger. So here we go. I took this terrible mess. Look at that. What a disaster. What a disaster. How would you calculate the column rank? Well, the answer is do Gauss's method. Oh, look at that. Oh, anyway, it took me a long time. Anyway, I got it. I eventually got it. When you do Gauss's method, you get 3 linearly independent rows, and there's a 0 row. Since there are 3 linearly independent rows, the row rank is 3. But the row rank equals the column rank, so the column rank must be 3 also. In particular, can you see that 2, 0, 0, 0 is one element of a basis? Minus 1, 3/2, 0, 0 is another element of a basis. 3 minus 7/2, 8/3, 0 is another element of a basis. That's 3 basis elements from among what amounts to sort of 3 tall vectors. This is essentially a 3 tall vector. Don't want to sort basically. This is essentially a 3 tall vector. This is essentially a 3 tall vector. This is essentially a 3 tall vector. I have here 3 of what are essentially 3 tall vectors, so they span what's left. Anyway, the row rank and the column rank are the same. Okay? For a linear system with n unknowns and a matrix of coefficients A, then the two statements, the rank of A is R, and the vector space of solutions of the associated homogeneous system, it has dimension n minus R, are equivalent. So if you tell me that you have n unknowns, and then you say that when I do Gauss's method on it, the number of rows that remain, non-zero rows that remain, is R, then I can tell you that that you will have n minus R many free variables. If there are R many leading variables, there must be n minus R free variables, and so the n minus R free variables give you n minus R degrees of freedom. Okay, and again, we have all this terminology, we have all this technology, we're able to sort of tie it all together. So the rank of A is R if and only if Gaussian reduction ends with R many non-zero rows. And of course, that holds if and only if the echelon form matrices are row equivalent to A have R many leading variables, and that in turn holds if and only if there are n minus R many free variables. And the finish, the last thing for today, tie this all together. Okay, where the matrix is n by n, then the following statements are equivalent. So, sometimes people in this class have not run across the following are equivalent before. Any one of these statements, any one of these 5 statements, is the same as saying any of the others. For example, if you say A is non-singular, that's the same as saying the columns of A form a linearly independent set. That's an if and only if statement. A is non-singular if and only if the columns of A form a linearly independent set. So I have 5 statements, each of which is equivalent to the other. Each of which is if and only if the other. Now you can go through and say, prove 1 if and only if 2, 1 if and only if 3, 1 if, but usually there's a shortcut, and in this case the shortcut is 1 if and only if 2, 2 if and only if 3, 3 if and only if 4 are all pretty clear. Okay, A is n by n, so if there are n linearly independent rows, if the row rank of A is n, then the column rank of A has to be n also, but A has n many columns, so they must form a linearly independent set. So you can see that 1 if and only if 2, 2 if and only if 3, 3 if and only if 4 are pretty straightforward. And the last one, if the columns of the square matrix form a linearly independent set, then any linear system whose matrix coefficient is A has one and only one solution. Again, it really ties us back to the very first day. Unique solutions for linear systems. And I'm going to say if the set of column vectors is linearly independent, then it's a basis for Rn. But then the system here has a unique solution for all choices of D's. Right? Has a unique solution for all choices of D's because we saw this result that if you have a basis, you can express the members of the space, true, 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 but you can express them in only one way. You express them uniquely. That's led to the definition of representation. Okay. Okay, very good. Now, now that ends the second chapter. So I want to take the opportunity to remind you of two different things. So the first thing is, I should say first, congratulations, end of the second chapter. Great, 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 great celebration. So the first thing I want to remind you of is it sometimes is the case, if you're a person working on this on their own, it sometimes is the case that there's a tendency to leave the homework off and say, well, I watched the videos and I kind of look through the homework and I get it. And I can't overemphasize that that's not so. It would be way better to get all the homeworks and not watch the videos than vice versa. The homework is the point. The whole point of this is that you can answer questions about these systems. So if you find yourself saying, well, I can watch the video sort of when I have a couple minutes of downtime, but doing the homework takes that a lot of extra time, so I have a tendency to watch the videos and not do the homework, please you know that that's not right. You need the most important part is being able to do problems. Okay, that's the first thing. Second thing, I want to remind you that there are these videos on the internet I've recommended before by just look on YouTube, for example, by 3 Blue 1 Brown, and he does just a great job. He doesn't have associated homeworks or anything like that, but he does just a great job with fancy graphics and all kinds of things that genuinely aid a person's understanding of these things. And if you haven't been checking those out, look on his linear algebra channel. If you haven't been checking those out, please, I urge you to give them a look. They give a person an additional insight. In some ways, they're like the material that we did today. They take a person back and over the things that you saw before, but from perhaps some new point of view. And sometimes if you see the same thing from 2 or 3 different directions, it really reinforces what it is that you were trying to understand. Okay, very good. Next time we're going to start in on the 3rd chapter. Very exciting, starting on the 3rd chapter. So looking forward to that. Okay, all right, bye-bye.
Hello, hi. So last time we tied the ideas of the first chapter together with the ideas of the second and went through some topics at the end, the row space, column space, the fact that the dimension of the row space equals the dimension of the column space, and some other things that try to bring some of the ideas we are seeing together and connect sort of the old with the new. So naturally the check-in has to do with those ideas. So let's see if we how we do on these. So here's a matrix, a simple 3 by 3 matrix, and I'm observing that the first row plus twice the third, 1, 0, 4, plus twice minus 1, 2, minus 2, makes the second row. So there's some linear relationship among the rows of this matrix. It says find a basis for the row space, give the row rank, and then the second question is find a basis for the column space and give the column rank. So should be pretty easy. Let's give it a try. Okay, for our basis for the row space, all I have to do is Gauss's method. So I'm looking here at, let's see, 1, 0, 4, minus 1, 4, 0, and minus 1, 2, minus 2. And off I go with Gauss's method, row 1 plus row 2, and row 1 plus row 3. So I get 1, 0, 4 is unchanged, and I get 0, 4, 4, and then I get 0, 2, 2. And we spotted here that there's a redundant row. Minus 1/2 row 2 plus row 3 gives me 1, 0, 4. 0, 4, 4, and 0, 0, 0. So the 0, 0, 0 shows me that there was a redundant row. There were no row swaps, so it was the third row was redundant on the first two. So that means that a basis for the row space is the first two rows, 1, 0, 4, and 0, 4, 4. And so the row rank is 1, 2. I can count to 2. The row rank is 2. Okay, and question 2 is not especially harder. For question 2, you want to know the basis for the column space, so you transpose the columns into rows, do row reduction, and then transpose them back. So you transpose first, and you get, if I did it right, 1, minus 1, minus 1, 0, 4, 2, and 4, 0, minus 2. Gauss's method proceeds in the usual way, minus 4 row 1 plus row 2. Oh, plus row 3. I'm sorry, excuse me. 1, minus 1, minus 1, 0, 4, 2, and 0, 4, 2. And again, a person spots that there is redundant, it was a column, but now it's a row. There was a redundant vector here. And so here we go. We take minus row 2 plus row 3, minus row 2 plus row 3, and 1, minus 1, minus 1, 0, 4, 2, 0, 0, 0. So the redundancy is perfectly plain. You get then a basis. I'm going to switch them back, transpose them back to be columns. So a basis for the column space is going to be 1 minus 1 minus 1, the transpose of the first row, and the transpose of the second row. 0, 4, 2. And so the column rank is 2. And of course, one of the theorems that we saw last time, a surprising theorem perhaps, is that the column rank and the row rank are the same, and obviously they work out to be the same. Okay, so a relatively straightforward check-in this time, or a relatively easy, straightforward calculation, but it tells us that the row rank and the column rank are the same. Reminds us that the row rank and the column rank are the same. Okay, well, very exciting. We're starting on a new a new day today, starting on a new chapter, and we're going to learn something sort of genuinely new. I think that for most people in this class, the kinds of things that we're doing in the third chapter are something that they have never seen before, and so we'll go slow, go lots of examples, tons of examples, and some careful development. But it's always exciting to do something that is fresh. Okay, enough talk. Let's do. So let's see, isomorphisms it's called, and I'll start off by defining what an isomorphism is so that we'll know what we're talking about. So the basic idea is we have the intuition that the two tall vectors and the linear polynomials are the same in some sense, in that they're both two component spaces. So I'm sure that you have remarked to yourself that the vector 1, 2 is just like the vector 1 plus 2x in the respective spaces, and that minus 3 1/2 is just like minus 3 plus 1/2 x in their respective spaces. What makes these alike, what makes us able to say just like, is that the association is upheld throughout the operations. So for example, if I take 1, 2 and minus 3 1/2, that's just like 1 plus 2x and minus 3 plus 1/2 x. And the same thing works for scalar multiplication. If I triple 1, 2, that's the same thing as tripling 1 plus 2x, or at least I get basically just like tripling 1 plus 2x. And similarly, I can link each two tall vector, not just 1, 2, but I can link each two tall vector with a linear polynomial. You just take the a and the a and the b and the b, and you think of them as somehow just like. Our job today will be to try to give a definition of what just like means. The important thing is that not only is there a connection between the left-hand side and the right-hand side, but that the connection holds, the connection continues to take place, the connection respects the vector space operations of addition and scalar multiplication. That if you add in the first vector space and you compare that to adding the associated things in the second vector space, why it's just like also. If you scalar multiply in the first vector space and you compare that to scalar multiplying in the second vector space, why it's just like also. And the technical jargon is that this association, this back and forth arrow, this association preserves the structure of the space. So the fact that we're studying linear spaces, the fact that we're studying vector spaces, linearity, means that we're interested in the structure. So of course, if we want to say just like, we mean just like in that the structure continues to hold. Just another example, because as I say, I think it's a new idea for almost everybody taking this course. So the two tall matrices, the 2 by 2 matrices and the 4 tall vectors are just like in that you can associate them in this way. If you had the 4 by 4, 2 by 2 matrix, 1, 2, 3, 4, you could associate that with the 4 tall vector, 1, 2, 3, 4, and you think of them as the same. So here we can think of these two as somehow just like, not equal, but just like. A person might say the difference is typographic. And again, the important thing of just like is that the association persists under addition or scalar multiplication. I couldn't fit scalar multiplication on the slide, so it's on the next slide. But association persists under addition and scalar multiplication if you add 2 by 2 matrices versus if you add the 4 tall vectors, the 4 tall column vectors. So addition of 2 by 2 matrices is just like addition of 4 tall column vectors, and this illustrates. And likewise, scalar multiplication of 2 by 2 matrices is just like scalar multiplication of 4 tall vectors. And this illustrates. Okay, so time for a definition, time to make it precise. And again, very sensitive to the fact that for many folks taking this class, the first time you see this definition will be like, what the heck is this? So we're going to do lots of examples, going to work through this at a deliberate pace. Okay. Isomorphism is the technical jargon here. Isomorphism between two vector spaces is a function. That back and forth arrow is supposed to denote a function that is a correspondence.
So the function is 1 to 1 and onto. We're going to go again at some length into all these parts. You probably have heard, I'm sure you have heard the words 1 to 1 and onto in a calculus class, but we're going to go through and carefully describe how you verify these things. And also, number 2, preserve structure. That f of v1 plus v2 is f of v1 plus f of v2. So that's the preserve structure part that was on the previous slide for addition. And here's the preserve structure part on the previous slide for scalar multiplication. You see this symbol here, it's like an equal sign with a little twiddle written above it, so in some ways it's like a combination of equals and approximately equals. You read that as V is isomorphic to W. They're not equal, but they're just like each other. They're alike. And the function describes in what way they're alike. Okay, so again, sensitive to the fact that a person is typically a little at sea when they first encounter these kind of functions. So one level of knowledge, kind of the base level of knowledge, is able to grind through some extremely routine homework. So I want to accomplish that base level of knowledge. So here we go. I'm giving you a how-to slide to get a person off the ground and started. And as we work through, we'll talk more and more about the concepts involved. But very first thing is, how do I do homework question sort of number 5? Okay, so that makes sense. So there are 4 things: to show that a function is 1 to 1, to show that a function is onto, to show that a function preserves addition, and to show that a function preserves scalar multiplication. Of course, this was labeled item number 1 on the previous slide, the first 2. This was this was labeled item number 2 on the previous slide, the second 2. So to show that a function is 1 to 1, you assume that you have vectors from the space, vector 1 and vector 2. You assume that f of vector 1 equals f of vector 2, and you go on to derive that therefore vector 1 equals vector 2. To show that function is onto, you take a vector, a generic vector from the codomain W, and you find a vector from the domain that maps to it. And again, going to do lots of examples of all this stuff. To show that a function preserves additions, we have to check that f of v1 plus v2 equals f of v1 plus f of v2. Lots of examples. And to show that f preserves scalar multiplication, we have to check that f of r times v equals r times f of v. Okay, so high time for an example, of course, but I'm going to keep referring back to the how-tos. Okay, so quadratic polynomials is isomorphic to R3. These A0, A1, A2, and A0, A1, A2, you think of those as somehow being associated. What does associated mean? That means there's a function which takes as inputs quadratic polynomials and gives as outputs 3 tall vectors, and it links the parts together. We think of the first part as being the first part, think of the second part as being the second part, think of the third part as being the third part. So this is the terminology for what I vaguely started off today with as a double arrow. This is kind of the technical way of saying the double arrow. And I can't overemphasize, whenever something seems too abstract to you, and there will be sometimes when you're working through this course when parts seem too abstract to you. Whenever something seems too abstract to you, extremely important, the key technique is to take out a pencil and put down some numbers. So A0, A1, A2, you're starting to say, what is happening here? Put down a 1, a 2, and a 3. Put down a 3 and a 4. And then you say, oh, well, you just take the constant term, you put it there. You take the coefficient of x, you put it there. You take the, okay, all right, I get it. And of course, that's exactly what the formula says. But you know, a person who is just learning their way through this doesn't have the capability of reading the formulas at a glance the way that an experienced person does. How do you get that capability? You write down concrete examples, lots of them. And then all of a sudden you start saying, wait, oh, no, that's actually easy. Okay, well, that's the good part. Once you say to yourself, oh, this is actually easy, good. You're on the other side of the divide now. You've passed through the gateless gate, and now you get it. Okay, so I have to check the 4 things from the previous slide. I have to check condition 1 and the condition 2. So to check that f is 1 to 1, we're going to follow a do this kind of level, because that's where we are. To check that f is 1 to 1, I will start off supposing that f of v1 equals f of v2, and I'll end up concluding that therefore v1 equals v2. So let's start in. F of v1 equals f of v2. So here's a member of the domain. Here's a member of the domain. The definition of f gives that you take the constant term and put the coefficient of the constant and put it there, coefficient in front of x, put it there, coefficient in front of x squared, put it there. Constant term, put it there, coefficient of x, put it there, coefficient of x squared, put it there. Now I have three tall vectors that are equal. Well, we know what it means for three tall vectors to be equal. It means a0 and b0 must be the same. a1 and b1 must be the same. a2 and b2 must be the same. And that gives me the conclusion I want, that a0 equals b0, a1 equals b1, a2 equals b2 means that the starting polynomials were the same. So in the how-to, back we go. There we go. In the how-to, you start off, you assume f of v1 equals f of v2, you do some thinking, and you conclude that v1 equals v2. That's exactly what I did. Next step, to show that f is onto, you pick a generic element of the output space. You can't take 1, 2, 3. It's got to be letters. You pick a generic element of the output space, the codomain, and you find what maps to it. You name, you exhibit what maps to it. Okay, here I go. So to show that f is onto, I pick a generic, this is not 1, 2, 3, 4, 5, 6. These are letters. Pick a generic member of the output space and you figure out who maps to it. Well, it's not hard in this case. Who maps to the output vector a0, a1, a2? And the answer is, of course, the input vector a0 plus a1x plus a2x squared. So for every member of R3, there's a member of poly 2 that maps to it. That's onto. Next, preserves addition, and of course preserves multiplication is going to be on the next slide. Preserves addition. Maybe I should go back and make sure a person looks at the how-to. Check that f of v1 plus v2 equals f of v1 plus f of v2, and then for multiplication it's going to be much the same. Okay, there's f of v1 plus v2. You see how the f parentheses are there and there? I put a little extra space to help your eye spot them. There's v1 plus v2 inside the parentheses. All the way down at the bottom is f of v1, see the parentheses there, match those parentheses, plus f of v2, and see there's matching parentheses. So that's what the how-to tells me to show, and of course there's some steps along the way, but the most important thing here is not the steps, they'll turn out to be very straightforward. The most important thing is understanding what you have to show. In fact, a lot of times when I solve these, I write down the beginning, I write down the end, and then it's kind of like a crossword puzzle. You say, how do I get from the start to the end? Okay, well, the way to get to the start, from the start to the end here is you add the vectors to add the constant terms, add the coefficients of x, add the coefficients of x squared. And now this is f of a single thing. See how the parentheses match there? This is f of a single thing. Well, what does f do? F takes the constant term and writes it on the top of the vector, takes the coefficient of x and writes it in the middle, takes the coefficient of x squared and writes it on the bottom. Down here, I'm going to need a0, a1, a2 because that's f of this, and I'm going to need b0, b1, b2 because that's f of this. So I need to get from here to here. Is that legal? Okay. Oh yes, it's obvious because that's how you do vector addition. Those two are equal, that's right. Okay, so step, 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 that's right, done. The steps in the middle tend not to be hard. It's understanding the beginning and the end that tends to be the part where people say, I don't get it, what am I doing? So here, for preservation of scalar multiplication, I've got to show that f of r times a vector is equal to r times f of that vector. So there's the beginning, there's the end. I've got to get from there to there. Again, notice where the parentheses match. Open paren, close paren, right there. Okay, so inside the parens, r times a quadratic polynomial, you take r of the constant term, r times the coefficient of x, and r times the coefficient of x squared. That's how you multiply a polynomial by a real number. What does f do here? F takes the constant term and writes it on top. F takes the coefficient of x, writes it in the middle. F takes the coefficient of x squared, writes it on the bottom. Can I get from there to the, I need this because this here is f of a0 plus a1x plus a2x squared. So I need, yes, that's absolutely right. That's the definition of scalar multiplication. That's how you multiply a vector times a real, is you multiply the components times the real. So that's right. So I have equal, 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 so I'm done. So again, if you write down the beginning and write down the end, and sometimes I have the beginning and work as far as I can go. I have the end and work as far as I can go, and then I say to myself, can I make them match? Oh yeah, they do match. Good, I'm done. Okay, well this is the first time through for something that's tricky and that is brand new, not just a small twist on something you've seen before, but brand new. So two examples really. One example is not enough. Okay? So a second example. I have the 2x2 matrices that have a 0 in the lower right, and the 3 wide row vectors. And I'm going to define an isomorphism that's a little more abstract than the previous one. A, B, C, 0 is associated with, well, you take the upper right and you put it first. You take the upper left and you double it and put it second. And why do you do this? It's just an example. Don't get too excited about why you do this. It's just an example. I just want to show this is an isomorphism. First one was very straightforward. This one is slightly less straightforward. That's how you do examples. What do you put in the third slot? You take the upper left, add the lower left. Put that in the third slot. So as an example, 3210 maps to 264. And I'm going to verify. The how-to has 4 steps to verify. There's 1-to-1, person sees it on top. There's onto, person sees it on the bottom. There's preserves addition. There's preserves scalar multiplication. Okay, one at a time. And you might have a little trouble remembering how it goes. I'll flip back a couple times. For 1-to-1, what do you start with? What do you end with? You start by assuming that f of v1 equals f of v2. See it there? So f of a first matrix equals f of a second matrix. And you end by concluding that the two matrices are equal. There's stuff in the middle. I'll go through the stuff in the middle. But you start by assuming that f of the first equals f of the second, and you end by concluding that the first and second are equal. Okay, here we go. F of the first equals f of the second. Well, what's f of the first? F of the first is you take the upper right and put it first. You take the upper left and double it, put it second. You take upper left plus lower left, add them, put it third. Likewise over here. Well, let's see. Now I have 2 row vectors. B1 equals B2 is an obvious conclusion. If 2A1 equals 2A2, then A1 equals A2 is an obvious conclusion. Knowing that A1 equals A2, A1 plus C1 equals A2 plus C2 gives you that C1, and you're done. Onto. For onto, you start with a member of W. If you have scratch paper and you want to say to yourself, well, I'll try it with 1, 2, 3, and I'll try it with 4, 5, 6, and I'll get some idea of what to do, great, great, great. But that's scratch paper. When you go to actually give the argument, you have to use letters. So I often take out scratch paper and do it with numbers. That's how you make something concrete. Perfectly fair. But when you go to write down the answer, when, for example, you're doing the homework, when you go to write down the answers, you have to use letters. Okay, so here I go with letters. I have a 3 wide row vector, and being not a very imaginative person, I wrote X, Y, Z. I remember the idea is to figure out what is the beginning and what is the end. So I write down a generic member of W, generic member of the codomain, and I've got to find somebody who maps to X, Y, Z. So down here you see I've found somebody who maps to X, Y, Z. Okay, so I have to find an input that maps to that output. Well, you know what, again, it helps to have scratch paper here. So remind yourself what happens from the previous slide here is that, remind yourself what happens from the previous slide is that the entry that goes first is simply the upper right. The entry that goes second is you double the upper left sort of stuff. So here we go. The entry that goes first there it is. I had a little trouble finding it. The entry that goes first is the upper right. That's what was called B in the previous slide. The entry that goes second, the middle entry, remember it said 2A? Well, so in order to get a Y there, I need to start off with Y over 2. And similarly, in order to get a Z there, I'd have to start off with Z minus Y over 2 because you add those two together to get what goes in the third slot. It helps, again, to do this with numbers, but in the end, what you actually have to do is take out the numbers and put in letters. Preserves addition, same thing as the previous one, except it's somewhat more complicated with the A's and B's. You have to say f of first thing plus second thing. and you got to end with f of first thing plus f of second thing. This one I think is actually a little easier than onto. Onto is often the stumbling block. So how do you add two matrices? We know, of course, that you add the components. So this is f of that sum. So this is f of a single thing. What does f do? F takes the upper right and puts it first. F takes the upper left, doubles it, puts it second. And then f adds upper left plus upper right and puts it third. Okay, and how am I going to get to here? How am I going to get from here to here? Well, sometimes it helps to go backwards. So f of a1, b1, c1, 0 is this fella right here. Recognize it? F of a2, b2, c2, 0 is this fella right here. Recognize it? Does this? Yes, it does. These two are equal. As row vectors, the first component of this row vector is b1 plus b2. The first component of this sum, it gives you b1 plus b2, and like that. So if you put down the beginning and put down the end, and again, like a crossword puzzle, you say to yourself, how am I going to get from the beginning to the end? You work out the intermediate steps. Eventually you get better at it and you don't have to make such a big deal of it. But the first dozen that you do, half dozen or dozen that you do, you start saying to yourself, what do I have to do? So you put down the beginning, you put down the end, and you work your way toward the middle. Scalar multiplication is exactly the same deal. Put down the beginning, f of r times a member of the domain. Put down the ending, r times f of a member of the domain. And see if you can't work your way from the beginning and ending, work your way toward to making the two sides match up. Let's see, what do you do? So you say here, r times a member of the domain gives you this. Well, you multiply a real number times a matrix by multiplying the components. That's right. Maybe I'll go down to the bottom here and work my way up from the bottom. So r times f of a member of the domain. So f of a member of the domain is you take the upper right, put it first, upper left, double it, put it second, upper left plus lower left, put it third. So now I have those parts. Can I make them meet? Well, f of RA, RB, RC, 0 is indeed, you take the upper right, put it first, take the upper left, double it, put it second, take the upper left plus upper right, that's right, and put it third. And now are those two are equal. Done. So these steps often here follow in this kind of just sort of grinded out way. I will say that the onto often gives a person trouble, often gives me trouble, and the way to get onto typically is try it on scratch paper with 1, 2, 3. Try it on scratch paper with 5, 9, 12. If you do two of them with numbers and you figure out what maps to 1, 2, 3, and you'll figure it out. What maps to 5, 9, 12? And again, you'll figure it out. Well, once you've figured out what happens with how to get backwards from 1, 2, 3 to the V, from 5, 9, 12 to the V, well, then doing it with letters turns out to be just, oh, well, you always do. And so that's the trick for onto. So the how-to gives you, back to the how-to here. The how-to gives you 4 steps to verify that something is an isomorphism. And of course, the homework consists of verifying that things are isomorphisms. The how-to gives you 4 steps. To show the part 1, you have to show one-to-one and onto. To show the part 2, you have to show preserves, addition, and scalar multiplication. And really, I can't for doing the homework, you're being exposed to something brand new in almost all cases. You're being exposed to something you've never seen before. Sort of take the how-to out and do, first question, second question, third question, fourth question, until you start saying to yourself, oh, kind of stuff. That's a good feeling. That's the feeling that, this is starting to make the right mental model, the mental schema that fits this part all together. So when you start saying to yourself, oh, I thought this was easy, but it's not actually, I thought this was hard, but it's not actually all that hard. It's actually kind of easy. That's a good spot to be in. That's a very good spot to be in. Okay, so we've gone through a couple of these examples of showing that something is an isomorphism. So I think a person is ready to think about the homework. And next time, of course, we'll go through and look at some more for isomorphisms. Brand new idea. We'll look at some more examples and try to kind of piece it all together and make some sense of what the parts have to say. Okay, very good. Hi, hello. So of course, last time we started a new chapter, so very exciting, starting something brand new. And the very first thing that we saw, isomorphisms, is something that is usually, for folks in this class, is usually something they've never seen really too much like it before. So we went through a couple of examples. You have to start off with easier examples. So for the check-in, what I want to do is do an example that's just a little harder, just that sort of that notch, sort of more technically complicated. Same ideas, but more technically complicated. Okay, so let's get to it. So we have the space R2, the regular plane, and the space P1, which is the linear polynomials, and I want to show that they're isomorphic, not using the sort of obvious isomorphism that the first component maps to the constant term and the second component maps to the coefficient of x, but instead using a little different isomorphism, and so that makes it kind of more technically difficult, and so that illustrates what it is that we want to illustrate for the check-in. Okay, so let me bring that down and start working. We saw last time the how-to, 4 different steps that a person needs to show. Person needs to show one-to-one, onto, and preservation of addition and preservation of scalar multiplication. So I'll just start in. I better remind myself how it goes. Let's see, it is AB is associated with, and it's A minus B plus A plus B x. And now, perfectly sensible, perfectly reasonable for a person to say, what is, what is happening here? And the answer to an abstraction, if you're saying, I'm not getting what this formula is trying to tell me, the answer to an abstraction is always the same. It's to concretize, that's a word. It is to try it with some numbers. So I'm going to put in some numbers, 1, 5, and 1, 5 is associated with negative 4 plus 6x. So 2, 2 is associated with 0 plus 4x. Okay. So all that's happening here is I'm mapping 2 tall vectors. I'm associating 2 tall inputs with linear polynomial outputs, and it's a somewhat peculiar or at least a little bit not unexpected association. But okay, fine. Okay, so let's start off. We got to show that it's one-to-one. And the how-to says, here's how you show it's one-to-one. You assume that F maps a first one to a second one. A1, B1. I think I got that right. There's the matching parens. And A2, B2. And again, I think I got that right. A lot of parens, but I think I got it right. And then when I finish, I have to show that A1, B1 equals A2, B2. So my goal is to get from here to here. Okay, so let's see here. F of A1, B1 is what? A1 minus B1 plus A1 plus B1 x, that's this part here, and then this part here is A2 minus B2 plus A2 plus B2 x. Okay, so again, I'm trying to get from here to here. For this, I just wrote in what it equals. That's all. So how am I going to get this? In order to get this, I need, working backwards, I would need this. What? To get that, then I would need A1 equals A2 and B1 equals B2 is what I would need to get that. So let's see. So I have here 2 linear polynomials, and I got to conclude this. So it seems to me I have to conclude that A1 equals A2 and B1 equals B2 by looking at the constant terms. So from we have A1 minus B1 equals A2 minus B2. And A1 plus B1 equals A2 plus B2. Okay? And how do I get from there to there?
Well, I guess there's a variety of things that a person could do. A person could set up some linear systems, but personally, I would simply add. I would take the left-hand sides, a1 minus b1 and a1 plus b1, and add them to get 2a1, and I would take the right-hand sides, a2 minus b2 and a2 plus b2, and add them to get 2a2. So adding gives 2a1 equals 2a2. And can you see that subtracting will give? I'm sorry about my handwriting. Gives, so a1 minus a1 goes away, negative b1 minus b1, so minus 2b1 equals minus 2b2. So I got, and I even had exact right amount of space, which hardly ever happens. Okay. So one-to-one was a question of writing down where you start from, writing down where you have to end, and figuring out how to make the two meet in the middle. And of course, it can be the case for an individual problem. They say, I just don't get it. I just didn't see how to make them meet in the middle. But there must be a way to make them meet in the middle. Okay? Onto is a little trickier, so we'll try a fresh piece of paper. So for 2, onto. So for onto, what I find is that what does me the most good is to try it first concretely with with numbers, and then right away I'll start saying, okay, so the pattern is. So I'm going to ask myself, if I pick kind of some numbers, I'm going to ask myself, f of what makes, how about 3 plus 4x? I didn't pick 3 and 4 for any good reason. I just made up two numbers. In fact, if you make up, if you don't pick sort of 0 and 1, if you try to pick up kind of crazy numbers, that is often more helpful than picking sort of special numbers. Okay, so I need that a minus b equals 3. So so I'm looking at f of ab equals 3 plus 4x, and I'm asking what are a and b. So of course I need that. You remember that ab maps to a minus b, a plus bx. So I need that a minus b is 3, and a plus b is equal to 4. Well, this is familiar territory. Off I go on Gauss's method. Minus rho 1 plus rho 2 gives me a minus b equals 3, and what minus 2b equals 1, minus 2b equals 1, minus 2b equals 1, and so b is 1/2, and a minus 1/2 is equal to 3, so a is 7/2. Okay, so the key idea there, once I boiled it down to some numbers, the key idea there was that I got an equation where a and b are the unknowns, and the given things, the 3 and the 4, are the constants on the other side. So if I want to figure out f of what equals p plus qx, then I get a linear system. A minus b equals p, and a plus b equals q. Gauss's method, I'm just aping what I did with numbers, only with letters. Gauss's method, minus rho 1 plus rho 2, takes you to a minus b equals p, and 2b, oh, this is a plus 2b. That's right, I copied it down wrong, I apologize. So 2b equals, what is this now, minus p plus q? Minus p plus q. And so I conclude that b is equal to b equals minus p plus q over 2. And from that I get a minus p plus q over 2 equals p. And so what a is, change the sign of a is p over 2 plus q over 2. A is p over 2 plus q over 2. Okay, so given a p and a q, I can tell you what a and b are. Now I'm ready for onto. So here's the argument for onto. So consider P plus QX in the outputs. Observe that we have that f of P over 2 plus Q over 2 and B is minus P over 2 plus Q over 2. I got the parentheses all wrong. There we go. So that's P over 2 plus Q over 2 minus P over 2 plus positive Q over 2 is equal to P plus QX. And that's easy to verify. Maybe I shouldn't have just written this. Maybe I should have written something like this. It's equal to P over 2 plus Q over 2 minus negative P over 2 plus Q over 2 plus A plus B. P over 2 plus Q over 2 plus negative P over 2 plus Q over 2 X. Sorry about the handwriting. And when all the smoke clears, the P over 2's add, that minus minus makes plus, P over 2 adds to make a P, and the P over 2 and the minus P over 2 cancel to make a Q. And so a lot of mess with the handwriting, but anyway, it turns out that I did a lot of work to figure out what's the right formula, but once I have the right formula, I just pull it out, verify that it works, and boom, you're done. So given a member of the output space, there is an appropriate member of the input space. Took me a little while to figure it out, and the key there, it always seems to me the key there, is to start off with numbers and then switch with letters. If you're scratching your head, what am I asked to do? Change it to numbers, and then it's so much easier to figure out what to do when you change it to numbers. Then at some point you say to yourself, I see the pattern, I'll change it to letters. Now you've got a formula. Verifying that the formula works is usually easy. Okay, that was on to. Fortunately, the other two parts are usually routine. So for 3, preservation of addition. There we go, a little sideways. Preservation of addition. For preservation of addition, it's usually just a question of seeing if you can make the beginning match the end. So I have f of A1, B1 plus A2, B2. And I've got to get, after some amount of work, maybe half a page's worth of work, I got to get f of A1, B1 plus f of A2, B2. Okay? And I do think when you first start these out, it helps to break it into 2 parts and work from the bottom up and the top down. But a person does get better after some point, so let's give it a get better whack. F of A1 plus A2, B1 plus B2. And what does F do? It takes the first minus the second, so that's A1 plus A2 minus B1 plus B2. That's the constant term. And then the coefficient of x is A1 plus A2 plus B1 plus B2. And the whole thing is multiplied by x. And then, right, it's pretty clear what I got to do. I got to bring the 1's and the 2's and separate them out. So I get equals A1 minus B1 plus A1 plus B1 x plus A2 minus B2 plus A2 plus B2 x. And then that line and that line are fine. I didn't leave the right amount of space, but I almost never do. Okay, and if you didn't see how to do that, you could certainly work from the bottom up and see that this is f of A1, B1 right there. This is f of A2, B2. This is what happens when you f the combined, and then you say to yourself, they're the same. Okay. And then for 4, preservation of scalar multiplication. So here it's much the same thing. I write down here f of r times ab. I don't need the ones and the twos. They're not wrong, but I don't need them anymore. There's only one vector. And I got to somehow make that come down to r by f of ab. And again, if you get stuck, you can always work from the bottom up and the top down at the same time and see if they meet. I'm gonna do top to bottom because a person does get better at this over time. So this is f of RA RB, because that's how you scale and multiply vectors. And what does f do? It takes the first component minus the second, RA minus RB, and then the first component plus the second, RA plus RB. And I'm going to bring out all the, oops, I forgot the equal sign. I'm going to bring out all the r's, r times a minus b plus a plus bx. And that's right. Okay, so I made the two come out equal. And again, if you're having a little trouble with it, what's a good technique is to write down here r times f of ab, and that would give you this. F of ra rb would give you this, and you say the two are the same. So we're good. Okay, so that one's a little trickier. In particular, the onto is the part that often gives a person trouble. And to me, the technique that works the most there is the technique of a technique that always works with abstraction. Anytime you have trouble with abstraction, see if you can make it concrete. If you can somehow turn it into numbers instead of letters, that seems to help a person, or often seems to help a person sort of make sense of it, put it together in their head. What part is what? Okay. Okay, so we're ready for talking about the second half of isomorphisms, and it's really sort of more of the same. So last time we introduced isomorphisms and we worked with them, a couple of relatively easy ones. In the check-in, we work with a relatively hard one, so feel like we have some practice now. We'll get a little more practice today and talk a little bit about what isomorphisms has to say. One way sometimes to help understand what something is to talk about examples of what it isn't. You know, it's a silly example, but if you want to teach a 3-year-old what a cat is, you might show them also a couple dogs and say, not a cat. So what is it about preserved addition and preserved scale and multiplication that a person can learn? And it does seem to me one way to help understand that is to look at an example of a map that does not preserve. So here's a map that does not preserve. F of xy is the too tall vector x squared y squared. And it doesn't preserve, for example, 1, 0 and 2, 0 add to make 3, 0. F takes 3, 0 to 9, 0. However, f of 1, 0 and f of 2, 0 doesn't give 9, 0. F of 1, 0 is 1, 0, f of 2, 0 is 4, 0, doesn't give 9, 0. So it is not necessarily the case that all functions have this property of where you can break along the plus sign. That preservation of addition property doesn't hold for all functions. In fact, it rarely holds. So that preservation property is special. And special means that it will give us special results. Okay, so talking about isomorphisms, one kind of isomorphism that we'll talk about a number of times is isomorphism of a space with itself. An isomorphism of a space with itself is called an automorphism. So we're talking here about how spaces are related. We might want to relate a space to itself. So if we relate a space to itself, that's called an automorphism. Morphism means map, auto means self, so self-map. Just as an example, I'm going to take the plane, regular xy plane, and a dilation map multiplies all vectors by some non-zero scalar. In my drawing here, I multiplied them all by 1.5. I couldn't multiply them, it's too big because it fell off the top of the map. So I multiplied them all by 1.5. Okay, that's called a dilation map. And it's a perfectly good isomorphism. It's easy to check that it's an isomorphism. Go through the 4 steps and it's easy to check. Another automorphism is a rotation. So you can turn all of the vectors by the same angle. I'm rotating counterclockwise because that's traditional to rotate counterclockwise. Here by an angle of pi over 6 radians. Okay, so it's easy to check that that's an isomorphism. You might want to close your eyes and say to yourself, is it one-to-one? Is it onto? Does it preserve addition? Does it preserve multiplication?
One more automorphism is a map that flips all the vectors over a line through the origin. So here I have a vector u and a line through the origin. That's the line at 45 degrees just because I thought it made it something easy to see. And when you reflect u over that line, you get f sub l of u, and that, again, that's an isomorphism. It's an isomorphism of the space with itself, checking that each of these three, the dilation, the rotation, and the flip, is an isomorphism, is pretty routine as one of the exercises. Well, a person might say, why are we studying automorphisms? I thought isomorphism meant just like, and it's obvious that the plane is just like itself, so isn't this entirely silly? So I want to go back and think about the rotations of the plane by theta radians counterclockwise. They say something. If you're saying that the plane is the same as itself after you rotate it 15 degrees, if you're saying that the plane is the same as itself, you're talking somehow about uniformity. You're describing the plane as being uniformly flat over the entire plane. So the part near the origin and the part that's near, x equals y equals whatever it is, those parts are the same. There's a flatness there. So with respect to rotation. So the fact that rotation gives you an automorphism has something to say about the structure of the space. These maps tell us things about the spaces that are being mapped. So the space in this case near the x-axis is just like the space near the y-axis, because you can rotate 90 degrees and turn the x-axis into a just like area, the y-axis. So these maps will tell us something about what the spaces are like. So one lesson is that we can use the map to describe relationships between spaces. If maps are isomorphic, then the relationship makes precise the intuition of just like, and in particular, if you talk about a space and itself, you can describe somehow a uniformity of the space. When I did dilation, I multiplied everybody by 1.5. The space is just like itself, further out. So in is the same as further out. Okay, and then the second lesson, also the lesson of the check-in, is that while there are obvious automorphisms, there are obvious functions from the space to itself that are isomorphisms. Nonetheless, there are non-obvious, non-trivial automorphisms of spaces, and that they have something to say. They tell us something about the space. They give us a description of the space as uniform with respect to some measure. Okay, so ending up with a couple of quick results about isomorphisms. First is that an isomorphism maps a zero vector to a zero vector, and this is just simply some straightforward algebra. So you fix some v in the vector space capital V, and remember that vector spaces are never empty, so there must be such a thing. Then f of the zero vector is f of 0 times v. Preservation of scalar multiplication means you bring the zero out. And 0 times f of v is 0 times is the zero vector in W. So that gives you that. Okay, one more result here for the day. So if you have a map between vector spaces, then these statements are equivalent. The two that we had in the definition of isomorphism, preserves addition and preserves scalar multiplication, is equivalent, says the same thing as, saying that f preserves linear combinations of the two. So you can take these two statements and combine them into one, and indeed sometimes it's more convenient when you're trying to check, for example, that something's an isomorphism, by checking one statement rather than by checking two. And you can do this with more than two vectors. You can do it with any finite number of vectors. Okay. The book contains the details of both the proofs. They're not especially interesting, so I'm not going to go through them. They don't really have anything. You won't look at it and say, really, what's line 7 saying? All right, and then the remark down here says, if you look at the proofs, they only depend on the clause 2 of the definition about preservation. They don't depend on one-to-one and onto. So we'll say more about that in the next section. In the next section, section 2 of this chapter, we'll consider maps that aren't necessarily one-to-one and onto, but that do preserve. Okay, one last example. Here's a line through the origin with slope 2. y equals 2x. That's a vector space. If you parameterize it, it's all multiples of 1, 2. We've done this many times. What that suggests is that the line L is somehow just like R. There's a point on L associated with 1, namely 1 times 1, 2. There's a point on L associated with 2, namely 2 times 1, 2. There's a point on L associated with minus 1 times 1, 2. That is to say that the parameterization suggests a just likeness. So again, what we're seeing is that we're using isomorphism. We're using isomorphism to describe somehow just likeness. That the 1, 2 stays fixed and the t varies shows how this line is somehow like the real line with only the letter t to describe it. Verifying that it's 1-to-1 is routine, especially with the check-in. Verifying that it's onto is routine, again, especially with the check-in. If you want to show that, for example, there is a member of the line y equals 2x that maps to 7, you just say to yourself, well, 7 times 2x, excuse me, 7 times 1, 2 maps to 7. And then preservation of addition and preservation of scalar multiplication is on the next slide. Whoops. Preservation of preservation of combinations is just as routine. To show that f of a combination is the combination of the f's. To show that f of a combination is the combination of the f's is just the kind of algebra that we've been doing. You bring out the 1, 2's. F applied just simply strips out the 1, 2, and there you are. Okay, so again, the idea here is that these maps, something I expect is new to a person, these maps describe something about the spaces in a precise way, but describe something about the spaces that you've probably already intuited in the second chapter. You said to yourself, well, this is really just like. Yes. So for example, the line y equals 2x is just like the regular real number line in that, for example, 5 times 1, 2 is just like 5. And 12 times 1, 2 is just like 12. Yes, that's right. The definition of isomorphism simply makes all that mathematically precise. Okay, very good. Next time we'll talk about dimension characterizes isomorphism, and so we'll see it for next time. Okay, bye-bye. Hi, hello. Okay, last time, of course, we talked about automorphisms, and so I'm trying to sort of nail some of the intuition about these kinds of maps down. And so the check-in involves a geometry question. We're trying to talk about what does preservation of addition mean when you draw it in pictures. So let's get to it. I have two vectors in the plane, 1, 2, and 3, 1. And I'm going to apply 3 different automorphisms. The map that multiplies all the vectors by 2, the map that rotates all the vectors by pi over 6, and the map that flips all the vectors, in this case about the line y equals x. Okay, so let's see how I do with this here. Probably not very well. So I'm looking at the two vectors. I'm looking at the two vectors 1, 2, and 3, 1. And w equals 3, 1. And drawing is definitely not a strength of mine, which is why I get the computer to draw as many pictures as I can get away with. But it's not awful either, so let's give it a whack here. You'd think I could do something. So I'll draw, and this is going to be the x-axis, and this is going to be the y-axis. I'll draw 1, 2, and I'll draw 3, 1, and I'll draw the parallelogram picture. Let's see, 1, 2, 1, 2, and 3, 1, 3, 1. And the parallelogram picture goes to what? 4, 3. 4, 3. There we go. Okay, so 4, 3. Okay, then question 1 says multiply everybody by 2. Look at the automorphism, that the dilation map that multiplies everybody by 2. So for example, 2u is going to be 2, 4. And 2w, 2v, sorry about that. Why did I not put vector bars? 2v is going to be, 6, 2. And I'm going to have to draw a bigger picture. So instead of going to 4. I gotta go there. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay, 2, 4. 2, 4. So 6, 2. 3, 6, 2. So, and when you add them together, 8, 6. 8, 6. So what this is telling me is this vector right here is d of u plus d of v. 8, 6. If you compare the two pictures, what it's telling me is that if you add d of u and d of v, you get the same answer as if you take the 4, 3 and double it. So double first and then add gives you the same answer as add first and then double. That's what preservation of addition tells you, of course, in this context. Okay, let's try rotating. I'm not gonna do the trigonometry to get the rotated vectors. I'm just gonna pretend that I rotated the vectors, and I actually don't even know whether they whether this one goes past the axis, but I'm gonna pretend it does, and then rotate that by pi over 6. I don't know, maybe so. And maybe the parallelogram diagram goes like so. Isn't it awful? I never did line to draw. There we go. So this is what happens if you rotate u and you rotate v, and you add. But it's also what happens if you add first and then rotate. Okay, so the geometry of preservation of addition is that you can add first and then rotate, or you can rotate first and then add. You'll get the same result. Okay, so for the third one, of course, going to do the flip. So what is the flip of u? Oh, u disappeared off the top of the page. What is the flip of u? Well, you take 1, 2 and flip it about the line y equals x. I think you get 2, 1. And the flip of v is you take 3, 1 and flip it about the line y equals x, you get 1, 3. See how I do with this drawing. Two, 1, 2, 1. 1, 3, 3. Versus 2 and 1, 1 and 3, so 3, 4. And again, the point of contrasting what's on the top to what's on the bottom is that you can think of this vector right here, the long side of the parallelogram, you can think of that vector either as the flip of u added to the flip of v, or it's also correct to thinking of it as the flip of u plus v. Okay, so preservation of addition somehow has something to say about this, the sort of before and after pictures here. These before and after pictures capture the whole f of u plus f of v equals f of u plus v. Okay, great. So let's see, what am I doing here? Oh yes, I have to pop that up, pop that down. There we go. Okay, got lost there for a second. Okay, so we're ready for what we're talking about for the day. The dimension characterizes isomorphism. We have a result that we want to talk about today. That how do you know when two vector spaces are isomorphic? And the answer will be if and only if they have the same dimension. So that's our big result for the day. The idea will be just this simple. If you have two vector spaces, and you find a basis for the first, maybe it has 3 vectors. You find a basis for the second, maybe it has 3 vectors. Those will be isomorphic vector spaces. They are in some sense just like each other. And in fact, the isomorphism can be as simple as you take the 2 bases and associate them. That is to say, you take the first basis vector in the first space, associated with the first basis vector in the second space. Second in the first space, second in the second space, third in the first space, third in the second space. So you associate the bases. So isomorphisms will associate all those things that are just like the things in the other space. And for example, they will associate bases. Okay, so let's go to it. So in order to prove the result that we need, I need a couple of technical things. In particular, I need this result. This is an interesting and sort of worth doing result all of its own. It's not obvious by any means, but I'm headed towards something bigger. So I'm going to give this one a little bit of short shrift. I am going to prove it, but you'll see I'm going to do it at sort of at a faster pace than the one that we're talking about today. Okay, so I have a space V and a space W, and there's an isomorphism from one to the other. I want to remember that an isomorphism is a correspondence. It's a one-to-one and onto map, and that any correspondence has an inverse function that takes you not from V to W, but instead from W to V, and the inverse function is also a correspondence. Okay, so that's a result about correspondences, about one-to-one and onto maps, and you can check the appendix if you need a little refresher on that. To finish, then, I have to show that the function f inverse preserves addition and preserves scale and multiplication. We saw the result last time that we can combine the two together if we like and just show that it preserves linear combinations of 2 vectors. So I'm going to take that. It's not a much of a shortcut, but it's something of a shortcut, so I'm going to take it. So here it is. F inverse takes a linear combination and gives you, after a little bit of work, gives you a linear combination of the F inverses. Okay, so let's go through the steps. To get from F inverse of this linear combination, note that these are W's because F inverse starts in capital W. So to take F inverse of this linear combination, the first thing I did was rewrite W1 as F of V1 and W2 as F of V2. An isomorphism is a correspondence, so there's exactly, if you start with W1, there's exactly one V1 that F takes to W1, and there's exactly one V2 that F takes to W2, so I just wrote those in. F is an isomorphism, so it preserves linear combinations. Here we go. I rewrote C1 F of V1 plus C2 F of V2 as F of C1 V1 plus C2 V2. F and F inverse cancel each other. I got C1 V1 plus C2 V2, and I rewrote V1 as F inverse of W. So this is just some algebraic manipulation, one step to the other. Not trivial, but it is stuff that we've done before, not all that long ago, all the recent classes, in fact. So I'm going to pass over it a little bit. I am going to give an example, though. The statement that we just saw has something to say about isomorphisms that reinforces the kind of thing I've been talking about for a couple of videos now. In particular, in the last video, I talked about the line through the origin y equals 2x. I parameterized it this way. It's all multiples of 1, 2. And I said you can, if you like, one isomorphism you can make between this line through the origin y equals 2x and the real line, the vector space R1, is you can take t and associate it with t. So that, for example, 5, 10 is associated with 5. 2, 4 is associated with 2. And the inverse simply goes in the other direction. What's F inverse of 5? Why, it's 5, 10. What's F inverse of 2? Why, it's 2, 4. So you'll remember that when we first did introduction of isomorphism, the first couple of examples we did to try to build up some intuition had double-ended arrows. It said the things at the beginning and the things at the end match up with each other. And that's all we're saying here, is that the things in the beginning and the things in the end match up with each other. The 2 and the 2, 4 is a double-ended arrow between the two. They're associated together one-to-one and onto. Okay. So saying that everything matches up is saying that the two spaces somehow are just like each other, and so the universe of all vector spaces breaks up into cases. You have vector spaces that are just like each other, vector spaces that are just like each other, vector spaces that are just like each other. You break up into these communities of vector spaces where inside of a class, all the vector spaces are just like each other. Inside of a class, all the vector spaces are just like it. Inside the class, all the vector spaces are just like each other. And the point of the day today is to characterize those classes. If you look at a particular class, all the vector spaces that are just like R2, what's in there? And of course, I gave it away already. It's all the vector spaces that are two-dimensional. Vector spaces are isomorphic if and only if they have same dimension. In the book's presentation, because each of the two halves is substantive, I broke it into two separate statements. And the two separate statements are, if spaces are isomorphic, then they have same dimension. And if spaces have the same dimension, then they're isomorphic. So basically what we show is that the bases correspond. The proof of the first depends on showing that under an isomorphism, the image of a domain basis is a range basis. So the bases correspond. And then the second depends on giving an explicit isomorphism from an n-dimensional domain to Rn. So the book has the full proofs, and as I often do in these videos, instead of giving the full proof, I'm going to give an illustration that I hope helps a person get ready to read the full proof. Okay, so I'm going to look here at a two-dimensional space, the plane 2x minus y plus z equals 0 in R3. And based on the drawings that I drew at the beginning of this video, you can see why I got the computer to draw the plane for me. That area is the plane 2x minus y plus z equals 0, and those are two vectors in the plane, and based on this parameterization down here, the vectors are 1/2, 1, 0, and minus 1/2, 0, 1. This is minus 1/2, 0, 1. Can you see that it's a little bit back? Lies in the xz plane, and that's a height of 1. And so this must be 1/2, 1, 0. So this lies in the xy plane, and it's x equals 1/2, y equals 1. You can see why I got the computer to draw these things for me. I'm totally incompetent at it. So what I get then is that a basis for this plane is these two vectors. Is the sequence consisting of those two vectors, 1/2, 1, 0, minus 1/2, 0, 1. I copied that to this slide just so that I wouldn't forget it. Because the basis has two vectors, P is a two-dimensional space. Okay, and we talked last time about how the word two-dimensional matches up with our intuition of two-dimensional, that a plane is two-dimensional. All right, and then the second lemma's proof that this explanation is really supposed to be a warm-up for, it says that the following is an isomorphism. The map that associates each element in P, each member of the plane, with its representation with respect to this basis. Remember that the representation with respect to a basis is a two-tall vector. So I'm going to associate each vector in the plane, each vector with the property that 2x minus y plus z equals 0, I'm going to associate with a two-tall vector. And here's a typical example. I'll take 7/2, 3, and minus 4, and I'll associate it with 3 and minus 4. What's the association? Well, 7/2, 3 minus 4 is a member of the plane. So you can represent it with respect to this basis. So I did. I did the arithmetic. I'm not going to bother you with the arithmetic. So 1/2, 1, 0 times 3 minus 1/2, 0, 1 times minus 4. That's the 3. This 3 right here is this 3 right here. This minus 4 right here is this minus 4 right here. So I associate a member of the domain with its representation with respect to the fixed basis. I fix a basis, and I associate 7/2, 3 minus 4 gets associated with 3 and minus 4 because that's the representation of that vector with respect to that basis. Another example, same sort of stuff. I picked some crazy one at random from the plane, minus 17/4, 1/2, 9, some crazy thing that satisfies the property for the plane. And I represented it with respect to the basis. This basis up here, I got a 1/2 and a 9. And again, I'm not going to bother you with the Gauss's method to do that. I got a 1/2 and a 9, so I associate this vector v2 with 1/2, 9. So if you want to know who matches up in the domain space with who in R2, and the answer is just look at the coordinates of each vector in the domain space, write them as a 2 tall vector. That's who the association is with. The first lemma's proof shows that any isomorphism takes basis to basis. If you have a basis in the domain, then the image of that basis is a basis in W in the codomain in the range. So who's the basis here for the domain? 1/2, 1, 0 and minus 1/2, 0, 1. Who's the basis for the codomain for the range here? Well, this basis here is 1/2, 1, 0 gets associated with 0, 1, and this basis vector here, minus 1/2, 0, 1 gets associated with 0, 1. And obviously, of course, this makes a basis, namely the standard basis for R2. So the basis from the domain gets mapped over to the basis from the range. So we have an association, one to the other, of your coordinates with respect to the basis in the plane and your coordinates with respect to the basis in R2. Your coordinates with respect to the basis in P and your coordinates with respect to the basis in R2. And that's the association. That's the isomorphism. The corollary is that every finite dimensional vector space is isomorphic to one and only one of the Rn's, and that the reason for that is if you give me a finite dimensional vector space, it's got some number of elements in its basis. N. Every basis has the same number. Anyway, they all have n. This map that I just illustrated in the previous slide shows you how to associate members of the vector space you gave me with Rn. So every finite dimensional vector space, namely every n-dimensional vector space, is isomorphic to Rn. So when I had that picture earlier where I broke the universe of all vectors, finite dimensional vector spaces, up into separate parts, the parts that are all like each other, the parts that are all like each other, the parts that are all like each other, it turns out that in those classes, in those isomorphism classes, in those equivalence classes, in those parts, there's exactly one real vector space. So for example, all of the two-dimensional vector spaces are all together. They're in the same part, they're in the same equivalence class as R2. All of the three-dimensional vector spaces are all together. They're in the same equivalence class as R3. All the one-dimensional vectors, all the zero-dimensional vectors. Out here, I didn't draw because I can't draw infinitely many cases, but out here, all the 50-dimensional vector spaces, they're all together in the same equivalence class. They're all isomorphic to each other, and in particular, they're all isomorphic to R50. So in some sense, the Rn's represent their class. The technical jargon is the real spaces Rn form a set of canonical representative. Canonical means natural or obvious, or the thing that you would reach for. Okay? Okay. So big result, of course, didn't go through the proofs, but nonetheless tried to give some intuition about what's happening in the proofs. Basically, under isomorphism, everything corresponds. That includes bases, and it also includes representations with respect to the bases. So everything corresponds, everything of interest in a vector space corresponds the one to the other. I had a professor who used to say, under isomorphism, the second space is just the first space colored green. That is to say that there really isn't any, as far as vector spaces are concerned, differences between the two cases. The way I would characterize it is that any differences are typographic. If you have an isomorphism between 2x2 matrices and 4 tall vectors, it's just a different way of writing it. You could write it as a square. You could write it as up to down. It's just simply typographic. And he used to imagine that in one the numbers were blue and one the numbers were green, and that was the only difference. So vector space isomorphism tells you when things are alike, and it turns out we have a complete characterization of when things are alike. Things are alike when they have the same dimension. Okay, all right, very good. So So next time we're going to start the next section where we take the map isomorphism that has it's a correspondence and it preserves linear combinations, and we're going to drop the correspondence part. Okay, very good. See. Hi. Okay, so last time we finished off the section on isomorphism, and we learned that that the representation map gives us an isomorphism between the two spaces, whatever space it is we were working with, and some real n space. So the way the representation map works is that in the domain you fix a basis, and then you take the representation of vectors in that domain vector space, and that gives you an association with Rn. So we'll see that here on the checking. So the domain space that we're working with is the quadratic polynomials, and I fixed a basis. I just made up a basis. I don't know, I just made one up. So x squared plus x, and x squared plus 1 is 3 different quadratic polynomials, and you can check that it's linearly independent and that it spans the space. The basis that I'm working with for R3 is the standard basis. And I'm going to look at a particular quadratic polynomial and ask what's it associated with. The representation map associates this quadratic polynomial with which 3 tall vector, and then question 2 asks the reverse question. If you have a 3 tall vector, what's the member of, if you have a 3 tall vector, what's the member of the domain that is associated with it? Okay, all right, so let's have a look. So let's see if I can remember what the parts are now that I clicked away from it. So B is, it's x squared plus x, and x squared plus 1. And then, of course, the D is the standard basis, which I know a person remembers. But anyway, just to have written it down. Okay, oops, doesn't quite all fit on the screen. Okay. All right, and then I want to remind a person again how the representation map goes. The representation map with respect to a basis B of V says this: find the ABC so that V is equal to A times the first thing plus B times the second thing plus C times the third thing. And when you do, the representation map takes V over to ABC. Okay, so we're thinking of representation as taking domain elements over to R3. All right, so the instructions up here tell a person exactly what to do. I happen to be given, I wrote it down because I knew I'd forget, -1, -2x, and plus 4x squared. So all I got to do is figure out what A, B, and C are in this expression. A times x squared, B times x squared plus x, C times x squared plus 1. I figure out what A, B, and C are in that expression, and that'll give me the 3 tall vector. That's it. Now, obviously, I could set up Gauss's method. I could set up a linear system, do Gauss's method, come up with answers. But as we've talked about before, nobody made it a crime to be able to look at a problem and see the answer. And I think this is one of those, which is why I chose this basis, because it has that property. So if you look left side, right side, you'll notice that on the right side, the only term that has a constant in it is the third. So from that, I get that C is -1. So by inspection, by looking at the darn thing, you see that C is -1. Likewise with the x's, it was a -2x and a bx. That's it for x's. So b must be -2. And then combining those two, once you know C is -1 and b is -2, you can figure out A. So let's see, -1 and -2 is how many x squareds I have so far. So I must need 2 x squareds to cancel them out. So A is 2. 2 and minus 2 and minus 1. Oh, 4, 4, 4, 4. Sorry, I messed that up. So C is minus 1, B is minus 2. That makes a total of minus 3. So I need A to be 7. Whoops, sorry about that. 7. Is that what I wrote down? That's what I wrote down. Oops. Sorry about that. Okay, so what's happening here then is that the representation with respect to the basis B, minus 1 minus 2x plus 4x squared, is the member of R3 is got to put them in the right order, 7 minus 2 minus 1. Okay, and the flip of that, the inverse of that, is just the flip. So instead of starting with minus 1 minus 2x plus 4 squared, instead of starting with something from the domain, you start with something from the range, and you just ask yourself what's going on. So we're asking here, what is it that maps under representation over to its minus 1, 2. Okay, and the answer simply is V is equal to minus 1 times, where is it? It's up here. There it is, minus 1 times x squared. Minus 1 times x squared plus x. And C is 2 here. X squared plus 1. And if you can read the handwriting and work out what the heck is supposed to happen, I think I've got minus x squared, another minus x squared, 2x squared, so I think I get 0 for x squared. I've got minus x, so minus x, and a plus 2. Okay, so V is plus 2. Okay, so the idea again is that if you fix a domain basis, then the representation takes you back and forth between 3 tall vectors, in this case because the domain basis has size 3, between 3 tall vectors and the vectors in the space that you're interested in. So we can represent what we're doing by working with 3 tall vectors. Well, of course, what we're doing for real is we're really working with polynomials, but we can represent it in some way by working with 3 tall vectors. Okay, very good. Now, last time we talked about the fact that we are going to start something new. This is a new second section of the third chapter. So the new thing is, in some sense, easier than the old thing. Isomorphism has 2 different properties. First of all, it's a correspondence. Second of all, it preserves linear combinations. Homomorphisms will have only one of those 2 properties, and so in that sense, they're easier than isomorphisms. However, homomorphisms are less conceptually clear than isomorphisms. When a person is working through Chapter 2 on vector spaces, at some point you say to yourself, wait, the 3 tall vectors and the 3 wide vectors, it's the same thing. It's just a typographic difference. You have 2 spaces, but they're really the same space, just in some kind of disguise. Well, you've surreptitiously discovered isomorphisms. Of course, you have to write all that down officially, and you have to check that you understand the parts and everything. But nonetheless, there's an intuition there that everybody gets at some point in the middle of the second chapter. Now, with homomorphisms, the way we're developing is we're going to say we're going to start with isomorphism and we'll drop the condition of correspondence. But we have to explain, as we work through homomorphisms, we'll have to explain the significance of what they are. What do you get when you do that? Because it's less clear. So isomorphisms are in some sense easier than homomorphisms because they're conceptually more clear, and that's why I've put them second. But a person can also, sort of strictly mathematically speaking, say homomorphisms are in some sense simpler because they have fewer conditions. But that turns out not to really be true in terms of understanding. Anyway, all stuff that doesn't matter for doing homework. So for homomorphism, the definition of a homomorphism is a function between vector spaces that preserves addition, and of course we've seen the preserves addition definition before, and preserves scalar multiplication, and again we've seen that before. It's called a homomorphism or a linear map. Those 2 terms are both very widespread, and I'll try to, maybe not exactly, strictly speaking, alternate from one to the other, but often use one and often use the other. Homomorphism or linear map. Okay, and we have seen a number of homomorphisms already because every isomorphism is automatically a homomorphism. It's a homomorphism with extra special conditions. Extra, comma, special conditions, I guess, comma. Anyway, but so we've already seen a bunch of examples. Of course, we're going to see some more. I'm looking at two different functions from R2 to R. One of them is a homomorphism. One of them is not a homomorphism, and a person does spot the same sort of thing that you started to catch on to, I think, for isomorphisms, that this plus 1 is going to cause you trouble. 2x minus 3y is a linear map or a homomorphism. 2x minus 3y plus 1 is not going to be a linear map or homomorphism. So the map H respects addition. We've been doing this for a while now, so I think it's reasonably routine. H of vector 1 plus vector 2 equals H of vector 1 plus H of vector 2. And the steps in the middle, again, we've gone through a bunch of these, so I don't think I need to hammer on these. The map H also respects scalar multiplication. R times H of V is H of R times V. And again, we've done a bunch of these. Don't get me wrong, I'm not embarrassed about what I wrote, but we've done a bunch of these. I don't think a person is going to say, what are you doing here? Because we've seen it a bunch of times before. The contrast is that G does not respect addition. In order to show that G does not respect addition, the most straightforward thing to do is to produce two vectors where G of V1 plus V2 is not the same as G of V1 plus G of V2. And to tell you the truth, that any two vectors you write down, the first two vectors that come to mind, and that's what I did. I just wrote down the first two vectors that came to mind, and it turns out you get minus 17 in one case and you get minus 16 in another, and it just doesn't work. So what works for H here just doesn't work for G, and a person is right in suspecting that the minus 1 is the troubling aspect. We already have some results from that we're carrying over from isomorphisms. The first is that we said that an isomorphism sends the zero vector to the zero vector, but if you examine the proof, we never used that an isomorphism in the correspondence, so the same proof works here. So any homomorphism or any linear map, the two words mean the same thing. I'm going to try to use them sort of one and the other so a person gets used to both of them, sends the zero vector to the zero vector. And then the other result we saw that, again, doesn't use correspondence, so it just simply carries over to here, is that if you have a map from V to W, it's equivalent to say it's a homomorphism, or to say that it respects linear combinations of two vectors, or to say that it respects linear combinations of n vectors. Okay? Where n is greater than 1. So those three things are the same thing. It's often the case that we use 2, and we've used 2 a couple times already in the last video, for example. So just really trying to have a whack at some examples. We're going to do some examples this time, and then we'll just take a break just to not have too much in one video, and we'll do some more results and examples in the next video. So between any two vector spaces is a zero map. The zero map takes any input and maps it to W, and it's sort of trivially true, but it's nonetheless true that it's a homomorphism. It's a linear map. So just to check it with case 2 here, the zero map applied to C1V1 plus C2V2 is equal to the C1 times the zero map applied to V1 plus C2 times the zero map applied to V2, and that's just because 0 equals 0 plus 0. That's all. It's nothing complicated. So started off with an example that's simple, maybe too simple to be enlightening. Here's another example, again, just trying to have some examples that we have not already seen. So some examples that are not isomorphisms, just to illustrate something new. So I have the inclusion map. That's an iota. It's not the letter I because it's missing the little dot on top. So it doesn't have that, so it's a Greek letter iota. Anyway, the inclusion map from R2 to R3 takes 2 tall vectors and makes 3 tall vectors. Outputs 3 tall vectors, and that's a homomorphism. The verification, we've done the verification for isomorphisms an awful lot, so this is just not going to be a surprise to anybody. If you apply iota to a linear combination, then you get the linear combination of the iotas. I'll go through the steps, but it isn't anything we haven't seen before. The inclusion map applied to C1V1 plus C2V2. Well, add inside the parentheses to get that the first component is C1x1 plus C2x2, and the second component is C1y1 plus C2y2. Next step, you apply iota. It's the same thing, only it's got a 0 on the bottom. Next step, you split those along the plus sign. Of course, 0 equals 0 plus 0. Of course, the third entries work out. and recognize this as C1 times iota of E1, and this as C2 times iota of E2. That's all. So very routine in the light of having done a bunch of them in the context of isomorphism. Now here's one that I think is new and interesting, I think. Okay, it says the derivative function, the regular derivative function from calculus 1, is a transformation. It's a function on polynomial spaces. It takes one polynomial space and outputs another polynomial. So it takes vectors, for example, takes quadratic polynomials and outputs linear polynomials. I'm writing the derivative as d dx. I just don't want to fool around with primes, so I wrote it as d dx. And everybody knows, everybody who's watching this video, knows that d dx of ax squared plus bx plus c is 2ax plus b. And I don't have to explain why 2ax plus b is an interesting formula. A person that thinks about the slope of the tangent line, all this kind of stuff. And anyway, that's a perfectly legitimate formula that a person uses all the time. Just reminding somebody that the derivative of 3x squared minus 2x plus 4 is just exactly what it is in calculus 1. Derivative of x squared plus 1 is just exactly what it is in calculus 1. This is the calculus 1 statement. I haven't made anything tricky at all. I'm observing that it's a homomorphism. That if you apply this function to a linear combination of quadratic polynomials, the result splits along the plus sign, brings out the real variables. I'll go through the steps, of course I will, but you already know this. It's just that I'm pointing out that homomorphism, linear map, is something you've seen in another context, and so it's at least not totally unfamiliar. All right, let's see how I do. So d dx applied to the linear combination r1v1 plus r2v2. Okay, I broke things out by x squared, x, and constant term. Because when you take the derivative, that's what you want to work with. We know how to take the derivative of an x squared type of thing. You take the 2 and move it down in front. I don't know, you don't actually move it. But anyway, you rewrite this as 2 times coefficient times x. What happens over here? Well, you drop the x. You just write the coefficient. What happens over here? You drop it. It's gone. That is to say, you follow this formula. Okay, well, I can go from this line here to rewrite it to say 2r1a1x plus r1b, 2r2a2x plus r2b in the usual preserves linear combinations way. And then recognize that as r1 times d dx v1, r2 times d dx v2. So the familiar derivative is, in fact, one of these functions. So these functions are something that, you have some familiarity before. You've been using them to some extent before. They didn't come completely out of left field. Another example, the previous one was, I hope, was familiar to a person. Now this one is going to be, unfamiliar to a person. So the trace map takes 2 by 2 matrices and outputs real numbers. And I'm not going to explain where it comes from, because the point of this example is that there's all kinds of things that you haven't seen that are also linear maps. So the trace function on a, b, c, d is a plus d. Now, with derivatives, I didn't think I needed to go in and say, why was derivative interesting? Well, with trace, I'm refusing to say, why is trace interesting? Then my point is that there's a wide collection of things, some of which you know, and a whole pile of things you don't yet know that are also linear maps. So here we go. Trace of a linear combination is a linear combination of the traces, and it works just exactly like the others. One of the things I want to emphasize here and in the next video is that these are actually familiar, in part because we did it in the first section of the third chapter, and in part because some of them you've seen before. Okay, so what happens when you take r1v1 plus r2v2, and we've seen this before. You start out by combining inside the parentheses. Apply the trace map to you add the upper left to the lower right. There's the upper left, there's the lower right. So again, the point of trace is it adds the upper left to the lower right. So there's the upper left, there's the lower right. I gathered together the things with a subscript 1. I gathered together the things with a subscript 2. And that gives me the linear combination. So, if this was the first day of doing isomorphisms, I'd need to go extra slow and make sure I walk through exactly what happened at each step. But a person has done a lot of problems like this in the homework, so I'm figuring that we're good with that. Okay, so we've seen the definition of homomorphism, and we've seen a number of examples, and the theme of the examples, I think, is that some of these are familiar, some of these are less familiar, but all of them work like the isomorphism examples that you've seen before. Okay, and then next time when we come in, we're gonna start learning something about homomorphisms work, about the mechanics of how homomorphisms work. So that'll just be simply more of the same, trying to do more examples and understanding what's happening. Okay, all right, see you then. Very good. Hi, hello. So last time, of course, we defined what a homomorphism is, and so naturally the check-in is checking that a couple of things are homomorphisms. So let's get to it. So let's see, each of these is a linear map. This takes the cubic polynomials as input and gives two tall vectors as outputs. This takes 2 by 2 matrices as input and gives 2 by 2 matrices as outputs. So we'll check each of them. Here we go. So if I have it right, then a plus bx plus cx squared plus dx cubed maps to, it's a plus d, the two tall vector a plus d, and c minus 2a. So for example, you notice that b doesn't appear, just as an illustration of the kinds of things that can happen or not happen. Okay, so we have to check that it preserves addition and that it preserves multiplication, and we're going to shortcut that by checking that it preserves linear combinations. Okay, so let's see, h of r1 times the first polynomial, so a1 plus b1x plus c1x squared plus d1x cubed, plus r2 times the second polynomial, a2 plus b2x plus c2x squared plus d2x cubed. Okay, so h of a combination. And we've done many of these, so I'm not gonna go through it very, very slowly. I'm gonna sort of combine a couple of steps. So let's see, h of. So in particular, I'm going to add these two together to get the combination, and it's r1a1 plus r2a2 plus r1b1 plus r2b2 x, and then r1c1 plus r2c2 x squared, and finally, see if I can fit in the x cubes. r1d1 plus r2d2 x cubed. I didn't really make it. Okay, so of course now what h does is it takes the constant term and the coefficient of x cubes and puts it on the top of the two tall matrix, excuse me, two tall vector, and then it takes the coefficient of x squared minus twice the constant term and puts that on the bottom. So we're looking here at r1a1 plus r2a2, that's the constant term, plus r1d1 plus r2d2, and of course that's the coefficient of x cubed. And then on the bottom goes the coefficient of x squared, so that's r1c1 plus r2c2 minus twice r1a1 plus r2a2. Okay, and again, we've done so many of these that I'm not bothering to write where we start and where we need to end. Instead, I just assume that a person's done a good number of practice with the isomorphism and remembers what it is that we have to do. So then I'm going to break this into two parts and get what r1a1 plus r1d1, and then r1c1 minus twice r1a1. That was right. And then it's r2a2 plus r2d2,
and R2C2 minus twice R2A2. Okay, and then we recognize this as R1 times H of the first, A1 plus B1x plus C1x squared plus D1x cubed plus R2 times the second. H of, let's see, it's A2 plus B2x plus C2x squared plus D2x cubed. Okay, so we have that H of a combination is the combination of the H's, and that's good enough to show that it's a linear map, that it's a homomorphism. I don't know if I'm going to fit it down. I'm going to give it a try. Okay, so that was question number 1. Question number 2, maybe a little less space this time. So I got to check the G of, and of course I'm taking R1 times the first, A1, B1, C1, D1, plus R2 times the second, A2, B2, C2, D2. And at the end, I've got to get R1 G of the matrix with 1's in the subscript plus R2 G of the matrix with 2's in the subscript. And really, it's the exact same steps. So it's going to be G of, and the matrix is R1A1 plus R2A2. And then R1B1 plus R2B2. And like that. This is R1C1 plus R2C2, and then finally R1D1 plus R2D2. So all I did so far was to add together the combination up here. Of course, exactly what G does is it flips the lower left and the upper right. That's the definition of G. So it takes the upper right and writes it in the lower left. It takes the lower left and writes it in the upper right. Just, I don't know, I had to make something up. I made that up. So that's what G does. So we end up with what here? R1A1 plus R2A2. And over here is R1C1 plus R2C2, just because that's the definition of what G does. And also what G does is to write R1B1 plus R2B2 and R1D1 plus R2D2. So G takes, in its argument, takes the upper right and writes it in the lower left in its output, and then takes what's in the lower left and writes it in the upper right. And then, of course, I'm going to do exactly the same thing here. I'm going to break this up into the subscript 1's and the subscript 2's. So here we go. Need a little more room. I'm falling off of my desk. So we're looking at R1 times, and it's A1C1 B1D1 plus R2 times A2C2 B2D2. So it does remind you of this step up here. They're exactly the same in spirit. No, maybe not the algebraic details, but the same idea. And then this, I just recognize this as R1 times G of A1, B1, C1, D1 plus R2 times G of A2, B2, C2, D2. And so the larger view is that I had G of a combination, and down here I got the combination of the G's. So, so the definition of the definition of homomorphism, the definition of linear map, called on me to check those conditions. I combine the conditions just as a matter of convenience, and I find myself, going through the same steps that we went through for isomorphism. Okay, so let's move on then with what it is that we're going to be talking about today. So I doubt you forgot, because it involved is for the homework. But here is the definition of homomorphism: preserves addition, preserves scalar multiplication. Okay, homomorphism or linear map, either word. I tried to use the one and then the other in turn. Okay. Just all the stuff that we talked about last time, and it brings us to the theorem that I want to cover today. Theorem says that a homomorphism is determined by its action on a basis. If you tell me what the basis is, and you say what does the first basis element map to,
what does the second basis element map to, what does the third basis element map to, etc., all the way out to what does the last basis element map to, and they could be the case that two of them map to the same place. Excuse me. Then there's one and only one homomorphism with that action. There is one. You can't go wrong. If you say to yourself, I want to send beta 1 here, and I want to send beta 2 here, you can't go wrong. Guaranteed there's going to be a homomorphism that does that, and furthermore, that homomorphism is unique. Now, the book has the proof, and so often, as we do in these slides here, because this is an introduction to the part rather than sort of the formal details, I'm trying to give the idea first, and then a person should read it in the book. Okay, so here's the idea. I'm looking to invent a map from the plane to the plane. I fixed a basis for the plane 1, 1, 1, 0. And I'm just arbitrarily sending 1, 1 to 1, 3 and 1, 0 to 2, 0. There's nothing magical about 1, 3. I don't have to meet any conditions on 1, 3. I can do whatever I like with 1, 3. That's whatever I like is perfectly fine. The point is that if you tell me where do these two basis vectors go, if you tell me what is the action of H on these two basis vectors, then I can figure out the action of H on any other member of the domain. So I picked a member of the domain minus 1, 5. I didn't pick it for any good reason. I just made it up as the first one that occurred to me. First thing I do is express minus 1, 5 as a combination of basis vectors. That is to say, I represent minus 1, 5 with respect to the given basis. The given basis here is 1, 1, 1, 0. Represent minus 1, 5 with respect to that basis. It turns out when you do the Gauss's method arithmetic, or maybe you're good at this and can see the answer, it turns out that it's 5 times the first minus 6 times the second. And now I just use the definition of homomorphism to compute where does H map minus 1, 5. So here we go. H of V is minus 1, 5. The definition of homomorphism says you can expand the minus 1, 5 as a combination of basis vectors, so I did. And then I know that this will be 5 times H of 1, 1 minus 6 times H of 1, 0. So to get from here to here, this is 5 times H of 1, 1. You'll remember H of 1, 1, there it is. Minus 6 times H of 1, 0. And there's H of 1, 0. And then just do the arithmetic, you get minus 715. I hope. I got minus 715. Whether it's the right answer is another matter. Okay? So if you tell me where H sends a basis, I can tell you where H sends anything. More sort of slickly said, homomorphism is determined by its action on a basis. Another example. I'm going to find a map that sends R3 to R3 by telling you what it does to the standard basis. That's 1, 0, 0, that's 0, 1, 0, that's 0, 0, 1. F sends 1, 0, 0 to this vector, F sends 0, 1, 0 to itself, F sends 0, 0, 1 to this vector. Okay, so we saw on the last slide there are two steps. Figure out if you want to figure out the effect of F on some member of the domain, and I just picked minus 5, 0, 10, I don't know, I just made it up. A lot of times when you do these, it's better to do a generic one rather than say 0, 0, 0, or so. It's better to do kind of a made-up screwy numbers one. It illustrates the point better, so that's what I did. I made up minus 5 and 0 and 10 just because it has relatively screwy numbers. So the last slide we saw that the idea is to represent that vector with respect to the basis, but there's no, oops, I have one too many E3s here. I'm sorry, that's a typo. But there's no difficulty with representing with respect to the standard basis because we know that with respect to the standard basis, a vector is represented by itself. So I saved myself a little arithmetic on this line. By using the standard basis, I saved myself a little arithmetic at this stage. And then to figure out what does F do to that generic vector, that vector that I just made up some crazy numbers, well, you simply write minus 5 times F of E1, 0 times F of E2, 10 times F of E3, and you do the arithmetic and it comes out to that. Okay, so again, The function f is determined by its action on a basis, by its effect on a basis. If you know f of e1, f of e2, and f of e3, then you can figure out what is f of anything at all. This idea of you figure out where f sends an arbitrary thing by taking the -5, the 0, and the 10, and multiplying it by the three vectors that we saw in the top line. That has a terminology for that we'll be using. So V and W are vector spaces. B is a basis for V. A function defined on that basis. So if you tell me where does f send e1, where does f send e2, where does f send e3, a function defined on that basis can be extended linearly to a function that's defined on all of V. So here f maps B to W, here f hat maps V to W. In the way that example illustrates is that if you tell me that V has coefficients of C1 through Cn, then the action of the map is that f hat of V has coefficients C1 through Cn, and that's it. So that's called extending linearly. So you tell me how to define the action of the map on the basis, and I extend linearly to the entire space to get the action of the map on any element of the space. You figure out what are the coefficients, and you put those coefficients down. Here's an example to try to illustrate that this is, try to illustrate just how useful this is. So here's an example. I'm going to figure out the formula for rotating in the plane. So here's the action t sub theta that rotates vectors in the plane through an angle counterclockwise of theta. And these drawings obviously show that the map satisfies addition and scalar multiplication, so it's a linear map, it's a homomorphism. I happen to have illustrated with pi over 6, but there's nothing magical about pi over 6. Okay, and here's the formula. This extending linearly idea gives you the formula for this very easily. And the formula is simply this. Fix a basis for the domain, and I'll fix the standard basis because, as we saw a couple slides ago, it saves you a bit of arithmetic. Figure out where do the basis vectors map under the geometric action that you want. So the geometric action is to rotate by theta radians counterclockwise. So 1, 0, there's 1, 0 in gray, rotated counterclockwise gives you cosine theta sine theta. 0, 1, there's 0, 1, there's 0, 1 right there. There's 0, 1, rotated counterclockwise by theta, radians, I suppose you could do degrees if you were insistent, gives you that for an endpoint of that vector, minus, it's clearly negative, right? The x component is clearly negative, minus sine cosine. So you figure out where the geometry tells you the basis goes, and you just extend linearly to figure out what happens to an arbitrary x comma y, a general x comma y. Expand x comma y in terms of the basis, the vector xy. Expand it in terms of the basis. Apply the definition of homomorphism here, that homomorphism of a combination is the combination of the homomorphisms. T of theta of 1, 0, it says right here. T sub theta of 0, 1 says right here. You get this, that's this. So this is the formula for rotation of x comma y's in the plane. And I got it simply by specifying where does the geometry tell you these basis vectors go. Once you know where the basis vectors go, it's just a question of writing down working through the details of homomorphism. The formula drops right out. Here's another example, illustrates the same thing. This theorem is extremely handy. This idea of extending linearly is extremely handy. So one basis for the space of quadratic polynomials is x squared comma x comma 1. In some ways, it's the most natural basis. So I'm going to define a map, eval sub 3, by specifying where it sends members of that basis. It sends x squared to 9. That's a member of R1. This is the one-dimensional real space. It sends x to 3, and it sends 1 to 1. And of course, as sort of thinking people, we say to ourselves, well, the 9, the 3, and the 1 were chosen because if you were to plug in 3, you'd get 9. If you were to plug in 3, you'd get 3. And if you plug in 3, you'd get 1. But the linear algebra doesn't care about your motivation for sending x squared to 9, x to 3, and 1 to 1. The linear algebra works the same no matter what you did. So I just extend linearly that eval sub 3 on any quadratic polynomial gives you 9a plus 3b plus c. For instance, eval 3 on x squared plus 2x plus 3 gives you 18. So evaluation, what you might call in calculus plugging in, evaluation is a linear map. Evaluation by plugging in 3 is a linear map. Okay. A special case, just like a special case of isomorphisms was automorphism, so too a special case of linear maps is when you look at a linear map from a space to itself. I'm going to use the terminology, this is not standard terminology, but I'm going to use the terminology linear transformation. So many authors, most typically authors, use linear transformation as a synonym for a linear map, as a synonym for homomorphism. I'm going to restrict myself. I'll only use the word transformation when I'm talking about the same domain as codomain. I don't know, I like it better since I think of the space as being transformed in some way by the map. But anyway, just a heads up, if you look on the internet or in another book, they'll use the term transformation to mean in general any map. But I'm going to stick for those maps that send a space to itself. And obviously the identity map is a transformation. To check that it's linear is really trivial. I won't bother you with it. Here's another example of a linear transformation. I'm going to reflect vectors over the xy plane. So sort of close your eyes and think of the think of the yz plane. I misspoke. I said xy. Think of the yz plane. So I think of that as kind of being the right wall. So you think of the yz plane and you have a vector out in space and you reflect it across the yz plane. So in general, if you have, for example, 5, 4, 3, it maps when you reflect it across the yz plane to minus 5, 4, 3. If you had negative 6, 1, 2, that would reflect to 6, 1, 2. And checking that it's a linear transformation, checking that it's a linear map is perfectly routine. I'm restricting the term transformation to those cases where the space maps to itself, so clearly that applies here. And then checking that it's a linear map is very straightforward. F sub yz of a combination is a combination of the f sub yz's. Okay. And I want to finish today by observing something about linear transformations, about linear functions from V to W. So if you look at the vector spaces V and W, then the set of linear functions from V to W, that's a set. You have a whole bunch of different linear functions from V to W. I'm observing something about that. That set is in fact itself a vector space. So I got to tell you what's in it. Well, I actually already told you what's in it. It's a collection of linear functions from V to W, and then I also got to tell you what is the addition operation and what is the scalar multiplication operation. So as usual here, I'm going to do some examples instead of going through the sort of letters version of this. I'm doing examples, and the letters version is in the book, but I'm using a script L there to denote the space of linear maps from V to W. So what do I mean by adding two linear maps? What do I mean by scalar multiplying? And well, we naturally know. So suppose I look, for example, at two linear maps from the linear polynomials to the plane. And maybe here's this first map that takes in linear polynomials and puts out two tall vectors. And here's a second map that takes in linear polynomials and puts out two tall vectors. And it's easy to check that those are both of them homomorphisms to linear maps. And what does it mean to take a combination of them? Well, we know what it means to take a combination of them. 2 times the first plus 3 times the second on the input. So 2 times the first plus 3 times the second should be, you take 2a0 plus 2a1 and add it to 4a1. And so I think you get, 2a0 plus 2a1 and add it to 3 times 4a1. So that's 12 and 12 and 2 makes the 14, and the a naughts is 2. That's right. That was right. and then I'm taking 2f plus 3g on the second component. So 2 times 0 plus 3 times a1 does give you a1. So I did the arithmetic right. So we know how to add two such functions, and we know how to scale and multiply such functions. So we already know what is the algebraic operation that takes place here. How do you add two of these folks, two functions from v to w, and how do you do linear functions from v to w, and how do you scale and multiply? We already know. So this is a place, this collection of functions from v to w is a place where linear combinations can take place. If you take a combination like 2f plus 3g, that will still be a linear function. Now, of course, I have to check that with a's and b's and i's and j's, but it sure looks like it's a linear function. Okay, it's closed under linear combinations. Another example. So I'm going to look at the linear maps from R to R2. And a member of script L of R to R2 is a linear map, and a linear map is determined by its action on a basis. So I'm going to fix bases. I fixed sort of the canonical basis for the one-dimensional space and the canonical basis for the two-dimensional space, the plane. And so functions are determined by basically where does this basis element 1 get mapped to? So you have to figure out what's the coefficient of 1, 0 and what's the coefficient of 0, 1. And so we can understand what it means to be a member of this space. It just depends on what is your C1 and your C2. So I could write each member of the space as H sub C1 comma C2. That's two parameters, and so in fact the set of linear maps from R to R2 is a dimension 2 vector space. Perfectly fair vector space, it's got dimension 2. Okay, that ends it for the day, and when we come back, we're going to talk about an important factor of these spaces, of what is the range and what is the null space. Okay, very good. Bye-bye. Hi, hello. Hope everyone is well. Okay, so last time we talked about the key idea in a homomorphism is that it's determined by its action on a basis. So naturally, the check-in talks about that. Let's see. We have a map that it sends x plus 1 sends the quadratic polynomials in such to the two tall vectors in such a way that x plus 1 maps under the function f to 0, 2. That x maps under the function f to -1, -1, and that x squared under the function f maps to 1, 1, 1. Okay. And I hope that a person sees that these three are just arbitrary. I mean, I just made them up. They're just supposed to be any old two tall vectors. All right, then we're asked, for example, what happens to f of minus x squared? And of course, this is just going to be the negative of this. That is a homomorphism. One of the properties is that if you multiply by a scalar, then the outcome is multiplied by a scalar too. That is f of r v is r f of v. So I should just take -1 times 1, 1. All right. And then let's see, number 2 is not much harder. It's f of 1 plus x squared. And a person sees here that x plus 1 and x squared, so I'm taking the sum of these two. And again, the whole definition of homomorphism is that it should map the sum of 1 plus x and x squared to the sum of the two outputs. F of v1 plus v2 is f of v1 plus f of v2. So here we go. I'm just simply adding 0, 2 to 1, 1 and getting what, 1, 3, I hope. Okay. So so the idea here is set, I hope. Then a person says what is f of let's see, it's going to be 5 minus x plus 2x squared. And so the idea is we simply want to find A, B, C so that 5 minus x plus 2x squared is equal to A times the first vector, B times the second vector, and C times the third vector. All right, and again, a person can set up the linear system and apply Gauss's method, and that's always a fallback in the cases where you can't quite see what to do here. But in this case, it seems to me a person can see what to do, because there's only one x squared on both sides, so it must be that C is 2. And let's see, there is only a constant term on both sides, so it must be that A is 5. And with C is 2 and A is 5, I get that 5x and what makes minus x? B is minus 6. So it's just a matter then, that is to say, I have to represent the given input with respect to the given basis. Whoops, given basis. Okay, so now then f of 5 minus x plus 2x squared is just simply going to be 5 times, don't want to lose it there, 5 times 0, 2, and that 5 is this 5. And I forgot, b is minus 6 times minus 1, minus 1. And C is there it is, C is 2. 2 times 1, 1. And so minus 6, I get 8, and 10 plus 6 plus 2, 18. Okay, so if you know what is the action of the function on the basis, then all you got to do is find the coordinates of the given input with respect to the basis, and just drop them right in, and the rest is arithmetic. Okay, so extending linearly is a computational scheme that we don't have to express the function somehow on all the space at once. We can just express the function in a couple of places, namely on the basis, and then the rest just follows immediately. Okay, we saw the handiness of that last time. All right, so ready to move on to the next step then. So we are thinking about here the range space and the null space. So going to do them as two. They're tied together, so going to do them together as two parts of a whole. So the first thing is that under a homomorphism, the image of any subspace of the domain is a subspace of the codomain. In particular, the image of the entire space, the range of the homomorphism, is a subspace of the codomain. All right, and the book has the proof, but as so often happens in here, I'm going to instead do an example that I hope gives a person insight into what the proof has to say, and then at that point, going through the proof is just a question of recognizing what the i's and j's are. Okay, so here's my example. I took a map from the plane R2 to the 2 by 2 matrices. Oops, my pointer's in the way. To the 2 by 2 matrices, and it's just some crazy map. It's not supposed to be anything particularly interesting. Just some crazy numbers that are not too crazy, so a person can actually read them. Checking that it's a linear map is perfectly routine. And then I'm going to pick a subspace of the domain. So a subspace of the plane, for example, would be the x-axis, the multiples of 1, 0. It's easy to see that when you apply this function to the x-axis, what you get is you range over all possible a's. So you always have zeros for b's, but you could have a 1 for the a's, you could have a 2 for the a's, you could have a 3 for the a's. So you range over all possible a's, but you take the b's to be 0, and this is the result. And that's a subspace of the codomain, and it's pretty clear that it's closed under addition. Let's say if you add a pair of 2 by 2 matrices, each of which have zeros on the bottom row, then you get a 2 by 2 matrix that has a 0 in the bottom row. And similarly, if you multiply a 2 by 2 matrix that has zeros on the bottom row by a number, 17, then you get a 2 by 2 matrix that has zeros on the bottom. Another subspace of R2 is the entire plane is R2 itself. So so what happens when you apply this function over all possible A's and B's? Well, it seems to me clear that what happens when you vary the A's is you get components of this kind here. There's an A there, there's an A there. You take C1 to be A, and you're getting all possible. So this is the contributor that happens by varying the A's over all possible real number A's. And likewise, when you vary over all possible real number b's, you get contributors of a b there, a 2b there, and a b there. So that's written this way, where you vary over all possible b's. So this will be the subspace of the 2 by 2 matrices. It'll be those matrices that have this form. It's clear this is just a basis, right, for the outcome. This is that you get all possible matrices that have this form. Right, so it's a two-dimensional subspace of the four-dimensional space of 2 by 2 matrices. Okay. Just another example here is that if you take the angle theta, then the function that rotates vectors counterclockwise to the angle theta is a linear map, and we've talked about that before. In the domain, the plane, each line through the origin is a subspace. The image of that line is, so you start with, there I am. You start with a you start with a subspace, a line, let's say, that's at a 30-degree angle, and you rotate it by some theta. Imagine that theta is 20 degrees. So now you have a line that's at a 50-degree angle. Everything in that line, the entire subspace, all rotates together. So if you imagine adding this vector in the subspace to this vector in the subspace, well, when you rotate, you're adding this vector in the subspace to this vector in the subspace. So the image of the subspace is a subspace. The range space, then, is the image of the entire space. So it's the special case of the previous result that takes the subspace to be the entire space, takes the subspace of V to be the entire space. I'll write it with a script R there. There's different notations you see around. If you Google around, you might see some people write RAN for range. You'll see other things also. I think script R is a compromise between writing it, relatively short and being relatively clear. So R makes it clear that it's a range, it seems to me anyway. You sometimes see it denoted as H of V. You often see it denoted as H of V. That I prefer to do script R, but you will see this sometimes. So I try to be in the habit of doing script R, but everybody does it different, and you sometimes see H of V. I know that strictly speaking, H is a map that takes in lowercase v's. That is, takes in elements of capital V, so there's a type issue here. But anyway, you often see this notation. The dimension of the range space is called the map's rank. You'll remember that we use the word rank for matrices. There'll be a connection later on. Okay, so here's a map that goes from the 2 by 2 matrices to the two tall vectors. A, B, C, D under the map is sent to A plus B and 2A plus 2B. I know that C and D never occur, but so what? That doesn't matter. The range space, then, you can see that the first line and second line are related. Here the second line is twice the first line, so the range space is going to be all the vectors where the second component is twice the first. That is to say, the familiar y is equal to twice x line. Okay, well, we know that that's a one-dimensional space because it's all the multiples of 1, 2. So the range space of this map is the line y equals x. So this shows that if you take a 2 by 2 matrix, you get a vector in the line through the origin, and this shows that every vector in the line through the origin is the image of some 2 by 2 matrix. Okay, another example, just like to do a couple of examples of anything new that we see. The derivative map, the familiar derivative map, take the derivative like calculus 1 derivative. I'm going from 4th degree polynomials to 4th degree polynomials just to do an example of something. Of course, everybody knows, everybody watching this knows that the derivative of a 4th degree polynomial is a 3rd degree polynomial. And furthermore, if you give me a 3rd degree polynomial, it's the derivative of some 4th degree polynomial. Everybody has done antiderivatives too, I'm sure. So the rank of the derivative function is the dimension of the cubic polynomials. And of course, the cubic polynomials, don't be misled by the subscript 3. The cubic polynomials are not dimension 3. The cubic polynomials are dimension 4 because you have constants, coefficients of x squared, and coefficients of x cubed. So there's sort of 4 degrees of freedom. Okay, another example. We're going to talk a lot about the geometry here today. Another example is projection, oh, my darn pointer, projection from R3 to R2. So projection from 3 space to the plane. It's a linear map, and I'm not going to check that. The check is perfectly routine. The range space is all of the plane, because when you pick a vector in the plane, say the vector 5, 6, that's the projection of something. Oh yeah, it's the projection of 5, 6, 1. It's the projection of 5, 6, 2. It's a projection of 5, 6, 3. In fact, there are infinitely many things that project down to 5, 6. So you can imagine if you stand on the point 5, 6 in the plane and look up, you see all those points above you that project down, or look down, you see all the points below you that project up. Okay, so the rank of the projection map is 2 because the output space, the range space, in this case, the range of the entire map is two-dimensional. Okay, and we'll later on do more examples of determining the range space. We'll have a computational procedure for determining the range space. As often in this class, we like to boil things down to a computational procedure. Okay, so in moving from isomorphism to homomorphisms, we drop the requirement that the maps be onto and one-to-one. I'm going to argue that one of those requirements was not especially critical. The other requirement, though, is. So the first is that onto is not especially critical because any homomorphism is onto its range. So dropping the onto condition has in some way no effect on the range anyway. It doesn't allow anything essentially new to happen. Everybody's got a range. But one-to-one is different. So in contrast, but the fact that we drop the one-to-one condition means that an output vector may have many associated inputs. That wasn't true for isomorphisms. So remember back for the previous slide, you're looking at the projection map and you're standing at 5, 6. You look up, there are many vectors that project to you. You look down, there are many vectors, infinitely many, of course, vectors that project to your location. So recall that if for any function, for example, for the projection function, the set of elements that map to a given one, for example, the set of vectors that project to 5, 6, the set of elements that map to a given one is called the inverse image. H superscript minus 1 doesn't mean 1 over, it means inverse image of W, lowercase w here. I'm standing at the point 5, 6. H superscript minus 1 of W is the set of V's that H to W. So if you imagine it's the projection map, it's the set of vectors up and down that project to you. Basically, it's the vertical line of vectors that go, all the vectors whose tip is above you, all the vectors whose tip is below you, plus the vector you're on. I want to talk about, the rest of today, I want to talk about the structure of the inverse image set, because I think when a person first learns isomorphism and homomorphism, but more now homomorphism because we're focused on that. When a person learns homomorphisms, a person has to form kind of the right mental sort of skeleton on which to hang later sections. So what exactly is a homomorphism doing? And it helps to have a mental picture of what it's doing so that you can attach later ideas onto that mental picture. So that's our goal for the day. We've defined homomorphisms and done enough to do some homeworks on them, practice with them. And now we're trying to build up a mental conception of what it is that homomorphisms have to say. Okay. So here, a projection in this case, it's going to go from R2 to R, just because I can draw them. I've got a bunch of vectors. I can draw them. So pi of x, y is x. And I have some colors. Here are some elements of the inverse image of 2. So these are vectors that project down to 2. Every one of these, I know there's infinitely many, but I drew 5. 5? 5. They all project down to 2. In fact, there are ones below the x-axis, ones with negative y's, that project up to 2, but I can only draw so many. I drew the ones I drew. Okay. These, the blue ones, are vectors that project down to 3, or up to 3, but I only drew the downs. Of course, 2 plus 3 makes 5. So since I'm interested in preservation of addition, I'm going to look at the elements that project to 5. So I'm thinking that red vectors and blue vectors combine to make purple vectors. How do red vectors plus blue vectors combine? What is happening there? Of course, that's going to be that's going to be next. I'm interested in the preservation of addition condition because I'm interested in having a person build up a mental model of exactly what a homomorphism is. I know the definition tells you what a homomorphism is, but what kind of is it? You know, it's like if you give a person the definition of a fish and you never show them a fish. What kind of is it? Or if you give a person definition of chess and you never tell them the idea is to capture the king. Well, what exactly does a homomorphism good for? What's it accomplish? Okay, so the point here is we'll take a red vector, a vector that maps to 2, and a blue vector, a vector that maps to 3, and when I add, of course, pi of u, that gives me 2. When I to pi of v, that gives me 3. I should get pi of u plus v, that's 5. So u plus v should be vectors that add to 5. So a vector that adds to 2 and a vector that adds to 3, if you were to combine those before mapping, you'd find that they added to 5. That is to say, a red vector plus a blue vector, and I just kind of picked one from the previous slide. A red vector plus a blue vector has to make a, I guess I called it magenta. Looks purple to me, but magenta, a red vector plus a blue vector makes a magenta vector, and you can draw in the parallelogram diagram yourself. And the interpretation of preservation of scalar multiplication it works exactly the same way, but I'll let you think that out through for yourself. So that is to say, what this equation tells us is that any red vector, any 2 vector, whatever that means, plus any blue vector, any 3 vector, any vector associated with 3, makes a magenta vector, a vector associated with 5. 2 vector plus a 3 vector makes a 5 vector. Here's another example. Of course, one example of this size is not nearly enough. It's not projection, it's some little more complicated geometry. xy maps to x plus y, 2x plus 2y. A person does notice that the second component is twice the first. So all of these here are vectors that the outcomes are going to be vectors that are multiples of 1, 2. Okay. So here, for example, are the vectors that multiply to 1, 2. Excuse me, the vectors that map to 1, 2. Vectors in the plane that map to 1, 2. Okay. Here, so it's that the dots. Here are the vectors that map to 1.53. All the blue dots. Every vector that maps to 1.53 lies on that line. Just like every vector that mapped to 1, 2 lies on that line. And then there's the map, and then it's going to 1, 2. Here, these are the vectors that map to 1.53, and I chose 1.53 because I didn't want it to get too big. It fell off my screen. Maps to 1.53. And you get the idea, right? A red vector plus a red vector plus a blue vector is going to map to a magenta vector. What are the magenta vectors? 2.55. It's all the vectors that map to 2.55. Where did the 2.5 and 5 come from? 1 plus 1.5 makes 2.5. 2 plus 3 makes 5. A red vector plus a blue vector makes a magenta vector. That is to say, this map breaks the domain up into these diagonal lines. The red line, the blue line, the magenta line. All the vectors that are in the same diagonal line are in the same category. They're all red vectors, or they're all blue vectors, or they're all magenta vectors. They all map to the same output. And the point of preservation of addition is that any red vector plus any blue vector makes any magenta vector. That is to say, there's a structure on this broken up domain. Another example. Here's a red vector, blue vector, and magenta vector from the previous slide, and we see them adding there. I don't know how well the parallelogram shows up on your screen, but there's a kind of a ghostly parallelogram in my diagram. In any event, you can eyeball it that there's a parallelogram, that any red vector plus any blue vector makes a magenta vector. If, for example, I had chosen a different blue vector like this one here, why, I would get a very long and skinny parallelogram that would end with a magenta vector here. So I am breaking the domain up into parts, breaking the domain up into parts. And those parts are red part, the blue part, the magenta part. I'm breaking those vectors into categories. Okay, so h of red plus h of blue is h of, can I call it red plus blue? Magenta. So that is to say, one of the lessons that we want to take away from homomorphisms, not just the definition, but a first idea of what it is they do. Homomorphisms organize the domain. The intuition is that linear maps organize the domain into inverse images in such a way that the sets reflect the structure of the range. Red plus blue makes magenta. So what do I mean by organize the domain into inverse images? Well, remember when we looked at projection from R3 to R2, and you stood on 5, 6, and you looked up and looked down, those are all the vectors associated with your current location. If you paint your current location red, all of those vectors would become red. Similarly, you move over a little bit, you stand at some spot, you paint it blue, all those vectors become blue. What happens if you add red plus blue? Why, you get magenta. All those vectors become magenta. That is drawn here in my crude way, that this is the inverse image of some vector vector w from the codomain. This is the inverse image of some vector, another vector w from the codomain. This is the inverse image of another vector w from the codomain. I drew it as these vertical dots because I'm generalizing that picture of you're standing on 5, 6 and you'll look up and look down. Okay. Here's my projection example. So AXYZ goes to XY. We draw the range as the XY plane. Technically, I should draw them as two separate places, but there's a temptation to make the picture look a certain way. So I put the outcome space over here in this diagram over here. Oops, there we go. I went too far. I have the output space and the input space drawn separately. I really should do that in this picture, but forgive me, I put the output space inside the input space, and I hope it doesn't cause confusion. And again, the idea is that a red vector plus a blue vector makes a magenta vector. There is the inverse image of the red vectors, the inverse image of the blue vectors, and the inverse image of the magenta vectors. The best I can draw. I'm not a very good drawer. If you pick any vector, I don't know, what are there, 10 dots there? Any vector from the inverse image of the red vectors, and any vector plus from the inverse image of the blue vector. If you pick the bottom one here and the top one there, that should add to a vector from the inverse image of the magenta vectors. So again, homomorphisms divide the output space, the range, into components. 1 component, 2 components, 3 components. And those components have a structure. They act in a way that reflects the structure of the domain. Red plus blue makes magenta. Okay? Whoops, what happened? Oh, I went too far. Forgive me. Oh, that's annoying. There we go. I'm finally back to where I want to be. There we go. I don't know what happened. I hit a button and something went crazy. So do you remember I was just here before I hit the button and it went crazy? Maybe I hit the end button instead of the down button. And now I have a red vector plus a blue vector makes a magenta vector. Okay. this interpretation of the definition of homomorphism also holds for spaces that I can't, that I'm not going to be able to draw because I don't, I'm not able to draw, for example, the quadratic polynomials. Or at least I'm not able to draw them very well. But if I take three members of the output space, where W1 plus W2 makes W3, and I look at the inverse image of W1, it's all those quadratic polynomials that lie in this set here. If I take the inverse image of W2, it's all the quadratic polynomials that lie in this set here. And then the inverse image of W3 is all the quadratic polynomials that lie in this set here. Okay? So the inverse image of W1 is you got to have a 1 in that B place. The inverse image of W2 is you got to have a -1 in the B place. And the inverse image of W3 is you got to have a 0 in the B place. Coefficient of X. And any member of the H inverse of W1, any quadratic polynomial that has a 1 in the X place, coefficient of X, plus any member of the inverse image of W2, any quadratic polynomial that has a -1 in front of X, adds to a member of W3, of H inverse of W3. If you take a 7x squared plus 1x plus 9 and you add 16x squared minus 1x plus 4, you'll get somebody, I lost track of what I said, but it'll have a 0 in front of x. Okay, and in each of those examples, the homomorphism shows how to view the domain as organized into inverse images. When we come back next time, this has been a long day today. When we come back next time, we're going to understand what those inverse images are. It's related to what's called the null space, the inverse image of the origin. Okay, so we started off by talking about the range space today. Homomorphisms organize the range space into these inverse images in such a way that the inverse images have a structure. And next time we're asking the question, what do the inverse images look like? Okay, so of course that'll be part 2. Very good. We'll see you then. Hi, hello. Okay, last time we talked about how homomorphisms organize the domain into these inverse images of points in the range. So naturally, the check-in is to practice a little of this. So let's have a look. Okay, so H is going to take the real 3 space over to real 1 space to the line, and it's going to send x, y, z to x minus y minus 2z. Okay, and I'm asked to find first H inverse of 1. Of course, 1 is a member of the range, so that's perfectly sensible question. So this is the set of x, y, z's that map to 1. And seen this kind of thing many times before. We'll imagine this to be a single equation linear system. Leading variable is x. We'll express x in terms of the other 2 variables to get the set of, let's see, it's going to be a 1 plus y plus 2z and yz, where y and z are free. And I'll write that in the usual way. So 1, 0, 0 plus 1, 1, 0, y plus 2, 0, 1, z, where y and z are free. Okay? Now, the thing is that the second question asks for H inverse of -1, and it's all the same, except it says a -1. So the answer is going to be basically the exact same thing, except it's going to say -1, 0, 0. Where y and z are free. Okay, and then H inverse of 0 is the exact same thing, except that'll say 0, 0, 0. So I could leave it out. terrible handwriting. Okay, now the question asked me to find those three parts, and then also asked me to find pick a vector from the first and a vector from the second and verify that they add to make a vector from the third. So I'm just picking one. So how about if I take y to be 1 and z to be 1? So that's let's see, that's 1 and 1 makes 2 and 2 more makes 4, and 1 and 1. So that's a member of this here. Okay. For a member of this here, I'll take, how about if I take y to be 2 and z to be 0? Okay, so y is 2 and z is 0, so 1, 2, 0. Okay, and when we add them together, we get 5, 3, 1. And we want to verify that that 531 is a member of H inverse of 0. So we'll just ask ourselves, is it the case that the x component minus the y component minus twice the z component makes 0? I don't know, the suspense is killing me. So let's see, that's 5 minus 3 minus 2 makes 0, and the answer is yes. Okay, so if we pick sort of a random thing from here, a random thing from here, and add them, we get a random thing from here. And the answer, why does that work? That's because 1 plus minus 1 makes 0. Okay, very good. So last time we talked about how the range is organized into parts that all the parts look alike. So I want to talk now about, look like what? What exactly? Okay, so let's see here. In each of those examples, the homomorphism shows how to view the domain as organized into inverse images of an element of the range. Gee, did I misspeak earlier? Did I say the range was organized? Anyway, the domain is organized into inverse images of a member of the range, just like we just did on the piece of paper. We found the inverse image of -1, the inverse image of +1, the inverse image of 0, and those were all members of the domain R3. In the examples, those inverse images all look the same. In this case, they were all of them were two-dimensional subspaces of R3. That is to say, all of them were planes, but they might be shifted. They might have a vector of 1, 0, 0. They might have a vector of -1, 0, 0. Or they might have a vector of 0, 0, 0. So they shifted. So so they all look the same. So if we understand one of them, then we understand them all in some sense. So we're going to look at the inverse image of 0 because it's guaranteed that the output space has a 0. Okay, so the lemma is that for any homomorphism, the inverse image of a subspace of the range is a subspace of the domain, in particular the inverse image of the trivial subspace of the range, namely, the 0 vector. The trivial subspace of the range is a subspace of the domain. And the book, of course, has the proof, and as we do so often here, I'm going to give an example or two, and then figure that then when a person turns to the book to look at the proof, they'll have a leg up. So the idea here is that the null space, or kernel, two different words mean the same thing, of a linear map is the inverse image of the 0 element in the range. To be a subspace, it has to have a 0 element, so that's guaranteed to happen. The null space is kind of a script n. You also see H inverse notation. Those two things mean the same thing. It's a set of things in the domain where H of V is 0. And the dimension of the null space is called the map's nullity. Now, strictly speaking, the trivial subspace of the codomain is not 0. So when I wrote here the 0 vector with the subscript 0, strictly speaking, I should say the set containing 0 because the subspace has got to be a set. But really, are you staying awake nights worrying about it? I'm not going to distinguish between H inverse of W and H inverse of the trivial subspace, the set of W. Anyway, we're not worried about that. Okay. All right, so I'm going to look at a couple of examples. You see a couple of examples on this slide. The derivative map from P2 to P1. The null space is all of the quadratic polynomials whose derivative is 0. 2ax plus b makes 0. Now, remember that 0 is the zero polynomial, 0x plus 0, element of P1, 0x plus 0. So 2ax plus b equals 0 means that they have the same constant coefficient, namely b is 0, and the same x coefficient, so 2a equals 0. So that means that that means that the thing the restriction you don't have is there's no restriction on c. So the null space is the set of all quadratic polynomials ax squared plus bx plus c, where a is 0 and b is 0, but c can be anything. And of course, that's the familiar result from Calculus 1, that if you want to see which functions have a derivative of 0, which polynomial functions have a derivative of 0, it's all the ones with a constant term. This constant term could be anything, and the other part disappear. Okay. So the null space is all the constant polynomials. Nullity is 1. Here's a function, just kind of a random function. And so it maps R2 to R1, AB maps to 2A plus B. The null space is the set of all ABs, the vector AB, where 2A plus B is 0. And you do you imagine that this is a one equation linear system. A is the leading variable for each free. B is free. You express A in terms of B. And you end up with all multiples of minus 1 half 1. So it's clearly a dimension 1 space. It's all multiples of that one size 1 basis. And so the nullity is 1. More examples of finding the null space. Here's a homomorphism from the 2 by 2 matrices to the two tall vectors. A, B, C, D maps over to A plus B, C plus D. For the null space, you get that that A plus B has to make 0 and C plus D has to make 0. That's a linear system with 2 equations and 4 unknowns. Leading is A and C, free are B and D. There you go. That's clearly a dimension 2 space. It's a subspace of the collection of all 2 by 2 matrices and clearly a dimension 2 subspace. So the nullity is 2. Okay, so null space looks like the same kind of stuff we've been doing all along. Dilation is to multiply everybody by 3 in this case. AB maps to 3A, 3B. And you ask yourself which vectors go to the 0 thing in the range. Well, the 0 thing in the range is the 2 tall 0 vector. AB goes to the 2 tall 0 vector simply means that, that AB must be 0. So this is the 0 element of the domain. I know the domain and the range are the same, but anyway, this is the 0 element of the domain. So in this case, the nullity is 0 because you ask yourself, what's the dimension of the trivial subspace of the plane? And the answer is the dimension is 0 because it has a basis of size 0. Anyway, the dimension is 0. Okay, now I want to talk about the rank and the nullity because the two of them are saying the things that we described in the last video. So let's return to this map here where xy maps to x plus y, 2x plus y. And of course the output has, the second component is twice the first. So the output is the line y equals 2x, the range is the line y equals 2x. And we saw before that if you're asking yourself who maps, for example, to the vector 1, 2, who maps to the vector 1, 2, then you need for x and y to be related in this way. You need who maps to the vector 1, 2. Why you need that x plus y equals 1 and 2x plus 2y equals 2. Right? And so it's all the case where x plus y equals 1. X plus y equals 1 in y equals mx plus b terms is y equals 1 minus x, minus 1 times x plus 1. So it's a line with slope minus 1, and you get all different lines with slope minus 1. So one way to imagine what's happening here is that vectors in the plane is the domain, so it's the entire plane. The range is just the line y equals x, so the range is only one dimensional. To imagine what's happening here, you can imagine that the two-dimensional space is going over to a one-dimensional output. What happened to that dimension? Why, this one point, 1, comma 2, this one vector 1, comma 2, is the recipient of this entire one dimension of vectors. The entire one dimension of vectors. The dimension of vectors where x plus y makes 1. That's clearly a one-dimensional sort of, not in terms of vector space, but it's a line. So x plus y makes 1, collapses, all those infinitely many vectors collapse to be this single vector. So this map drops the dimension we can account for by intuitively thinking that each output point absorbs a one-dimensional set. And the theorem is that if you want to think what's happening here, you say to yourself, what happened to the two-dimensional plane? It collapsed to be a one-dimensional output. So the one-dimensional output versus the two-dimensional plane, the dimension of the domain is 2, the dimension of the output space, the range, is 1. Where did that extra dimension go? Well, the answer was that all of those vectors collapsed down, that one dimension worth of vectors collapsed down to be a single point, a zero-dimensional object, in the output space. So the one-dimensional output space plus the dimension's worth of collapse explains where the two dimensions worth of starting vectors went. So let's look at some examples. Here we're going from R3 to R. X over 2, y over 5 plus z. The null space is clearly this plane. That's a two-dimensional space. The other inverse images are also planes, the two-dimensional space that's sort of up at 1, the two-dimensional space sort of stuff, so they move up and down. Up at 1, down at -1, up at 5, down at -5. But they all look the same. They all look like the null space. They are stacked up like this. These are planes that are just stacked up above each other. They're two-dimensional spaces, and they all collapse to be single points in this map. In the map that we just had, all of that entire 2 dimensions worth of spaces collapse to be the single output 0. Maybe this entire 2 dimensions worth of spaces collapse to be the single output 1. So where did the 3 dimensions of the domain go? And the answer was that, well, 1 dimension of it is the range. 2 dimensions of it is that 2 dimensions, whoops, I got to click, there we go. 2 dimensions worth for each point in the range, 2 dimensions worth of input collapse to be that single point. Okay, another example, projection from R3 to R2. We talked about this before. You're standing at the point 5, 6. You look up, you look down. There's a line's worth of vectors that all collapse to be where you're standing. 3-dimensional domain collapses to be the 2-dimensional range. Where did that extra dimension go? And the answer is all of the lines, all the vectors above and below, that entire line's worth of vectors collapses to that one point. So the nullity is 1. In particular, the vectors above and below the origin collapse to be that one point. So just to step through the proof, just very briefly to refer to the proof here, that if you wanted to prove that rank plus nullity equals the dimension of the domain, you start with the basis for the null space. You expand that to a basis for the entire domain, and then you see what projection does. So you start with a basis for the null space. The null space is the z-axis. You expand that to make a basis for the entire domain. I'm using the standard basis just because it's an illustration. When you apply projection, of course, the null space projects down to 0. And so the domain is organized into inverse images that are vertical lines, one-dimensional sets that look like the null space. And so you have sort of 2 dimensions of freedom, and 1 dimension has gone away. Where did it go? Well, it projected down to 0. Okay, now there are just really a couple of quick examples. The derivative function here has this for our range space, and this is its null space. So the range space is all the linear polynomials, and the null space is where the constant term can be anything, because we know when you take the derivative, it ignores the constant term. The dilation function AB maps to 3A, 3B, the one we saw earlier. Of course, the null space is trivial. The rank is 2, the nullity is 2. So again, the example here is that the null space can have dimension 0. Don't leave that case out. Don't forget the case that if the null space is only the trivial subspace of the domain, then the nullity is 0. Okay, now we're going to compute more null spaces when we get to the next section. We're going to compute more range and null spaces when we get to the next section, just as a heads up. Just a couple more, just to finish, a couple more results here. Under a linear map, a linearly dependent set maps to a linearly dependent set. And that's just, if you write down, if you have some linear dependence and you apply H to both sides, of course you continue to get inequality. So we have that, that some Ci is non-zero. And just, for the example, here's the trace function A, B, C, D maps to A plus D. And this set of matrices is dependent, obviously. The 3 matrices map to 1, 0, and 2, and the set 1, 0, 2, subset of R, is certainly linearly dependent. For example, you can take C1 to be 0, C2 to be 5, and C3 to be 0. And finally, to finish, we have these 3 statements, these 5 statements, all say the same thing. We're trying to understand what it is that homomorphisms have to say. Homomorphisms organize, as we've talked about before, homomorphisms organize the domain into inverse images of the range space, and all these things have to say the same thing. So if the map is 1-to-1, then the map has an inverse from its range to its domain, and furthermore, the inverse is a linear map. We saw that result. If the map is 1-to-1, then the null space just contains one element, because any inverse image only contains one element. And in particular, the null space contains one element. And that's, of course, the same thing as saying that the nullity is 0. If the nullity is 0, why then the rank must be n. So all these things are equivalent. And finally, stated in terms of bases, if you have a basis for V, then the image of that basis is a basis for the range space. So all these 5 things say the same thing. They all say this is the case where the homomorphism is an isomorphism with its range. This is the case where the homomorphism is an isomorphism with its range. Okay. All right, very good. So so we're going to talk some more next time about homomorphisms, of course. So we'll see you next time. Hi, hello. Okay, so we have been working through the definition of homomorphism, and I want to make a couple comments about where we are. So most folks who take this course don't really struggle too much with the solving of linear systems. It seems very concrete to them. You follow these steps, you always get the right answer. That seems very sensible. The next step up in abstraction, not very abstract. The next step up in abstraction is to study collections of linear combinations. And most folks, when you study vector spaces, are pretty good with that. Okay, so vector spaces have these rules. You always follow these rules. They arise naturally somehow from linear systems. It all makes a lot of sense. Or at least it makes pretty good sense. Next up, though, you start studying connections between vector spaces. So isomorphisms, which is pretty natural because when you study vector spaces, you start saying to yourself, this space is just like that space. So that's called an isomorphism. But then you get to homomorphism. And my experience in teaching the class is that that's kind of the point where you have built up this pile of stuff and it's starting to seem a little shaky, just a little shaky. So that's the point. That's exactly the moment when a person needs to say, let's stop. We'll make this concrete by doing lots of numerical examples. 3s and 2s and 5s help to make x's and y's make sense. We'll look at it this way. We'll look at it that way. So that's the whole idea. of what we're doing now. We're not racing ahead, we're stopping, because this is the point at which very often a person taking this class starts to feel like, I was getting it good in the first chapter, and now the second chapter, okay, but this third chapter, it's starting to feel a little fuzzy to me. So when things start to feel fuzzy, you say, stop, take a breath, let's make it concrete and do lots of examples, look at it different ways. So far we have looked at it one way, the definition of homomorphism, and sort of chugging through, can we prove that something is a homomorphism? Can we verify this thing, that thing? You get a feel for what homomorphisms look like. Second thing we did was to worry about the sort of how homomorphisms act. They organize the domain into inverse images of elements from the range. So the example that I talked about a number of times so far is you look at the homomorphism that is projection from R3 to R2. You stand at a point in R2, I've been thinking of 5, 6, I think, and you ask yourself which vectors project to me. You look up, you look down, all the vectors above and below you, that entire line of vectors, all the vectors above and below you collapse down to be you. I call those, say, the red vectors. And then the definition of homomorphism, the preserves addition part of the definition of homomorphism, is that you can understand that a red vector plus a blue vector makes a magenta vector. That is to say, these inverse images of points from the range, these ways that the homomorphism organizes the domain, have a structure to them. They add according to the rules that the definition of homomorphism gives you. Okay, and we saw a number of examples, and work through some. Do it in this case. Do it in this case. Do it in this case, so a person gets some feel for how exactly it works. Today, we'll see yet another example of trying to understand what homomorphisms are. So we are going to draw some pictures. We'll look at some homomorphisms and say, here's some pictures. To draw some pictures, the obvious thing to do is to work with real spaces, the plane in this case, because I can draw plane pictures better. And so I'm going to have some homomorphisms of what do they do in the plane. Okay, so last time we did the sort of algebraic expression of this homomorphism divides the domain up into inverse images of points in the range. The algebraic way to state that is to say the nullity plus the rank equals the dimension of the domain. That if you're looking at the homomorphism of projection and you're standing in the plane at 5, 6. There's an entire dimension's worth, a line of points above and below you. That's a one-dimensional set. That entire dimension collapses. So the three-dimensional domain and the two-dimensional range, where'd the one dimension go? And the answer is, for every point in the range, an entire dimension's worth of points collapses to become that point. Rank plus nullity equals the dimension of the domain. So of course the check-in has some examples of that, and here we go. So two different homomorphisms, and as usual, I'm not going to verify that they're homomorphisms. We're kind of past that now, and I'm looking to find the null space and the range space for each. Okay, let's see how I do here. Organize my desk. There we go. Okay. So I'm looking first at let's see, how's it go? It's ABC. Maps under G to the quadratic polynomial 0 plus a plus 2c x plus 0x squared. I could have just written a plus 2cx. I wrote the 0x squared and the 0 just to try to emphasize that this is a quadratic polynomial. It happens to have a constant term of 0 and a coefficient of x squared of 0, but anyway, it's a quadratic polynomial. And I'm asking myself, what is the null space? And in a minute, I'll ask myself, what is the range space? So we've done lots of these, but you can always do more. It really helps to make something concrete, to do sort of overlearning. Do enough examples that you start saying to yourself, yeah, they all go the same way. I'm tired of this already. That's a good feeling. When you're tired of it already, it means there are no surprises left. Anyway, enough blabbing on my part. So we're looking at the set of ABCs where a plus 2c is 0. And so I'm looking at here, this is the set of, in place of A, I'll write a minus 2C. So that's right, where B and C are free. And so I'll parameterize that as I always do by breaking out the B and the C. And 0, 1, 0, B, and minus 2, 0, 1 by C. Again, B and C are free. Okay. And obviously the basis here is, I'm not going to verify that it's a basis. I'm not going to check linear independence or any of that stuff. But 0, 1, 0 and minus 2, 0, 1. It's a basis. So because there are two things in the basis, the nullity is 2. Okay, so we have a good sense of what the null space is. It's a plane. Inside of R3, it's a plane. These two vectors whose bodies lie in the plane, not just the tip, the entire body lies in the plane. These two vectors form a basis for that plane. What about the range space? A range space of G, sorry, I forgot to write the G. Now, because the nullity is 2, and the dimension of the domain is 3, so we have that the rank of the map must be, 2, 3, I mean, it's a 1. So what that tells you is that the range space is just all multiples of x. That's right. So one-dimensional. It's a one-dimensional space. It can't be just like the even numbers multiplied by x, or that doesn't make any sense. You have to be able to multiply by any scalar, so it's all numbers multiplied by x. And obviously a basis for the range space would be, a basis here would be just singleton x. The sequence consisting only of an x. Okay? I'm kind of out of space on this paper, so let's have a whack of it at a new paper for the next map. All right, and the next map happens to be from R to R3, and I called it H just to give it a different name, and it takes a number from the real line to A, 3A, 0. Okay, and same two questions: the nullity, the null space, and the range space. Okay, so the null space is obviously it's the set of members of the domain with the property that A equals 0 and 3A equals 0. I know the second equation is redundant on the first, but anyway, I wrote it. And of course, that's exactly the set that contains only the number 0. So this is the trivial subspace of the domain. Trivial subspace of the domain. Okay, you might remember it's a little bit obscure, but I'm reminding you. So you might remember because I'm telling you that the basis for the trivial subspace is the empty sequence, and that the nullity, what makes the arithmetic work out, the nullity is 0 because there are 0 many things in that basis. And here I go now. I'm working on the range space. So because the nullity is 0, it's H, H equals 0, then the dimension of the domain is 1. So what I meant by the arithmetic working out is that within the rank of the map must be 1. And in fact, the range space of H is obviously the set of points that lie in the xy plane because there's a 0 there, and lie on the line in the xy plane, lie on the line y equals 3x. So that's the line y equals 3x in the xy plane. Okay, so once, as with the first example, the fact that we found the nullity enabled me to find the rank, and so I was, it's clear that the range is a subspace, but the range has to be all of, or else it wouldn't have the right rank. Okay, very good. Oops, put the cap on my pen so it doesn't run out. Okay, very good. Okay, so what I want to talk about today then is what I began discussing. We want to look at homomorphisms. Homomorphisms are the point in this course where people start saying, I thought I was getting this and now I'm not so sure. So we want to look at homomorphisms in a couple of different ways and do lots of examples. Examples means numbers. If things are getting too abstract, then try it with numbers. Still too abstract, try it with more numbers. Do another 5 kind of stuff, and that's how it becomes concrete, until at some point you're saying to yourself, oh, these all go the same way. And you go back and look at the theorem, and darn it if that isn't exactly what the theorem says. So we're in that stage, we're in the middle of that process, and we're trying to build up the habit of doing that. Okay, so here we go. I'm trying to understand what linear maps are by understanding how they act in the plane. Just a third way to look at homomorphisms, at linear maps, is I'm fixing some place I can draw, namely the plane, and I'm going to draw some. All right, so in real n space, a line through the origin is the set of all multiples of some vector. So if you fix a transformation from real n space to real n space, remember, I personally try to limit the word transformation to where the input and output spaces are the same, but that's not universal. Not everybody does that. I try to stick to that, but other people do something different. But here we go. That's a transformation from Rn to Rn, and it's a linear map. It's homomorphism. So its action has to be that R times V maps to, under T, maps to R times T of V. So the members of this line map to the members of this line. R times V maps to R times T of V. Here I called it S instead of R, but it's the same thing. Multiples of V become multiples of T of V. That's a line. So this paragraph says that under a transformation from Rn to Rn, lines through the origin map to lines through the origin. That's simply a restatement of the rule, the second rule for the definition of linear map. Lines through the origin map to lines through the origin. So the action of T is determined by its effect on any non-zero element of the domain line. If you tell me where V goes to such and such, whatever T of V is, then I know where everybody in the line goes. 3 times V goes to 3 times T of V. 5 times V goes to 5 times T of V. So all you got to do is tell me where V goes, and I know where everybody goes. Okay. So how does that help here? So let's look at the line y equals 2x, sort of canonical line in the plane. And pick a transformation, and I'm not a very imaginative person, so when I have to pick a transformation, I pick 1, 2, 3, 4. So the map effect on any vector in the line is easy to compute. Where does 1, 2 go? It goes to 7, 10, because I plugged in 1 and 2. And then the linear map property that T of R times V is R times T of V imposes a uniformity on what T does. What is T going to do to twice V? It's going to do twice the thing. It's going to have twice the effect. What is T going to do to minus 1 times V? It's going to have minus 1 times the effect. What is T going to do to 100 times V? It's going to have 100 times the effect. So 2, 4, minus 3, minus 6, R2R, they all show the exact action of T. 2, 4 is double the 7, 10. Minus 3, minus 6 is minus 3 times the 7, 10. And R2R is R times the 7, 10. In short, here, summarizing, the action of T on any non-zero vector in the line determines its action on any other vector in the line. Did you see the notation's a little tight there? So that's the span of the set containing the one vector V. In other words, that's the line. Multiples of V. Okay, so again, I talked about how lines map to lines, and you can figure out where any point in the line goes by knowing where the one point in the line goes. So how does that help me picture homomorphisms? And the answer is that every plane vector, except for the origin, is a non-zero member of some line through the origin. So to understand what a map from the plane to the plane does to plane elements, it suffices to understand what it does to lines through the origin. If I want to know what t does to an arbitrary element of the plane, well, that arbitrary element of the plane is on a line through the origin. So if I understand what t does to every line through the origin, I understand what t does to everything in the plane. By the prior slide, to understand what t does on a line through the origin, fix the line y equals 2x. To understand what t does on a line through the origin, it suffices to understand what it does to one non-zero member of that line. If you know what t does to 1, 2, then you know what t does to every vector in the line y equals 2x. Okay? So all I got to do is pick one point from each line through the origin, figure out what t does to that one point, and I'll know what t does to every point in the plane. Again, I'll pick one point on each line through the origin. For example, in the line y equals 2x, I pick the point, for example, 1, 2. If I know what t does to 1, 2, then I know what t does to every point on that line through the origin. So I'm called upon to pick one point on each line through the origin. I'll pick the point that is a distance 1 away from the origin, because 1. And we know how to draw the points that are 1 away from the origin. It is the point whose x-coordinate is cosine and y-coordinate is sine, for where t is the angle. You see that these are colored, and I'll talk about what the colors mean in soon enough, but have to do one thing at a time. You might notice, it's a little bit subtle, but you might notice down here that this point at 180 degrees, this point at pi radians, is not actually included because I included the point at 0 degrees or radians, and I only want one point from the line through the origin, so that's why that's an open circle. Anyway, it's a very fine point, that doesn't matter. So I'm going to start looking at some linear maps. This is the first linear map I looked at because it's the easiest linear map I could think of. Easiest, not trivial. Linear map I could think of. You double the x and you leave the y's the same. What does it do to every point in the plane? Well, we pick one point from each line through the origin and see what it does to that, and it's very straightforward. What does it do, for example, to the point 1, 0? Why, it sends it to 2, 0. What does it do to the point 0, 1? Why, it sends it to 0, 1. What does it do to intermediate points? They go to intermediate places. So this semicircle maps to this upper half of the ellipse. This semicircle maps to this upper half of the ellipse. Well, what happens if you multiply x instead of by 2 if you multiply by a negative, like -2 or -5? So I did -1 just to an illustration. And so it's a little trickier to see here. Do you see that this goes red? Oops, I went the wrong place. Sorry. This goes red, orange, yellow, green, blue, indigo, violet kind of stuff. So this is Roy G. Biv. So it starts with red on the right-hand side and moving counterclockwise, moves through blue and violet. When you multiply by -1, now red is on the left-hand side and it moves like so. So that is to say that the action of multiplying by -x changes this from changes the orientation by which you traverse this circle from counterclockwise to clockwise. Changes the orientation under which we are traversing this circle as t, the parameter, the angle, goes from 0 to pi. First we were counterclockwise, now we're clockwise. So we're starting to get some small picture. We'll see many more examples, but some small picture. Transformations of the plane are going to change this semicircle to different shapes, ellipses, to different shapes. And another thing they can do is change the direction under which you traverse the circle. That's why I needed the colors. Next example. before I change the x in my two examples so far. Here I'm going to change the y. So x goes to minus x is held the same from the previous picture, but now y goes to 3y, and a person can see I had to change the scale of the picture to make it fit in good. You can see what happens is that instead of being 1 tall, I'm now 3 tall. So I'm still, again, it's a little hard to read, but I still, again, the minus x causes the semicircle was traversed counterclockwise, and over here the semicircle was traversed clockwise. If you go Roy G. Biv, it's clockwise. But the difference is, although it's still at +1 and -1 on the x-axis, now it goes up to +3 on the y-axis, so it stretches, dilates, it elongates the picture by a factor of 3. The two dilations combine independently, and the first coordinate of the output uses only x, and the second coordinate of the output uses only y. So what happens, for example, if I mix some x's and y's in the first component, some x's and y's in the second component? So, here I go. I'm mixing some x's and y's. So y goes to y just to hold that, so that's not a factor. X goes to x plus 2y. So again, with the semicircle over here, what happens to points on lines through the origin? Well, over here you can see. What the heck? This is skewed. So what's happening here? I'm asking a person to think of this picture. Imagine that you had, say, a deck of cards. Oops, there we go, a deck of cards, and you push it, but you don't push the whole deck. Instead, you lean on it so that it starts to go like this. So the top slides more than the bottom. The bottom doesn't slide at all. I'm trying to get flat. Not so good with the camera. The bottom doesn't slide at all, but because you leaned on the top slides quite a lot. That's called a shear. So what's happening here is that for those points in the plane, those xy's where y is 0, this map sends xy to xy, because the 2y has no effect. For those points in the plane where y is 1, this map adds a 2 to the x coordinates. See, there it is, 2 to the x coordinates. So the effect of this map is a perfectly good linear map, perfectly good linear transformation. The effect of this map is to change the x coordinate depending on the starting y coordinate. With a high y coordinate, you'll see a big change in the x coordinate. With a low y coordinate, meaning 0, you'll see no change at all in the x coordinate. So this is a skew. And again, it's like you had a rickety table, and you leaned on the table. And so what's happening then in that case is that the top of the table is moving a lot. The part of the table, the part that's stuck to the ground, is not moving at all. So this is called a skew. And linear transformations can do that. Here is a skew in the y direction. So I'm gonna mix the x's and y's in this way. Leave the x alone, mix the x's and y's in this way, and you see the same effect here. You see that something interesting is happening here. Is that what's happening here is that when we change the when we put x's down here, if x is not 0, and indeed x is not 0. Oops, I'm sorry, pointing in the wrong place. And indeed x is not 0 here. If x is not 0, then there's a pronounced effect. So if x is not 0, then you see that the point moves. The red point moves. So does the violet point. On the other hand, if x is 0, if x is 0 right here, you see no effect at all. So the green maps to the green. Standing back from it, understanding it as a skew, but standing back from it, what you see is a rotation. I am no longer projecting, I'm no longer looking like, there we go, no longer looking like a sort of flat ellipse. Instead, I'm looking like an ellipse, there we go, looking like an ellipse that has rotated. So there's some action of rotation here to move the ellipse that we saw earlier, so that its long axis is no longer on the x-axis. Its long axis is now somehow pointing off here in an arbitrary line, in some kind of line. Hard to see how it's arbitrary. It's of course determined mathematically. So I went from 2x to 1/2 x, just playing with the numbers because that's how you make things concrete. And with 1/2 x, you see instead of being 2x, you go to 1/2 x. So you see sort of a quarter of the effect. Again, points that have an x value are affected. Points that have an x value are affected. Points that have a 0 for an x value are not affected. Points that have a 0 for an x value, the green points, are not affected. They are unchanged. But changed are the points that have x equals 1 or x equals minus 1. Of course, x equals a half is also changed, but it's not changed by as much. I'm going to observe something that's a little hard to see here. Restating what I just said a minute ago, is that a red vector gets moved a lot, a green vector gets moved not at all. So we are affecting points in this curve, they're not affected uniformly. Okay, so some points it's not like we picked up this half circle and somehow moved it uniformly. That's not right. Some points on the half circle are remaining the same. Some points on the half circle are moving. Another example of an action that we've seen for linear maps that we talked about, for example, when we did bases, is rotation. So here I did rotation. This is plain, simple rotation. Everybody rotates. You pick up the entire half circle and rotate everybody by whatever degrees, whatever angle theta is. No change of orientation here. This goes red, orange, yellow, green, blue, indigo, violet, counterclockwise. Red, orange, yellow, green, blue, indigo, violet, counterclockwise. So it's very uniform. We've seen, of course, with linear transformations, we just were talking about a few minutes ago, projection from R3 to R2. Well, here I don't have R3, so I'm projected to R1, and it just, it just squeezes down here, and there you go. You can hardly see it. It's on the x-axis, so it's basically gone. You can kind of see the colors a little bit. Now, the map doesn't have to squeeze down to the x-axis. You can make it squeeze down to the line, for example, y equals 2x. So there we go. I've projected to the line y equals 2x. So some points project up, some points project down, but they all project to the line y equals 2x. And again, I'm not a very imaginative person, so when I go to make up an arbitrary map, I made up 1, 2, 3, 4, I don't know. So I typed 1, 2, 3, 4 into my computer drawing program, and from 1, 2, 3, 4, this tells me what is the action of the map on every point in the plane. So red goes to red, blue, green, indigo, violet, etc. And again, you see that your output is half of an ellipse. And again, you see that there's been some rotation, so that the long axis, the major axis it's called, of the ellipse is not on the x-axis or the y-axis. Instead, the major axis of the ellipse is somehow at some angle. And it's a little subtle, but you might notice, because your sort of antennae have been raised to this point, you see that this goes red, orange, yellow. This is a counterclockwise. You traverse counterclockwise when you go from red to violet. And here you're going clockwise when you go to from red to violet. So here you're seeing that the orientation has been reversed. It's a little subtle, but that's why I have the colors. So not only do you see dilation, that you see stretching, you see some kind of rotation, but you'll also see orientation reversal. So 1, 2, 3, 4 is actually a pretty good example. Okay, so again, what is happening here is that we are trying to find different ways to look at homomorphisms. What is it that homomorphisms can do, and get some picture in our mind, some sort of framework or schema on which we can hang new homomorphism thoughts. So homomorphisms can do some things, and they can't do other things. What kinds of things can homomorphisms do? And we've seen it's an exhaustive list, but you have no way of knowing that it's an exhaustive list. But we've seen the pictures of what a homomorphism can do in the plane. Basically, these I listed, dilation, rotation, orientation, reversal, all things that homomorphism can do, for example. Okay, so that today's material was in some sense a little bit extra, that's outside of kind of the main stretch, and now next time we're going to go back to talking sort of back in the main flow of things, and we will try to find a computational scheme for representing homomorphisms, a way to compute homomorphisms that's convenient, and that computational scheme will involve matrices, and at that point we'll sort of really know what matrices are doing. Okay, very good. Hi. Okay, so we've been working with homomorphisms and we've been computing things about them. Today we're going to talk about the sort of correct scheme, the correct method that we're going to use to write down how to represent a linear transformation, a linear map, and homomorphism, and figure out sort of what's its effect on kind of arbitrary members of the domain. So we need a computational scheme that makes it easy to do the kinds of calculations that we're going to be doing. Before that, of course, we're going to do the check-in. The check-in goes back to the rank and the nullity and that kind of stuff. So so it's kind of a quick one. Let's have a it's a reminder. Let's have a whack. So let's see. How do I do? I'm looking at the derivative map. So it's the derivative map from P3 to P2, from polyspace 3 to polyspace 2. And I expect that a person knows what the derivative map is, but even if you don't, it's simply this. A plus bx plus cx squared plus dx cubed is b plus 2c, I'm out of room, b plus 2c times x plus 3d times x squared. I could write plus 0x cubed, but maybe I'll stop doing that at this point. I hope that a person knows that I want to get a quadratic out because I'm interested in a quadratics as out. Okay, so I'm asked to find the null space, asked to find the nullity, and asked to find the rank. So the null space is the kind of stuff we've done lots of times before. The null space of the ddx map is it's the set of a plus bx plus cx squared plus dx cubed, where, let's see here, I need to have that b plus 2cx plus 3dx squared is 0, and that's, of course, the 0 polynomial in poly 2. So then that gives me the set of a plus bx plus cx squared plus dx cubed, where so to be the 0 polynomial, I need b equals 0. 2cx gives me 2x. Excuse me, gives me 0. So and 2c equals 0 and 3d equals 0. Ran out of room. It says and 3d equals 0. If you could only read it, it would say that. So basically, b equals 0, c equals 0, and d equals 0. And so I'm just simply looking at the constant polynomials, a times 1. I don't know how to make it sort of extra clear that this is meant to be the constant polynomials, where a is free. Okay, so basically what everybody knows is that when you take a derivative of a constant polynomial, you get 0. And if you take the derivative of a non-constant polynomial, you don't get 0. So 2, the nullity. The nullity is the dimension of the null space. So of course I already wrote in the basis there. The basis for the null space is I don't know at what length is it helpful to write it. So maybe I'll do the absolute silliest thing and write 0 plus 0. It's going to be 1 plus 0x plus 0x squared. Excuse me, plus 0x cubed. I don't know, that's way overkill, but anyway, I wrote it. So the nullity is 1. The dimension of that basis, the number of things in that basis is 1. The dimension of the null space is 1. Nullity is 1. Okay, and then for the rank, of course, we have the formula, and I'm determined to apply it. So we know that the dimension, oops, sorry, spelled no wrong. Know that the dimension of the domain, which is the dimension of polyspace 3, is 4. There are 4 letters, 1, 2, 3, 4, A, B, C, D, so the dimension is 4. So that means that since rank plus nullity equals the dimension of the domain, so the rank is 3. Okay, so without computing the range space, I can find the dimension of the range space. The dimension of the range space, the rank is 3. So that rank plus nullity equals the dimension of the domain comes up a lot. Turns out to be a very convenient formula. Okay, good. So I'm ready to talk about what I want to talk about today, the scheme for computing with linear maps. So I have to introduce it. It involves basically writing out the parts and organizing them into some convenient form. The convenient form will prove to be a matrix. So I'm going to represent linear maps with matrices. So we've already seen the result that I hope I emphasized is key, that the action of a linear map is determined by its action on a basis. That if you know what h does to beta 1 through beta n, then you know what h does to any v. And we, of course, had a term for how do you get from the betas to v. We call that extending the action of the map linearly from the basis to the entire domain. So I'm going to introduce a scheme for the calculations, and it basically just involves using those c's. So I'm going to pick just an arbitrary domain space and an arbitrary codomain space, range space, and I have a basis for each of them, and I deliberately didn't pick the easiest basis because, as I've said a number of times before, sometimes the easy basis hides some things that you want to see. So if you pick kind of a generic, kind of arbitrary thing, don't pick a killer, but pick something that's relatively messy. Sometimes you see things that you don't see if you go for the absolutely most straightforward thing. So here we go. I have a basis 1 plus x plus x squared. So I displayed the action of h on 1 plus x, and on 1 plus x squared. And again, I didn't make the result be easy. I tried to make it be kind of generic, not brutal, 8 decimal places kind of craziness, but instead not 0, 0, 0, 1, sort of relatively jumbled up numbers. Okay, relatively jumbled up, relatively generic numbers. And then I want to find, with this action, this is copied from the previous slide, with this action on the domain's basis, I'm going to represent 0, 1, 3, 2, and minus 2, minus 1 with respect to the output spaces. So remember the output, the range basis is 2, 0, minus 1, 1. So I'm going to represent 0, 1 with respect to W's basis. I'm going to represent 3, 2 with respect to W's basis. And I'm going to represent minus 2, minus 1 with respect to W's basis. So I'm getting numbers for all these things. And then I'm going to put the numbers in some organized form. It'll be in a matrix. And that'll be how we do the computation. So we wrote down the representation of 0, 1, the representation of 3, 2, and the representation of minus 2, minus 1. And I included the calculation if you want to remind yourself what does representation mean. So as I represented 0, 1 with respect to the range spaces basis, I represented 3, 2 with respect to the range spaces basis, and I represented a minus 2, minus 1 with respect to the range spaces basis. And I got 6 different numbers, the 1/2, the 5/2, the minus 3/2, the 1, the 2, the minus 1. And they're just numbers. And again, I deliberately chose numbers that aren't pretty because sometimes you see more when the numbers are somehow generic. I'm going to summarize all the calculations I've done so far by writing these. I take this vector, I put it there. I take this vector, I put it there. I take beta 3's vector, and I put it in the third column. So you summarize the calculations I've done so far by putting those numbers down into some organized form, namely a matrix. 2 rows, 3 columns. I'm going to call that the matrix representation of H with respect to the starting and ending basis, BV and BW. And the point is to calculate the effect of the map on an arbitrary V from the domain. So you take an arbitrary V from the domain, and what exactly does H do to it? And you see at the bottom of this slide, to figure out what is the action of H on an arbitrary V, you find how to represent V with respect to the basis. You get a C1, a C2, and a C3. And then you take the numbers from the matrix. Remember the matrix? 1/2, 5/2, minus 3/2. There they are, 1/2, 5/2, minus 3/2. And you remember the matrix was 1, 2, minus 1. So there's the 1, 2, minus 1. Why is that again? Well, because if you want to figure out what h does to this vector v, what does h do to v? Well, the fact that h is a linear map means that the h of the combination is the combination of the h's. What is c times h of beta 1? Well, there you go. It's c1 times, there you go. We just saw on the previous slide that this is how you express h of beta 1. I used, of course, expressed it with respect to the output space as basis. But anyway, this right here, this expression is a correct way to write down h of beta 1. This is a correct way to write down h of beta 2. This is a correct way to write down h of beta 3. And the c1 gets multiplied by the half and also by the 1. There it is. The c1 is multiplied by the half and also by the 1. The c2 gets multiplied by the 5 halves and also by the 2. The c2 gets multiplied by the 5 halves and also by the 2. And finally, the c3 gets multiplied by the minus 3 halves and the minus 1. And there's the c3 by those two numbers. So this, in short, is just simply the way that the numbers fall. 2, 0 gets multiplied by c1 times a half, c2 times 5 halves, c3 times minus 3 halves. That's what 2, 0 gets multiplied by when you break out the 2, 0. Minus 1, 1 gets multiplied by 1 and also by 2 and also by minus 1. That's simply that's just the way the numbers work out. They combine in this way. The combinatorics is just that. You end up multiplying 1 half times the c1, 5 halves times the c2, and minus 3 halves times the c3, and like that for the bottom line. So we're going to represent that by writing the matrix here, writing the column vector representation here, and we will define the combination of this matrix and this column to be you take the first thing in that row, combine it with the c1. Take the second thing in that row, combine it with the c2. Take the third thing in that row, combine it with the c3, and make that the first row of the result. That's the definition. And why did we define it that way? We defined it that way because that's the way the letters work out. That's just how they combine. When you do the distributive law and then factor out the 2, 0, that's just what you get. That's all. That's just how they combine. So that the definition of how do they combine is just what it was on the previous slide. No more complicated than that. So the representation of h of v is you combine the things in the way that they combine. And the rest is a question of getting used to this particular computational scheme. So this is not some sort of gift where I'm telling you something that's just a brilliant idea. If you just write down what the numbers are, you try to make the abstract concrete. You just write down what the numbers are and you see this combines with this combines with this. This is just simply how they combine. So the way the numbers combine to do this computation is you take the dot product of the rows of the matrix with the column representing the input. And the result is the column representing the output. Again, you take the dot product. Remember we defined dot product a couple weeks ago. You take the dot product of the rows of the matrix with the column representing the output. Representing the input, forgive me. And the result is the column representing the output. That's just how they combine. When you put down numbers and you do the this combines with it and factor out the 2, 0, it's just how they combine. Okay, so we write this down as a definition, but it isn't a definition that kind of came from nowhere. It's a definition that came from writing down how linear maps act. So if the representation of h of beta 1 is this column and the representation of h of beta n is this column, you write those columns down, first column, second column, third column, write those columns down into a matrix, and you call that the representation of the map with respect to the starting and ending bases. And again, I can't overemphasize, whoops, there we go, that I just simply took the first column here, wrote it there. First column here, wrote it there. Second column here, wrote it there. Third column there, wrote it there. Because, I don't know, you got to put them together somehow. Putting them together side by side seems like a reasonable thing to do. What's the point? The point is that you get the coefficient of 2, 0 by putting the parts together in this way. You get the coefficient of minus 1, 1 by putting the parts together in this way. And that's all that we're going to write down here. So this is the matrix, and next is going to be the definition of the action of the matrix. Where we go? There we go. The definition of the action of the matrix. The matrix acts on the column in this way. You take the dot product of the first row, dot product of the second row, etc., through dot product of the last row. And it isn't magical. It's because that's just how the parts combine when you write them down. Okay, back we go to the matrix representing the map. You saw there were 3 examples. So the first example is projection from R2 to R2, projection onto the x-axis. I have a starting basis and an ending basis. You have to be told enough to do the problem, so you have to get the starting basis and the ending basis. And again, I picked ones that aren't necessarily straightforward because those are often good first examples. They often illustrate what happens better than straightforward examples. So what do you have to do to find the representation of the map? Why, you figure out what is the action of the map on the first basis element. There it is. What is the action of the map on the second basis element? There it is. So I took the first basis element and projected it. I took the second basis element and projected it. I followed this formula. Once you know what is the action of the map on the first basis element, represent it with respect to the second basis. Represent it with respect to D. And likewise down here. Once you know the action of the map on the second basis element, represent it with respect to the output basis. So you figure out the action and represent with respect to the codomain spaces. Figure out the action and represent with respect to the codomain spaces. You get 2 column vectors because representations are column vectors. You write those down first column, second column. So you write them down in some organized fashion, and the kind of natural organized fashion is to write them next to each other. So we get 4 numbers there, and those 4 numbers somehow represent this map. What happens if you change the basis? So I took the same map, changed the basis. This time I changed it to an easier one. I've been kind of talking up how a generic one makes a better first example. So my second example is to take an easy basis. Okay, but same thing to do. You figure out what is the projection of the first basis, figure out what is the projection of the second basis vector. Once you've figured out what is the action of the map on each basis vector, you represent those with respect to the second basis. So here 1, 0 is from capital B, 0, 1 is from capital B. Here I'm representing pi of beta 1 with respect to D. I'm representing pi of beta 2 with respect to D. So how do you represent 1, 0 with respect to E2? And you might remember that for the standard basis, every vector represents itself. So 1, 0 represents itself. And again, for the standard basis, D, every vector represents itself. So 0, 0 represents itself. A0 is always represented by 0, 0. But anyway, 0, 0 represents itself. You take these 2 columns, you write it next to each other, done. Just to do some different map. So here, AB maps it to the real number 2a plus 3b. And again, I'm going to use the standard basis. So where does 1, 0 go? Where does 0, 1 go? So 2a plus 3b, it puts out a 2. 2a plus 3b puts out a 3. Represent those with respect to the codomain spaces. That in this case is the standard basis for the real line. So represent those 2 with respect to the codomain spaces. Everything represents itself. Everything represents itself. Put them next to each other. Okay, so the same 3 steps. Figure out the action of the map on each of the domain basis elements. Represent those with respect, represent the 2 and the 3 in this case, represent those with respect to the codomains basis. And finally, just put them, or but the 2, put them next to each other as vertical vectors, as column vectors, and here they're only 1 column tall, so there's not much columnist to them. And then this says theorem. It says that if you write matrices in the way that we've just been practicing, and you write the representation of an arbitrary vector with respect to the domain basis, then the representation of h of v, the representation of the action of h on v, will be this column vector. And again, I can't overemphasize that it says theorem, but really the definitions are set up so that the theorem has to be true. That is, we organized here, organized the parts in such a way that we just looked how they combined, and they combine in this way. And so that the theorem, in some sense, if the theorem wasn't true, we'd change the representation to make it true in some ways. Okay, so the proof formalizes the example that began the subsection. There is an exercise that asks the person to go through the i's and j's. So, of course, we define then the matrix vector product of an m by n matrix and an n by 1 vector is just the action that we just described here. If you multiply a matrix times a vector, you get the action that we just described. And I didn't make up the matrix vector product and then discover that it represents that's not what we're doing. What we're doing in this class instead is we're writing down linear maps. How do they act? It turns out they act this way, and so this gives us a natural way, a reasonable way to combine matrices and vectors because we found ourselves combining them. Okay. So the lesson for today, we talked today about how to represent maps with respect to domain and codomain basis, and the point is to make it be the case that when you take that matrix representation and apply it to the representation of the vector, why you get the representation of h of v. So the important part to remember here is that these definitions are not arbitrary. They're made up by just picking some numbers and seeing where the way the different parts combine, and then the result is just a question of saying, well, we wrote down the information in an organized way. It combines to give you this, and that's what we're going to take for the definition. Okay, of course, when we come back next time, we'll do some more practice with the matrix vector definition that we finished with today. Okay, very good, very good. Hi. So last time we learned how to represent a matrix in such a way that it makes easy the computation of h of v. So we have, represent a map so that it makes easy the computation of h of v. So we basically put the information that we need into a matrix. We just take these columns and put them one next to each other, and then we figured out the way that the numbers in that kind of tiny little database, the way that the numbers in that matrix combine with the numbers for the representation of the vector, and it just turns out to be this sort of these things combined with these things. We call that the definition of matrix vector multiplication, and that's how we compute the effect of a linear map. If we have an arbitrary linear map, that's how we figure out how to compute it. So of course, the check-in exactly asks us to to do an example of that. Of course it does. So let's have a whack. Okay, so let's see now. Whoops, push my stuff out of the way. Let's have a look. So looking at here a map that took, darn it, all this stuff is all over the place. There we go. We have a map that takes the plane to the 2x2 matrices. And it's given by, oops, I didn't make my R line very good. It's given by xy goes to 3x, 0, 0, and 2x minus y. I don't know, I made it a 2x2 matrix, and I didn't want to have too much in there just to make it, it just simply makes it longer to do. It doesn't illustrate anymore, so I made it a diagonal matrix. Okay, and of course the first question said represent it with respect to the bases, so I have to write down the bases if I can get them right. B is Hadamard basis 1, 1, 1 minus 1. And D is a basis for the 2x2 matrices that is supposed to be not trivial. I've mentioned any number of times that when you're making up examples for yourself to think about, you don't want to make up sort of the easiest possible example, but you don't want to be too hard either. So I is 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0, and 0, 0, 0, 4. Okay, so just a tip, you don't want it to be too hard, but you don't want it to be too easy. Too easy can hide some subtleties. Too hard is just, you're just beating yourself up. Okay, so let's represent this map here, H, with respect to these bases. So the steps are, first of all, figure out what does H do to each basis element. So H does to 1, 1, and H does to 1 minus 1. And now just go up here. What H does to 1, 1 is it sends it to 3, 0, 0, 1. 2 times 1 minus 1 is 1. And what does H do to 1 minus 1? Why, it sends it to 3, 0, 0, 3. Okay. Represent that with respect to D. So the representation with respect to D of the first thing, 3, 0, 0, 1, and the representation with respect to D of the second thing, 3, 0, 0, 3. Okay, and again, I didn't make D too hard because I don't want to have to go through the Gauss's method where I won't learn anything new, but I didn't want to make it too easy. So anyway, I made what I made it. So how many of these, how many of these, how many of these, and how many of these do you need? So I guess it seems to me you need 3 of these, 0 of these, 0 of these, and 1/4 of these. I'll put down a little d there just to emphasize. Okay, and likewise down here, I didn't really make enough room. 3, 0, 0, 3/4. D, that's a 3/4. I'm sorry, my handwriting is so embarrassing. 3, 0, 0, 3/4. So for a person who can't read, 3/4 it says. Okay, and then to represent the matrix with respect to the bases, excuse me, to represent the map with respect to the bases, representation with respect to B comma D of the map H, you just take these two and put them into a matrix. 3, 0, 0, 1/4, 3, 0, 0, 3/4. We often leave the subscript out, but since I'm illustrating, I'll put it in the subscript. 2 is to represent the vector. I think the vector was 5, 3. So we want to represent with respect to B the vector V equals 5, 3. So if you remember the basis up here, so I'm looking to write down something like A times 1, 1 plus B times 1 minus 1 equals 5, 3. And of course, that gives you some linear system. You're looking at A plus B equals 5 and A minus B equals 3. And I'll show you a tip about this basis up here. I'll show you a little trick. I mean, you know, nobody made it a crime to know something. Of course, I could go ahead with Gauss's method and get an answer. And I've done that a half dozen times with this basis already. But maybe we're at the point now where we're ready to be able to look at things and say, aha, this is an old friend, I know just what to do. Okay, so this particular basis is an old friend, and the way to look at this linear system is you say to yourself something, well, that from A, if I go up, I get to 5. If I go down, I get to 3. So that is to say, A is right smack in the middle. A is the average of the two. A is 5 plus 3 over 2. I know that's 4. And B is the increment. B is the amount you go up or down. So from 4, you go up to get to 5. From 4, you go down to get to 3. So B is the increment. You could write down increment. Nobody made that a crime, but I'll write it as 5 minus 3 over 2. In short, the representation with respect to B of 5, 3 is what to 4, 1. Again, I'm illustrating what's happening, so trying to be extra careful about writing the parts. Okay, and then there's a part 3 that I don't think I left myself enough room for on this piece of paper. So let me do the part 3. Part 3. I want to use those two, the matrix and the representation of the vector. So the representation of the map and the representation of the vector, I want to use those two to figure out what is h of v. What is the representation with respect to D of h of v? Okay, and the answer is a question of writing down the matrix. See if I copy the matrix from what I had. It was 3, 3, 0, 0, 0, 0, and 1/4, 3/4. The representation of the vector was a 4, 1. I just wrote it a second ago. You'd think I could remember it, but. And the answer is going to be a representation with respect to D. I'll compute it, but the answer is going to be a representation with respect to D. Okay, and we saw that the parts just combine in whatever way they combine. We call that combination the dot product, but in any event, the parts just combine. That's just the way that the combinatorics works out. So 3 times 4 plus 3 times 1 makes 15. 0, 0, and 1/4 times 4 plus 3/4 times 1 makes 7/4. So this is the representation with respect to D of the answer. To make it concrete, of course, I'm going to check. That's right. It's always wise to check, so I'm going to check. So the definition of h says that 5/3 under h goes to, let's see, this said 3x, so that's going to be 15. Then 0 and 0, and this said, oh, what, 2x minus y, so 2 times 5 is 10, minus 3 is 7. And what's the representation? Representation with respect to D of 15, 0, 0, 7. So how many times 1, 0, 0, 0? How many times 0, 2, 0, 0? How many times 0, 0, 3, 0? And how many times 0, 0, 0, 4? So yeah, that's right. Okay, very good. Okay, so this is a key result. We are figuring out how to work with arbitrary maps, not to sort of rotation, nothing wrong with rotation or projection or dilation, but we're trying to work with arbitrary any old kind of maps, and so we're representing those using a computational scheme that that is going to enable us to do arbitrary computations. If you're in science or engineering sort of stuff, you're trying to model fluid flow over an airplane wing or so, well, you don't expect your matrices to have lots of zeros in them or sort of stuff. You expect it to be kind of a mess. So here's the theorem that we just practiced with. If you have the representation of the map and the representation of the vector, then the combinatorics, the way that the parts put themselves together is you take the row here and combine it with the column there using the dot product operation, and you get that first entry. You take the second row, combine it with the single column, you get the second entry. You finally down to the mth row, combine it with the single column, and you get the mth entry. Okay, so this is the theorem that we just applied to do the check-in. So just skip past here. We defined the matrix vector product to be that operation. This is the natural way to combine matrices and vectors. It's natural because it turns out to be what you want to do. When you want to represent how this arbitrary sort of function, linear function, is working, why you want to write down its representation and the representation of the input vector, and then that's how the parts get put together. Now, last time we stopped with the definition of matrix vector product, but I want to go on and explore it just a little more today. First point, we can perform the matrix vector product operation, but without any talk about maps or spaces or bases. You absolutely can write down a kind of an arbitrary matrix and an arbitrary vector and combine them in the way that's defined in the definition there in the line above. And it so happens when you write down this matrix and this vector, you get 5 minus 13 for the components of the result, I hope. And it's just simply a sort of mechanical process. And there's in the exercises, there's lots of examples of there's at least a couple of examples of that this turns out to be handy even in contexts where you don't immediately say we're looking at a linear map. I mean, you can have data about how many, what is the pay per hour of the employees and how many hours did they work, and when you combine them, you get what should be the total pay of the employees, kind of stuff. So matrix vector product, we defined it because in the representation of the action of a linear map, it's how the representation of the map and the representation of the input vector combine to give a representation of the output vector. But you can use this definition in other ways. In particular, the product of this matrix and this vector is not defined because you have the wrong sizes. Up here, it's careful to say an M by N matrix, M by N matrix, and an N by 1 column vector. So that N and that N have to be the same. So that's in the definition. It's careful to say the N and the N have to be the same. But just looking down here, if you tried to take the first row, 1, 2, and combine it with the 5, 6, 7, you'd take 1 times 5, 2 times 6, and you got nothing to go with the 7. Are you going to make up a 0 or a 1? That doesn't make any sense. You simply instead say not defined. In practice, when one of these is not defined, it's typically telling you you've made a mistake. You tried to put together parts that don't make any sense. There's some analogy to when you're doing computer programming and you're trying to combine two objects of different types. If you take, for example, a string and you try to combine it somehow with a matrix, and you say, well, strings and matrices don't combine via addition, that's because you programmed something wrong. So too here, in some sense, the type of this is 2 by 2. The type of this is 3 by 1, and the two types just don't mesh. So in practice, usually when you see something like that, it's a caution that you've done something wrong. You should back up and figure out which part you're putting and which part that doesn't fit. Okay, and I just want to do two examples because this idea of representing the map by some systematic process, representing the map and then using it to figure out where the vectors go is a key idea that we're going to spend really the rest of the semester on. Okay, so the familiar geometric action of projection here onto the x-axis. We saw this before, that if you fix these bases and you want to represent projection onto the x-axis, you do it with this matrix. I'm going to pick a particular domain vector, and I picked minus 1, 5. And again, you know my scheme for picking things to make examples. I try to pick things that are not too hard, but also not too easy. So minus numbers, plus numbers, not 5,000, just 5, but not 1, 0 either. Okay, and so now I have to represent V with respect to the domain basis. That's the domain basis. It looks a lot like the one we did on the check-in. Anyway, you represent minus 1, 5 with respect to the domain basis, and it turns out to be a 2 and a 3, a 2 and a 3. And then you just combine to get minus 1 times 2, 1 times 3 gives you the 1. 1/2 times 2 minus 1/2 times 3 gives you the minus 1/2. And this is the representation with respect to the output basis, with respect to the codomain basis. This is the representation with respect to the codomain basis of the result of projecting minus 1, 5 down onto the x-axis. So, of course, I'm going to check. Of course I am. If you project minus 1, 5 down onto the x-axis, you should get minus 1, 0. So does minus 1, 0 work out to be what happens if you take the 1 and the minus 1? And it does. Of course it does. Of course, I would have changed the slide to make it right. Okay, so just like the check-in. So can't overemphasize that. I know often people coming to this class have seen matrix vector multiplication before. That's great. It's good to know things. That's absolutely fine. But I'm presenting a point of view. And the point of view is that the functions come first. The central object of study here is the functions. The matrices represent those functions. So I'll make some analogy. It's a silly analogy, but it helps me. One time I took a trip to go go visit a conference, faraway conference, and I drove there. I had when I went through tolls, I had receipts from the tolls. I had meal receipts. I had a receipt for the hotel, all that kind of stuff. I brought it back and I handed it into the person in the accounting office. Okay. To me, what happened was a trip. That the accounting, the sort of numbers, the receipts, all that stuff was what was sort of representing my trip, was kind of what you use to compute my trip, but it isn't actually the trip. So too here, the point of view that we're taking is that the functions, the linear functions, the h's and g's, the functions are the real thing, and the matrices only represent those functions. That doesn't mean that they're embarrassing, but it means that the real things are the functions. The pi is the real thing, and the matrix vector multiplication, which you may have learned in another class, is the way in which we compute the function. Okay, so we're giving the function primary, trying to help a person build the right mental scaffolding in their mind. What comes first, what comes second? And the point of view that we're presenting is that what comes first is functions of a certain kind, linear functions, homomorphisms. And what comes second is that the matrices and column vectors represent those in the way that the receipts, the chits that I handed in, represented my trip. They're not actually the trip. Okay, enough. Enough of a lecture of finger wagging. One more example. So here's a map that we saw before, so I don't have to compute the matrix representation kind of stuff. So this map sends R2 to R, and it sends the too tall vector AB over to the single number 2A plus 3B. So that's right. And I represented it with respect to the standard bases, E2 and E1, by 2, 3. Okay, not a coincidence that it's 2 and 3 because things are represented by themselves with respect to standard bases. But anyway, you'll remember from a prior slide, we saw that. If I take a domain basis, domain vector, for example, minus 2, 2, represented with respect to the standard basis, of course, it represents itself. That's the good thing. That's the easy thing about the standard basis. And then if I want to figure out what is h of v, what does h do to negative 2, positive 2, when a is negative 2 and b is positive 2, why you take 2, 3, that's a 1 row, 2 column matrix. You multiply it by this column vector, minus 2, 2, and you get here 4, take away, negative 4, add 6, and you get just the 1 row, 1 column matrix. Sometimes people leave out the matrix, the parentheses. 1 row, 1 column, 2. And of course, since that's a representation with respect to the standard basis E1, in fact, the image is h of v is 2. Okay? Okay, so next time we're going to reverse what we have here. We've figured out how to represent a linear map with respect to bases by using a matrix. And now we want to work with arbitrary linear maps. So what we need to do next is we need to show that whatever matrix you write down is a linear map. And so that's what we'll do next time. Okay, very good. Hi. Lot to do today, so we want to move quickly. And in particular, I have a check-in that's not very complicated. So it's just asking a person to do the matrix vector multiplication operation in 3 cases. That's all. So just to move on here to the paper. So the matrix vector multiplication for the first one was 1, 3, minus 1, 5 by 1, 2. And it's not very hard. It's just how the parts combine, that's all. 1 times 1, 3 times 2, that makes 1 plus 6, so it makes a total of 7. For the next, minus 1 times 1, 5 times 2, so I think that's a minus 1 plus 10, so that's 9. Okay? So it's just arithmetic. A person can get the arithmetic wrong, but in some sense it isn't actually hard. The only other point here is with the 2 remaining parts of the question is that if you take a matrix that is 2 wide and try TWO wide and try to multiply it by a vector that is 3 tall, it just doesn't work. It's not defined, is the sort of official title, but it simply doesn't work. You take the 1 times the 1, the 3 times the 2, and who is there to multiply by the 0? And sometimes people try to say something like, well, 0 is nothing, so it doesn't count. No. 0 is not nothing. Okay? So we've got an entry there. It doesn't matter whether it's a 0 or whether it's a 5,218. It doesn't matter. It is the wrong size. So 2 columns has to be 2 rows. Likewise here, single row just simply doesn't suffice. So for number 1, we gave the answer of what, 7, 9, the vector consisting of 7 and 9. And number 2 and number 3, you simply write not defined. That's all there is to it. Okay, very good. So next we want to get into what we're talking about today because, like I mentioned, it's a lot of material to cover, and so I'm going to mostly do it as I often do when we have a lot to cover. I'm going to mostly do it by examples. So what we want to say is that these representations of linear maps can tell us an awful lot. So for starters, I want to show that no matter what matrix you write down, for example, the matrix 1, 2, 3, 4, it represents a linear map. So it's not the case that only some matrices represent linear maps. Instead, any matrix you scribble down represents a linear map. So I wrote down a matrix and I fixed some bases. So I decided that the domain space was going to be R2 and I fixed the standard bases. I decided that the codomain space is going to be the linear polynomials and I fixed some bases, and I just made them up, it doesn't matter. And I'm going to show that the map represented by H with respect to these bases is linear. So of course we know what to do. What do I mean by the map represented by H? Well, the map represented by H takes V, where V's coordinates with respect to the domain basis are C1 and C2, takes V over to W, where these are W's coordinates with respect to the codomain basis. So that's the definition. You write down C1 plus 2C2, 3C1 plus 4C2. That comes from the 1, 2, 3, 4. And then what's H of V? H of V is just simply whatever this number is, C1 plus 2C2, multiplied by the first basis vector, and 3C1 plus 4C2 multiplied by the second basis vector. That's how H is defined to act. We're asking, is that linear? So, of course, the answer is going to be yes. Otherwise, I wouldn't be doing this. So what I have here is that if you follow it through, then 1, 2, 3, 4 acting on a combination gives you the combination of the 1, 2, 3, 4s. 1, 2, 3, 4 acting on a combination, and I just followed it through. I'll let you go through the 1s, the 2s, the 3s, and the 4s, but it's not very hard, is the combination of the 1, 2, 3, 4s. So H on a combination is the combination of the H's. That means that this represents a linear map, that the action of H is linear. Okay, the action of capital H is linear. Okay. So any matrix represents a homomorphism between vector spaces of appropriate dimensions with respect to any pair of bases. What does appropriate dimensions mean? Well, in the previous example, H was a 2 by 2 matrix, so I need to have that the dimension of the domain and the dimension of the codomain are they're both two-dimensional spaces. Okay? And the proof is just a question of going through the previous example and putting in i's and j's, beta 1s and beta 2s, delta 1s and delta 2 kind of stuff. That's all. Right, and again, the thesis for today is that we can use these representations to figure out facts about the map. You remember my finger wagging last time where I tried to make sure that a person is focused on the maps first and the matrices second, the maps first and the representations of those maps second. So what map information can we figure out from the matrix, and that's what we want to figure out today. So we're going to show how to study the map using the associated matrix. It's nice to have it all in one place, and this is the key result, that if you have the matrix representing H, you multiply it by the column vector representing V, then you get the column vector representing H of V. Okay? So this is an instance of that, of the equation star. The first part is about the dimensions. So the 2-row, 3-column matrix has to multiply by a 3-row, 1-column vector, and you got to get a 2-row, 1-column output. So the dimension of H's domain has to be the number of columns in H, because when you represent things in the domain, they have 3 components. And the dimension of H's codomain, little h's codomain, has to be the number of the number of rows here, which of course is the number of rows here. So the fact that we have a 2 by 3 matrix in this example means that the domain is dimension 3, the codomain, the output space, is dimension 2. So that's just the way the parts combine. Next is an easy one. What about the zero map? Well, the zero map, I'm going to skip the proof and just go to the example here. The argument isn't hard. I'm just simply going to skip it. So the zero map is represented by the zero matrix of the appropriate size, but once you get the bookkeeping right, it's all zeros. So the zero map, for example, from R2 to R3 is represented by the zero matrix. Rank. The rank of a matrix is equal to the rank of any map it represents. So you'll remember that the rank is the dimension of the range. The rank of a map is the dimension of the range. So this says the rank of a matrix, you do Gauss's method and how many rows, non-zero rows remain. That's equal to the rank of the map that it represents. What's the dimension of the range? And I'm going to, as with other ones here, I'm going to do an example. So I'm going to take a linear transformation that sends the two tall input AB to the two tall output 2A minus B, 2A minus B, and a person can see that the output space is one-dimensional. So the rank of the map is 1. I then went in and represented that map T with respect to some bases. I just made up bases, and I represented, and I got here this matrix. I think you can see we've done so many Gauss's methods. I think you can see that when you do Gauss's method on that matrix, you're going to get, right, one non-zero row. That the second row is a multiple of the first. Second row is linearly dependent on the first. Okay, so if I represent it with respect to different bases, I get a different matrix, but the same result. Same map, different bases, I get a different matrix, but still, Gauss's method on that matrix will yield one non-zero row. So the rank of the matrix, do Gauss's method, count the number of non-zero rows. The rank of the matrix is equal to the rank of the map. What's the dimension of the range? So if you want to compute the rank of the map, maybe an easy way is to represent the map and do Gauss's method. One-to-one and onto. So if H is a linear map represented by the matrix capital H, then little h is onto if and only if the rank of capital H equals the number of rows. That is to say, the dimension of the range is equal to the dimension of the codomain. And H is one-to-one if and only if the rank of capital H equals the number of its columns. So just that's simply because the number of columns is the dimension of H's domain, and the number of rows is the dimension of the codomain. That's all. So just as another example here, so I have the transformation of rotating vectors counterclockwise by theta radians, and of course we know that that's one-to-one and onto. If you take vectors in the plane and rotate them all by theta radians, why you get a map that is one-to-one and onto. And we can see by looking at this matrix, or by looking at this matrix, whichever version you think is simpler, we can see by looking at this matrix that when you do Gauss's method on that, you're going to get two non-zero rows. So we get that this map is both one-to-one and onto. A linear map that's one-to-one and onto is non-singular. You'll remember that we used the word non-singular at the very beginning of the course, and of course there's a connection here. We're going to make the connection here right now. A linear map that's one-to-one and onto is non-singular, otherwise you call it singular. That is, a linear map is non-singular if and only if it's an isomorphism. And a non-singular linear map is represented by a square matrix. If you want to be both one-to-one and onto, you have to be represented by a square matrix in that case. So, excuse me, it says, a square matrix represents, I had trouble reading the thing. Square matrix represents non-singular maps if and only if it's a non-singular matrix. That is to say, in summary, I can read it over here. A matrix represents isomorphism if and only if it's square and non-singular. So you want to know if your map is an isomorphism. Remember, we did some reasonably complicated calculations in the first section of the third chapter. You want to know if your map is an isomorphism. Here is a strictly computational way, requires no insight. You don't have to do the hard part about ontos. You represent it with respect to some basis for the domain and codomain. You do Gauss's method. Do you have a square matrix that has no zero rows? Then it's an isomorphism. Okay, and again, I'm going to just in the interest of time, the slides are an introduction really, rather than the whole the whole presentation. The whole presentation is in the book. So, of course, I'm going to do an example. So that matrix certainly is square. Does it represent an isomorphism? And the answer, of course, if you do Gauss's method on that matrix, it's obvious that it will have no zero rows. So it represents an isomorphism. With respect to what? With respect to anything. If you fix any domain that you like, got to be two-dimensional domain, or how about the linear polynomials? And any codomain that you like, got to be two-dimensional. So how about the two wide row vectors? You fix any basis for the domain and any basis for the codomain. This matrix represents an isomorphism. Okay. Another example, less kind of dopey. Gauss's method will show you that matrix is singular. That there'll be a zero row. So any map it represents will be a linear map, fair enough, linear, but not an isomorphism. Again, represents with respect to what? What's the domain? What's the codomain? And the answer is any domain, any codomain. Because that matrix is square, I'm talking about a three-dimensional domain and a three-dimensional codomain. I'm talking about any basis for any three-dimensional domain and any basis for any three-dimensional codomain. That will represent a map that's linear, a homomorphism, but not an isomorphism. Okay, linear map, but not an isomorphism. Okay, and then I want to finish off by computing the range space and null space. So I picked a linear map. That's, again, not too easy, not too hard. So a function is onto if every codomain member W is the image of at least one domain member V. This function's not onto because there's a restriction. The first component of the output has to be the average of the other two. Do you see that? X is the average of X plus Z and X minus Z. A function's one-to-one if every codomain member W is the image of at most one domain member W. And this function is not one-to-one because the output entries don't use Y at all. So if you hold X and Z constant, let's say you said X equals 5 and Z equals 4, and vary Y, you'll get that many inputs all go to the same output. So we can decide by, thinking it through, one-to-oneness and onto-ness for this function, but the problem is that we're always afraid that we're going to someday, they will be called out by a function that we just can't do hard. We just can't figure it out. No amount of being quick on the draw will suffice to figure out the range space and null space for this kind of, how do we, what's an algorithm? And of course the algorithm involves Gauss's method. Are you shocked and appalled to hear that? So for the calculations, I'm going to use the standard basis just because I could pick another basis, but I'm using the standard basis because it's relatively easy. Here's the action of H on the domains basis, okay, the standard basis, and I got the action of H from right here. And I represented those with respect to the codomains basis. If the codomains basis is the standard basis, then every vector is represented by itself. So that's nice. It saves me a certain amount of work. And that gives me the matrix H. You just drop them down one column next to the other. So here's an example of the calculation of representation of lowercase h, representation of the map, representation of the vector is going to give me, of course, the representation of the application of the map to that vector. And to find the range space, of course, I want to figure out which ABCs can happen. So I do Gauss's method, and I find that some ABCs can happen, but some ABCs cannot. And the restriction is that an ABC can happen if a representation can happen, a representation with A, B, and C can happen, exactly if 0 equals negative 2A plus B plus C. So again, the output representation here, this is a representation with respect to D, is possible exactly if and only if 0 equals minus 2A plus B plus C. So there's a restriction on which vectors in the output space can happen. It's those vectors whose representation satisfies this condition. So the rank is 2. H is not onto specifically the range space consists of those W's whose representation satisfies that restriction. To decide if H is one-to-one, you can solve the associated homogeneous system as we have in the past. And of course, we get that the associated homogeneous system is, you solve x equals 0 and z equals 0, but y can be anything it likes. So H is not one-to-one because the null space is not the trivial space. So the null space is the set of domain vectors whose representation falls in that one-dimensional set. The null space is a subspace of the domain, of course. The null space is a set of domain vectors whose representation has a 0 in the first entry and a 0 in the second entry, but can have anything at all in the middle entry. Okay, and again, back to the 1, 2, 3, 4, because I'm not a very imaginative person, and also because it kind of, is clearly an arbitrary matrix that has it's not cooked up to be special in any way. And this matrix obviously has rank 2, since the second matrix, the second row is not a multiple of the first. All right, and so we're looking at the equation star, the representation of the map, the representation of the input vector gives you the representation of the output vector. To figure out what is in the range, I do this Gauss's method here. And it turns out that if you give me an A and a B, I can find an associated, way to combine the inputs. So we get that this map is onto. For all codomain vectors A and B, there's an associated domain vector V. Namely, x is minus 2a plus b, and y is 3/2 a minus 1/2 b. Up here, x is minus 2a plus b, y is 3/2 a minus 1/2 b. So the map is onto, the range space of the map is all of the codomain r squared, and the rank of H is 2. For one-to-one, a person can reason in a number of ways, but for one-to-one, the most straightforward thing to do is to do the homogeneous system by starting off with A and B to be 0. If A and B are 0, you go through all the Gauss's method steps, and you're looking at the only answer is x equals 0, y equals 0. So H is one-to-one, and the null space is a trivial space. But there's other ways that a person could reason. A person could also reason, I'll just mention this in passing, a person could also reason that rank plus nullity equals the dimension of the domain. Dimension of the domain is 2, rank is 2, leaves 0 for nullity. So the null space has to be trivial. It's also a correct way to reason. Nothing wrong with the way I did it. I wanted to illustrate that you can do one Gauss's method here, and then for your null space, take A to be 0 and B to be 0 and get sort of a second calculation for free. But there's nothing wrong with the rank and nullity calculation either. Here's an example that isn't square. So suppose I have this for a representation, and I do the calculation that I did on the prior slide, except I do it with this non-square example. For each A and B, there's at least one x, y, z that works. And you can see that the map is onto, since the output space, the codomain space, has dimension 2, because that's the number of rows in the starting matrix. Since the codomain space has dimension 2, the rank of the map, it covers the entire codomain space. That's what onto means. The rank of the map is 2. For each A and B, there's more than one triple x, y, z. So the map is not one-to-one. If you said it another way, if you take A and B to be 0, you're solving the homogeneous system, then you get 1, 0, minus 3, 0, 0, 1, 2, 0. X and Y are leading, but Z is free. So the null space is got here, you see, the null space has got one free variable, so the nullity is 1. The basis for the null space is the sequence consisting of a single vector, 3, minus 2, 1. So the nullity is 1. So the idea here, ran through a lot of ideas, but the idea here is that we can determine a lot of things about the map by fixing some bases and calculating with the representation. So I'm going to close with an example showing how to extend those calculations to the underlying spaces. So I'm going to fix these three things: a basis for the domain, a basis for the codomain, and a representation of the map. I do the Gauss's method calculation here with the ABCs. The null space is trivial, so H is 1 to 1. If you take A and B and C to be 0, then you get that X equals 0, Y equals 0. So the null space is trivial, so H is 1 to 1. The range, on the other hand, contains those output vectors whose representations satisfy that 0 equals A minus 2B plus C. So H is not onto only some of the codomain space's elements are in the range, namely those whose representations satisfy that, with respect to this basis, satisfy that A minus 2B plus C equals 0. To get the underlying elements of the codomain, you don't want just the representations, you want to know what are the elements of the codomain. So you say to yourself, well, I want to know which elements of the codomain satisfy this property, that A minus 2B plus C equals 0. All right, so satisfy that property, so I put it in. So minus 2b plus c times 1 plus x, b times 1 minus x, and c times x plus x squared, those of course came from right here. And you do the arithmetic, it's not very interesting, and you get b times 3 plus x, c times minus 1 plus x squared. And so the range is actually the span of 3 plus x and minus 1 plus x squared. That's a basis, clearly linearly independent. So the range is of dimension 2 with this for a basis. So I can figure out not just the representations of members of the range, but I can actually figure out the range. So I can figure out things about the underlying space as well as about the representations. Okay, very good. A lot today, but nonetheless also a lot learned today. So this business of representing the function with respect to bases and looking at what that representation has to tell us proves to be very fruitful. Okay, so very good. See you next time. Hi. Okay, last time we talked about trying to understand functions by looking at the representations, and naturally the check-in has to do with that. We're going to look at the representation of a function, not given the function, given its representation, and given the basis for the domain space and the basis for the codomain space, we're going to calculate the null space and the range space, all that kind of stuff. Okay, so let's start it. So let's see here. I write down the parts. I have that F is, the representation is the matrix 2, 1, minus 1, 3. The first basis is the one we've used so often, 1, 1, and 1 minus 1. And the second basis is same sort of thing, not too easy, not too hard. This is the basis for the codomain space, which happens also to be R2, minus 1, 0, and 2, 1. Okay. And the calculation that we did last time goes like this. We imagine that we're given an output, a member of the codomain. So of course the codomain members can be expressed uniquely with respect to this basis. So I'm going to imagine it's expressed as AB, and I'm asking myself which ABs are possible. So 2, 1A and minus 1, 3B. And I'm going to figure out what, which XYs, which members of, components of the representation of V with respect to B, which XYs are possible, which ABs are possible by figuring out here, I'll do the Gauss's method here and figure out which ABs can be the result of applying this matrix to some XY. Okay. So I'll spare you the arithmetic, which gave me a certain amount of trouble, and 1/2 row 1 plus row 2. Then also 1/2 row 1, and then 2/7 row 2, and then finally minus 1/2 row 2 plus row 1. And I ended up when all the smoke cleared with a 1, 0, and it says 3/7 A minus 1/7 B, and then 0, 1, and I got here over here 1/7 A plus 2/7 B, the kind of thing a person might need to do a couple of times. Okay, so what exactly is happening here is what we have figured out is that if you give me an AB from the representation of from the codomain, so given an AB from the codomain, representing a vector from the codomain, we know we know how to calculate x and y, representing a vector from the domain. There are no restrictions. We didn't get a line that said something like 0 over here and 1/7 a plus 2/7 b. That would have told me that the only representations in the codomain that are possible are ones satisfying that restriction. Instead, what we got was no restriction. If you give me an A and a B, I can find the associated x and y. So that is to say that every AB is associated with some xy. So for every AB representing, with respect to D, some W, there is an AB. There is an XY representing, with respect to B, some V. In short, this map is onto. And the range space of F is all of the codomain. Okay, the range space of F is all of the codomain. The same calculation shows if you take A and B to be 0, then you're determining what's in the null space. There's a unique solution. Oh, my pen is running out. We get that for 0, 0, that's the representation with respect to D in the codomain, the representation with respect to D of the 0 vector. Only xy equals 0, 0 maps to it. So the same calculation, I know I expressed the details, but the same calculation shows how to think about the range space and how to think about the null space. So the null space here of F is the trivial subspace of the domain. So this map is 1-to-1. And since it's also onto, so it is an isomorphism. The map well, I haven't written down the map, but the map that is represented by this matrix with respect to these bases is an isomorphism from R2 to R2, and so I almost snuck it out there early. That makes it an automorphism. Okay, so we can calculate, remembering always that we're working with the representations, we can calculate facts about the map from their sort of computational shades, the sort of the matrices and the representations of the bases and etc. Okay. Okay. So next up, I want to think about the operations that we do with these matrices, that we do with these the computational aspects, the computational reflections of the underlying maps. And so we're thinking about here, oops, let me click that way. We're thinking about here matrix operations. So I presented the point of view last time, the point of view that we're taking, that in some sense we have real things and we have things that are the sort of accounting aspects of those real things. So the real things are the vector spaces and the maps. And we use matrices and representations as a way to compute the vector spaces and the maps and compute the relationships between vector spaces which are expressed by the maps. So again, the matrix represents the map. We take the point of view that the map it is that is the primary object. Okay, all right. So what's the point of that? The point of that is that there are map operations. We already saw, multiply a map by a scalar. If I know what the linear map f does, then I know what the linear map 3f does. It just multiplies everything by 3. If I know what the linear maps f and g are, then I know what the linear map f plus g is. So the question is, if you're going to compute things, how do you compute those with matrices? Okay, fair enough. So I'm going to do sums and scalar products of matrices. Those will reflect the map facts. Before I give the definitions, can't overemphasize too much that we're starting with the maps. We're deriving the properties of matrices from those properties of maps. We're going to define that the sum of two matrices is whatever it takes to represent the sum of the two maps. And the scalar multiple of the matrix is whatever it takes to represent the scalar multiple of the map. It will turn out that the sum and scalar product definitions are easy, very easy. They're so easy that a person could miss that point. When you look at the definition of sum and scalar product of a matrix, you never ask yourself, why would you do such a crazy thing? Because it isn't a crazy thing, it's very straightforward. It's so straightforward that it could fool a person. We start with maps. That gives us a definition for sum and scalar product. It's not that we made up the sum and scalar product definition because they're easy. It's rather that we made up the sum and scalar product definition because they reflect what happens with the underlying maps. Okay, enough blabbing, but I'll need that for the next video. Okay, so I'm reminding a person what it means to take the scalar multiple of a function or to add two functions. These are all linear functions, but it doesn't actually matter for this definition. So if you know where a function f maps lowercase v, excuse me, if you know where function f maps lowercase v, then the function rf, that's a function. The function rf outputs r times f of v inside of W. So RF is a function. It's not two different things. It's one thing. RF is a function. And likewise, if you have F and G both taking V to W, then you can make sense of what it means to add those two functions together. It takes V to F of V plus G of V. So again, F plus G is not one thing, it's two things. I said exactly backwards. F plus G is not two things, it's one thing. It's the sum of two things. Just like if you take 5 and 3 and you add them together to get 8, 8 is now one thing. F plus G is now one thing. And the question that we're asking is, if you know the representation of F, what's the representation of RF? If you know the representation of F and the representation of G, what's the representation of F plus G? And again, the problem with this answer to this question is that it will be easy. And you won't ask yourself, why would you do such a crazy thing? Because it's so easy. But the point is that we're doing this because we have map facts and we need to represent them. So when we go to the next video, which will be matrix multiplication, and we ask ourselves, why would you do such a crazy thing? It will have the same answer. The answer will be, we're doing this crazy thing because we're representing a function operation. Okay, all right, so enough talk. So here we go. The way I'm going to do this is the way I always do these things. I try to do them with numbers. Whenever something seems to me to be abstract, I try to give an example with numbers, and then taking a step back and putting in letters in the place of numbers is usually pretty straightforward. Okay, so I'm going to pick a domain V and a codomain W, and I'm going to imagine that the basis for V is beta 1 and beta 2, and the basis for W is delta 1, delta 2. I have an H mapping V to W is a linear, and I'm considering 6. Well, it says 6F. It's supposed to say I guess it's supposed to say 6h. I'm sorry, I mistyped. These are supposed to be h's. I apologize. Oops. Okay, so here's the representation of h of v. We know what 6 does to what the 6 does. It multiplies h of v by 6. It multiplies all the parts by 6, so you get 6w delta plus 6w1 delta plus 6w2 delta. So that's to say, if you have a w1 there and a w2 there, then in the 6h function, I apologize about the f's. In the 6h function, you should have a 6w1 and a 6w2. It's just to multiply, to figure out the representation of 6h, you multiply all its components of the outcome by 6. That's all. The entry by entry factor of 6. That's all. So you multiply everybody by 6. Easy. So just as a for instance, if you have a map H that's represented by a capital H that is 2, 1, 3, 4, then the action of H is you give it a V1, V2 representation. You multiplies it by 2, 1, 3, 4. We've seen that lots of times. 2 times V1, 1 times V2 sort of stuff. If you want to figure out what's the action of 6H, why it does 6 times. So instead of being 2V1, it's 12V1. Instead of being V2, it's 6V2. And so the matrix representing 6H, what matrix is it that will give you an outcome of 12V1, 6V2? It's got to have a 12 and a 6. And 18V1, 24V2, it's got to have an 18 and 24. When you compare this to compare this, what's the comparison? Well, of course, it's 6 times. So to figure out the matrix representing 6H, you multiply everybody by 6. I don't think you're going to be astonished by what happens for plus, for the sum of two functions. If you have two linear functions from v to w, and you represent here f of v and g of v, f of lowercase v and g of lowercase v, then what happens when you when you take the sum of the two functions f plus g, y v goes to u plus v. And how does that affect the representations? Why the u1 and the u2 look like this. The w1 and the w2 look like so, because that's what representation means. It means you take the first component, multiply by a first basis vector, second component, multiply by the second basis vector. And bringing out all the delta 1 stuff and all the delta 2 stuff, why you end up with a u1 plus a w1 in the first component and a u2 plus a w2 in the second component. So that is to say, what will be the outcome of f plus v if this is the outcome of f and this is the outcome of f plus g if this is the outcome of f and this is the outcome of g? Why, you just plus them. Plus them. What matrix is it that gives you that? Why, of course, if this represents f and this represents g, then to get the plus of the two, you just take 2 plus 5 makes 7. 1 plus 8 makes 9. You add together component-wise. So to represent the map f plus g, you take the representation of f, of course same bases here, you take the representation of f and the representation of g and you add them together component by component. So it's the simplest thing that could possibly happen. Again, you start with a representation of f and a representation of g, please, same b and d in both cases. Then the representation of the map f plus g is you add these together component-wise. Just like on the previous slide, we multiplied component-wise by r. Okay, so that gives me the definition for the scalar multiple of a matrix and the definition for the sum of two same-size matrices. The scalar multiple of a matrix is the result of the entry by entry scalar multiplication, and the sum of two same-size matrices is their entry by entry sum. So as a first example here, if this is A and this is C, then A plus C is going to be add the 1 and the 1 to make 2, add the minus 1 and the 0 to make minus 1, 2 plus 8 makes 10, 3 plus minus 1 makes 2. What about 5 times B? Multiply everybody in capital B by 5. Some of these are not defined. It doesn't make sense to add A to B. You don't imagine that there are extra zeros in A. That doesn't make any sense. It doesn't make any sense because the underlying functions don't match up. This has a three-dimensional domain So whatever maps B represent have a three-dimensional domain. Whatever maps A represent have a two-dimensional domain. It doesn't make sense to add them. They just don't. They don't. Not the right types. So A plus B doesn't make any sense. B plus A doesn't make any sense. All that kind of stuff. But when you go to do the operation, it isn't actually hard. If you ever find yourself trying to add a 2 by 2 and a 2 by 3, it'll always be the case when you look back, you'll say, oh no, I made a mistake. I was supposed to put it over here, and now they add to the right sizes, that kind of stuff. So if you find yourself trying to add different sizes 99 times out of 100, it's because you made some error, and it's actually kind of catching your error. Okay, and the theorem says that says what we've been saying all along, that the map R times H is represented by R times the matrix H, and the map H plus G is represented by the matrix A plus G. And this is one of those theorems that has to be true. It has to be true because if it wasn't true, we would have changed the definition of R times capital H. If it wasn't true, we would have changed the definition of capital H plus capital G. That is to say, the times operation on matrices is defined to make this theorem true, and the plus operation on matrices is defined to make this theorem true. If the theorem wasn't true, we'd have to change, so the theorem has to be true. Okay. Okay, and it just simply generalizes the examples that I gave above. I gave examples using numbers like 6, but if you change that to the number k, then you get exactly the same argument, and it all will go through. Oops, 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 darn it, hit the wrong button again. Darn this thing. Much too much stuff here. Much too much stuff. There we go. Sorry about that. Okay, that's where we were. Okay, I've shown all my stuff, although very quickly, I've shown all my stuff. We talked already about the zero matrix. Zero matrix has all entries that are zero. We write, of course, a capital Z sub n by m, or simply Z, to indicate the size of the matrix. And then what I'm just observing that the zero matrix is the identity element for matrix addition, so that if you want to add two matrices, 0 acts like 0 in regular arithmetic. Okay. Okay, very good. When we come in next time, we're going to talk about the more complicated operation of matrix multiplication. You see that it has two parts. And again, the key idea to remember there, as a person is practicing the homework from the section that we just did, is that we don't define scalar multiplication of matrices and sum of matrices because it's easy. We define it because it reflects the underlying map. Then when we get to matrix multiplication, that will reflect something about the underlying maps, and it will all make sense. Make more sense. Okay, bye-bye. Hi. Okay, last time, of course, we defined the operations of matrix scalar multiplication and matrix addition. And the key point there, I'm going to, of course, go through an example of doing those operations, but the key point there was that we defined the scalar multiplication of a matrix so that it reflected the scalar multiplication of the underlying map. And we defined the sum of two matrices so that they reflect, so that operation reflects the representation of the underlying maps, the sum of the underlying maps. So we're going to do more of that today, so keen on emphasizing that. Okay, here we go. So obviously I just made up an example where we have two maps, and I'm going to consider the H and G and H plus G and all that kind of stuff, and then represent those. Okay, let's get started. All right, so let's see here. I've got to remember what I'm doing here. So H and G map poly 2 to r squared. Poly 2 to r squared. Okay, and H does what? H takes a plus bx plus cx squared and gets you to b and a plus c. Whereas G takes the same thing, a plus bx plus cx squared, and gets you to, what does it say? A plus b and minus 2c. A plus b and minus 2c. Okay. Okay, so I've got to figure out here what is h of what is h of 3 plus 2x plus x squared, h of 3 plus 2x plus x squared, so 3, 2, 1. And of course, the action of h is to take the coefficient of x and put it on top, and take the constant term and the coefficient of x squared and add them together and put that in as the second component. So 3 and 1 makes 4. G, on the other hand, takes the same thing, 3 plus 2x plus x squared. And G's action is to take the constant term and the coefficient of x, add them together and make that the first component. And then take the negative 2 times the coefficient of x squared and make that the bottom, so minus 2. And then 4h, acting on the same thing, 3 plus 2x plus x squared, it just goes to whatever 4 times 2 is 8, and 4 times 4 is 16. And h plus g, acting on the same thing, 3 plus 2x plus x squared, write it halfway between the two because it's a combination of the two maps, and you add 2 plus 5 to get 7, and 4 plus minus 2 to get 2. Okay, so it makes sense to multiply h by 4, it makes sense to add h and g. The second question says represent h with respect to the given bases. So 2, I'm given bases b and d, and b is what here 1 plus x, and 1 plus x squared. Okay, and then d is the standard basis for 2 space. That's terrible. Standard basis for 2 space, which is of course 1, 0, 0, 1. Okay. Okay. So to represent h with respect to b and d, I have to figure out where do the elements of b go, and then represent them with respect to the basis d. So where do the elements of b go? And they go to 0, 1, they go to 1, 1, and they go to 0, 2. And of course, the representation of these three with respect to d is the standard basis, so vectors are represented by themselves. So the representation with respect to d of 0, 1 is 0, 1. The representation with respect to d of 1, 1 is 1, 1. A lot of chicken scratching. And the representation with respect to d of 0, 2 is 0, 2. And when all the smoke clears, when all the blab stops, you're looking at the representation with respect to BD of H is, you just put those three together, 0, 0 as, excuse me, 0, 1 as the first column, 1, 1 as the second column, and 0, 2 as the third column. So 0, 1 as the first column, 1, 1, and then 0, 2. The representation of G is pretty much the same thing. You figure out what does G send the members of the basis B. So 1 goes to under G, 1 plus x goes to under G, and 1 plus x squared goes to under G. And it is 1, 0, it is 2, 0, and it is 1 minus 2. I have to represent those with respect to D. The representation with respect to D, because D is the standard basis, the representation with respect to D is 1, 0, 2, 0, and 1 minus 2. I'll spare you the agony and just write the representation with respect to B comma D of G is, write them all down, 1, 0, 2, 0, 1 minus 2. Okay, you can write that if you like. You can leave it out if you like, whatever suits you. And then finally, the last part, the sort of point of the question, is represent 4h, representation of 4h with respect to b comma d. 4h is a perfectly good function. I have an example of 4h's action right here. And the representation of 4h is you simply find the representation of h and you multiply it component by component times 4. So 0, 4, let's see if I can do that. 0, 4, 4, 8. That's a perfectly good function. Here I show its action on some input element, some member of the domain, and to get the representation of 4h with respect to the same bases, B and D, you just multiply component by component. And finally, the representation with respect to BD of H plus G. And of course, we would take the matrix for H and the matrix for G, and we'll add them together, component by component. So 0 plus 1 makes 1. 1 plus 2 makes 3. 0 plus 1 makes 1. 1 plus 0 makes 1. 1 plus 0 makes 1. 2 plus minus 2 makes 0. Okay, so the sum of the two matrices is the representation of the sum of the two maps. And again, the idea from last time is that the sum of two matrices is very easy. It's so easy that a person wouldn't ask themselves, why are we doing this? But a person needs to ask himself, why are we doing this? Because in order to understand what we're talking about today. Okay, so let's turn to what we're talking about today. We're talking about representing a function operation, namely the function operation of composition. We already did the function operation of multiplying by a scalar. We already did the function operation of adding two functions. The function operation we're going to do now is the composition of two functions. So if you have f as a linear function, g is a linear function, and it's legal to compose them, the domains and codomains match up, then how do you represent f composed with g? Okay, so another function operation besides scalar multiplication and addition is composition, and the composition of linear maps is linear. We actually have already seen that, but it's not very hard to show. So I have G composed with H, and I've arranged so that the domains and codomains match up. Specifically, the outputs of H and the inputs of G are the same. So G circle H on a combination is the combination of the G circle H's. And we've done lots of these before, so I won't go through the steps. G circle H on a linear combination is the linear combination of the G circle H's. Now, the way that I developed the theory, the formula for scalar multiplication of a map and the formula for the sum of two functions was I did some example with numbers, and then when you go to say to yourself what should the right definition be, there was just no question. So we're going to do the same thing here. We have two linear functions, f from v to w and g from w to x. So you notice again the w and the w, so it makes sense to take h first and then g. It makes sense to take g circle h. And I made up a matrix representing H and a matrix representing G. You'll notice that they don't share any numbers. So when we get further down, if you see like a 3 or a 6 or a 10, you won't say to yourself, which 10 is that again? Oh, and I spelled explanatory wrong. So I'm going to do the composition. That is to say, I'm going to take a vector from V, find h of little v, going to take a vector little v, find h of little v, and then I'll find g of that, g of h of little v, and that will tell me how the two matrices combine. So it's really the most straightforward thing a person would do. If nobody had invented this before and you were sitting in a room thinking to yourself, what do I have to do? This is exactly what you'd do. You take some vector from capital V and represent it with respect to the basis B. It so happens the shape of this matrix is such that the elements of the domain domain is two-dimensional. Elements of the domain are represented by a too tall vector because there's two columns. So I picked a too tall vector just because that's the example that I'm doing. I'm not working with i's and j's. I'm working with actual numbers, just thinking that it makes the whole thing more concrete. And we know how to do this: 3 times v1 plus 1 times v2, and etc. So this is how you figure out h of v, h of little v. And now the next thing I'm going to do is going to take g of this. 8, 7, 11, 9, 10, 12 of this. So Here we go. I didn't make it all on that slide. I had to go on the next slide. So here we go. I'm taking G of what was on the previous slide. So 8, 7, 11, 9, 10, 12. And it's a little long. It took a lot to write. It's not actually very hard to figure out. It's 8 times the first, 7 times the second, 11 times the third. Next line, next row, is 9 times the first, 10 times the second, 12 times the third. But it takes a lot to write down. Let's see what happens. Well, I'm going to gather together all the V1 things and going to gather together all the V2 things. So that's 8 times 3, 7 times 2, 11 times 4, and that's what it says there. To gather together all the V2 things, it's 8 times 1, 7 times 5, and 11 times 6. So there it is. So the V1s are there and the V2s are there. Rewriting that in terms of matrices, there's the 8, 3, the 7, 2, and the 11, 4 that I pulled out of there. It goes there. There's the 8, 1, the 7, 5, the 11, 6. There it is. I just pulled those out and broke this up to express it as a matrix times a vector. But this is the matrix I'm looking for. This is how you compute the composition G circle H on the vector V. So this is how the two starting matrices combine. If you start with, remember here's G and here's H, because in composition you write the thing done first on the right. You put down the thing done first on the right, you put down the thing done second on the left. That's how you do composition. That's the notation. So that's what I did. I put the thing done first on the right and the thing done second on the left. Okay, fair enough. Here's the H matrix. Here's the G matrix. This is capital H. This is capital G. And this is just how they combine. So in the last class, in the last video, when I said this is the way that the parts of a matrix get combined when you want to multiply, when you want to look at the map for F. And this is the way that the parts of the matrix combine when you want to look at them, represent the map F plus G. Well, this is just how the parts of the matrices combine when you want to look at the composition G circle H. That is just how they combine, that's all. How do they combine? So 8, 7, 11, and 3, 2, 4. So you take the first row and the first column, 8, 7, 11, 3, 2, 4, and you take the dot product. There it is right there. And why do you do such a crazy thing? Because that's just simply how they combine, that's all. 8, 7, 11, 1, 5, 6. So to figure out the thing in row 1, column 2, you take row 1, 8, 7, 11, and column 2, 1, 5, 6, and dot product them. And a person can very sensibly say, when you first see matrix multiplication, that's what we got here, matrix multiplication. A person can very sensibly say, why are you combining them in such a strange way? And the answer is, we're combining them in such a strange way because that's simply how they combine. So the definition is, the matrix multiplicative product of the M by R matrix G with the R by N matrix H is the M by N matrix P, where you figure out that component, you figure out the element of row I and column J by taking row I dot product with column J. You take row I of capital G dot product with column J of capital H, and that gives you entry IJ. That's what it says here. The dot product is more clear here, but the row I and the column J is more clear here. So just as an example, just to pick an example here, I just made up some numbers entirely divorced from any consideration of functions. So 316 and 259 by 204, 1 minus 3, 5, 4, 2, 7. A person notices that these are 3 wide and these are 3 tall. That's necessary. You got to have R, got to be the same as R. So just to pick on one, I'll just pick on, how about if I take 316 and dot product it with 0 minus 3, 2. That's the first row, dot producted with the second column. First row, second column will be this fellow right here. I think, I could have made a mistake, but I don't think so. 3 times 0, 1 times minus 3, 6 times 2, add them together, give you a 9. So you take row I, column J, and that gives you the entry for row I and column J in the result. And again, I can't overemphasize that it isn't an arbitrary definition. This definition is just simply the way the letters fall. That's all. When you go back to this slide, that's just simply the way the components fall when you do the composition. When you do H first and then G, the parts just simply combine in this way, and this is a transcription of how the parts combine. Another example. So here I have 3 wide, 3 wide, and 3 wide. Here I have 2 tall. 2 tall. So if the number of columns on the left does not equal the number of rows on the right, then it's not defined. This matrix product is just simply not defined. And it's not defined for the simple reason that it can't make sense as a composition of two functions. This has a three-dimensional domain. I mean, it just doesn't make sense. It just doesn't line up as a composition of two functions. Sometimes people ask me something like, well, can I imagine that there's a row of zeros? No, because that doesn't make sense in terms of the domains and codomains of the underlying function. Square matrices of the same size always have the defined product, so that's a especially convenient fact about them. So here I have a 3 by 3 and a 3 by 3, so of course 3 wide and 3 tall. So the fact that these matrices are square means that means that you can combine them, multiplicatively combine them, and that reflects the fact that we can always compose two functions from a space to itself. So if h is a function from v to v and g is a function from v to v, then v is three-dimensional. Then you're just looking at g circle h. Of course, it makes sense because the codomains and domains are all the same. Just to pick on an example, how about if I take the bottom row here, 2, 0, 0, and combine it with the third column, and I'll get bottom row, third column. So 2, 0, 0. Dotted with 1, 0, 2. 2 times 1, 0 times 0, 0 times 2. I think I do get the 2. A person might notice that second row has all zeros, so when I take the second row and dot it with the first column, or the second row dotted with the second column, or the second row dotted with the third column, anything you dot with 0, 0, 0 is going to give you zeros, and so a row of zeros will result in a row of zeros. There are some things you can notice about how the parts of these matrices combine with the mechanics of matrix multiplication. We'll talk about that. That's coming up. We'll certainly have a lot to say about that. And then the takeaway here. Of course, when a person does the homework, they're going to be saying to themselves, how do you combine this part? And what happened? Oh, I lost a minus sign. I got to go back. But no, and this is not defined. But don't lose track. Don't lose the forest for the trees. The composition of linear maps is represented by the matrix product of the representatives. That is to say, matrix multiplication is a somewhat peculiar definition. You say, so why are you doing this crazy way? And the answer is because it represents the composition of the functions. So if you have some conception of what the functions are, this function rotates and then this function makes 3 bigger, then you can make sense of what happens when you multiply the underlying matrices. Okay, now next time we're going to do more of the same, more practice, but it's certainly time for a person to go away and try some problems. Okay, very good. Okay, bye-bye.